Chapter 7: The Forms of Tissues or Cell Aggregates. We now pass from the consideration of the solitary cell to that of cells in contact with one another, to what we may call in the first instance cell aggregates, through which we shall be led ultimately to the study of complex tissues. In this part of our subject, as in the preceding chapters, we shall have to give some consideration to the effects of various forces. But, as in the case of the conformation of the solitary cell, we shall probably find, and we may at least begin by assuming, that the agency of surface tension is especially manifest and important. The effect of this surface tension will chiefly manifest itself in the production of surfaces minime aerei, where, as Plato was always careful to point out, we must understand by this expression not an absolute, but a relative minimum, an area. That is to say, which approximates to an absolute minimum as nearly as circumstances and the conditions of the case permit. There are certain fundamental principles, or fundamental equations, besides those which we have already considered, which we shall need in our inquiry. For instance, the case which we briefly touched upon, on p. of the angle of contact between the protoplasm and the axial filament in a heliozoan we shall now find to be but a particular case of a general and elementary theorem. Let us restate as follows, in terms of energy, the general principle which underlies the theory of surface tension or capillarity. When a fluid is in contact with another fluid, or with a solid or a gas, a portion of the energy of the system, that, namely, which we call surface energy, is proportional to the area of the surface of contact. It is also proportional to a coefficient which is specific for each particular pair of substances, and which is constant for these, save only in so far as it may be modified by changes of temperature or of electric charge. The condition of minimum potential energy in the system, which is the condition of equilibrium, will accordingly be obtained by the utmost possible diminution in the area of the surfaces in contact. When we have three bodies in contact, the case becomes a little more complex. Suppose for instance we have a drop of some fluid, A, floating on another fluid, B, and exposed to air, C. The whole surface energy of the system may now be considered as divided into two parts, one at the surface of the drop, and the other outside of the same. The latter portion is inherent in the surface BC, between the mass of fluid B and the superincumbent air, C. But the former portion consists of two parts, for it is divided between the two surfaces AB and AC, that namely which separates the drop from the surrounding fluid and that which separates it from the atmosphere. So far as Figure 99. The drop is concerned, then, equilibrium depends on a proper balance between the energy, per unit area, which is resident in its own two surfaces, and that which is external thereto, that is to say, if we call EBC the energy at the surface between the two fluids, and so on with the other two pairs of surface energies, the condition of equilibrium, or of maintenance of the drop, is that EBC less than EA plus EAC. If, on the other hand, the fluid A happens to be oil and the fluid B, water, then the energy per unit area of the water-air surface is greater than that of the oil-air surface and that of the oil-water surface together, i.e. EWA greater than EOA plus EAO. Here there is no equilibrium, and in order to obtain it the water-air surface must always tend to decrease and the other two interfacial surfaces to increase. Which is as much as to say that the water tends to become covered by a spreading film of oil, and the water-air surface to be abolished. The surface energy of which we have here spoken is manifested in that contractile force, or tension, of which we have already had so much to say. In any part of the free water surface, for instance, one surface particle attracts another surface particle, and the resultant of these multitudinous attractions is an equilibrium of tension throughout this particular surface. In the case of our three bodies in contact with one another, and within a small area very near to the point of contact, a water particle, for instance, will be pulled outwards by another water particle. But on the opposite side, so to speak, there will be no water surface, and no water particle, to furnish the counterbalancing pull, this counterpull. Figure 100. Figure 101. Which is necessary for equilibrium, must therefore be provided by the tensions existing in the other two surfaces of contact. In short, if we could imagine a single particle placed at the very point of contact, it would be drawn upon by three different forces, whose directions would lie in the three surface planes, and whose magnitude would be proportional to the specific tensions characteristic of the two bodies which in each case combine to form the interfacial surface. Now for three forces acting at a point to be in equilibrium, they must be capable of representation, in magnitude and direction, by the three sides of a triangle, taken in order, in accordance with the elementary theorem of the triangle of forces. So, if we know the form of our floating drop, Fig, then by drawing tangents from O, the point of mutual contact, we determine the three angles of our triangle, Fig. And we therefore know the relative magnitudes of the three surface tensions, which magnitudes are proportional to its sides. And conversely, if we know the magnitudes, or relative magnitudes, of the three sides of the triangle, we also know its angles, and these determine the form of the section of the drop. It is scarcely necessary to mention that, since all points on the edge of the drop are under similar conditions, one with another, the form of the drop, as we look down upon it from above, must be circular. And the whole drop must be a solid of revolution. The principle of the triangle of forces is expanded, as follows, by an old 17th-century theorem, called Lamy's theorem, if three forces acting at a point be in equilibrium, each force is proportional to the sine of the angle contained between the directions of the other two. That is to say, P, Q, R equals sin QR, sin PR, sin POQ. Or P sin QR equals Q sin ROP equals R sin POQ. And from this, in turn, we derive the equivalent formulae, by which each force is expressed in terms of the other two, and of the angle between them. P2 equals Q2 plus R2 plus 2 QR cos, QR, etc. From this and the foregoing, we learn the following important and useful deductions. 1. The three forces can only be in equilibrium when any one of them is less than the sum of the other two, for otherwise, the triangle is impossible. Now in the case of a drop of olive oil upon a clean water surface, the relative magnitudes of the three tensions, at 15 degrees Celsius, have been determined as follows. Water-air surface, oil-air surface, oil-water surface. No triangle having sides of these relative magnitudes is possible, and no such drop therefore can remain in equilibrium. 2. The three surfaces may be all alike, as when a soap bubble floats upon soapy water, or when two soap bubbles are joined together, on either side of a partition film. In this case, the three tensions are all equal, and therefore the three angles are all equal, that is to say, when three similar liquid surfaces meet together, they always do so at an angle of 120 degrees. Whether our two conjoined soap bubbles be equal or unequal, this is still the invariable rule, because the specific tension of a particular surface is unaffected by any changes of magnitude or form. 3. If two only of the surfaces be alike, then two of the angles will be alike, and the other will be unlike, and this last will be the difference between 360 degrees and the sum of the other two. A particular case is when a film is stretched between solid and parallel walls, like a soap film within a cylindrical tube. Here, so long as there is no external pressure applied to either side, so long as both ends of the tube are open or closed, the angles on either side of the film will be equal, that is to say the film will set itself at right angles to the sides. Many years ago Sachs laid it down as a principle, which has become celebrated in botany under the name of Sachs's rule, that one cell wall always tends to set itself at right angles to another cell wall. This rule applies to the case which we have just illustrated. And such validity as the rule possesses is due to the fact that among plant tissues it very frequently happens that one cell wall has become solid and rigid before another and later partition wall is developed in connection with it. 4. There is another important principle which arises not out of our equations but out of the general considerations by which we were led to them. We have seen that, at and near the point of contact between our several surfaces, there is a continued balance of forces, carried, so to speak, across the interval. In other words, there is physical continuity between one surface and another. It follows necessarily from this that the surfaces merge one into another by a continuous curve. Whatever be the form of our surfaces and whatever the angle between them, this small intervening surface, approximately spherical, is always there to bridge over the line of contact. And this little fillet, or bourrelet, as Plateau called it, is large enough to be a common and conspicuous feature in the microscopy of tissues, Fig. For instance, the so-called splitting of the cell wall, which is conspicuous at the angles of the large parenchymatous cells in the succulent tissues of all higher plants, Fig. Is nothing more than a manifestation of Plateau's bourrelet, or surface of continuity. We may now illustrate some of the foregoing principles, before we proceed to the more complex cases in which more bodies than three are in mutual contact. But in doing so, we must constantly bear in mind the principles set forth in our chapter on the forms of cells, and especially those relating to the pressure exercised by a curved film. Figure 102. After birth old. Figure 103. Parenchyma of maize. Let us look for a moment at the case presented by the partition wall in a double soap bubble. As we have just seen, the three films in contact, viz. the outer walls of the two bubbles and the partition wall between, being all composed of the same substance and all alike in contact with air, the three surface tensions must be equal. And the three films must therefore, in all cases, meet at an angle of 120 degrees. But, unless the two bubbles be of precisely equal size, and therefore of equal curvature, it is obvious that the tangents to the spheres will not meet the plane of their circle of contact at equal angles. And therefore that the partition wall must be a curved surface, it is only plain when it divides two equal and symmetrical cells. It is also obvious, from the symmetry of the figure, that the centers of the spheres, the center of the partition, and the centers of the two spherical surfaces are all on one and the same straight line. Figure 104. Now the surfaces of the two bubbles exert a pressure inwards which is inversely proportional to their radii, that is to say P, 1r, 1r. And the partition wall must, for equilibrium, exert a pressure, P, which is equal to the difference between these two pressures, that is to say, P equals 1r equals 1r 1r equals, RR. It follows that the curvature of the partition wall must be just such a curvature as is capable of exerting this pressure, that is to say, R equals RR. The partition wall, then, is always a portion of a spherical surface, whose radius is equal to the product, divided by the difference, of the radii of the two vesicles. It follows at once from this that if the two bubbles be equal, the radius of curvature of the partition is infinitely great, that is to say the partition is, as we have already seen, a plane surface. The geometrical construction by which we obtain the position of the centers of the two spheres and also of the partition surface is very simple, always provided that the surface tensions are uniform throughout the system. If P be a point of contact between the two spheres, and CP be a radius of one of them, then make the angle CPM equals 60 degrees, and mark off on PM, PC equal to the radius of the other sphere. In like manner, make the angle CPN equals 60 degrees, cutting the line CC in C, then C will be the center of the second sphere, and C that of the spherical partition. Figure 105. Figure 106. Whether the partition be or be not a plane surface, it is obvious that its line of junction with the rest of the system lies in a plane, and is at right angles to the axis of symmetry. The actual curvature of the partition wall is easily seen in optical section, but in surface view, the line of junction is projected as a plane, Fig. perpendicular to the axis, and this appearance has also helped to lend support and authority to Sax's rule. Figure 107. Filaments, or chains of cells, in various lower algae. A. Nostoc, B. Anabina, C. Rivularia, D. Oscillatoria. Many spherical cells, such as Protococcus, divide into two equal halves, which are therefore separated by a plane partition. Among the other lower algae, akin to Protococcus, such as the Nostocs and Oscillatorii, in which the cells are embedded in a gelatinous matrix, we find a series of forms such as are represented in Fig. Sometimes the cells are solitary or disunited, sometimes they run in pairs or in rows, separated one from another by flat partitions. And sometimes the conjoined cells are approximately hemispherical, but at other times each half is more than a hemisphere. These various conditions depend, according to what we have already learned, upon the relative magnitudes of the tensions at the surface of the cells and at the boundary between them. In the typical case of an equally divided cell, such as a double and co-equal soap bubble, where the partition wall and the outer walls are similar to one another and in contact with similar substances, we can easily determine the form of the system. For, at any point of the boundary of the partition wall, O, the tensions being equal, the angles QOP, ROP, QR are all equal, and each is, therefore, an angle of 120 degrees. But OQ, or being tangents, the centers of the two spheres, or circular arcs in the figure, lie on perpendiculars to them, therefore the radii CO, CO meet at an Figure 108. Angle of 60 degrees, and COC is an equilateral triangle. That is to say, the center of each circle lies on the circumference of the other, the partition lies midway between the two centers, and the length, i.e. the diameter, of the partition wall, PO, is 2 sin 60 degrees equals 1,732 times the radius, or 866 times the diameter, of each of the cells. This gives us, then, the form of an aggregate of two equal cells under uniform conditions. As soon as the tensions become unequal, whether from changes in their own substance or from differences in the substances with which they are in contact, then the form alters. If the tension along the partition, P, diminishes, the partition itself enlarges, and the angle QR increases, until, when the tension P is very small compared to Q or R, the whole figure becomes a circle, and the partition wall, dividing it into two hemispheres, stands at right angles to the outer wall. This is the case when the outer wall of the cell is practically solid. On the other hand, if P begins to increase relatively to Q and R, then the partition wall contracts, and the two adjacent cells become larger and larger segments of a sphere, until at length the system becomes divided into two separate cells. Fig. 109, Spore of Pellia. After Campbell. In the spores of liverworts, such as Pellia, the first partition wall, the equatorial partition in Fig. A, divides the spore into two equal halves, and is therefore a plane surface, normal to the surface of the cell, but the next partitions arise near to either end of the original spherical or elliptical cell. Each of these latter partitions will, like the first, tend to set itself normally to the cell wall. At least the angles on either side of the partition will be identical, and their magnitude will depend upon the tension existing between the cell wall and the surrounding medium. They will only be right angles if the cell wall is already practically solid, and in all probability, rigidity of the cell wall not being quite attained, they will be somewhat greater. In either case the partition itself will be a portion of a sphere, whose curvature will now denote a difference of pressures in the two chambers or cells, which it serves to separate. The later stages of cell division, represented in the figures B and C, we are not yet in a position to deal with. We have innumerable cases, near the tip of a growing filament, where in like manner the partition wall which cuts off the terminal cell constitutes a spherical lens-shaped surface, set normally to the adjacent walls. At the tips of the branches of many Floridae, for instance, we find such a lenticular partition. In Dictyota dichotoma, as figured by Reinke, we have a succession of such partitions. And, by the way, in such cases as these, where the tissues are very transparent, we have often in optical section a puzzling confusion of lines. One being the optical section of the curved partition wall, the other being the straight linear projection of its outer edge to which we have already referred. In the conical terminal cell of Chara, we have the same lens-shaped curve, but a little lower down, where the sides of the shoot are approximately parallel, we have flat transverse partitions, at the edges of which, however, we recognize a convexity of the outer cell wall and a definite angle of contact, equal on the two sides of the partition. Figure 110. Cells of Dictyota. After Reinke. Figure 111. Terminal and other cells. Of Chara. Figure 112. Young Antheridium of Chara. In the young Antheridia of Chara, Fig. And in the not dissimilar case of the sporangium, or conidiophore, of Mucor, we easily recognize the hemispherical form of the septum which shuts off the large spherical cell from the cylindrical filament. Here, in the first phase of development, we should have to take into consideration the different pressures exerted by the single curvature of the cylinder and the double curvature of its spherical cap, P. And we should find that the partition would have a somewhat low curvature, with a radius less than the diameter of the cylinder, which it would have exactly equaled but for the additional pressure inwards which it receives from the curvature of the large surrounding sphere. But as the latter continues to grow, its curvature decreases, and so likewise does the inward pressure of its surface, and accordingly the little convex partition bulges out more and more. In order to epitomize the foregoing facts, let the annexed diagrams, Fig, represent a system of 3 films, of which one is a partition wall between the other 2. And let the tensions at the 3 surfaces, or the tractions exercised upon a point at their meeting place, be proportional to T, T, and T. Let alpha, beta, gamma be, as in the figure, the opposite angles. Then 1. If T be equal to T, and T be relatively insignificant, the angles alpha, beta will be of 90 degrees. Figure 113. 2. If T equals T, but be a little greater than T, then T will exert an appreciable traction, and alpha, beta will be more than 90 degrees, say, for instance, 100 degrees. 3. If T equals T, then alpha, beta, gamma will all equal 120 degrees. The more complicated cases, when T, T, and T are all unequal, are already sufficiently explained. The biological facts which the foregoing considerations go a long way to explain and account for have been the subject of much argument and discussion, especially on the part of the botanists. Let me recapitulate, in a very few words, the history of this long discussion. Some 50 years ago, Hofmeister laid it down as a general law that the partition wall stands always perpendicular to what was previously the principal direction of growth in the cell, or, in other words, perpendicular to the long axis of the cell. 10 years later, Sachs formulated his rule, or principle, of rectangular section, declaring that in all tissues, however complex, the cell walls cut one another, at the time of their formation, at right angles. Years before, Schwendener had found, in the final results of cell division, a universal system of orthogonal trajectories. And this idea Sachs further developed, introducing complicated systems of confocal ellipses and hyperbolae, and distinguishing between periclinal walls, whose curves approximate to the peripheral contours, radial partitions, which cut these at an angle of 90 degrees, and finally anticlines, which stand at right angles to the other 2. Reinke, in 1880, was the first to throw some doubt upon this explanation. He pointed out various cases where the angle was not a right angle, but was very definitely an acute one. And he saw, apparently, in the more common rectangular symmetry merely what he calls a necessary, but secondary, result of growth. Within the next few years, a number of botanical writers were content to point out further exceptions to Sachs's rule, and in some cases to show that the curvatures of the partition walls, especially such cases of lenticular curvature as we have described, were by no means accounted for by either Hofmeister or Sachs. While within the same period, Sachs himself, and also Rauber, attempted to extend the main generalization to animal tissues. While these writers regarded the form and arrangement of the cell walls as a biological phenomenon, with little if any direct relation to ordinary physical laws, or with but a vague reference to mechanical conditions, the physical side of the case was soon urged by others, with more or less force and cogency. Indeed, the general resemblance between a cellular tissue and a froth had been pointed out long before, by Melsons, who had made an artificial tissue by blowing into a solution of white of egg. In 1886, Berthold published his Protoplasmechanic, in which he definitely adopted the principle of minimal areas, and, following on the lines of Plateau, Compared the forms of many cell surfaces and the arrangement of their partitions with those assumed under surface tension by a system of weightless films. But, as Klebs points out in reviewing Berthold's book, Berthold was careful to stop short of attributing the biological phenomena to a definite mechanical cause. They remained for him, as they had done for Sachs, so many phenomena of growth, or properties of protoplasm. In the same year, but while still apparently unacquainted with Berthold's work, Herrera published a short but very lucid article, in which he definitely ascribed to the cell wall, as Hofmeister had already done, the properties of a semi-liquid film and drew from this as a logical consequence the deduction that it must assume the various configurations which the law of minimal areas imposes on the soap bubble. So what we may call Herrera's law is formulated as follows: a cellular membrane, at the moment of its formation, tends to assume the form which would be assumed, under the same conditions, by a liquid film destitute of weight. Soon afterwards Chabry, in discussing the embryology of the ascidians, indicated many of the points in which the contacts between cells repeat the surface tension phenomena of the soap bubble, and came to the conclusion that part, at least, of the embryological phenomena were purely physical. And the same line of investigation and thought were pursued and developed by Robert, in connection with the embryology of the mollusca. Driesch again, in a series of papers, continued to draw attention to the presence of capillary phenomena in the segmenting cells of various embryos, and came to the conclusion that the mode of segmentation was of little importance as regards the final result. Lastly, de Wildman, in a somewhat wider, but also vaguer generalization than Herrera's, declared that the form of the cellular framework of vegetables, and also of animals, in its essential features, depends upon the forces of molecular physics. Let us return to our problem of the arrangement of partition films. When we have 3 bubbles in contact, instead of 2 as in the case already considered, the phenomenon is strictly analogous to our former case. The 3 bubbles will be separated by 3 partition surfaces, whose curvature will depend upon the relative. Figure 114. Size of the spheres, and which will be plane if the latter are all of the same dimensions. But whether plane or curved, the 3 partitions will meet one another at an angle of 120 degrees, in an axial line. Various pretty geometrical corollaries accompany this arrangement. For instance, if Fig. represent the 3 associated bubbles in a plane drawn through their centers, C, 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 or what is the same thing, if it represent the base of 3 bubbles resting on a plane, then the lines UC, UC, or SC, SC, etc. drawn to the centers from the points of intersection of the circular arcs, will always enclose an angle of 60 degrees. Again, Fig. If we make the angle CUF equal to 60 degrees, and produce UF to meet CC in F, F will be the center of the circular arc which constitutes the partition O, and further, the 3 points F, G, H, successively determined in this Figure 115 manner, will lie on one and the same straight line. In the case of coequal bubbles or cells, as in Fig. B, it is obvious that the lines joining their centers form an equilateral triangle, and consequently, that the center of each circle, or sphere, lies on the circumference of the other 2. It is also obvious that UF is now parallel to CC, and accordingly that the center of curvature of the partition is now infinitely distant, or, as we have already said, that the partition itself is plane. When we have 4 bubbles in conjunction, they would seem to be capable of arrangement in 2 symmetrical ways, either, as in Fig. A, with the 4 partition walls meeting at right angles, or, as in B, with 5 partitions meeting, 3 and 3, at angles of 120 degrees. This latter arrangement is strictly analogous to the arrangement of 3 bubbles in Fig. Now, though both of these figures, from their symmetry, are apparently figures of equilibrium, yet, physically, the former turns out to be of unstable. Figure 116. And the latter of stable equilibrium. If we try to bring our 4 bubbles into the form of Fig. A, such an arrangement endures only for an instant. The partitions glide upon each other, a median wall springs into existence, and the system at once assumes the form of our second figure, B. This is a direct consequence of the law of minimal areas, for it can be shown, by somewhat difficult mathematics, as was first done by Lamarck, that, in dividing a closed space into a given number of chambers by means of partition walls, the least possible area of these partition walls, taken together, can only be attained when they meet together in groups of 3, at equal angles, that is to say at angles of 120 degrees. Wherever we have a true cellular complex, an arrangement of cells in actual physical contact by means of a boundary film, we find this general principle in force. We must only bear in mind that, for its perfect recognition, we must be able to view the object in a plane at right angles to the boundary walls. For instance, in any ordinary section of a vegetable parenchyma, we recognize the appearance of a froth, precisely resembling that which we can construct by imprisoning a mass of soap bubbles in a narrow vessel with flat sides of glass. In both cases we see the cell walls everywhere meeting, by threes, at angles of 120 degrees, irrespective of the size of the individual cells, whose relative size, on the other hand, determines the curvature of the partition walls. On the surface of a honeycomb we have precisely the same conjunction, between cell and cell, of 3 boundary walls, meeting at 120 degrees. In embryology, when we examine a segmenting egg, of 4, or more, segments, we find in like manner, in the great majority of cases, if not in all, that the same principle is still exemplified. The 4 segments do not meet in a common center, but each cell is in contact with 2 others, and the 3, and only 3, common boundary walls meet at the normal angle of 120 degrees. A so-called polar furrow, the visible edge of a vertical partition wall, joins, or separates, the 2 triple contacts, precisely as in Fig. B. In the 4-celled stage of the frog's egg, Rauber, an exceptionally careful observer, shews us 3 alternative modes in which the 4 cells may be found to be conjoined, Fig. In A, we have the commonest arrangement, which is that which we have just studied and found to be the simplest theoretical one. That namely where a straight, polar furrow intervenes, and where, at its extremities, the partition walls are conjoined 3 by 3. In B, we have again a polar furrow, which is now seen to be a portion of the first segmentation furrow, cf. Fig, etc., by which the egg was originally divided into 2, the 4-celled stage being reached by the appearance of the transverse furrows and their corresponding partitions. In this case, the polar furrow is seen to be sinuously curved, and Rauber tells us that its curvature gradually alters, as a matter of fact. It, or rather the partition wall corresponding to it, is gradually setting itself into a position of equilibrium, that is to say of equiangular contact with its neighbors. Which position of equilibrium is already attained or nearly so in Fig. A. In Fig. C, we have a very different condition, with which we shall deal in a moment. Figure 117. Various ways in which the 4 cells are co-arranged in the 4-celled stage of the frog's egg. After Rauber. According to the relative magnitude of the bodies in contact, this polar furrow may be longer or shorter, and it may be so minute as to be not easily discernible. But it is quite certain that no simple and homogeneous system of fluid films such as we are dealing with is in equilibrium without its presence. In the accounts given, however, by embryologists of the segmentation of the egg, while the polar furrow is depicted in the great majority of cases, there are others in which it has not been seen and some in which its absence is definitely asserted. The cases where 4 cells, lying in one plane, meet in a point, such as were frequently figured by the older embryologists, are very difficult to verify, and I have not come across a single clear case in recent literature. Considering the physical stability of the other arrangement, the great preponderance of cases in which it is known to occur, the difficulty of recognizing the polar furrow in cases where it is very small and unless it be specially looked for, and the natural tendency of the draftsman to make an all but symmetrical structure appear wholly so, I am much inclined to attribute to error or imperfect observation all those cases where the junction lines of 4 cells are represented, after the manner of Fig. A, as a simple cross. But while a true 4-rayed intersection, or simple cross, is theoretically impossible, save as a transitory and highly unstable condition, there is another condition which may closely simulate it, and which is common enough. There are plenty of representations of segmenting eggs, in which, instead of the triple junction and polar furrow, the four cells, and in like manner their more numerous successors, are represented as rounded off and separated from one another by an empty space, or by a little drop of an extraneous fluid, evidently not directly miscible with the fluid surfaces of the cells. Such is the case in the obviously accurate figure which Rauber gives, Fig. C, of the third mode of conjunction in the four-celled stage of the frog's egg. Here Rauber is most careful to point out that the furrows do not simply cross, or meet in a point, but are separated by a little space, which he calls the pulgruption, and asserts to be constantly present whensoever the polar furrow, or Brechungslinie, is not to be discerned. This little interposed space, with its contained drop of fluid, materially alters the case, and implies a new condition of theoretical and actual equilibrium. For, on the one hand, we see that now the four intercellular partitions do not meet one another at all, but really impinge upon four new and separate partitions, which constitute interfacial contacts, not between cell and cell, but between the respective cells and the intercalated drop. And secondly, the angles at which these four little surfaces will meet the four cell partitions, will be determined, in the usual way, by the balance between the respective tensions of these several surfaces. In an extreme case, as in some pollen grains, it may be found that the cells under the observed circumstances are not truly in surface contact, that they are so many drops which touch but do not wet one another, and which are merely held together by the pressure of the surrounding envelope. But even supposing, as is in all probability the actual case, that they are in actual fluid contact, the case from the point of view of surface tension presents no difficulty. In the case of the conjoined soap bubbles, we were dealing with similar contacts and with equal surface tensions throughout the system. But in the system of protoplasmic cells which constitute the segmenting egg we must make allowance for an inequality of tensions, between the surfaces where cell meets cell, and where on the other hand cell surface is in contact with the surrounding medium, in this case generally water or one of the fluids of the body. Remember that our general condition is that, in our entire Figure 118 system, the sum of the surface energies is a minimum. And, while this is attained by the sum of the surfaces being a minimum in the case where the energy is uniformly distributed, it is not necessarily so under non-uniform conditions. In the diagram, Fig. If the energy per unit area be greater along the contact surface CC, where cell meets cell, than along CA or CB, where cell surface is in contact with the surrounding medium, these latter surfaces will tend to increase and the surface of cell contact to diminish. In short, there will be the usual balance of forces between the tension along the surface CC, and the two opposing tensions along CA and CB. If the former be greater than either of the other two, the outside angle will be less than 120 degrees. And if the tension along the surface CC be as much or more than the sum of the other two, then the drops will stand in contact only, save for the possible effect of external pressure, at a point. This is the explanation, in general terms, of the peculiar conditions obtaining in nostoc and its allies, P, and it also leads us to a consideration of the general properties and characters of an epidermal layer. While the inner cells of the honeycomb are symmetrically situated, sharing with their neighbors in equally distributed pressures or tensions, and therefore all tending with great accuracy to identity of form, the case is obviously different with the cells at the borders of the system. So it is, in like manner, with our froth of soap bubbles. The bubbles, or cells, in the interior of the mass are all alike in general character, and if they be equal in size are alike in every respect, their sides are uniformly flattened, and tend to meet at equal angles of 120 degrees. But the bubbles which constitute the outer layer retain their spherical surfaces, which however still tend to meet the partition walls connected with them at constant angles of 120 degrees. This outer layer of bubbles, which forms the surface of our froth, constitutes after a fashion what we should call in botany an epidermal layer. But in our froth of soap bubbles we have, as a rule, the same kind of contact, that is to say, contact with air, both within and without the bubbles. While in our living cell, the outer wall of the epidermal cell is exposed to air on the one side, but is in contact with the Figure 119. Protoplasm of the cell on the other, and this involves a difference of tensions, so that the outer walls and their adjacent partitions are no longer likely to meet at equal angles of 120 degrees. Moreover, a chemical change, due for instance to oxidation or possibly also to adsorption, is very likely to affect the external wall, and may tend to its consolidation. And this process, as we have seen, is tantamount to a large increase, and at the same time an equalization, of tension in that outer wall. And will lead the adjacent partitions to impinge upon it at angles more and more nearly approximating to 90 degrees, the bubble-like, or spherical, surfaces of the individual cells being more and more flattened in consequence. Lastly, the chemical changes which affect the outer walls of the superficial cells may extend, in greater or less degree, to their inner walls also, with the result that these cells will tend to become more or less rectangular throughout, and will cease to dovetail into the interstices of the next subjacent layer. These then are the general characters which we recognize in an epidermis. And we perceive that the fundamental character of an epidermis simply is that it lies on the outside, and that its main physical characteristics follow, as a matter of course, from the position which it occupies and from the various consequences which that situation entails. We have however by no means exhausted the subject in this short account, for the botanist is accustomed to draw a sharp distinction between a true epidermis and what is called epidermal tissue. The latter, which is found in such a seaweed as laminaria and in very many other cryptogamic plants, consists, as in the hypothetical case we have described, of a more or less simple and direct modification of the general or fundamental tissue. But a true epidermis, such as we have it in the higher plants, is something with a long morphological history, something which has been laid down or differentiated in an early stage of the plant's growth, and which afterwards retains its separate and independent character. We shall see presently that a physical reason is again at hand to account, under certain circumstances, for the early partitioning off, from a mass of embryonic tissue, of an outer layer of cells which from their first appearance are marked off from the rest by their rectangular and flattened form. We have hitherto considered our cells, or bubbles, as lying in a plane of symmetry, and further, we have only considered the appearance which they present as projected on that plane, in simpler words. We have been considering their appearance in surface or in sectional view. But we have further to consider them as solids, whether they be still grouped in relation to a single plane, like the 4 cells in Fig, or heaped upon one another, as for instance in a tetrahedral form like 4 cannonballs. And in either case we have to pass from the problems of plane to those of solid geometry. In short, the further development of our theme must lead us along 2 paths of inquiry, which continually intercross, namely, 1. The study of more complex cases of partition and of contact in a plane, and 2. The whole question of the surfaces and angles presented by solid figures in symmetrical juxtaposition. Let us take a simple case of the latter kind, and again afterwards, so far as possible, let us try to keep the 2 themes separate. Where we have 3 spheres in contact, as in Fig or in either half of Fig. B. Let us consider the point of contact, O, Fig, not as a point in the plane section of the diagram, but as a point where 3 furrows meet on the surface of the system. At this point, 3 cells meet. But it is also obvious that there meet here 6 surfaces, namely the outer, spherical walls of the 3 bubbles, and the 3 partition walls which divide them, 2 and 2. Also, 4 lines or edges meet here, viz. the 3 external arcs which form the outer boundaries of the partition walls, and which correspond to what we commonly call the furrows in the segmenting egg. And as a 4th edge, the iris or junction of the 3 partitions, perpendicular to the plane of the paper, where they all 3 meet together, as we have seen, at equal angles of 120 degrees. Lastly, there meet at the point 4 solid angles, each bounded by 3 surfaces, to wit, within each bubble a solid angle bounded by 2 partition walls and by the surface wall. And, fourthly, an external solid angle bounded by the outer surfaces of all three bubbles. Now in the case of the soap bubbles, whose surfaces are all in contact with air, both outside and in, the 6 films meeting at the point, whether surface films or partition films, are all similar, with similar tensions. In other words, the tensions, or forces, acting at the point are all similar and symmetrically arranged, and it at once follows from this that the angles, solid as well as plane, are all equal. It is also obvious that, as regards the point of contact, the system will still be symmetrical, and its symmetry will be quite unchanged, if we add a 4th bubble in contact with the other 3, that is to say, if where we had merely the outer air before, we now replace it by the air in the interior of another bubble. The only difference will be that the pressure exercised by the walls of this 4th bubble will alter the curvature of the surfaces of the others, so far as it encloses them. And, if all 4 bubbles be identical in size, these surfaces which formerly we called external and which have now come to be internal partitions, will, like the others, be flattened by equal and opposite pressure, into planes. We are now dealing, in short, with 6 planes, meeting symmetrically in a point, and constituting their 4 equal solid angles. Figure 120. If we make a wire cage, in the form of a regular tetrahedron, and dip it into soap solution, then when we withdraw it we see that to each one of the 6 edges of the tetrahedron, i.e. to each one of the 6 wires which constitute the little cage, a film has attached itself, and these 6 films meet internally at a point, and constitute in every respect the symmetrical figure which we have just been describing. In short, the system of films we have hereby automatically produced is precisely the system of partition walls which exist in our tetrahedral aggregation of 4 spherical bubbles, precisely the same, that is to say, in the neighborhood of the meeting point, and only differing in that we have made the wires of our tetrahedron straight, instead of imitating the circular arcs which actually form the intersections of our bubbles. This detail we can easily introduce in our wire model if we please. Let us look for a moment at the geometry of our figure. Let O, Fig, be the center of the tetrahedron, i.e. the center of symmetry where our films meet. And let OA, OB, OC, OD, be lines drawn to the 4 corners of the tetrahedron. Produce AO to meet the base in P, then APD is a right-angled triangle. It is not difficult to prove that in such a figure, O, the center of gravity of the system, lies just 3/4 of the way between an apex, A, and a point, P, which is the center of gravity of the opposite base. Therefore, OP equals OA3 equals OD3. Therefore, cos DOP equals 1/3 and cos AOD equals 1/3. That is to say, the angle AOD is just, as nearly as possible, 109 degrees 28/16. This angle, then, of 109 degrees 28/16, or very nearly 109 degrees and a half, is the angle at which, in this and every other solid system of liquid films, the edges of the partition walls meet one another at a point. It is the fundamental angle in the solid geometry of our systems, just as 120 degrees was the fundamental angle of symmetry so long as we considered only the plane projection, or plane section, of 3 films meeting in an edge. Out of these 2 angles, we may construct a great variety of figures, plane and solid, which become all the more varied and complex when, by considering the case of unequal as well as equal cells, we admit curved, e.g. spherical, as well as plane boundary surfaces. Let us consider some examples and illustrations of these, beginning with those which we need only consider in reference to a plane. Let us imagine a system of equal cylinders, or equal spheres, in contact with one another in a plane, and represented in section by the equal and contiguous circles of Fig. I borrow my figure, by the way, from an old Italian naturalist, Bonanni, contemporary of Borelli, of Hay and Willoughby and of Martin Lister, who dealt with this matter in a book chiefly devoted to molluscan shells. It is obvious, as a simple geometrical fact, that each of these equal circles is in contact with 6 surrounding circles. Imagine now that the whole system comes under some uniform stress. It may be of uniform surface tension at the boundaries of all the cells, it may be of pressure caused by uniform growth or expansion within the cells, or it may be due to some uniformly applied constricting pressure from without. In all of these cases the points of contact between the circles in the diagram will be extended into lines of contact, representing surfaces of contact in the actual spheres or cylinders. And the equal circles of our diagram will be converted into regular and equal hexagons. The angles of these hexagons, at each of which 3 hexagons meet, are of course angles of 120 degrees. So far as the form is concerned, so long as we are concerned only with a morphological result and not with a physiological process, the result is precisely the same whatever be the force which brings the bodies together in symmetrical apposition. It is by no means necessary for us, in the first instance, even to inquire whether it be surface tension or mechanical pressure or some other physical force which is the cause, or the main cause, of the phenomenon. Figure 121. Diagram of hexagonal cells. After Bonanni. The production by mutual interaction of polyhedral cells, which, under conditions of perfect symmetry, become regular hexagons, is very beautifully illustrated by Prof. Bernard's Tourbillon's Cellulaires, cf. page 259, and also in some of Leduc's diffusion experiments. A weak, 5%, solution of gelatin is allowed to set on a plate of glass, and little drops of a 5 or 10% solution of ferrocyanide of potassium are then placed at regular intervals upon the gelatin. Immediately each little drop becomes the center, or pole, of a system of diffusion currents, and the several systems conflict with and repel one another, so that presently each little area becomes the seat of a double current system. From its center outwards and back again. Until at length the concentration of the field becomes equalized and the currents. Figure 122. An artificial tissue, formed by colored drops of sodium chloride solution diffusing in a less dense solution of the same salt. After Leduc. Fig. 123, an artificial cellular tissue. Formed by the diffusion in gelatin of drops of a solution of potassium ferrocyanide. After Leduc. Cease. After equilibrium is attained, and when the gelatinous mass is permitted to dry, we have an artificial tissue of more or less regularly hexagonal cells, which simulate in the closest way an organic parenchyma. And by varying the experiment, in ways which Leduc describes, we may simulate various forms of tissue, and produce cells with thick walls or with thin, cells in close contact or with wide intercellular spaces, cells with plane or with curved partitions, and so forth. The hexagonal pattern is illustrated among organisms in countless cases, but those in which the pattern is perfectly regular, by reason of perfect uniformity of force and perfect equality of the individual cells, are not so numerous. The hexagonal epithelium cells of the pigment layer of the eye, external to the retina, are a good example. Here we have a single layer of uniform cells, reposing on the one hand upon a basement membrane, supported. Figure 124. Epidermis of Gerardia. After Goebel. Behind by the solid wall of the sclerotic, and exposed on the other hand to the uniform fluid pressure of the vitreous humor. The conditions all point, and lead, to a perfectly symmetrical result, that is to say, the cells, uniform in size, are flattened out to a uniform thickness by the fluid pressure acting radially. And their reaction on each other converts the flattened discs into regular hexagons. In an ordinary columnar epithelium, such as that of the intestine, we see again that the columnar cells have been compressed into hexagonal prisms. But here as a rule the cells are less uniform in size, small cells are apt to be intercalated among the larger, and the perfect symmetry is accordingly lost. The same is true of ordinary vegetable parenchyma. The originally spherical cells are approximately equal in size, but only approximately, and there are accordingly all degrees in the regularity and symmetry of the resulting tissue. But obviously, wherever we have, in addition to the forces which tend to produce the regular hexagonal symmetry, some other asymmetrical component arising from growth or traction, then our regular hexagons will be distorted in various simple ways. This condition is illustrated in the accompanying diagram of the epidermis of Gerardia. It also accounts for the more or less pointed or fusiform cells, each still in contact, as a rule, with 6 others, which form the epithelial lining of the blood vessels, and other similar, or analogous, instances are very common. Figure 125. Soap froth under pressure. After Rumbler. In a soap froth imprisoned between 2 glass plates, we have a symmetrical system of cells, which appear in optical section, as in Fig. B, as regular hexagons. But if we press the plates a little closer together, the hexagons become deformed or flattened, Fig. A. In this case, however, if we cease to apply further pressure, the tension of the films throughout the system soon adjusts itself again, and in a short time the system has regained the former symmetry of Fig. B. Figure 126. From leaf of Elodia canadensis. After birth old. In the growth of an ordinary dicotyledonous leaf, we once more see reflected in the form of its epidermal cells the tractions, irregular but on the whole longitudinal, which growth has superposed on the tensions of the partition walls, Fig. In the narrow elongated leaf of a monocotyledon, such as a hyacinth, the elongated, apparently quadrangular cells of the epidermis appear as a necessary consequence of the simpler laws of growth which gave its simple form to the leaf as a whole. In this last case, however, as in all the others, the rule still holds that only 3 partitions, in surface view, meet in a point. And at their point of meeting the walls are for a short distance manifestly curved, so as to permit the junction to take place at or nearly at the normal angle of 120 degrees. Briefly speaking, wherever we have a system of cylinders or spheres, associated together with sufficient mutual interaction to bring them into complete surface contact, there, in section or in surface view, we tend to get a pattern of hexagons. While the formation of an hexagonal pattern on the basis of ready-formed and symmetrically arranged material units is a very common, and indeed the general way, it does not follow that there are not others by which such a pattern can be obtained. For instance, if we take a little triangular dish of mercury and set it vibrating, either by help of a tuning fork, or by simply tapping on the sides, we shall have a series of little waves or ripples starting inwards from each of the 3 faces. And the intercrossing, or interference of these 3 sets of waves produces crests and hollows, and intermediate points of no disturbance, whose loci are seen as a beautiful pattern of minute hexagons. It is possible that the very minute and astonishingly regular pattern of hexagons which we see, for instance, on the surface of many diatoms, may be a phenomenon of this order. The same may be the case also in our cella, where an apparently hexagonal pattern is found not to consist of simple hexagons, but of straight lines in 3 sets of parallels. The lines of each set making an angle of 60 degrees with those of the other 2 sets. We must also bear in mind, in the case of the minuter forms, the large possibilities of optical illusion. For instance, in one of Abbe's diffraction plates, a pattern of dots, set at equal interspaces, is reproduced on a very minute scale by photography. But under certain conditions of microscopic illumination and focusing, these isolated dots appear as a pattern of hexagons. A symmetrical arrangement of hexagons, such as we have just been studying, suggests various simple geometrical corollaries, of which the following may perhaps be a useful one. We may sometimes desire to estimate the number of hexagonal areas or facets in some structure where these are numerous, such for instance as the cornea of an insect's eye, or in the minute pattern of hexagons on many diatoms. An approximate enumeration is easily made as follows. For the area of a hexagon, if we call delta the short diameter, that namely which bisects 2 of the opposite sides, is delta 2 times 3, 2, the area of a circle being d2 pi 4. Then, if the diameter, d, of a circular area include n hexagons, the area of that circle equals, n, delta, 2 times pi 4. And, dividing this number by the area of a single hexagon, we obtain for the number of areas in the circle, each equal to a hexagonal facet, the expression n 2 times pi 4 by 2 3 equals 0,907 n2, or 910, N2, nearly. This calculation deals, not only with the complete facets, but with the areas of the broken hexagons at the periphery of the circle. If we neglect these latter, and consider our whole field as consisting of successive rings of hexagons about a central one, we may obtain a still simpler rule. For obviously, around our central hexagon there stands a zone of 6, and around these a zone of 12, and around these a zone of 18, and so on. And the total number, excluding the central hexagon, is accordingly 4. 1 zone is equal to 2 times 3. Is equal to 3 times 1 times 2. 2 zones is equal to 3 times 6. Is equal to 3 times 2 times 3. 3 zones is equal to 4 times 9. Is equal to 3 times 3 times 4. 4 zones is equal to 5 times 12. Is equal to 3 times 4 times 5. 5 zones is equal to 6 times 15. Is equal to 3 times 5 times 6. And so forth. If n be the number of zones, and if we add 1 to the above numbers for the odd central hexagon, the rule evidently is, that the total number, h, equals 3n, n plus 1, plus 1. Thus, if in a preparation of a fly's cornea, I can count 25 facets in a line from a central one, the total number in the entire circular field is 3 by 25 by 26, plus 1 is equal to 1951. The same principles which account for the development of hexagonal symmetry hold true, as a matter of course, not only of individual cells, in the biological sense, but of any close-packed bodies of uniform size and originally circular outline. And the hexagonal pattern is therefore of very common occurrence, under widely different circumstances. The curious reader may consult Sir Thomas Browne's quaint and beautiful account, in the Garden of Cyrus, of hexagonal, and also of quincuntial, symmetry in plants and animals, which doth neatly declare how nature geometrizeth and observeth order in all things. We have many varied examples of this principle among corals, wherever the polyps are in close juxtaposition, with neither empty space nor accumulations of matrix between their adjacent walls. Favosites gothlandica, for instance, furnishes us with an excellent example. In the great genus Lithostrotion we have some species that are massive and others that are fasciculate. In other words, in some the long cylindrical corallites are in close contact with one another, and in others they are separate and loosely bundled, Fig. Accordingly in the former the corallites are. Figure 127. Lithostrotion Martini. After Nicholson. Figure 128. Cyathophilum hexagonum. From Nicholson, after Zittel. Squeezed into hexagonal prisms, while in the latter they retain their cylindrical form. Where the polyps are comparatively few, and so have room to spread, the mutual pressure ceases to work or only tends to push them asunder, letting them remain circular in outline, e.g. Thecosmilia. Where they vary gradually in size, as for instance in Cyathophilum hexagonum, they are more or less hexagonal but are not regular hexagons. And where there is greater and more irregular variation in size, the cells will be on the average hexagonal, but some will have fewer and some more sides than 6, as in the annexed figure of Arachnophyllum, Fig. Where larger and smaller cells, corresponding to two different kinds of zooids, are mixed together, we may get various results. If the larger cells are numerous enough to be more or less in contact with one another, e.g. various monticulipari, they will be irregular hexagons, while the smaller cells between them will be crushed into all manner of irregular angular forms. If on the other hand the large cells are comparatively few and are large and strong-walled compared with their smaller neighbors, then the latter alone will be squeezed into hexagons, while the larger ones will tend to retain their circular outline undisturbed, e.g. Helioptera, Heliolites, etc. Figure 129. Arachnophyllum pentagonum. After Nicholson. Figure 130. Heliolites. After Woods. When, as happens in certain corals, the peripheral walls or thecae of the individual polyps remain undeveloped but the radiating septa are formed and calcified, then we obtain new and beautiful mathematical configurations, Fig. For the radiating septa are no longer confined to the circular or hexagonal bounds of a polypite, but tend to meet and become confluent with their neighbors on every side. And, tending to assume positions of equilibrium, or of minimal area, under the restraints to which they are subject, they fall into congruent curves. And these correspond, in a striking manner, to the lines of force running, in a common field of force, between a number of secondary centers. Similar patterns may be produced in various ways, by the play of osmotic or magnetic forces. And a particular and very curious case is to be found in those complicated forms of nuclear division known as triasters, polyasters, etc., whose relation to a field of force Hartog has explained. It is obvious that, in our corals, these curving septa are all orthogonal to the non-existent hexagonal boundaries. As the phenomenon is wholly due to the imperfect development or non-existence of a thecal wall, it is not surprising that we find identical configurations among various corals, or families of corals, not otherwise related to one another. We find the same or very similar patterns displayed, for instance, in Synhelia, Oculinity, in Phylloxastria, rugosa, in Thamnostria, Fungida, and in many more. The most famous of all hexagonal conformations and perhaps the most beautiful is that of the bee's cell. Here we have, as in Figure 131, surface views of corals with undeveloped thecae and confluent septa. A. Thamnostria. B. Comaceris. From Nicholson, after Zittel. Our last examples, a series of equal cylinders, compressed by symmetrical forces into regular hexagonal prisms. But in this case we have two rows of such cylinders, set opposite to one another, end to end. And we have accordingly to consider also the conformation of their ends. We may suppose our original cylindrical cells to have spherical ends, which is their normal and symmetrical mode of termination. And, for closest packing, it is obvious that the end of any one cylinder will touch, and fit in between, the ends of three cylinders in the opposite row. It is just as when we pile round shot in a heap. Each sphere that we set down fits into its nest between three others, and the four form a regular tetrahedral arrangement. Just as it was obvious, then, that by mutual pressure from the six laterally adjacent cells, any one cell would be squeezed into a hexagonal prism, so is it also obvious that, by mutual pressure against the three terminal neighbors, the end of any one cell will be compressed into a solid trihedral angle whose edges will meet, as in the analogous case already described of a system of soap bubbles, at a plane angle of 109 degrees and so many minutes and seconds. What we have to comprehend, then, is how the six sides of the cell are to be combined with its three terminal facets. This is done by beveling off three alternate angles of the prism, in a uniform manner, until we have tapered the prism to a point. And by so doing, we evidently produce three rhombic surfaces, each of which is double of the triangle formed by joining the apex to the three untouched angles of the prism. If we experiment, not with cylinders, but with spheres, if for instance we pile together a mass of bread pills, or pills of plasticine, and then submit the whole to a uniform pressure, it is obvious that each ball, like the seeds in a pomegranate, as Kepler said, will be in contact with 12 others, 6 in its own plane, 3 below and 3 above, and in compression it will therefore develop 12 plane surfaces. It will in short repeat, above and below, the conditions to which the bee's cell is subject at one end only. And, since the sphere is symmetrically situated towards its neighbors on all sides, it follows that the 12 plane sides to which its surface has been reduced will be all similar, equal and similarly situated. Moreover, since we have produced this result by squeezing our original spheres close together, it is evident that the bodies so formed completely fill space. The regular solid which fulfills all these conditions is the rhombic dodecahedron. The bee's cell, then, is this figure incompletely formed. It is a hexagonal prism with one open or unfinished end, and one trihedral apex of a rhombic dodecahedron. The geometrical form of the bee's cell must have attracted the attention and excited the admiration of mathematicians from time immemorial. Pappus the Alexandrine has left us, in the introduction to the 5th book of his collections, an account of its hexagonal plan, and he drew from its mathematical symmetry the conclusion that the bees were endowed with reason, there being then 3 figures which of themselves can fill up the space round a point, viz. the triangle, the square and the hexagon. The bees have wisely selected for their structure that which contains most angles, suspecting indeed that it could hold more honey than either of the other two. Erasmus Bartholinus was apparently the first to suggest that this hypothesis was not warranted, and that the hexagonal form was no more than the necessary result of equal pressures, each bee striving to make its own little circle as large as possible. The investigation of the ends of the cell was a more difficult matter, and came later, than that of its sides. In general terms this arrangement was doubtless often studied and described, as for instance, in the Garden of Cyrus, and the combs themselves so regularly contrived that their mutual intersections make 3 lozenges at the bottom of every cell, which severally regarded make 3 rows of neat rhomboidal figures, connected at the angles, and so continue 3 several chains throughout the whole comb. But Maraldi, Cassini's nephew, was the first to measure the terminal solid angle or determine the form of the rhombs in the pyramidal ending of the cell. He tells us that the angles of the rhomb are 110 degrees and 70 degrees. Chaque base d'alvéole est formé par 3 rhombs presque toujours égaux semblables, que, suivant les mesures que nous avons prises, ont les 2 angles obtus chacun de 110 degrees. Et par conséquent les 2 angles chacun de 70 degrees. He also stated that the angles of the trapeziums which form the sides of the body of the cell were identical angles, of 110 degrees and 70 degrees, but in the same paper he speaks of the angles as being, respectively, 109 degrees 28 and 70 degrees 32. Here a singular confusion at once arose, and has been perpetuated in the books. Unfortunately Réaumur chose to look upon this second determination of Maraldi's as being, as well as the first, a direct result of measurement, whereas it is in reality theoretical. He speaks of it as Maraldi's more precise measurement, and this error has been repeated in spite of its absurdity to the present day. Nobody appears to have thought of the impossibility of measuring such a thing as the end of a bee's cell to the nearest minute. At any rate, it now occurred to Réaumur, as curiously enough, it had not done to Maraldi, that, just as the closely packed hexagons gave the minimal extent of boundary in a plane, so the actual solid figure, as determined by Maraldi, might be that which, for a given solid content, gives the minimum of surface, or which, in other words, would hold the most honey for the least wax. He set this problem before Koenig, and the geometer confirmed his conjecture, the result of his calculations agreeing within 2 minutes, 109 degrees 26 and 70 degrees 34, with Maraldi's determination. But again, Maclaurin and Lullier, by different methods, obtained a result identical with Maraldi's, and were able to shew that the discrepancy of 2 was due. Figure 132. To an error in Koenig's calculation, of tan theta equals 2, that is to say to the imperfection of his logarithmic tables, not, as the books say, to a mistake on the part of the bee. Not to a mistake on the part of Maraldi, is, of course, all that we are entitled to say. The theorem may be proved as follows. ABCDF is a right prism upon a regular hexagonal base. The corners BDF are cut off by planes through the lines AC, CE, EA, meeting in a point V on the axis Vn of the prism, and intersecting BB, DD, FF, at X, Y, Z. It is evident that the volume of the figure thus formed is the same as that of the original prism with hexagonal ends. For, if the axis cut the hexagon ABCDEF in N, the volumes ACVN, ACBX are equal. It is required to find the inclination of the faces forming the trihedral angle at V to the axis, such that the surface of the figure may be a minimum. Let the angle NVX, which is half the solid angle of the prism, equals theta. The side of the hexagon, as AB, equals A, and the height, as AA, equals H. Then AC equals 2a cos 30 degrees equals a 3. And Vx equals a sin theta, from inspection of the triangle LXB. Therefore the area of the rhombus VXC equals a 2 3, 2 sin theta. And the area of OBX equals a 2, 2h 1/2 Vx cos theta. Equals a 2, 2h a 2 cot theta. Therefore the total area of the figure equals hexagon ABCDEF plus 3a, 2h, a 2, cot theta. Plus 3a 2 3, 2 sin theta. Therefore D, area, d theta. Equals 3a 2 2, 1 sin 2 theta. 3 cosine theta, sine 2 theta. But this expression vanishes, that is to say, d, area, d theta equals 0, when cos theta equals 1 3, that is when theta equals 54 degrees 44 8. Equals 1/2, 109 degrees 28 16. This then is the condition under which the total area of the figure has its minimal value. That the beautiful regularity of the bee's architecture is due to some automatic play of the physical forces, and that it were fantastic to assume, with Pappus and Réaumur, that the bee intentionally seeks for a method of economizing wax, is certain, but the precise manner of this automatic action is not so clear. When the hive bee builds a solitary cell, or a small cluster of cells, as it does for those eggs which are to develop into queens, it makes but a rude production. The queen cells are lumps of coarse wax hollowed out and roughly bitten into shape, bearing the marks of the bee's jaws, like the marks of a blunt adze on a rough-hewn log. Omitting the simplest of all cases, when, as among some humble bees, the old cocoons are used to hold honey, the cells built by the solitary wasps and bees are of various kinds. They may be formed by partitioning off little chambers in a hollow stem, they may be rounded or oval capsules, often very neatly constructed, out of mud, or vegetable fiber or little stones, agglutinated together with a salivary glue. But they shew, except for their rounded or tubular form, no mathematical symmetry. The social wasps and many bees build, usually out of vegetable matter chewed into a paste with saliva, very beautiful nests of combs. And the close-set papery cells which constitute these combs are just as regularly hexagonal as are the waxen cells of the hive bee. But in these cases, or nearly all of them, the cells are in a single row. Their sides are regularly hexagonal, but their ends, from the want of opponent forces, remain simply spherical. In Melipona domestica, of which Darwin epitomizes Pierre Huber's description, the large waxen honey cells are nearly spherical, nearly equal in size, and are aggregated into an irregular mass. But the spherical form is only seen on the outside of the mass, for inwardly each cell is flattened into 2, 3, or more flat surfaces, according as the cell adjoins 2, 3, or more other cells. When one cell rests on 3 other cells, which from the spheres being nearly of the same size is very frequently and necessarily the case, the 3 flat surfaces are united into a pyramid. And this pyramid, as Huber has remarked, is manifestly a gross imitation of the 3-sided pyramidal base of the cell of the hive bee. The question is, to what particular force are we to ascribe the plane surfaces and definite angles which define the sides of the cell in all these cases, and the ends of the cell in cases where one row meets and opposes another? We have seen that Bartholin suggested, and it is still commonly believed, that this result is due to simple physical pressure, each bee enlarging as much as it can the cell which it is building, and nudging its wall outwards till it fills every intervening gap and presses hard against the similar efforts of its neighbor in the cell next door. But it is very doubtful whether such physical or mechanical pressure, more or less intermittently exercised, could produce the all but perfectly smooth plane surfaces and the all but perfectly definite and constant angles which characterize the cell, whether it be constructed of wax or papery pulp. It seems more likely that we have to do with a true surface tension effect. In other words, that the walls assume their configuration when in a semi-fluid state, while the papery pulp is still liquid, or while the wax is warm under the high temperature of the crowded hive. Under these circumstances, the direct efforts of the wasp or bee may be supposed to be limited to the making of a tubular cell, as thin as the nature of the material permits, and packing these little cells as close as possible together. It is then easily conceivable that the symmetrical tensions of the adjacent films, though somewhat retarded by viscosity, should suffice to bring the whole system into equilibrium. That is to say, into the precise configuration which the comb actually presents. In short, the Maraldi pyramids which terminate the bee's cell are precisely identical with the facets of a rhombic dodecahedron. Such as we have assumed to constitute, and which doubtless under certain conditions do constitute, the surfaces of contact in the interior of a mass of soap bubbles or of uniform parenchymatous cells. And there is every reason to believe that the physical explanation is identical, and not merely mathematically analogous. The remarkable passage in which Buffon discusses the bee's cell and the hexagonal configuration in general is of such historical importance, and tallies so closely with the whole trend of our inquiry, that I will quote it in full. Durée encore un mot. CES cellules de bilis, tant vantes, tant admires, me fournissent un preuve de plus contre l'enthousiasme et l'admiration. Cette figure, tout géométrique et tout régulière qu'elle nous paraît, et qu'elle est en effet dans la spéculation, n'est ici qu'un résultat mécanique et assez imparfait que s'y trouve souvent dans la nature. Et qu'elle en remarque même dans les productions les plus brutes. Les Christox et plusieurs autres pierres, quelques cells, etc., prenant constamment cette figure dans leur formation. Qu'on observe les petites écailles de la peau d'une recette, on verra qu'elles sont hexagons, parce que chaque écaille croissante en même temps s'y fait obstacle. Et tend à occuper le plus d'espace qu'il est possible dans un espace don, on voit ces mêmes hexagons dans le second estomac de animaux ruminants, on les trouve dans les grains, dans leurs capsules, dans certaines fleurs, etc. Qu'on remplisse un vaisseau de poise, au plutôt de quelque autre grain cylindrique, et qu'on le ferme exactement après y avoir vers autant d'eau que les intervalles correspondent entre ces grains peuvent en recevoir. Qu'on fasse bouillir cette eau, tous ces cylindres deviendront de colonnes à six pans. On y voit clairement la raison, que est purement mécanique. Chaque grain, dont la figure est cylindrique, tend par son renflement à occuper le plus d'espace possible dans un espace don, elles deviennent donc tous nécessairement hexagons par la compression réciproque. Chaque habile church à occuper de même le plus d'espace possible dans un espace don Illinois est donc nécessaire aussi, puisque le corps de bilis est cylindrique, que leurs cellules sont hexagons, par la même raison de obstacles réciproques. On donne plus d'esprit aux muchas dont les ouvrages sont les plus réguliers, les habiles sont, dit-on, plus ingénieuses que les équipes, que les freelands, etc. Que savant aussi l'architecture, mais dont les constructions sont plus grossières et plus irrégulières que celles de habiles, on ne veut pas voir, ou l'on ne doute pas que cette régularité, plus ou moins grande, dépend uniquement du nombre et de la figure, et nullement de l'intelligence de ces petites bêtes. Plus elles sont nombreuses, plus il y a de forces que agissent également et s'opposent de même, plus il y a par conséquent de contraintes mécaniques, de régularité forcée, et de perfection apparente dans leurs productions. A very beautiful hexagonal symmetry, as seen in section, or dodecahedral, as viewed in a solid, is presented by the cells which form the pith of certain rushes, e.g. Juncus effusus, and somewhat less diagrammatically by those which make the pith of the banana. These cells are stellate in form, and the tissue presents in section the appearance of a network of six-rayed stars, Fig. C, linked together by the tips of the rays, and separated by symmetrical, air-filled, intercellular spaces. In thick sections, the solid 12-rayed stars may be very beautifully seen under the binocular microscope. Figure 133. Diagram of development of stellate cells, in pith of Juncus. The dark, or shaded, areas represent the cells, the light areas being the gradually enlarging. Intercellular spaces. What has happened here is not difficult to understand. Imagine, as before, a system of equal spheres all in contact, each one therefore touching 6 others in an equatorial plane, and let the cells be not only in contact, but become attached at the points of contact. Then instead of each cell expanding, so as to encroach on and fill up the intercellular spaces, let each cell tend to contract or shrivel up, by the withdrawal of fluid from its interior. The result will obviously be that the intercellular spaces will increase, the 6 equatorial attachments of each cell, Fig. A, or its 12 attachments in all, to adjacent cells, will remain fixed, and the portions of cell wall between these points of attachment will be withdrawn in a symmetrical fashion, B, towards the center. As the final result, C, we shall have a dodecahedral star, or star polygon, which appears in section as a 6-rayed figure. It is obviously necessary that the pith cells should not only be attached to one another, but that the outermost layer should be firmly attached to a boundary wall, so as to preserve the symmetry of the system. What actually occurs in the rush is tantamount to this, but not absolutely identical. Here it is not so much the pith cells which tend to shrivel within a boundary of constant size, but rather the boundary wall, that is, the peripheral ring of woody in other tissues, which continues to expand after the pith cells which it encloses have ceased to grow or to multiply. The 12 points of attachment on the spherical surface of each little pith cell are uniformly drawn asunder, but the content, or volume, of the cell does not increase correspondingly. And the remaining portions of the surface, accordingly, shrink inwards and gradually constitute the complicated surface of a 12-pointed star, which is still a symmetrical figure and is still also a surface of minimal area under the new conditions. A few years after the publication of Plateau's book, Lord Kelvin shewed, in a short but very beautiful paper, that we must not hastily assume from such arguments as the foregoing, that a close-packed assemblage of rhombic dodecahedra will be the true and general solution of the problem of dividing space with a minimum partitional area, or will be present in a cellular liquid foam, in which it is manifest that the problem is actually and automatically solved. The general mathematical solution of the problem, as we have already indicated, is, that every interface or partition wall must have constant curvature throughout. That where such partitions meet in an edge, they must intersect at angles such that equal forces, in planes perpendicular to the line of intersection, shall balance. And finally, that no more than 3 such interfaces may meet in a line or edge, whence it follows that the angle of intersection of the film surfaces must be exactly 120 degrees. An assemblage of equal and similar rhombic dodecahedra goes far to meet the case, it completely fills up space. All its surfaces or interfaces are planes, that is to say, surfaces of constant curvature throughout. And these surfaces all meet together at angles of 120 degrees. Nevertheless, the proof that our rhombic dodecahedron, such as we find exemplified in the bee's cell, is a surface of minimal area, is not a comprehensive proof. It is limited to certain conditions, and practically amounts to no more than this, that of the regular solids, with all sides plane and similar, this one has the least surface for its solid content. Figure 134. The rhombic dodecahedron has 6 tetrahedral angles, and 8 trihedral angles. And it is obvious, on consideration, that at each of the former 6 dodecahedra meet in a point, and that, where the 4 tetrahedral facets of each coalesce with their neighbors, we have 12 plane films, or interfaces, meeting in a point. In a precisely similar fashion, we may imagine 12 plane films, drawn inwards from the 12 edges of a cube, to meet at a point in the center of the cube. But, as Plateau discovered, when we dip a cubical wire skeleton into soap solution and take it out again, the 12 films which are thus generated do not meet in a point, but are grouped around a small central, plane, quadrilateral film, Fig. In other words, 12 plane films, meeting in a point, are essentially unstable. If we blow upon our artificial film system, the little quadrilateral alters its place, setting itself parallel now to one and now to another of the paired faces of the cube, but we never get rid of it. Moreover, the size and shape of the quadrilateral, as of all the other films in the system, are perfectly definite. Of the 12 films, which we had expected to find all plane and all similar, for are plane isosceles triangles, and 8 are slightly curved quadrilateral figures. The former have 2 curved sides, meeting at an angle of 109 degrees 28, and their apices coincide with the corners of the central quadrilateral, whose sides are also curved, and also meet at this identical angle. Which, as we observe, is likewise an angle which we have been dealing with in the simpler case of the bee cell, and indeed in all the regular solids of which we have yet treated. By completing the assemblage of polyhedra of which Plateau's skeleton cube gives a part, Lord Kelvin shewed that we should obtain a set of equal and similar 14-sided figures, or tetracadecahedra. And that by means of an assemblage of these figures space is homogeneously partitioned, that is to say, into equal, similar and similarly situated cells, with an economy of surface in relation to area even greater than in an assemblage of rhombic dodecahedra. In the most generalized case, the tetracadecahedron is bounded by 3 pairs of equal and parallel quadrilateral faces, and 4 pairs of equal and parallel hexagonal faces, neither the quadrilaterals nor the hexagons being necessarily plane. In a certain particular case, the quadrilaterals are plane surfaces, but the hexagons slightly curved anticlastic surfaces. And these latter have at every point equal and opposite curvatures, and are surfaces of minimal curvature for a boundary of 6 curved edges. The figure has the remarkable property that, like the plane rhombic dodecahedron, it so partitions space that 3 faces meeting in an edge do so everywhere at equal angles of 120 degrees. We may take it as certain that, in a system of perfectly fluid films, like the interior of a mass of soap bubbles, where the films are perfectly free to glide or to rotate over one another, the mass is actually divided into cells of this remarkable conformation. And it is quite possible, also, that in the cells of a vegetable parenchyma, by carefully macerating them apart, the same conformation may yet be demonstrated under suitable conditions. That is to say, when the whole tissue is highly symmetrical, and the individual cells are as nearly as possible equal in size. But in an ordinary microscopic section, it would seem practically impossible to distinguish the 14-sided figure from the 12-sided. Moreover, if we have anything whatsoever interposed so as to prevent our 12 films meeting in a point, and, so to speak, to take the place of our little central quadrilateral, if we have, for instance, a tiny bead or droplet in the center of our artificial system, or even a little thickening, or bourrelet, as Plateau called it, of the cell wall, then it is no longer necessary that the tetracadecahedron should be formed. Accordingly, it is very probably the case that, in the parenchymatous tissue, under the actual conditions of restraint and of very imperfect fluidity, it is after all the rhombic dodecahedral configuration which, even under perfectly symmetrical conditions, is generally assumed. It follows from all that we have said, that the problems connected with the conformation of cells, and with the manner in which a given space is partitioned by them, soon become exceedingly complex. And while this is so even when all our cells are equal and symmetrically placed, it becomes vastly more so when cells varying even slightly in size, in hardness, rigidity, or other qualities, are packed together. The mathematics of the case very soon become too hard for us, but in its essence, the phenomenon remains the same. We have little reason to doubt, and no just cause to disbelieve, that the whole configuration, for instance of an egg in the advanced stages of segmentation, is accurately determined by simple physical laws. Just as much as in the early stages of 2 or 4 cells, during which early stages we are able to recognize and demonstrate the forces and their resultant effects. But when mathematical investigation has become too difficult, it often happens that physical experiment can reproduce for us the phenomena which nature exhibits to us, and which we are striving to comprehend. For instance, in an admirable research, M. Robert shewed, some years ago, not only that the early segmentation of the egg of Tracheus, a marine univalve mollusk, proceeded in accordance with the laws of surface tension, but he also succeeded in imitating by means of soap bubbles several stages, one after another, of the developing egg. Figure 135. Aggregations of 4 soap bubbles, to shew various arrangements of the intermediate partition and polar furrows. After Robert carried his experiments as far as the stage of 16 cells, or bubbles. It is not easy to carry the artificial system quite so far, but in the earlier stages the experiment is easy. We have merely to blow our bubbles in a little dish, adding one to another, and adjusting their sizes to produce a symmetrical system. One of the simplest and prettiest parts of his investigation concerned the polar furrow, of which we have spoken on p. On blowing 4 little contiguous bubbles he found, as we may all find with the greatest ease, that they form a symmetrical system, 2 in contact with one another by a laminar film and 2, which are elevated a little above the others, and which are separated by the length of the aforesaid lamina. The bubbles are thus in contact 3 by 3, their partition walls making with one another equal angles of 120 degrees. The upper and lower edges of the intermediate lamina, the lower one visible through the transparent system, constitute the 2 polar furrows of the embryologist, Fig. 1-3. The lamina itself is plane when the system is symmetrical, but it responds by a corresponding curvature to the least inequality of the bubbles on either side. In the experiment, the upper polar furrow is usually a little shorter than the lower, but parallel to it. That is to say, the lamina is of trapezoidal form, this lack of perfect symmetry being due, in the experimental case, to the lower portion of the bubbles being somewhat drawn asunder by the tension of their attachments to the sides of the dish, Fig. 4. A similar phenomenon is usually found in trachus, according to Robert, and many other observers have likewise found the upper furrow to be shorter than the one below. In the various species of the genus Crepidula, Conklin asserts that the 2 furrows are equal in C. convexa, that the upper one is the shorter in C. fornicata, and that the upper one all but disappears in C. plana. But we may well be permitted to doubt, without the evidence of very special investigations, whether these slight physical differences are actually characteristic of, and constant in, particular allied species. Returning to the experimental case, Robert found that by withdrawing a little air from, and so diminishing the bulk of the 2 terminal bubbles, i.e. those at the ends of the intermediate lamina, the upper polar furrow was caused to elongate, till it became equal in length to the lower, and by continuing the process it became the longer in its turn. These 2 conditions have again been described by investigators as characteristic of this embryo, or that, for instance in Unio, Lilly has described the 2 furrows as gradually altering their respective lengths. And Wilson, as Lilly remarks, had already pointed out that, the reduction of the apical cross-furrow, as compared with that at the vegetative pole in mollusks and annelids, stands in obvious relation to the different size of the cells produced at the 2 poles. When the 2 lateral bubbles are gradually reduced in size, or the 2 terminal ones enlarged, the upper furrow becomes shorter and shorter. And at the moment when it is about to vanish, new furrow makes its instantaneous appearance in a direction perpendicular to the old one. But the inferior furrow, constrained by its attachment to the base, remains unchanged, and accordingly our 2 polar furrows, which were formerly parallel, are now at right angles to one another. Instead of a single plane quadrilateral partition, we have now 2 triangular ones, meeting in the middle of the system by their apices, and lying in planes at right angles to one another, Fig. 5-7. 2 such polar furrows, equal in length and arranged in a cross, have again been frequently described by the embryologists. Robert himself found this condition in trachus, as an occasional or exceptional occurrence. It has been described as normal in Asterina by Ludwig, in Branchippus by Spangenberg, and in Poticorin and Hydractinia by Bunting. It is evident that it represents a state of unstable equilibrium, only to be maintained under certain conditions of restraint within the system. So, by slight and delicate modifications in the relative size of the cells, we may pass through all the possible arrangements of the median partition, and of the furrows, which correspond to its upper and lower edges. And every one of these arrangements has been frequently observed in the 4-celled stage of various embryos. As the phases pass one into the other, they are accompanied by changes in the curvature of the partition, which in like manner correspond precisely to phenomena which the embryologists have witnessed and described. And all these configurations belong to that large class of phenomena whose distribution among embryos, or among organisms in general, bears no relation to the boundaries of zoological classification. Through mollusks, worms, coelenterate, vertebrates and what not, we meet with now one and now another, in a medley which defies classification. They are not vital phenomena, or functions, of the organism, or special characteristics of this or that organism, but purely physical phenomena. The kindred but more complicated phenomena which correspond to the polar furrow when a larger number of cells than 4 are associated together, we shall deal with in the next chapter. Having shown that the capillary phenomena are patent and unmistakable during the earlier stages of embryonic development, but soon become more obscure and incapable of experimental reproduction in the later stages. When the cells have increased in number, various writers including Robert himself have been inclined to argue that the physical phenomena die away, and are overpowered and cancelled by agencies of a very different order. Here we pass into a region where direct observation and experiment are not at hand to guide us, and where a man's trend of thought, and way of judging the whole evidence in the case, must shape his philosophy. We must remember that, even in a froth of soap bubbles, we can apply an exact analysis only to the simplest cases and conditions of the phenomenon. We cannot describe, but can only imagine, the forces which in such a froth control the respective sizes, positions and curvatures of the innumerable bubbles and films of which it consists. But our knowledge is enough to leave us assured that what we have learned by investigation of the simplest cases includes the principles which determine the most complex. In the case of the growing embryo, we know from the beginning that surface tension is only one of the physical forces at work. And that other forces, including those displayed within the interior of each living cell, play their part in the determination of the system. But we have no evidence whatsoever that at this point, or that point, or at any, the dominion of the physical forces over the material system gives place to a new condition where agencies at present unknown to the physicist impose themselves on the living matter, and become responsible for the conformation of its material fabric. Before we leave for the present the subject of the segmenting egg, we must take brief note of 2 associated problems, viz. 1. The formation and enlargement of the segmentation cavity, or central interspace around which the cells tend to group themselves in a single layer, and, 2. The formation of the gastrula. That is to say, in a typical case, the conversion, by invagination, of the one-layered ball into a 2-layered cup. Neither problem is free from difficulty, and all we can do meanwhile is to state them in general terms, introducing some more or less plausible assumptions. The former problem is comparatively easy, as regards the tendency of a segmentation cavity to enlarge, when once it has been established. We may then assume that subdivision of the cells is due to the appearance of a new formed septum within each cell, that this septum has a tendency to shrink under surface tension, and that these changes will be accompanied on the whole by a diminution of surface energy in the system. This being so, it may be shown that the volume of the divided cells must be less than it was prior to division, or in other words that part of their contents must exude during the process of segmentation. Accordingly, the case where the segmentation cavity enlarges and the embryo develops into a hollow blastosphere may, under the circumstances, be simply described as the case where that outflow or exudation from the cells of the blastoderm is directed on the whole inwards. The physical forces involved in the invagination of the cell layer to form the gastrula have been repeatedly discussed, but the true explanation seems as yet to be by no means clear. The case, however, is probably not a very difficult one, provided that we may assume a difference of osmotic pressure at the 2 poles of the blastosphere, that is to say between the cells which are being differentiated into outer and inner, into epiblast and hypoblast. It is plain that a blastosphere, or hollow vesicle bounded by a layer of vesicles, is under very different physical conditions from a single, simple vesicle or bubble. The blastosphere has no effective surface tension of its own, such as to exert pressure on its contents or bring the whole into a spherical form, nor will local variations of surface energy be directly capable of affecting the form of the system. But if the substance of our blastosphere be sufficiently viscous, then osmotic forces may set up currents which, reacting on the external fluid pressure, may easily cause modifications of shape. And the particular case of invagination itself will not be difficult to account for on this assumption of non-uniform exudation and imbibition. Chapter 8: The Forms of Tissues or Cell Aggregates, continued. The problems which we have been considering, and especially that of the bee's cell, belong to a class of isoparametrical problems, which deal with figures whose surface is a minimum for a definite content or volume. Such problems soon become difficult, but we may find many easy examples which lead us towards the explanation of biological phenomena. And the particular subject which we shall find most easy of approach is that of the division, in definite proportions, of some definite portion of space, by a partition wall of minimal area. The theoretical principles so arrived at we shall then attempt to apply, after the manner of Berthold and Herrera, to the actual biological phenomena of cell division. This investigation we may approach in two ways, by considering, namely, the partitioning off from some given space or area of 1/2, or some other fraction, of its content. Or again, by dealing simultaneously with the partitions necessary for the breaking up of a given space into a definite number of compartments. If we take, to begin with, the simple case of a cubical cell, it is obvious that, to divide it into two halves, the smallest possible partition wall is one which runs parallel to, and midway between, two of its opposite sides. If we call A the length of one of the edges of the cube, then A 2 is the area, alike of one of its sides, and of the partition which we have interposed parallel, or normal, thereto. But if we now consider the bisected cube, and wish to divide the 1/2 of it again, it is obvious that another partition parallel to the first, so far from being the smallest possible, is precisely twice the size of a cross partition perpendicular to it. For the area of this new partition is A times A 2. And again, for a third bisection, our next partition must be perpendicular to the other two, and it is obviously a little square, with an area of 1/2 A, 2 equals 1/4 A 2. From this we may draw the simple rule that, for a rectangular body or parallelepiped to be divided equally by means of a partition of minimal area, 1, the partition must cut across the longest axis of the figure. And 2, in the event of successive bisections, each partition must run at right angles to its immediate predecessor. Figure 136. After Berthold. We have already spoken of Sax's rules, which are an empirical statement of the method of cell division in plant tissues, and we may now set them forth in full. 1. The cell typically tends to divide into two co-equal parts. 2. Each new plane of division tends to intersect at right angles the preceding plane of division. The first of these rules is a statement of physiological fact, not without its exceptions, but so generally true that it will justify us in limiting our inquiry, for the most part, to cases of equal subdivision. That it is by no means universally true for cells generally is shown, for instance, by such well-known cases as the unequal segmentation of the frog's egg. It is true when the dividing cell is homogeneous, and under the influence of symmetrical forces. But it ceases to be true when the field is no longer dynamically symmetrical, for instance, when the parts differ in surface tension or internal pressure. This latter condition, of asymmetry of field, is frequent in segmenting eggs, and is then equivalent to the principle upon which Balfour laid stress, as leading to unequal or to partial segmentation of the egg, viz. the unequal or asymmetrical distribution of protoplasm and of food yolk. The second rule, which also has its exceptions, is true in a large number of cases. And it owes its validity, as we may judge from the illustration of the repeatedly bisected cube, solely to the guiding principle of minimal areas. It is in short subordinate to, and covers certain cases included under, a much more important and fundamental rule, due not to Sachs but to Herrera. That, 3, the incipient partition wall of a dividing cell tends to be such that its area is the least possible by which the given space content can be enclosed. Let us return to the case of our cube, and let us suppose that, instead of bisecting it, we desire to shut off some small portion only of its volume. It is found in the course of experiments upon soap films, that if we try to bring a partition film too near to one side of a cubical, or rectangular, space, it becomes unstable. and is easily shifted to a totally new position, in which it constitutes a curved cylindrical wall, cutting off one corner of the cube. It meets the sides of the cube at right angles, for reasons which we have already considered. And, as we may see from the symmetry of the case, it constitutes precisely 1/4 of a cylinder. Our plane transverse partition, wherever it was placed, had always the same area, viz. a 2. And it is obvious that a cylindrical wall, if it cut off a small corner, may be much less than this. We want, accordingly, to determine what is the particular volume which might be partitioned off with equal economy of wall space in one way as the other, that is to say, what area of cylindrical wall would be neither more nor less than the area a 2. The calculation is very easy. The surface area of a cylinder of length a is 2 pi r a, and that of our quarter cylinder is, therefore, pi r2, and this being, by hypothesis, equals a 2, we have a equals pi r2, or r equals 2a pi. The volume of a cylinder, of length a, is r2, and that of our quarter cylinder is a pi r24, which, by substituting the value of r, is equal to a 3 pi. Now precisely this same volume is, obviously, shut off by a transverse partition of area a 2, if the third side of the rectangular space be equal to a pi. And this fraction, if we take a equals 1, is equal to 0.318, or rather less than 1/3. And, as we have just seen, the radius, or side, of the corresponding quarter cylinder will be twice that fraction, or equal to 636 times the side of the cubical cell. Figure 137. If then, in the process of division of a cubical cell, it so divide that the two portions be not equal in volume but that one portion by anything less than about 3/10 of the whole, or 3/7 of the other portion, there will be a tendency for the cell to divide, not by means of a plane transverse partition, but by means of a curved, cylindrical wall cutting off one corner of the original cell. And the part so cut off will be 1/4 of a cylinder. By a similar calculation we can shew that a spherical wall, cutting off one solid angle of the cube, and constituting an octant of a sphere, would likewise be of less area than a plane partition as soon as the volume to be enclosed was not greater than about 1/4 of the original cell. But while both the cylindrical wall and the spherical wall would be of less area than the plane transverse partition after that limit, of 1/4 volume, was passed, the cylindrical would still be the better of the two up to a further limit. It is only when the volume to be partitioned off is no greater than about 0.15, or somewhere about 1/7, of the whole, that the spherical cell wall in an angle of the cubical cell, that is to say the octant of a sphere, is definitely of less area than the quarter cylinder. In the accompanying diagram, Fig., the relative areas of the three partitions are shown for all fractions, less than 1/2, of the divided cell. Figure 138. In this figure, we see that the plane transverse partition, whatever fraction of the cube it cut off, is always of the same dimensions, that is to say is always equal to a 2, or equals 1. If 1/2 of the cube have to be cut off, this plane transverse partition is much the best, for we see by the diagram that a cylindrical partition cutting off an equal volume would have an area about 25%. And a spherical partition would have an area about 50% greater. The point A in the diagram corresponds to the point where the cylindrical partition would begin to have an advantage over the plane, that is to say, as we have seen, when the fraction to be cut off is about 1/3, or 3/18 of the whole. In like manner, at B the spherical octant begins to have an advantage over the plane, and it is not till we reach the point C that the spherical octant becomes of less area than the quarter cylinder. Figure 139. The case we have dealt with is of little practical importance to the biologist, because the cases in which a cubical, or rectangular, cell divides unequally, and unsymmetrically, are apparently few. But we can find, as Berthold pointed out, a few examples, for instance in the hairs within the reproductive conceptacles of certain fuci, Sphacilaria, etc., Fig., or in the paraphyses of mosses, Fig. But it is of great theoretical importance, as serving to introduce us to a large class of cases, in which the shape and the relative dimensions of the original cavity lead, according to the principle of minimal areas, to cell division in very definite and sometimes unexpected ways. It is not easy, nor indeed possible, to give a generalized account of these cases, for the limiting conditions are somewhat complex, and the mathematical treatment soon becomes difficult. But it is easy to comprehend a few simple cases, which of themselves will carry us a good long way, and which will go far to convince the student that, in other cases which we cannot fully master, the same guiding principle is at the root of the matter. The bisection of a solid, or the subdivision of its volume in other definite proportions, soon leads us into a geometry which, if not necessarily difficult, is apt to be unfamiliar. But in such problems we can go a long way, and often far enough for our particular purpose, if we merely consider the plane geometry of a side or section of our figure. For instance, in the case of the cube which we have been just considering, and in the case of the plane and cylindrical partitions by which it has been divided, it is obvious that, since these two partitions extend symmetrically from top to bottom of our cube, that we need only consider, so far as they are concerned, the manner in which they subdivide the base of the cube. The whole problem of the solid, up to a certain point, is contained in our plane diagram of Fig. And when our particular solid is a solid of revolution, then it is obvious that a study of its plane of symmetry, that is to say any plane passing through its axis of rotation, gives us the solution of the whole problem. The right cone is a case in point, for here the investigation of its modes of symmetrical subdivision is completely met by an examination of the isosceles triangle which constitutes its plane of symmetry. The bisection of an isosceles triangle by a line which shall be the shortest possible is a very easy problem. Let ABC be such a triangle of which A is the apex. It may be shown that, for its shortest line of bisection, we are limited to three cases, viz. To a vertical line AD, bisecting the angle at A and the side BC, to a transverse line parallel to the base BC. Or to an oblique line parallel to AB or to AC. The respective magnitudes, or lengths, of these partition lines follow at once from the magnitudes of the angles of our triangle. For we know, to begin with, since the areas of similar figures vary as the squares of their linear dimensions, that, in order to bisect the area, a line parallel to one side of our triangle must always have a length equal to 1/2 of that side. If then, we take our base, BC, in all cases of a length equals 2, the transverse partition drawn parallel to it will always have a length equal to 2/2 or equals 2. The vertical partition, AD, since BD equals 1, will always equal tan beta, beta being the angle ABC. And the oblique partition, GH, being equal to AB 2 equals 1, 2 cos beta. If then we call our vertical, transverse, figure 140, and oblique partitions, V, T, and O, we have V equals tan beta, T equals 2, and O equals 1, 2 cos beta, or V, T, O equals tan beta 2, 1, 1, 2 cos beta. And, working out these equations for various values of beta, we very soon see that the vertical partition, V, is the least of the three until beta equals 45 degrees, at which limit V and O are each equal to 1, 2 equals 707. And that again, when beta equals 60 degrees, O and T are each equals 1, after which T, whose value always equals 1, is the shortest of the three partitions. And, as we have seen, these results are at once applicable, not only to the case of the plane triangle, but also to that of the conical cell. Figure 141. In like manner, if we have a spheroidal body, less than a hemisphere, such for instance as a low, watch-glass-shaped cell, Fig. A, it is obvious that the smallest possible partition by which we can divide it into two equal halves is, as in our flattened disk, a median vertical one. And likewise, the hemisphere itself can be bisected by no smaller partition meeting the walls at right angles than that median one which divides it into two similar quadrants of a sphere. But if we produce our hemisphere into a more elevated, conical body, or into a cylinder with spherical cap, it is obvious that there comes a point where a transverse horizontal partition will bisect the figure with less area of partition wall than a median vertical one, C. And furthermore, there will be an intermediate region, a region where height and base have their relative dimensions nearly equal, as in B, where an oblique partition will be better than either the vertical or the transverse. Though here the analogy of our triangle does not suffice to give us the precise limiting values. We need not examine these limitations in detail, but we must look at the curvatures which accompany the several conditions. We have seen that a film tends to set itself at equal angles to the surface which it meets, and therefore, when that surface is a solid, to meet it, or its tangent if it be a curved surface, at right angles. Our vertical partition is, therefore, everywhere normal to the original cell walls, and constitutes a plane surface. But in the taller, conical cell with transverse partition, the latter still meets the opposite sides of the cell at right angles, and it follows that it must itself be curved. Moreover, since the tension, and therefore the curvature, of the partition is everywhere uniform, it follows that its curved surface must be a portion of a sphere, concave towards the apex of the original, now divided, cell. In the intermediate case, where we have an oblique partition, meeting both the base and the curved sides of the mother cell, the contact must still be everywhere at right angles, provided we continue to suppose that the walls of the mother cell, like those of our diagrammatic cube, have become practically rigid before the partition appears, and are therefore not affected and deformed by the tension of the latter. In such a case, and especially when the cell is elliptical in cross-section, or is still more complicated in form, it is evident that the partition, in adapting itself to circumstances and in maintaining itself as a surface of minimal area subject to all the conditions of the case, may have to assume a complex curvature. Figure 142. Shaped partitions, A, from Taunia automaria. After Reinke, B, from paraphyses of fucus. C, from rhizoids of moss, D, from paraphyses of polytrichum. While in very many cases the partitions, like the walls of the original cell, will be either plane or spherical, a more complex curvature will be assumed under a variety of conditions. It will be apt to occur, for instance, when the mother cell is irregular in shape, and one particular case of such asymmetry will be that in which, as in Fig, the cell has begun to branch, or give off a diverticulum, before division takes place. A very complicated case of a different kind, though not without its analogies to the cases we are considering, will occur in the partitions of minimal area which subdivide the spiral tube of a nautilus, as we shall presently see. And again, whenever we have a marked internal asymmetry of the cell, leading to irregular and anomalous modes of division, in which the cell is not necessarily divided into two equal halves and in which the partition wall may assume an oblique position, then apparently anomalous curvatures will tend to make their appearance. Suppose that a more or less oblong cell have a tendency to divide by means of an oblique partition, as may happen through various causes or conditions of asymmetry. Such a partition will still have a tendency to set itself at right angles to the rigid walls of the mother cell, and it will at once follow that our oblique partition, throughout its whole extent, will assume the form of a complex saddle-shaped or anticlastic surface. Figure 143. Diagrammatic explanation of shaped partition. Many such cases of partitions with complex or double curvature exist, but they are not always easy of recognition, nor is the particular case where they appear in a terminal cell a common one. We may see them, for instance, in the roots or rhizoids of mosses, especially at the point of development of a new rootlet, Fig. C, and again among mosses, in the paraphyses of the male prothallus, e.g. In Polytrichum, we find more or less similar partitions, D. They are frequent also among many fuci, as in the hairs or paraphyses of fucus itself, B. In Taunia automaria, as figured in Reinke's memoir on the Dictyotacea of the Gulf of Naples, we see, in like manner, oblique partitions, which on more careful examination are seen to be curves of double curvature, Fig. A. The physical cause and origin of these shaped partitions is somewhat obscure, but we may attempt a tentative explanation. When we assert a tendency for the cell to divide transversely to its long axis, we are not only stating empirically that the partition tends to appear in a small, rather than a large cross-section of the cell, but we are also implicitly ascribing to the cell a longitudinal polarity, Fig. A, and implicitly asserting that it tends to divide, just as the segmenting egg does, by a partition transverse to its polar axis. Such a polarity may conceivably be due to a chemical asymmetry, or anisotropy, such as we have learned of, from Professor McCallum's experiments, in our chapter on adsorption. Now if the chemical concentration, on which this anisotropy or polarity, by hypothesis, depends, be unsymmetrical, one of its poles being as it were deflected to one side, where a little branch or bud is being, or about to be, given off. All in precise accordance with the adsorption phenomena described on p. Then our polar axis would necessarily be a curved axis, and the partition, being constrained, again ex hypothesi, to arise transversely to the polar axis, would lie obliquely to the apparent axis of the cell, Fig. B, C. And if the oblique partition be so situated that it has to meet the opposite walls, as in C, then, in order to do so symmetrically, i.e. either perpendicularly, as when the cell wall is already solidified, or at least at equal angles on either side, it is evident that the partition, in its course from one side of the cell to the other, must necessarily assume a more or less shaped curvature, Fig. D. As a matter of fact, while we have abundant simple illustrations of the principles which we have now begun to study, apparent exceptions to this simplicity, due to an asymmetry of the cell itself, or of the system of which the single cell is but a part, are by no means rare. For example, we know that in cambium cells, division frequently takes place parallel to the long axis of the cell, when a partition of much less area would suffice if it were set crossways, and it is only when a considerable disproportion has been set up between the length and breadth of the cell, that the balance is in part redressed by the appearance of a transverse partition. It was owing to such exceptions that Berthold was led to qualify and even to depreciate the importance of the law of minimal areas as a factor in cell division, after he himself had done so much to demonstrate and elucidate it. He was deeply and rightly impressed by the fact that other forces besides surface tension, both external and internal to the cell, play their part in the determination of its partitions. And that the answer to our problem is not to be given in a word. How fundamentally important it is, however, in spite of all conflicting tendencies and apparent exceptions, we shall see better and better as we proceed. But let us leave the exceptions and return to a consideration of the simpler and more general phenomena. And in so doing, let us leave the case of the cubical, quadrangular or cylindrical cell, and examine the case of a spherical cell and of its successive divisions, or the still simpler case of a circular, discoidal cell. When we attempt to investigate mathematically the position and form of a partition of minimal area, it is plain that we shall be dealing with comparatively simple cases wherever even one dimension of the cell is much less than the other two. Where two dimensions are small compared with the third, as in a thin cylindrical filament like that of Spirogyra, we have the problem at its simplest. For it is at once obvious, then, that the partition must lie transversely to the long axis of the thread. But even where one dimension only is relatively small, as for instance in a flattened plate, our problem is so far simplified that we see at once that the partition cannot be parallel to the extended plane, but must cut the cell, somehow, at right angles to that plane. In short, the problem of dividing a much flattened solid becomes identical with that of dividing a simple surface of the same form. There are a number of small algae, growing in the form of small flattened discs, consisting, for a time at any rate, of but a single layer of cells, which, as Berthold shewed, exemplify this comparatively simple problem. And we shall find presently that it is also admirably illustrated in the cell divisions which occur in the egg of a frog or a sea urchin, when the egg for the sake of experiment is flattened out under artificial pressure. Figure 144. Development of erythrotrichia. After Berthold. Fig. Taken from Berthold's monograph of the Naples Bangiaceae, represents younger and older discs of the little alga Erythrotrichia decidua. And it will be seen that, in all stages save the first, we have an arrangement of cell partitions which look somewhat complex, but into which we must attempt to throw some light and order. Starting with the original single, and flattened, cell, we have no difficulty with the first two cell divisions. For we know that no bisecting partitions can possibly be shorter than the two diameters, which divide the cell into halves and into quarters. We have only to remember that, for the sum total of partitions to be a minimum, 3 only must meet in a point. And therefore, the 4 quadrantal walls must shift a little, producing the usual little median partition, or cross furrow, instead of one common, central point of junction. This little intermediate wall, however, will be very small, and to all intents and purposes. Figure 145. We may deal with the case as though we had now to do with 4 equal cells, each one of them a perfect quadrant. And so our problem is, to find the shortest line which shall divide the quadrant of a circle into 2 halves of equal area. A radial partition, Fig. A, starting from the apex of the quadrant, is at once excluded, for a reason similar to that just referred to. Our choice must lie therefore between 2 modes of division such as are illustrated in Fig. Where the partition is either, as in B, concentric with the outer border of the cell, or else, as in C, cuts that outer border. In other words, our partition may, B, cut both radial walls, or, C, may cut one radial wall and the periphery. These are the 2 methods of division which Sachs called, respectively, B, paraclinal, and C, anticlinal. We may either treat the walls of the dividing quadrant as already solidified, or at least as having a tension compared with which that of the incipient partition film is inconsiderable. In either case the partition must meet the cell wall, on either side, at right angles, and, its own tension and curvature being everywhere uniform, it must take the form of a circular arc. Now we find that a flattened cell which is approximately a quadrant of a circle invariably divides after the manner of Fig. C, that is to say, by an approximately circular, anticlinal wall, such as we now recognize in the 8-celled stage of erythrotrichia, Fig. Let us then consider that nature has solved our problem for us, and let us work out the actual geometric conditions. Let the quadrant OAB, in Fig, be divided into 2 parts of equal area, by the circular arc MP. It is required to determine, 1, the position of P upon the arc of the quadrant, that is to say the angle BOP, 2, the position of the point M on the side OA, and, 3, the length of the arc MP in terms of a radius of the quadrant. 1. Draw OP. Also PC a tangent, meeting OA in C, and PN, perpendicular to OA. Let us call A a radius, and theta the angle at C, which is obviously equal to OPN, or POB. Then, CP equals a cot theta, PN equals a cos theta. NC equals CP cos theta equals a cosine 2 theta, sine theta. The area of the portion PMN equals 1/2 CP 2 theta 1/2 PN NC equals 1/2 a 2 cot 2 theta. 1/2 a cosine theta a cosine 2 theta sine theta equals 1/2 a 2 cot 2 theta cosine 3 theta sine theta. And the area of the portion PNA equals 1/2 a 2 pi 2 theta 1/2 on NP equals 1/2 a 2 pi 2 theta 1/2 a sine theta a cosine theta equals 1/2 a 2 pi 2 theta sine theta cosine theta. Therefore the area of the whole portion PMA equals a 2 pi 2 theta plus theta cot 2 theta cosine 3 theta sine theta cosine theta equals a 2 pi 2 theta plus theta cot 2 theta cot theta. And also, by hypothesis, equals 1/2 area of the quadrant, equals pi a 2/8. Figure 146. Hence theta is defined by the equation. A 2 pi 2 theta plus theta cot 2 theta cot theta equals pi a 2/8. Or pi 4 theta plus theta cot 2 theta cot theta equals 0. We may solve this equation by constructing a table, of which the following is a small portion, for various values of theta. Theta. Pi 4. Theta. Cot theta. plus theta cot 2 theta equals x. 34 degrees 34. 78 54. 60 33. 1 45 14. Plus 1 27 09. Equals 0016. 35. 78 54. 60 36. 1 45 05. 1 2700. 0013. 36. 78 54. 60 39. 1 44 96. 1 26 90. 0009. 37. 78 54. 60 42. 1 44 87. 1 26 80. 0005. 38. 78 54. 60 45. 1 44 78. 1 26 71. 0002. 39. 78 54. 60 48. 1 44 69. 1 26 61. 0002. 40. 78 54. 60 51. 1 44 60. 1 26 52. 0005. We see accordingly that the equation is solved, as accurately as need be, when theta is an angle somewhat over 34 degrees 38. Or say 34 degrees 38 1/2. That is to say, a quadrant of a circle is bisected by a circular arc cutting the side and the periphery of the quadrant at right angles, when the arc is such as to include 90 degrees 34 degrees 38, i.e. 55 degrees 22 of the quadrantal arc. This determination of ours is practically identical with that which Berthold arrived at by a rough and ready method, without the use of mathematics. He simply tried various ways of dividing a quadrant of paper by means of a circular arc, and went on doing so till he got the weights of his two pieces of paper approximately equal. The angle, as he thus determined it, was 34.6°, or say 34 degrees 36. 2. The position of M on the side of the quadrant OA is given by the equation OM equals a cosec theta a cot theta. The value of which expression, for the angle which we have just discovered, is 30/28. That is to say, the radius, or side, of the quadrant will be divided by the new partition into two parts, in the proportions of nearly 3:7. 3. The length of the arc MP is equal to a theta cot theta, and the value of this for the given angle is 87/51. This is as much as to say that the curved partition wall which we are considering is shorter than a radial partition in the proportion of 8 3/4 to 10, or 7/8 almost exactly. Figure 147. But we must also compare the length of this curved, anticlinal, partition wall, MP, with that of the concentric, or periclinal, 1, rs, fig, by which the quadrant might also be bisected. The length of this partition is obviously equal to the arc of the quadrant, i.e. the peripheral wall of the cell, divided by 2, or, in terms of the radius, equals pi 2 equals 1 111. So that, not only is the anticlinal partition, such as we actually find in nature, notably the best, but the periclinal one, when it comes to dividing an entire quadrant, is very considerably larger even than a radial partition. The two cells into which our original quadrant is now divided, while they are equal in volume, are of very different shapes. The one is a triangle, map, with two sides formed of circular arcs, and the other is a four-sided figure, MO-BP, which we may call approximately oblong. We cannot say as yet how the triangular portion ought to divide. But it is obvious that the least possible partition wall which shall bisect the other must run across the long axis of the oblong, that is to say periclinally. This, also, is precisely what tends actually to take place. In the following diagrams, Fig, of a frog's egg dividing under pressure, that is to say when reduced to the form of a flattened plate, we see, firstly, the division into 4 quadrants, by the partitions 1, 2. Secondly, the division of each quadrant by means of an anticlinal circular arc, 3, 3, cutting the peripheral wall of the quadrant approximately in the Figure 148. Segmentation of frog's egg, under artificial compression. After Roux. Proportions of 3 to 7. And thirdly, we see that of the 8 cells, 4 triangular and 4 oblong, into which the whole egg is now divided, the 4 which we have called oblong now proceed to divide by partitions transverse to their long axes, or roughly parallel to the periphery of the egg. The question how the other, or triangular, portion of the divided quadrant will next divide leads us to another well-defined problem, which is only a slight extension, making allowance for the circular arcs. Of that elementary problem of the triangle we have already considered. We know now that an entire quadrant must divide, so that its bisecting wall shall have the least possible area, by means of an anticlinal partition, but how about any smaller sectors of circles? It is obvious in the case of a small prismatic sector, such as that shown in Fig. That a periclinal partition is the smallest by which we can possibly bisect the cell. We want, accordingly, to know the limits below which the periclinal partition is always the best, and above which the anticlinal arc, as in the case of the whole quadrant, has the advantage in regard to smallness of surface area. This may be easily determined, for the preceding investigation is a perfectly general one, and the results hold good for sectors of any other arc, as well as for the quadrant, or arc of 90 degrees. That is to say, the length of the partition wall MP is always determined by the angle theta, according to our equation MP equals a theta cot theta, and the angle theta has a definite relation to alpha, the angle of arc. Figure 149. Moreover, in the case of the periclinal boundary, RS, Fig. Orb, Fig, we know that, if it bisect the cell RS equals a alpha 2. Accordingly, the arc RS will be just equal to the arc MP when theta cot theta equals alpha 2. When theta cot theta greater than alpha 2. Or MP greater than RS. Then division will take place as in RS. When theta cot theta less than alpha 2. Or MP less than RS. Then division will take place as in MP. In the accompanying diagram, Fig. I have plotted the various magnitudes with which we are concerned, in order to exhibit the several limiting values. Here we see, in the first place, the curve marked alpha, which shews on the left-hand vertical scale the various possible magnitudes of that angle, viz. the angle of arc of the whole sector which we wish to divide, and on the horizontal scale the corresponding values of theta, or the angle which determines. Figure 150. The point on the periphery where it is cut by the partition wall, MP. 2 limiting cases are to be noticed here, 1, at 90 degrees, point A in diagram, because we are at present only dealing with arcs no greater than a quadrant. And 2, the point, B, where the angle theta comes to equal the angle alpha, for after that point the construction becomes impossible, since an anticlinal bisecting partition wall would be partly outside the cell. The only partition which, after the point, can possibly exist, is a periclinal one. This point, as our diagram shews us, occurs when the angles, alpha and theta, are each rather under 52 degrees. Next I have plotted, on the same diagram, and in relation to the same scales of angles, the corresponding lengths of the two partitions, viz. RS and MP, their lengths being expressed, on the right-hand side of the diagram, in relation to the radius of the circle, A, that is to say the side wall, OA, of our cell. The limiting values here are, 1, C, where the angle of arc is 90 degrees, and where, as we have already seen, the two partition walls have the relative magnitudes of MP, RS equals 0, 875, 1, 111. 2, the point D, where RS equals unity, that is to say where the periclinal partition has the same length as a radial one, this occurs when alpha is rather under 82 degrees, cf the points D, 3, the point E, where RS and MP intersect. That is to say the point at which the two partitions, paraclinal and anticlinal, are of the same magnitude. This is the case, according to our diagram, when the angle of arc is just over 62½ degree. We see from this, then, that what we have called an anticlinal partition, as MP, is only likely to occur in a triangular or prismatic cell whose angle of arc lies between 90 degrees and 62½ degree. In all narrower or more tapering cells, the paraclinal partition will be of less area, and will therefore be more and more likely to occur. The case, F, where the angle alpha is just 60 degrees is of some interest. Here, owing to the curvature of the peripheral border, and the consequent fact that the peripheral angles are somewhat greater than the apical angle alpha, the paraclinal partition has a very slight and almost imperceptible advantage over the anticlinal, the relative proportions being about as MP, RS equals 0.73, 0.72. But if the equilateral triangle be a plane spherical triangle, i.e. a plane triangle bounded by circular arcs, then we see that there is no longer any distinction at all between our two partitions, MP and RS are now identical. On the same diagram, I have inserted the curve for values of cosec theta cot theta equals OM, that is to say the distances from the center, along the side of the cell, of the starting point, M, of the anticlinal partition. The point C represents its position in the case of a quadrant, and shews it to be, as we have already said, about 3/10 of the length of the radius from the center. If, on the other hand, our cell be an equilateral triangle, then we have to read off the point on this curve corresponding to alpha equals 60 degrees, and we find it at the point F, vertically under F, which tells us that the partition now starts 4, 5, 10. Or nearly halfway, along the radial wall. The foregoing considerations carry us a long way in our investigations of many of the simpler forms of cell division. Strictly speaking, they are limited to the case of flattened cells, in which we can treat the problem as though we were simply partitioning a plane surface. But it is obvious that, though they do not teach us the whole conformation of the partition which divides a more complicated solid into two halves, yet they do, even in such a case, enlighten us so far that they tell us the appearance presented in one plane of the actual solid. And as this is all that we see in a microscopic section, it follows that the results we have arrived at will greatly help us in the interpretation of microscopic appearances, even in comparatively complex cases of cell division. Figure 151. Let us now return to our quadrant cell, OAPB, which we have found to be divided into a triangular and a quadrilateral portion, as in Fig or Fig. And let us now suppose the whole system to grow, in a uniform fashion, as a prelude to further subdivision. The whole quadrant, growing uniformly, or with equal radial increments, will still remain a quadrant, and it is obvious, therefore, that for every new increment of size, more will be added to the margin of its triangular portion than to the narrower margin of its quadrilateral portion. And these increments will be in proportion to the angles of arc, viz. 55 degrees 22, 34 degrees 38, or as 96, 60, i.e. as 8, 5. And accordingly, if we may assume, and the assumption is a very plausible one, that, just as the quadrant itself divided into two halves after it got to a certain size, so each of its two halves will reach the same size before again dividing. It is obvious that the triangular portion will be doubled in size, and therefore ready to divide, a considerable time before the quadrilateral part. To work out the problem in detail would lead us into troublesome mathematics. But if we simply assume that the increments are proportional to the increasing radii of the circle, we have the following equations. Let us call the triangular cell T, and the quadrilateral, Q, Fig. Let the radius, OA, of the original quadrantal cell equals A equals 1, and let the increment which is required to add on a portion equal to T, such as PPAA, be called X, and let that required, similarly, for the doubling of Q be called X. Then we see that the area of the original quadrant equals T plus Q equals 1/4 pi A2 equals 7854 A2, while the area of T equals Q equals 3927 A2. The area of the enlarged sector, POA, equals A plus X, 2 times 55 degrees 22, divided by 2, equals 4831, A plus X, 2. And the area OPA equals a 2 times 55 degrees 22, divided by 2, equals 4831A2. Therefore the area of the added portion, T, equals 4831, A plus X, to a 2. And this, by hypothesis, equals T, equals 3927A2. We get, accordingly, since A equals 1, x2 plus 2x, equals 3927, 4831, equals 810. And, solving, x plus 1, equals 181, equals 1, 345, or x, equals 0, 345. Working out x in the same way, we arrive at the approximate value, x plus 1 equals 1, 517. This is as much as to say that, supposing each cell tends to divide into 2 halves when, and not before, its original size is doubled, then, in our flattened disk, the triangular cell T will tend to divide when the radius of the disk has increased by about a third, from 1 to 1, 345, but the quadrilateral cell, Q, will not tend to divide until the linear dimensions of the disk have increased by about a half, from 1 to 1, 517. The case here illustrated is of no small general importance. For it shews us that a uniform and symmetrical growth of the organism, symmetrical, that is to say, under the limitations of a plane surface, or plane section, by no means involves a uniform or symmetrical growth of the individual cells, but may, under certain conditions, actually lead to inequality among these. And this inequality may be further emphasized by differences which arise out of it, in regard to the order of frequency of further subdivision. This phenomenon, or to be quite candid, this hypothesis, which is due to Berthold, is entirely independent of any change or variation in individual surface tensions. And accordingly it is essentially different from the phenomenon of unequal segmentation, as studied by Balfour, to which we have referred on p. In this fashion, we might go on to consider the manner, and the order of succession, in which the subsequent cell divisions would tend to take place, as governed by the principle of minimal areas. But the calculations would grow more difficult, or the results got by simple methods would grow less and less exact. At the same time, some of these results would be of great interest, and well worth the trouble of obtaining. For instance, the precise manner in which our triangular cell, T, would next divide would be interesting to know, and a general solution of this problem is certainly troublesome to calculate. But in this particular case we can see that the width of the triangular cell near P is so obviously less than that near either of the other two angles, that a circular arc cutting off that angle is bound to be the shortest possible bisecting line. And that, in short, our triangular cell will tend to subdivide, just like the original quadrant, into a triangular and a quadrilateral portion. But the case will be different next time, because in this new triangle, PRQ, the least width is near the innermost angle, that at Q. And the bisecting circular arc will therefore be opposite to Q, or, approximately, parallel to PR. The importance of this fact is at once evident, for it means to say that there soon comes a time when, whether by the division of triangles or of quadrilaterals, we find only quadrilateral cells adjoining the periphery of our circular disk. In the subsequent division of these quadrilaterals, the partitions will arise transversely to their long axes, that is to say, radially, as U, V. And we shall consequently have a superficial or peripheral layer of quadrilateral cells, with sides approximately parallel, that is to say what we are accustomed to call an epidermis. And this epidermis or superficial layer will be in clear contrast with the more irregularly shaped cells, the products of triangles and quadrilaterals, which make up the deeper, underlying layers of tissue. Figure 152. In following out these theoretic principles and others like to them, in the actual division of living cells, we must always bear in mind certain conditions and qualifications. In the first place, the the law of minimal area and the other rules which we have arrived at are not absolute but relative, they are links, and very important links, in a chain of physical causation. They are always at work, but their effects may be overridden and concealed by the operation of other forces. Secondly, we must remember that, in the great majority of cases, the cell system which we have in view is constantly increasing in magnitude by active growth. And by this means the form and also the proportions of the cells are continually liable to alteration, of which phenomenon we have already had an example. Thirdly, we must carefully remember that, until our cell walls become absolutely solid and rigid, they are always apt to be modified in form owing to the tension of the adjacent walls. And again, that so long as our partition films are fluid or semi-fluid, their points and lines of contact with one another may shift, like the shifting outlines of a system of soap bubbles. This is the physical cause of the movements frequently seen among segmenting cells, like those to which Rauber called attention in the segmenting ovum of the frog. And like those more striking movements or accommodations which give rise to a so-called spiral type of segmentation. Bearing in mind, then, these considerations, let us see what our flattened disk is likely to look like, after a few successive divisions. Figure 153. Diagram of flattened or discoid. Cell dividing into octants, to shew gradual tendency towards a position of equilibrium. Into component cells. In Fig. A, we have a diagrammatic representation of our disk, after it has divided into 4 quadrants, and each of these in turn into a triangular and a quadrilateral portion. But as yet, this figure scarcely suggests to us anything like the normal look of an aggregate of living cells. But let us go a little further, still limiting ourselves, however, to the consideration of the 8-celled stage. Wherever one of our radiating partitions meets the peripheral wall, there will, as we know, be a mutual tension between the 3 convergent films, which will tend to set their edges at equal angles to one another, angles that is to say of 120 degrees. In consequence of this, the outer wall of each individual cell will, in this surface view of our disk, be an arc of a circle of which we can determine the center by the method used on P. And, furthermore, the narrower cells, that is to say the quadrilaterals, will have this outer border somewhat more curved than their broader neighbors. We arrive, then, at the condition shown in Fig. B. Within the cell, also, wherever wall meets wall, the angle of contact must tend, in every case, to be an angle of 120 degree, and in no case may more than 3 films, as seen in section, meet in a point, C. And this condition, of the partitions meeting 3 by 3, and at coequal angles, will obviously involve the curvature of some, if not all, of the partitions, D, which in our preliminary investigation we treated as plane. To solve this problem in a general way is no easy matter, but it is a problem which nature solves in every case where, as in the case we are considering, 8 bubbles, or 8 cells, meet together in a, plane or curved, surface. An approximate solution has been given in Fig. D, and it will now at once be recognized that this figure has vastly more resemblance to an aggregate of living cells than had the diagram of Fig. A with which we began. Figure 154. Just as we have constructed in this case a series of purely diagrammatic or schematic figures, so it will be as a rule possible to diagrammatize, with but little alteration, the complicated appearances presented by any ordinary aggregate of cells. The accompanying little figure, Fig. Of a germinating spore of a liverwort, Richia, after a drawing of Professor Campbell's, scarcely needs further explanation, for it is well nigh a typical diagram of the method of space partitioning which we are now considering. Let us look again at our figures, on P, of the disk of Erythrotrichia, from Berthold's monograph of the Bangiaceae and redraw the earlier stages in diagrammatic fashion. In the following series of diagrams the new partitions, or those just about to form, are in each case outlined. And in the next succeeding stage they are shown after settling down into position, and after exercising their respective tractions on the walls previously laid down. It is clear, I think, that these 4 diagrammatic figures represent all that is shown in the first 5 stages drawn by Berthold from the plant itself. But the correspondence cannot in this case be precisely accurate, for the simple reason that Berthold's figures are taken from different individuals, and are therefore only approximately consecutive and not strictly continuous. The last of the 6 drawings in Fig is already 2. Figure 155. Theoretical arrangement of successive partitions in a discoid cell, for comparison with Fig. Complicated for diagrammatization, that is to say it is too complicated for us to decipher with certainty the precise order of appearance of the numerous partitions which it contains. But in Fig. I shew one more diagrammatic figure, of a disk which. Figure 156. Theoretical division of a discoid cell into 64 chambers, no allowance being made for the mutual tractions of the cell walls. Has divided, according to the theoretical plan, into about 64 cells. And making due allowance for the successive changes which the mutual tensions and tractions of the partitions must bring about, increasing in complexity with each succeeding stage, we can see, even at this advanced and complicated stage, a very considerable resemblance between the actual picture, Fig. And the diagram which we have here constructed in obedience to a few simple rules. In like manner, in the annexed figures, representing sections through a young embryo of a moss, we have very little difficulty in discerning the successive stages that must have intervened between the 2 stages shown, so as to lead from the just divided quadrants, one of which, by the way, has not yet divided in our figure, A, to the stage, B, in which a well-marked epidermal layer surrounds an at first sight irregular agglomeration of fundamental tissue. Figure 157. Sections of embryo of a moss. After Kenitzgerloff. In the last paragraph but one, I have spoken of the difficulty of so arranging the meeting places of a number of cells that at each junction only 3 cell walls shall meet in a line, and all 3 shall meet it at equal angles of 120 degrees. As a matter of fact, the problem is soluble in a number of ways. That is to say, when we have a number of cells, say 8 as in the case considered, enclosed in a common boundary, there are various ways in which their walls can be made to meet internally, 3 by 3, at equal angles. And these differences will entail differences also in the curvature of the walls, and consequently in the shape of the cells. The question is somewhat complex, it has been dealt with by Plateau, and treated mathematically by M. van Ries. Fig. 158, various possible arrangements of intermediate partitions, in groups of 4, 5, 6, 7, or 8 cells. If within our boundary we have 3 cells all meeting internally, they must meet in a point. Furthermore, they tend to do so at equal angles of 120 degrees, and there is an end of the matter. If we have 4 cells, then, as we have already seen, the conditions are satisfied by interposing a little intermediate wall, the 2 extremities of which constitute the meeting points of 3 cells each, and the upper edge of which marks the polar furrow. Similarly, in the case of 5 cells, we require 2 little intermediate walls, and 2 polar furrows. And we soon arrive at the rule that, for n cells, we require n 3 little longitudinal partitions, and corresponding polar furrows, connecting the triple junctions of the cells. And these little walls, like all the rest within the system, must be inclined to one another at angles of 120 degrees. Where we have only one such wall, as in the case of 4 cells, or only 2, as in the case of 5 cells, there is no room for ambiguity. But where we have 3 little connecting walls, as in the case of 6 cells, it is obvious that we can arrange them in 3 different ways, as in the annexed fig. In the system of 7 cells, the 4 partitions can be arranged in 4 ways. And the 5 partitions required in the case of 8 cells can be arranged in no less than 13 different ways, of which Fig shews some half-dozen only. It does not follow that, so to speak, these various arrangements are all equally good. Some are known to be much more stable than others, and some have never yet been realized in actual experiment. The conditions which lead to the presence of any one of them, in preference to another, are as yet, so far as I am aware, undetermined, but to this point we shall return. Examples of these various arrangements meet us at every turn, and not only in cell aggregates, but in various cases where non-rigid and semi-fluid partitions, or partitions that were so to begin with, meet together. And it is a necessary consequence of this physical phenomenon, and of the limited and very small number of possible arrangements, that we get similar appearances, capable of representation by the same diagram, in the most diverse fields of biology. Figure 159. Among the published figures of embryonic stages and other cell aggregates, we only discern these little intermediate partitions in cases where the investigator has drawn carefully just what lay before him, without any preconceived notions as to radial or other symmetry. But even in other cases we can generally recognize, without much difficulty, what the actual arrangement was whereby the cell walls met together in equilibrium. I have a strong suspicion that a leaning towards Sax's rule, that one cell wall tends to set itself at right angles to another cell wall, a rule whose strict limitations, and narrow range of application we have already considered, is responsible for many inaccurate or incomplete representations of the mutual arrangement of aggregated cells. Figure 160. Segmenting egg of Trocheus. After Robert. Figure 161. Two views of segmenting egg of Cynthia Partida. After Conklin. Figure 162. A. Section of apical cone of Solvinia. After Pringsheim. B. Diagram of probable actual arrangement. Figure 163. Egg of Pyrosoma. After Korotnev. Figure 164. Egg of Echinus, segmenting under pressure. After Driesch. In the accompanying series of figures, Figs. -167, I have set forth a few aggregates of 8 cells, mostly from drawings of segmenting eggs. In some cases they shew clearly the manner in which the cells meet one another, always at angles of 120 degrees, and always with the help of 5 intermediate boundary walls within the 8-celled system. In other cases I have added a slightly altered drawing, so as to shew, with as little change as possible, the arrangement of boundaries which probably actually existed, and gave rise to the appearance which the observer drew. These drawings may be compared with the various diagrams of Fig, in which some 7 out of the possible 13 arrangements of 5 intermediate partitions, for a system of 8 cells, have been already set forth. Figure 165. A. Part of segmenting egg of cephalopod, after Wattace. B. Probable actual arrangement. Figure 166. A. Egg of Echinus. B. Dew of Nereus, under pressure. After Driesch. Figure 167. A. Egg of frog under pressure, after Roux. B. Probable actual arrangement. It will be seen that M. Robert Tornoff's figure of the segmenting egg of Trocheus, Fig, clearly shews the cells grouped after the fashion of Fig. A. In like manner, Mr. Conklin's figure of the Ascidian egg, Cynthia, shews equally clearly the arrangement G. A sea urchin egg, segmenting under pressure, as figured by Driesch, scarcely requires any modification of the drawing to appear as a diagram of the type D. Turning for a moment to a botanical illustration, we have a figure of Pringsheim shewing an 8-celled stage in the apex of the young cone of Solvinia. It is in all probability referable, as in my modified diagram, to type C. Beside it is figured a very different object, a segmenting egg of the Ascidian pyrosoma, after Korotnev. It may be that this also is to be referred to type C, but I think it is more easily referable to type B. For there is a difference between this diagram and that of Solvinia, in that here apparently, of the pairs of lateral cells, the upper and the lower cell are alternately the larger, while in the diagram of Solvinia the lower lateral cells both appear much larger than the upper ones. And this difference tallies with the appearance produced if we fill in the 8 cells according to the type B or the type C. In the segmenting cuttlefish egg, there is again a slight dubiety as to which type it should be referred to, but it is in all probability referable, like Driesch's Echinus egg, to D. Lastly, I have copied from Roux a curious figure of the egg of Rana esculenta, viewed from the animal pole, which appears to me referable, in all probability, to type G. Of type F, in which the 5 partitions form a figure with 4 reentrant angles, that is to say a figure representing the 5 sides of a hexagon, I have found no examples among segmenting eggs. And that arrangement in all probability is a very unstable one. It is obvious enough, without more ado, that these phenomena are in the strictest and completest way common to both plants and animals. In other words, they tally with, and they further extend, the general and fundamental conclusions laid down by Schwann, in his Mikroskopische Untersuchungen über die Übereinstimmung in der Struktur und dem Wachstum der Tiere und Pflanzen. But now that we have seen how a certain limited number of types of 8-celled segmentation, or of arrangements of 8 cell partitions, appear and reappear, here and there, throughout the whole world of organisms, there still remains the very important question, whether in each particular organism the conditions are such as to lead to one particular arrangement being predominant, characteristic, or even invariable. In short, is a particular arrangement of cell partitions to be looked upon, as the published figures of the embryologist are apt to suggest, as a specific character, or at least a constant or normal character, of the particular organism? The answer to this question is a direct negative, but it is only in the work of the most careful and accurate observers that we find it revealed. Rauber, whom we have more than once had occasion to quote, was one of those embryologists who recorded just what he saw, without prejudice or preconception, as Boerhaave said of Swammerdam, quod videt id asserut. Now Rauber has put on record a considerable number of variations in the arrangement of the first 8 cells, which form a discoid surface about the dorsal, or animal, pole of the frog's egg. In a certain number of cases these figures are identical with one another in type, identical, that is to say, save for slight differences in magnitude, relative proportions, or orientation. But I have selected, Fig. 6 diagrammatic figures, which are all essentially different, and these diagrams seem to me to bear intrinsic evidence of their accuracy, the curvatures of the partition walls. And the angles at which they meet agree closely with the requirements of theory, and when they depart from theoretical symmetry they do so only to the slight extent which we should naturally expect in a material and imperfectly homogeneous system. Of these 6 illustrations, 2 are exceptional. In Fig. 5, we observe that one of the 8 cells is surrounded on all sides by the other 7. This is a perfectly natural condition, and represents, like the rest, a phase of partial or conditional equilibrium. But it is not included in the series we are now considering, which is restricted to the case of 8 cells extending outwards to a common boundary. The condition shown in Fig. 6, is again peculiar, and is probably rare. But it is included under the cases considered on P, in which the cells are not incomplete. Figure 168. Various modes of grouping. Of 8 cells at the dorsal or epiblastic pole of the frog's egg. After Rauber. Fluid contact, but are separated by little droplets of extraneous matter, it needs no further comment. But the other 4 cases are beautiful diagrams of space partitioning, similar to those we have just been considering, but so exquisitely clear that they need no modification, no touching up, to exhibit their mathematical regularity. It will easily be recognized that in Fig. 1 and 2, we have the arrangements corresponding to A and D of our diagram, Fig. But the other 2, i.e. 3 and 4, represent other of the 13 possible arrangements, which are not included in that diagram. It would be a curious and interesting investigation to ascertain, in a large number of frogs' eggs, all at this stage of development, the percentage of cases in which these various arrangements occur. With a view of correlating their frequency with the theoretical conditions, so far as they are known, or can be ascertained, of relative stability. One thing stands out as very certain indeed, that the elementary diagram of the frog's egg commonly given in textbooks of embryology, in which the cells are depicted as uniformly symmetrical quadrangular bodies, is entirely inaccurate and grossly misleading. We now begin to realize the remarkable fact, which may even appear a startling one to the biologist, that all possible groupings or arrangements whatsoever of 8 cells, where all take part in the surface of the group, none being submerged or wholly enveloped by the rest, are referable to some one or other of 13 types or forms. And that all the thousands and thousands of drawings which diligent observers have made of such 8-celled structures, animal or vegetable, anatomical, histological or embryological, are one and all representations of some one or another of these 13 types, or rather indeed of somewhat less than the whole 13, for there is reason to believe that, out of the total number of possible groupings, a certain small number are essentially unstable, and have at best, in the concrete, but a transitory and evanescent existence. Before we leave this subject, on which a vast deal more might be said, there are 1 or 2 points which we must not omit to consider. Let us note, in the first place, that the appearance which our plane diagrams suggest of inequality of the several cells is apt to be deceptive. For the differences of magnitude apparent in one plane may well be, and probably generally are, balanced by equal and opposite differences in another. Secondly, let us remark that the rule which we are considering refers only to angles, and to the number, not to the length of the intermediate partitions. It is to a great extent by variations in the length of these that the magnitudes of the cells may be equalized, or otherwise balanced, and the whole system brought into equilibrium. Lastly, there is a curious point to consider, in regard to the number of actual contacts, in the various cases, between cell and cell. If we inspect the diagrams in Fig. which represent 3 out of our 13 possible arrangements of 8 cells, we shall see that, in the case of type B, 2 cells are each in contact with 2 others, 2 cells with 3 others, and 4 cells each with 4 other cells. In type A 4 cells are each in contact with 2, 2 with 4, and 2 with 5. In type F, 2 are in contact with 2, 4 with 3, and 1 with no less than 7. In all cases the Figure 169 number of contacts is 26 in all. Or, in other words, there are 13 internal partitions, besides the 8 peripheral walls. For it is easy to see that, in all cases of n cells with a common external boundary, the number of internal partitions is 2n3. Or the number of what we call the internal or interfacial contacts is 2n3. But it would appear that the most stable arrangements are those in which the total number of contacts is most evenly divided, and the least stable are those in which some one cell has, as in type F, a predominant number of contacts. In a well-known series of experiments, Roux has shown how, by means of oil drops, various arrangements, or aggregations, of cells can be simulated, and in Fig. I shew a number of Roux's figures, and have ascribed them to what seem to be their appropriate types, among those which we have just been considering. But it will be observed that in these figures of Roux's the drops are not always in complete contact, a little air bubble often keeping them apart at their apical junctions. So that we see the configuration towards which the system is tending rather than that which it has fully attained. The type which we have called F was found by Roux to be unstable, the large, or apparently large, drop quickly passing into the center of the system, and here taking up a position of equilibrium in which, as usual, 3 cells meet throughout in a point, at equal angles, and in which, in this case, all the cells have an equal number of interfacial contacts. Figure 170. Aggregations of oil drops. After Roux. Figs. -6 represent successive changes in a single system. We need by no means be surprised to find that, in such arrangements, the commonest and most stable distributions are those in which the cell contacts are distributed as uniformly as possible between the several cells. We always expect to find some such tendency to equality in cases where we have to do with small oscillations on either side of a symmetrical condition. The rules and principles which we have arrived at from the point of view of surface tension have a much wider bearing than is at once suggested by the problems to which we have applied them. For in this elementary study of the cell boundaries in a segmenting egg or tissue we are on the verge of a difficult and important subject in pure mathematics. It is a subject adumbrated by Leibniz, studied somewhat more deeply by Euler, and greatly developed of recent years. It is the geometria situs of Gauss, the analysis situs of Riemann, the theory of partitions of Cayley, and of spatial complexes of Listing. The crucial point for the biologist to comprehend is, that in a closed surface divided into a number of faces, the arrangement of all the faces, lines and points in the system is capable of analysis, and that when the number of faces or areas is small, the number of possible arrangements is small also. This is the simple reason why we meet in such a case as we have been discussing, viz. the arrangement of a group or system of 8 cells, with the same few types recurring again and again in all sorts of organisms, plants as well as animals, and with no relation to the lines of biological classification, and why, further, we find similar configurations occurring to mark the symmetry, not of cells merely, but of the parts and organs of entire animals. The phenomena are not functions, or specific characters, of this or that tissue or organism, but involve general principles which lie within the province of the mathematician. The theory of space partitioning, to which the segmentation of the egg gives us an easy practical introduction, is illustrated in much more complex ways in other fields of natural history. A very beautiful but immensely complicated case is furnished by the venation of the wings of insects. Here we have sometimes, as in the dragonflies, a general reticulum of small, more or less hexagonal, cells, but in most other cases, in flies, bees, butterflies, etc. we have a moderate number of cells, whose partitions always impinge upon one another 3 by 3, and whose arrangement, therefore, includes of necessity a number of small intermediate partitions, analogous to our polar furrows. I think that a mathematical study of these, including an investigation of the deformation of the wing, that is to say, of the changes in shape and changes in the form of its cells, which it undergoes during the life of the individual, and from one species to another, would be of great interest. In very many cases, the entomologist relies upon this venation, and upon the occurrence of this or that intermediate vein, for his classification, and therefore for his hypothetical phylogeny of particular groups. Which latter procedure hardly commends itself to the physicist or the mathematician. Figure 171. A. Asterolamprha marylandica. Air, B, C, A, variabilis, Greve. After Greville. Another case, geometrically akin but biologically very different, is to be found in the little diatoms of the genus Asterolamprha, and their immediate congeners. In Asterolamprha we have a little disc, in which we see, as it were, radiating spokes of one material, alternating with intervals occupied on the flattened wheel-like disc by another, Fig. The spokes vary in number, but the general appearance is in a high degree suggestive of the Chladni figures produced by the vibration of a circular plate. The spokes broaden out towards the center, and interlock by visible junctions, which obey the rule of triple intersection, and accordingly exemplify the partition figures with which we are dealing. But whereas we have found the particular arrangement in which one cell is in contact with all the rest to be unstable, according to Roux oil-drop experiments, and to be conspicuous by its absence from our diagrams of segmenting eggs. Here in Asterolamprha, on the other hand, it occurs frequently, and is indeed the commonest arrangement, Fig. B. In all probability, we are entitled to consider this marked difference natural enough. For we may suppose that in Asterolamprha, unlike the case of the segmenting egg, the tendency is to perfect radial symmetry, all the spokes emanating from a point in the center. Such a condition would be eminently unstable, and would break down under the least asymmetry. A very simple, perhaps the simplest case, would be that one single spoke should differ slightly from the rest, and should so tend to be drawn in amid the others, these latter remaining similar and symmetrical among themselves. Such a configuration would be vastly less unstable than the original one in which all the boundaries meet in a point. And the fact that further progress is not made towards other configurations of still greater stability may be sufficiently accounted for by viscosity, rapid solidification, or other conditions of restraint. A perfectly stable condition would of course be obtained if, as in the case of Roux oil-drop, Fig. 6, one of the cellular spaces passed into the center of the system, the other partitions radiating outwards from its circular wall to the periphery of the whole system. Precisely such a condition occurs among our diatoms. But when it does so, it is looked upon as the mark and characterization of the allied genus Arachnoidiscus. Figure 172. Section of Alcyonarian polyp. In a diagrammatic section of an Alcyonarian polyp, Fig. we have 8 chambers set, symmetrically, about a ninth, which constitutes the stomach. In this arrangement there is no difficulty, for it is obvious that, throughout the system, 3 boundaries meet, in plane section, in a point. In many corals we have as simple, or even simpler conditions, for the radiating calcified partitions either converge upon a central chamber, or fail to meet it and end freely. But in a few cases, the partitions or septa converge to meet one another, there being no central chamber on which they may impinge. And here the manner in which contact is effected becomes complicated, and involves problems identical with those which we are now studying. Figure 173. Heterophilia angulata. After Nicholson. In the great majority of corals we have as simple or even simpler conditions than those of Alcyonium. For as a rule the calcified partitions or septa of the coral either converge upon a central chamber, or central columella, or else fail to meet it and end freely. In the latter case the problem of space partitioning does not arise. In the former, however numerous the septa be, their separate contacts with the wall of the central chamber comply with our fundamental rule according to which 3 lines and no more meet in a point. And from this simple and symmetrical arrangement there is little tendency to variation. But in a few cases, the septal partitions converge to meet one another, there being no central chamber on which they may impinge. And here the manner in which contact is effected becomes complicated, and involves problems of space partitioning identical with those which we are now studying. In the genus Heterophilia and in a few allied forms we have such conditions, and students of the Coelenterata have found them very puzzling. McCoy, their first discoverer, pronounced these corals to be totally unlike any other group, recent or fossil, and Professor Martin Duncan, writing a memoir on heterophilia and its allies, described them as paradoxical in their anatomy. Figure 174. Heterophilia sp. After Martin Duncan. The simplest or youngest heterophiliae known have 6 septa, as in Fig. A. In the case figured, 4 of these septa are conjoined 2 and 2, thus forming the usual triple junctions together with their intermediate partition walls, and in the case of the other 2 we may fairly assume that their proper and original arrangement was that of our type 6b, Fig. Though the central intermediate partition has been crowded out by partial coalescence. When with increasing age the septa become more numerous, their arrangement becomes exceedingly variable. For the simple reason that, from the mathematical point of view, the number of possible arrangements, of 10, 12 or more cellular partitions in triple contact, tends to increase with great rapidity. And there is little to choose between many of them in regard to symmetry and equilibrium. But while, mathematically speaking, each particular case among the multitude of possible cases is an orderly indefinite arrangement, from the purely biological point of view on the other hand no law or order is recognizable. And so McCoy described the genus as being characterized by the possession of septa destitute of any order of arrangement, but irregularly branching and coalescing in their passage from the solid external walls towards some indefinite point near the center where the few main lamellae irregularly anastomose. In the 2 examples figured, Fig, both comparatively simple ones, it will be seen that, of the main chambers, one is in each case an unsymmetrical one. That is to say, there is one chamber which is in contact with a greater number of its neighbors than any other, and which at an earlier stage must have had contact with them all. This was the case of our type F, in the 8-celled system, Fig. Such an asymmetrical chamber, which may occur in a system of any number of cells greater than 6, constitutes what is known to students of the Coelenterata as a fossula. And we may recognize it not only here, but also in Zophrentis and its allies, and in a good many other corals besides. Moreover certain corals are described as having more than one fossula, this appearance being naturally produced under certain of the other asymmetrical variations of normal space partitioning. Where a single fossula occurs, we are usually told that it is a symptom of bilaterality. And this is in turn interpreted as an indication of a higher grade of organization than is implied in the purely radial symmetry of the commoner types of coral. The mathematical aspect of the case gives no warrant for this interpretation. Let us carefully notice, lest we run the risk of confusing two distinct problems, that the space partitioning of heterophilia by no means agrees with the details of that which we have studied in, for instance, the case of the developing disc of erythrotrichia, the difference simply being that heterophilia illustrates the general case of cell partitioning as Plateau and Van Ries studied it. While in erythrotrichia, and in our other embryological and histological instances, we have found ourselves justified in making the additional assumption that each new partition divided a cell into co-equal parts. No such law holds in heterophilia, whose case is essentially different from the others, inasmuch as the chambers whose partition we are discussing in the coral are mere empty spaces, empty save for the mere access of seawater. While in our histological and embryological instances, we were speaking of the division of a cellular unit of living protoplasm. Accordingly, among other differences, the transverse or periclinal partitions, which were bound to appear at regular intervals and in definite positions, when co-equal bisection was a feature of the case, are comparatively few and irregular in the earlier stages of heterophilia, though they begin to appear in numbers after the main, more or less radial, partitions have become numerous. And when accordingly these radiating partitions come to bound narrow and almost parallel-sided interspaces, then it is that the transverse or periclinal partitions begin to come in, and form what the student of the Coelenterata calls the dissepiments of the coral. We need go no further into the configuration and anatomy of the corals. But it seems to me beyond a doubt that the whole question of the complicated arrangement of septa and dissepiments throughout the group, including the curious vesicular or bubble-like tissue of the cyathophilidae and the general structural plan of the tetracoralla. Fig. 175, diagrammatic section of a ctenophore. Euchorus, such as streptoplasma and its allies, is well worth investigation from the physical and mathematical point of view, after the fashion which is here slightly adumbrated. The method of dividing a circular, or spherical, system into 8 parts, equal as to their areas but unequal in their peripheral boundaries, is probably of wide biological application. That is to say, without necessarily supposing it to be rigorously followed, the typical configuration which it yields seems to recur again and again, with more or less approximation to precision, and under widely different circumstances. I am inclined to think, for instance, that the unequal division of the surface of a ctenophore by its meridian-like ciliated bands is a case in point, Fig. Here, if we imagine each quadrant to be twice bisected by a curved anticline, we shall get what is apparently a close approximation to the actual position of the ciliated bands. The case however is complicated by the fact that the sectional plan of the organism is never quite circular, but always more or less elliptical. One point, at least, is clearly seen in the symmetry of the ctenophores. And that is that the radiating canals which pass outwards to correspond in position with the ciliated bands, have no common center, but diverge from one another by repeated bifurcations, in a manner comparable to the conjunctions of our cell walls. In like manner I am inclined to suggest that the same principle may help us to understand the apparently complex arrangement of the skeletal rods of a larval echinoderm, and the very complex conformation of the larva which is brought about by the presence of these long, slender skeletal radii. Figure 176. Diagrammatic arrangement of partitions, represented by skeletal rods, in larval echinoderm, Ophiura. In Fig. I have divided a circle into its 4 quadrants, and have bisected each quadrant by a circular arc, BC, passing from radius to periphery, as in the foregoing cases of cell division. And I have again bisected, in a similar way, the triangular halves of each quadrant, DD. I have also inserted a small circle in the middle of the figure, concentric with the large one. If now we imagine those lines in the figure which I have drawn black to be replaced by solid rods, we shall have at once the framework of an ophiurid, Pluteus, larva. Let us imagine all these arms to be bent symmetrically downwards, so that the plane of the paper is transformed into a spheroidal surface, such as that of a hemisphere, or that of a tall conical figure with curved sides. Let a membrane be spread, umbrella-like, between the outstretched skeletal rods, and let its margin loop from rod to rod in curves which are possibly catenaries, but are more probably portions of an elastic curve. And the outward resemblance to a Pluteus larva is now complete. By various slight modifications, by altering the relative lengths of the rods, by modifying their curvature or by replacing the curved rod by a tangent to itself, we can wring the changes which lead us from one known type of Pluteus to another. The case of the Bipinnaria larvae of echinids is certainly analogous, but it becomes Figure 177. Pluteus larva of Ophiurid. Very much more complicated. We have to do with a more complex partitioning of space, and I confess that I am not yet able to represent the more complicated forms in so simple a way. There are a few notable exceptions, besides the various unequally segmenting eggs, to the general rule that in cell division the mother cell tends to divide into equal halves. And one of these exceptional cases is to be found in connection with the development of stomata in the leaves of plants. The epidermal cells by which the leaf is covered may be of various shapes. Sometimes, as in a hyacinth, they are oblong, but more often they have an irregular shape in which we can recognize, more or less clearly, a distorted or imperfect hexagon. In the case of the oblong cells, a transverse partition will be the least possible, whether the cell be equally or unequally divided, unless, as we have already seen, the space to be cut off be a very small one, not more than. Figure 178. Diagrammatic development of stomata in sedum. Cf. figure in Sax's Botany. 1882, page 103. About 3/10 the area of a square based on the short side of the original rectangular cell. As the portion usually cut off is not nearly so small as this, we get the form of partition shown in Fig. And the cell so cut off is next bisected by a partition at right angles to the first. This latter partition splits, and the two last formed cells constitute the so-called guard cells of the stoma. In Figure 179. Diagrammatic development of stomata in hyacinth. Other cases, as in Fig. There will come a point where the minimal partition necessary to cut off the required fraction of the cell content is no longer a transverse one, but is a portion of a cylindrical wall, 2, cutting off one corner of the mother cell. The cell so cut off is now a certain segment of a circle, with an arc of approximately 120 degree, and its next division will be by means of a curved wall cutting it into a triangular and a quadrangular portion, 3. The triangular portion will continue to divide in a similar way, 4, 5, and at length, for a reason which is not yet clear, the partition wall between the new formed cells splits. And again we have the phenomenon of a stoma with its attendant guard cells. In Fig are shown the successive stages of division, and the changing curvatures of the various walls which ensue as each subsequent partition appears, introducing a new tension into the system. It is obvious that in the case of the oblong cells of the epidermis in the hyacinth the stomata will be found arranged in regular rows. While they will be irregularly distributed over the surface of the leaf in such a case as we have depicted in sedum. While, as I have said, the mechanical cause of the split which constitutes the orifice of the stoma is not quite clear, yet there can be little or no doubt that it, like the rest of the phenomenon, is related to surface tension. It might well be that it is directly due to the presence underneath this portion of epidermis of the hollow air space which the stoma is apparently developed for the purpose of communicating with. This air surface on both sides of the delicate epidermis might well cause such an alteration of tensions that the two halves of the dividing cell would tend to part company. In short, if the surface energy in a cell-air contact were half or less than half that in a contact between cell and cell, then it is obvious that our partition would tend to split, and give us a twofold surface in contact with air. Instead of the original boundary or interface between one cell and the other. In Professor McCallum's experiments, which we have briefly discussed in our short chapter on adsorption, it was found that large quantities of potassium gathered together along the outer walls of the guard cells of the stoma, thereby indicating a low surface tension along these outer walls. The tendency of the guard cells to bulge outwards is so far explained, and it is possible that, under the existing conditions of restraint, we may have here a force tending, or helping, to split the two cells asunder. It is clear enough, however, that the last stage in the development of a stoma is, from the physical point of view, not yet properly understood. In all our foregoing examples of the development of a tissue, we have seen that the process consists in the successive division of cells, each act of division being accompanied by the formation of a boundary surface, which, whether it become at once a solid or semi-solid partition or whether it remains semi-fluid, exercises in all cases an effect on the position and the form of the boundary which comes into being with the next act of division. In contrast to this general process stands the phenomenon known as free cell formation, in which, out of a common mass of protoplasm, a number of separate cells are simultaneously, or all but simultaneously, differentiated. In a number of cases it happens that, to begin with, a number of mother cells are formed simultaneously, and each of these divides, by two successive. Figure 180. Various pollen grains and spores, after Berthold, Campbell, Goebel and others. 1. Epilobium, 2. Passiflora, 3. Neotia, 4. Paraploca greca, 5. Opossonum, 6. Erica, 7. Spore of Osmunda, 8. Tetraspore of Calithamnion. Divisions, into 4 daughter cells. These daughter cells will tend to group themselves, just as would 4 soap bubbles, into a tetrad, the 4 cells corresponding to the angles of a regular tetrahedron. For the system of 4 bodies is evidently here in perfect symmetry. The partition walls and their respective edges meet at equal angles, 3 walls everywhere meeting in an edge, and the 4 edges converging to a point in the geometrical center of the system. This is the typical mode of development of pollen grains, common among monocotyledons and all but universal among dicotyledonous plants. By a loosening of the surrounding tissue and an expansion of the cavity, or anther cell, in which they lie, the pollen grains afterwards fall apart, and their individual form will depend upon whether or no their walls have. Figure 181. Dividing spore of Anthoceros. After Campbell. Solidified before this liberation takes place. For if not, then the separate grains will be free to assume a spherical form as a consequence of their own individual and unrestricted growth. But if they become solid or rigid prior to the separation of the tetrad, then they will conserve more or less completely the plane interfaces and sharp angles of the elements of the tetrahedron. The latter is the case, for instance, in the pollen grains of Epilobium, Fig. 1, and in many others. In the passion flower, too, we have an intermediate condition, where we can still see an indication of the facets where the grains abutted on one another in the tetrad. But the plane faces have been swollen by growth into spheroidal or spherical surfaces. It is obvious that there may easily be cases where the tetrads of daughter cells are prevented from assuming the tetrahedral form, cases, that is to say, where the 4 cells are forced and crushed into one plane. The figures given by Goebel of the development of the pollen of Neotia, 3, g, all the figures referring to grains taken from a single anther, illustrate this to perfection. And it will be seen that, when the 4 cells lie in a plane, they conform exactly to our typical diagram of the first 4 cells in a segmenting ovum. Occasionally, though the 4 cells lie in a plane, the diagram seems to fail us, for the cells appear to meet in a simple cross, as in 5. But here we soon perceive that the cells are not in complete interfacial contact, but are kept apart by a little intervening drop of fluid or bubble of air. The spores of ferns, 7, develop in very much the same way as pollen grains. And they also very often retain traces of the shape which they assumed as members of a tetrahedral figure. Among the tetraspores, 8, of the Floridae, or red seaweeds, we have a phenomenon which is in every respect analogous. Here again it is obvious that, apart from differences in actual magnitude, and apart from superficial or accidental differences, referable to other physical phenomena, in the way of color, texture and minute sculpture or pattern. It comes to pass, through the laws of surface tension and the principles of the geometry of position, that a very small number of diagrammatic figures will sufficiently represent the outward forms of all the tetraspores, four-celled pollen grains, and other four-celled aggregates which are known or are even capable of existence. We have been dealing hitherto, save for some slight exceptions, with the partitioning of cells on the assumption that the system either remains unaltered in size or else that growth has proceeded uniformly in all directions. But we extend the scope of our inquiry very greatly when we begin to deal with unequal growth, with growth, that is to say, which produces a greater extension along some one axis than another. And here we come close in touch with that great and still, as I think, insufficiently appreciated generalization of Sachs, that the manner in which the cells divide is the result, and not the cause, of the form of the dividing structure, that the form of the mass is caused by its growth as a whole, and is not a resultant of the growth of the cells individually considered. Such asymmetry of growth may be easily imagined, and may conceivably arise from a variety of causes. In any individual cell, for instance, it may arise from molecular asymmetry of the structure of the cell wall, giving it greater rigidity in one direction than another, while all the while the hydrostatic pressure within the cell remains constant and uniform. In an aggregate of cells, it may very well arise from a greater chemical, or osmotic, activity in one than another, leading to a localized increase in the fluid pressure, and to a corresponding bulge over a certain area of the external surface. It might conceivably occur as a direct result of the preceding cell divisions, when these are such as to produce many peripheral or concentric walls in one part and few or none in another, with the obvious result of strengthening the common boundary wall and resisting the outward pressure of growth in parts where the former is the case. That is to say, in our dividing quadrant, if its quadrangular portion subdivide by paraclines, and the triangular portion by oblique anticlines, as we have seen to be the natural tendency, then we might expect that external growth would be more manifest over the latter than over the former areas. As a direct and immediate consequence of this we might expect a tendency for special outgrowths, or buds, to arise from the triangular rather than from the quadrangular cells. And this turns out to be not merely a tendency towards which theoretical considerations point, but a widespread and important factor in the morphology of the cryptogams. But meanwhile, without inquiring further into this complicated question, let us simply take it that, if we start from such a simple case as a round cell which has divided into two halves, or 4/4, as the case may be, we shall at once get bilateral symmetry about a main axis, and other secondary results arising therefrom, as soon as one of the halves, or one of the quarters, begins to shew a rate of growth in advance of the others. For the more rapidly growing cell, or the peripheral wall common to two or more such rapidly growing cells, will bulge out into an ellipsoid form, and may finally extend into a cylinder with rounded or ellipsoid end. This latter very simple case is illustrated in the development of a pollen tube, where the rapidly growing cell develops into the elongated cylindrical tube, and the slow-growing or quiescent part remains behind as the so-called vegetative cell or cells. Just as we have found it easier to study the segmentation of a circular disc than that of a spherical cell, so let us begin in the same way, by inquiring into the divisions which will ensue if the disc tend to grow, or elongate, in some one particular direction, instead of in radial symmetry. The figures which we shall then obtain will not only apply to the disc, but will also represent, in all essential features, a projection or longitudinal section of a solid body, spherical to begin with, preserving its symmetry as a solid of revolution, and subject to the same general laws as we have studied in the disc. 1. Suppose, in the first place, that the axis of growth lies symmetrically in one of the original quadrantal cells of a segmenting disc, and let this growing cell elongate with comparative rapidity before it subdivides. When it does divide, it will necessarily do so by a transverse partition, concave towards the apex of the cell, and, as further elongation takes place, the cylindrical structure which will be developed thereby will tend to be again and again subdivided by similar concave transverse partitions. If at any time, through this process of concurrent elongation and subdivision, the apical cell become equivalent to, or less than, a hemisphere, it will next divide by means of a longitudinal, or vertical partition. And similar longitudinal partitions will arise in the other segments of the cylinder, as soon as it comes about that their length, in the direction of the axis, is less than their breadth. Figure 182. But when we think of this structure in the solid, we at once perceive that each of these flattened segments of the cylinder, into which our cylinder has divided, is equivalent to a flattened circular disc. And its further division will accordingly tend to proceed like any other flattened disc, namely into 4 quadrants, and afterwards by anticlines and periclines in the usual way. A section across the cylinder, then, will tend to shew us precisely the same arrangements as we have already so fully studied in connection with the typical division of a circular cell into quadrants. And of these quadrants into triangular and quadrangular portions, and so on. But there are other possibilities to be considered, in regard to the mode of division of the elongating quasi-cylindrical portion, as it gradually develops out of the growing and bulging quadrantal cell. For the manner in which this latter cell divides will simply depend upon the form it has assumed before each successive act of division takes place. That is to say, upon the ratio between its rate of growth and the frequency of its successive divisions. For, as we have already seen, if the growing cell attain a markedly oblong or cylindrical form before division ensues, then the partition will arise transversely to the long axis. If it be but a little more than a hemisphere, it will divide by an oblique partition. And if it be less than a hemisphere, as it may come to be after successive transverse divisions, it will divide by a vertical partition, that is to say by one coinciding with its axis of growth. An immense number of permutations and combinations may arise in this way, and we must confine our illustrations to a small number of cases. The important thing is not so much to trace out the various conformations which may arise, but to grasp the fundamental principle, which is, that the forces which dominate the form of each cell regulate the manner of its subdivision. That is to say, the form of the new cells into which it subdivides. Or in other words, the form of the growing organism regulates the form and number of the cells which eventually constitute it. The complex cell network is not the cause but the result of the general configuration, which latter has its essential cause in whatsoever physical and chemical processes have led to a varying velocity of growth in one direction as compared with another. Figure 183. Development of sphagnum. After Campbell. In the annexed figure of an embryo of sphagnum we see a mode of development almost precisely corresponding to the hypothetical case which we have just described, the case, that is to say, where one of the 4 original quadrants of the mother cell is the chief agent in future growth and development. We see at the base of our first figure, A, the 3 stationary, or undivided quadrants, one of which has further slowly divided in the stage B. The active quadrant has grown quickly into a cylindrical structure, which inevitably divides, in the next place, into a series of transverse partitions. And accordingly, this mode of development carries with it the presence of a single, apical cell, whose lower wall is a spherical surface with its convexity downwards. Each cell of the subdivided cylinder now appears as a more or less flattened disc, whose mode of further subdivision we may prognosticate according to our former investigation, to which subject we shall presently return. Figure 184. 2. In the next place, still keeping to the case where only one of the original quadrant cells continues to grow and develop. Let us suppose that this growing cell falls to be divided when by growth it has become just a little greater than a hemisphere. It will then divide, as in Fig. 2, by an oblique partition, in the usual way, whose precise position and inclination to the base will depend entirely on the configuration of the cell itself, save only, of course, that we may have also to take into account the possibility of the division being into 2 unequal halves. By our hypothesis, the growth of the whole system is mainly in a vertical direction, which is as much as to say that the more actively growing protoplasm, or at least the strongest osmotic force, will be found near the apex, where indeed there is obviously more external surface for osmotic action. It will therefore be that one of the 2 cells which contains, or constitutes, the apex which will grow more rapidly than the other, and which therefore will be the first to divide, and indeed in any case. It will usually be this one of the two which will tend to divide first, inasmuch as the triangular and not the quadrangular half is bound to constitute the apex. It is obvious that, unless the act of division be so long postponed that the cell has become quasi-cylindrical, it will divide by another oblique partition, starting from, and running at right angles to, the first. And so division will proceed. Figure 185. Gemma of moss. After Campbell. By oblique alternate partitions, each one tending to be, at first, perpendicular to that on which it is based and also to the peripheral wall. But all these points of contact soon tending, by reason of the equal tensions of the three films or surfaces which meet there, to form angles of 120 degrees. There will always be, in such a case, a single apical cell, of a more or less distinctly triangular form. The annexed figure of the developing antheridium of a liverwort, Richia, is a typical example of such a case. In Fig. which represents a gemma of a moss, we see just the same thing. With this addition, that here the lower of the two original cells has grown even more quickly than the other, constituting a long cylindrical stalk and dividing in accordance with its shape, by means of transverse septa. In all such cases as these, the cells whose development we have studied will in turn tend to subdivide, and the manner in which they will do so must depend upon their own proportions. And in all cases, as we have already seen, there will sooner or later be a tendency to the formation of periclinal walls, cutting off an epidermal layer of cells, as Fig illustrates very well. Figure 186. Development of antheridium of Richia. After Campbell. Figure 187. Section of growing shoot of CELL-AGGREGATES, diagrammatic. Figure 188. Embryo of Jungermania. After Kienitz-Gerloff. The method of division by means of oblique partitions is a common one in the case of growing points. For it evidently includes all cases in which the act of cell division does not lag far behind that elongation which is determined by the specific rate of growth. And it is also obvious that, under a common type, there must here be included a variety of cases which will, at first sight, present a very different appearance one from another. For instance, in Fig. which represents a growing shoot of CELL-AGGREGATES, and somewhat less diagrammatically in the young embryo of Jungermania, Fig. we have the appearance of an almost straight vertical partition running up in the axis of the system, and the primary cell walls are set almost at right angles to it, almost transversely. That is to say, to the outer walls and to the long axis of the structure. We soon recognize, however, that the difference is merely a difference of degree. The more remote the partitions are, that is to say the greater the velocity of growth relatively to division, the less abrupt will be the alternate kinks or curvatures of the portions which lie in the neighborhood of the axis. And the more will these portions appear to constitute a single unbroken wall. Figure 189. 3. But an appearance nearly, if not quite, indistinguishable from this may be got in another way, namely, when the original growing cell is so nearly hemispherical that it is actually divided by a vertical partition, into two quadrants. And from this vertical partition, as it elongates, lateral partition walls will arise on either side. And by the tensions exercised by these, the vertical partition will be bent into little portions set at 120 degrees one to another, and the whole will come to look just like that which, in the former case, was made up of portions of many successive oblique partitions. Let us now, in one or two cases, follow out a little further the stages of cell division whose beginning we have studied in the last paragraphs. In the antheridium of Richia, after the successive oblique partitions have produced the longitudinal series of cells shown in Fig. It is plain that the next partitions will arise periclinally, that is to say parallel to the outer wall, which in this particular case represents the short axis of the oblong cells. The effect is at once to produce an epidermal layer, whose cells will tend to subdivide further by means of partitions perpendicular to the free surface, that is to say crossing the flattened cells by their shortest diameter. The inner mass, beneath the epidermis, consists of cells which are still more or less oblong, or which become definitely so in process of growth. And these again divide, parallel to their short axes, into squarish cells, which as usual, by the mutual tension of their walls, become hexagonal, as seen in a plane section. There is a clear distinction, then, in form as well as in position, between the outer covering cells and those which lie within this envelope. The latter are reduced to a condition which merely fulfills the mechanical function of a protective coat, while the former undergo less modification, and give rise to the actively living, reproductive elements. Figure 190. Development of sporangium of Osmunda. After Bauer. In Fig is shown the development of the sporangium of a fern, Osmunda. We may trace here the common phenomenon of a series of oblique partitions, built alternately on one another, and cutting off a conspicuous triangular apical cell. Over the whole system an epidermal layer has been formed, in the manner we have described. And in this case it covers the apical cell also, owing to the fact that it was of such dimensions that, at one stage of growth, a periclinal partition wall, cutting off its outer end, was indicated as of less area than an anticlinal one. This periclinal wall cuts down the apical cell to the proportions, very nearly, of an equilateral triangle, but the solid form of the cell is obviously that of a tetrahedron with curved faces. And accordingly, the least possible partitions by which further subdivision can be effected will run successively parallel to its four sides, or its three sides when we confine ourselves to the appearances as seen in section. The effect, as seen in section, is to cut off on each side a characteristically flattened cell, oblong as seen in section, still leaving a triangular, or strictly speaking, a tetrahedral, one in the center. The former cells, which constitute no specific structure or perform no specific physiological function, but which merely represent certain directions in space towards which the whole system of partitioning has gradually led, are called by botanists the tapetum. The active growing tetrahedral cell which lies between them, and from which in a sense every other cell in the system has been either directly or indirectly segmented off, still manifests, as it were, its vigor and activity, and now, by internal subdivision, becomes the mother cell of the spores. In all these cases, for simplicity's sake, we have merely considered the appearances presented in a single, longitudinal, plane of optical section. But it is not difficult to interpret from these appearances what would be seen in another plane, for instance in a transverse section. In our first example, for instance, that of the developing embryo of sphagnum, Fig. We can see that, at appropriate levels, the cells of the original cylindrical row have divided into transverse rows of 4, and then of 8 cells. We may be sure that the 4 cells represent, approximately, quadrants of a cylindrical disc, the 4 cells, as usual, not meeting in a point, but intercepted by a small intermediate partition. Again, where we have a plate of 8 cells, we may well imagine that the 8 octants are arranged in what we have found to be the way naturally resulting from the division of 4 quadrants. That is to say into alternately triangular and quadrangular portions. And this is found by means of sections to be the case. The accompanying figure is precisely comparable to our previous diagrams of the arrangement of an aggregate of 8 cells in a dividing disc, save only that, in 2 cases, the cells have already undergone a further subdivision. It follows in like manner, that in a host of cases we meet with this characteristic figure, in one or other of its possible, and strictly limited, variations, in the cross-sections of growing embryonic structures. Just as we have already seen that it appears in a host of cases where the entire system, or a portion of its surface, consists of 8 cells only. For example, in Fig. Figure 191. A, B, sections of younger and older embryos of Phascum, C, do. Of Adiantum. After Kienitz-Gerloff. We have it again, in a section of a young embryo of a moss, Phascum, and in a section of an embryo of a fern, Adiantum. In Figure 192. Section through frond of Gerardia. Sphacillaria. After Goebel. Fig. Shewing a section through a growing frond of a seaweed, Gerardia, we have a case where the partitions forming the 8 octants have conformed to the usual type. But instead of the usual division by paraclines of the 4 quadrangular spaces, these latter are dividing by means of oblique septa, apparently owing to the fact that the cell is not dividing into 2 equal, but into 2 unequal portions. In this last figure we have a peculiar look of stiffness or formality, such that it appears at first to bear little resemblance to the rest. The explanation is of the simplest. The mode of partitioning differs little, except to some slight extent in the way already mentioned, from the normal type. But in this case the partition walls are so thick and become so quickly comparatively solid and rigid, that the secondary curvatures due to their successive mutual tractions are here imperceptible. A curious and beautiful case, apparently aberrant but which would doubtless be found conforming strictly to physical laws, if only we clearly understood the actual conditions, is indicated in Figure 193. Development of antheridium of Pteris. After Strasburger. The development of the antheridium of a fern, as described by Strasburger. Here the antheridium develops from a single cell, whose form has grown to be something more than a hemisphere. And the first partition, instead of stretching transversely across the cell, as we should expect it to do if the cell were actually spherical, has as it were sagged down to come in contact with the base, and so to develop into an annular partition, running round the lower margin of the cell. The phenomenon is akin to that cutting off of the corner of a cubical cell by a spherical partition, of which we have spoken on p. And the annular film is very easy to reproduce by means of a soap bubble in the bottom of a cylindrical dish or beaker. The next partition is a periclinal one, concentric with the outer surface of the young antheridium. And this in turn is followed by a concave partition which cuts off the apex of the original cell, but which becomes connected with the second, or periclinal partition in precisely the same annular fashion as the first partition did with the base of the little antheridium. The result is that, at this stage, we have 4 cell cavities in the little antheridium, 1, a central cavity, 2, an annular space around the lower margin, 3, a narrow annular or cylindrical space around the sides of the antheridium, and 4, a small terminal or apical cell. It is evident that the tendency, in the next place, will be to subdivide the flattened external cells by means of anticlinal partitions, and so to convert the whole structure into a single layer of epidermal cells, surrounding a central cell within which, in course of time, the antherozoids are developed. The foregoing account deals only with a few elementary phenomena, and may seem to fall far short of an attempt to deal in general with the forms of tissues. But it is the principle involved, and not its ultimate and very complex results, that we can alone attempt to grapple with. The stock in trade of mathematical physics, in all the subjects with which that science deals, is for the most part made up of simple, or simplified, cases of phenomena which in their actual and concrete manifestations are usually too complex for mathematical analysis. And when we attempt to apply its methods to our biological and histological phenomena, in a preliminary and elementary way, we need not wonder if we be limited to illustrations which are obviously of a simple kind, and which cover but a small part of the phenomena with which the histologist has become familiar. But it is only relatively that these phenomena to which we have found the method applicable are to be deemed simple and few. They go already far beyond the simplest phenomena of all, such as we see in the dividing protococcus, and in the first stages, 2-celled or 4-celled, of the segmenting egg. They carry us into stages where the cells are already numerous, and where the whole conformation has become by no means easy to depict or visualize, without the help and guidance which the phenomena of surface tension, the laws of equilibrium and the principle of minimal areas are at hand to supply. And so far as we have gone, and so far as we can discern, we see no sign of the guiding principles failing us, or of the simple laws ceasing to hold good. Chapter 9 on Concretions, Spicules, and Spicular Skeletons. The deposition of inorganic material in the living body, usually in the form of calcium salts or of silica, is a very common and widespread phenomenon. It begins in simple ways, by the appearance of small isolated particles, crystalline or non-crystalline, whose form has little relation or sometimes none to the structure of the organism. It culminates in the complex skeletons of the vertebrate animals, in the massive skeletons of the corals, or in the polished, sculptured and mathematically regular molluscan shells. Even among many very simple organisms, such as the diatoms, the radiolarians, the foraminifera, or the sponges, the skeleton displays extraordinary variety and beauty. Whether by reason of the intrinsic form of its elementary constituents or the geometric symmetry with which these are arranged and interconnected. With regard to the form of these various structures, and this is all that immediately concerns us here, it is plain that we have to do with two distinct problems, which however, though theoretically distinct, may merge with one another. For the form of the spicule or other skeletal element may depend simply upon its chemical nature, as for instance, to take a simple but not the only case, when the form is purely crystalline. Or the inorganic solid material may be laid down in conformity with the shapes assumed by the cells, tissues or organs, and so be, as it were, molded to the shape of the living organism. And again, there may well be intermediate stages in which both phenomena may be simultaneously recognized, the molecular forces playing their part in conjunction with, and under the restraint of, the other forces inherent in the system. So far as the problem is a purely chemical one, we must deal with it very briefly indeed, and all the more because special investigations regarding it have as yet been few, and even the main facts of the case are very imperfectly known. This at least is evident, that the whole series of phenomena with which we are about to deal go deep into the subject of colloid chemistry. And especially with that branch of the science which deals with the properties of colloids in connection with capillary or surface phenomena. It is to the special student of colloid chemistry that we must ultimately and chiefly look for the elucidation of our problem. In the first and simplest part of our subject, the essential problem is the problem of crystallization in presence of colloids. In the cells of plants, true crystals are found in comparative abundance, and they consist, in the great majority of cases, of calcium oxalate. In the stem and root of the rhubarb, for instance, in the leaf stalk of begonia, and in countless other cases, sometimes within the cell, sometimes in the substance of the cell wall, we find large and well-formed crystals of this salt. Their varieties of form, which are extremely numerous, are simply the crystalline forms proper to the salt itself, and belong to the two systems, cubic and monoclinic, in one or other of which. According to the amount of water of crystallization, this salt is known to crystallize. When calcium oxalate crystallizes according to the latter system, as it does when its molecule is combined with two molecules of water of crystallization, the microscopic crystals have the form of fine needles, or rhaphides, such as are very common in plants. And it has been found that these are artificially produced when the salt is crystallized out in presence of glucose or of dextrin. Figure 194. Alcyonarian spicules, Siphonogorgia. And Anthogorgia. After Studer. Calcium carbonate, on the other hand, when it occurs in plant cells, as it does abundantly, for instance in the cystoliths of the Urticaceae and Acanthaceae, and in great quantities in Melibesia and the other calcareous or stony algae, appears in the form of fine rounded granules, whose inherent crystalline structure is not outwardly visible, but is only revealed, like that of a molluscan shell, under polarized light. Among animals, a skeleton of carbonate of lime occurs under a multitude of forms, of which we need only mention now a very few of the most conspicuous. The spicules of the calcareous sponges are triradiate, occasionally quadriradiate, bodies, with pointed rays, not crystalline in outward form but with a definitely crystalline internal structure. We shall return again to these, and find for them what would seem to be a satisfactory explanation of their form. Among the Alcyonarian zoophytes we have a great variety of spicules, which are sometimes straight and slender rods, sometimes flattened and more or less striated plates, and still more often rounded or branched concretions with rough or knobby surfaces, figs. 200. A third type, presented by several very different things, such as a pearl, or the ear bone of a bony fish, consists of a more or less rounded body, sometimes spherical, sometimes flattened. in which the calcareous matter is laid down in concentric zones, denser and clearer layers alternating with one another. In the development of the molluscan shell and in the calcification of a bird's egg or the shell of a crab, for instance, spheroidal bodies with similar concentric striation make their appearance. But instead of remaining separate they become crowded together, and as they coalesce they combine to form a pattern of hexagons. In some cases, the carbonate of lime on being dissolved away by acid leaves behind it a certain small amount of organic residue. In most cases other salts, such as phosphates of lime, ammonia, or magnesia, are present in small quantities. And in most cases if not all the developing spicule or concretion is somehow or other so associated with living cells that we are apt to take it for granted that it owes its peculiarities of form to the constructive or plastic agency of these. The appearance of direct association with living cells, however, is apt to be fallacious. For the actual precipitation takes place, as a rule, not in actively living, but in dead or at least inactive tissue, that is to say in the formed material or matrix which, as for instance in cartilage, accumulates round the living cells. In the interspaces between these latter, or at least, as often happens, in connection with the cell wall or cell membrane rather than within the substance of the protoplasm itself. We need not go the length of asserting that this is a rule without exception, but, so far as it goes, it is of great importance and to its consideration we shall presently return. Cognate with this is the fact that it is known, at least in some cases, that the organism can go on living and multiplying with apparently unimpaired health. When stinted or even wholly deprived of the material of which it is wont to make its spicules or its shell. Thus, Pouchet and Chabry have shown that the eggs of sea urchins reared in lime-free water develop in apparent health, into larvae entirely destitute of the usual skeleton of calcareous rods, and in which, accordingly, the long arms of the Pluteus larva, which the rods support and distend, are entirely suppressed. And again, when foraminifera are kept for generations in water from which they gradually exhaust the lime, their shells grow hyaline and transparent, and seem to consist only of chitinous material. On the other hand, in the presence of excessive lime, the shells become much altered, strengthened with various ornaments, and assuming characters described as proper to other varieties and even species. The crucial experiment, then, is to attempt the formation of similar structures or forms, apart from the living organism, but, however feasible the attempt may be in theory, we shall be prepared from the first to encounter difficulties. And to realize that, though the actions involved may be wholly within the range of chemistry and physics, yet the actual conditions of the case may be so complex, subtle and delicate, that only now and then, and in the simplest of cases, shall we find ourselves in a position to imitate them completely and successfully. Such an investigation is only part of that much wider field of inquiry through which Stéphane Leduc and many other workers have sought to produce, by synthetic means, forms similar to those of living things. But it is a well-defined and circumscribed part of that wider investigation. When by chemical or physical experiment we obtain configurations similar, for instance, to the phenomena of nuclear division, or conformations similar to a pattern of hexagonal cells, or a group of vesicles which resemble some particular tissue or cell aggregate, we indeed prove what it is the main object of this book to illustrate, namely, that the physical forces are capable of producing particular organic forms. But it is by no means always that we can feel perfectly assured that the physical forces which we deal with in our experiment are identical with, and not merely analogous to, the physical forces which, at work in nature, are bringing about the result which we have succeeded in imitating. In the present case, however, our inquiry is restricted and apparently simplified. We are seeking in the first instance to obtain by purely chemical means a purely chemical result, and there is little room for ambiguity in our interpretation of the experiment. When we find ourselves investigating the forms assumed by chemical compounds under the peculiar circumstances of association with a living body, and when we find these forms to be characteristic or recognizable, and somehow different from those which, under other circumstances, the same substance is wont to assume, an analogy presents itself to our minds, captivating though perhaps somewhat remote, between this subject of ours and certain synthetic problems of the organic chemist. There is doubtless an essential difference, as well as a difference of scale, between the visible form of a spicule or concretion and the hypothetical form of an individual molecule, but molecular form is a very important concept. And the chemist has not only succeeded, since the days of Wöhler, in synthesizing many substances which are characteristically associated with living matter, but his task has included the attempt to account for the molecular forms of certain asymmetric substances, glucose, malic acid and many more, as they occur in nature. These are bodies which, when artificially synthesized, have no optical activity, but which, as we actually find them in organisms, turn, when in solution, the plane of polarized light in one direction or the other. Thus dextroglucose and levomalic acid are common products of plant metabolism, but dextromalic acid and levoglucose do not occur in nature at all. The optical activity of these bodies depends, as Pasteur shewed more than 50 years ago, upon the form, right-handed or left-handed, of their molecules. Which molecular asymmetry further gives rise to a corresponding right or left-handedness, or enantiomorphism, in the crystalline aggregates. It is a distinct problem in organic or physiological chemistry, and by no means without its interest for the morphologist, to discover how it is that nature, for each particular substance, habitually builds up, or at least selects its molecules in a one-sided fashion, right-handed or left-handed as the case may be. It will serve us no better to assert that this phenomenon has its origin in fortuity, than to repeat the Abbé Galiani's saying, les dés de la nature sont pipes. The problem is not so closely related to our immediate subject that we need discuss it at length. But at the same time it has its clear relation to the general question of form in relation to vital phenomena. And moreover it has acquired interest as a theme of long-continued discussion and new importance from some comparatively recent discoveries. According to Pasteur, there lay in the molecular asymmetry of the natural bodies and the symmetry of the artificial products, one of the most deep-seated differences between vital and non-vital phenomena. He went further and declared that this was perhaps the only well-marked line of demarcation that can at present be drawn between the chemistry of dead and of living matter. Nearly 40 years afterwards the same theme was pursued and elaborated by Japp in a celebrated lecture, and the distinction still has its weight, I believe, in the minds of many if not most chemists. We arrive at the conclusion, said Professor Japp, that the production of single asymmetric compounds, or their isolation from the mixture of their enantiomorphs, is, as Pasteur firmly held, the prerogative of life. Only the living organism, or the living intelligence with its conception of asymmetry, can produce this result. Only asymmetry can beget asymmetry. In these last words, which, so far as the chemist and the biologist are concerned, we may acknowledge to be perfectly true, lies the crux of the difficulty. For they at once bid us inquire whether in nature, external to and antecedent to life, there be not some asymmetry to which we may refer the further propagation or begetting of the new asymmetries, or whether in default thereof we be rigorously confined to the conclusion, from which Japp saw no escape, that, at the moment when life first arose, a directive force came into play, a force of precisely the same character as that which enables the intelligent operator, by the exercise of his will, to select one crystallized enantiomorph and reject its asymmetric opposite. Observe that it is only the first beginnings of chemical asymmetry that we need to discover, for when asymmetry is once manifested, it is not disputed that it will continue to beget asymmetry. A plausible suggestion is now at hand, which if it be confirmed and extended will supply or at least sufficiently illustrate the kind of explanation which is required. We know in the first place that in cases where ordinary non-polarized light acts upon a chemical substance, the amount of chemical action is proportionate to the amount of light absorbed. We know in the second place, in certain cases, that light circularly polarized is absorbed in different amounts by the right-handed or left-handed varieties, as the case may be, of an asymmetric substance. And thirdly, we know that a portion of the light which comes to us from the sun is already plane polarized light, which becomes in part circularly polarized, by reflection, according to Jamin, at the surface of the sea, and then rotated in a particular direction under the influence of terrestrial magnetism. We only require to be assured that the relation between absorption of light and chemical activity will continue to hold good in the case of circularly polarized light. That is to say that the formation of some new substance or other, under the influence of light so polarized, will proceed asymmetrically in consonance with the asymmetry of the light itself. Or conversely, that the asymmetrically polarized light will tend to more rapid decomposition of those molecules by which it is chiefly absorbed. This latter proof is now said to be furnished by Byk, who asserts that certain tartrates become unsymmetrical under the continued influence of the asymmetric rays. Here then we seem to have an example, of a particular kind and in a particular instance, an example limited but yet crucial, if confirmed, of an asymmetric force, non-vital in its origin, which might conceivably be the starting point of that asymmetry which is characteristic of so many organic products. The mysteries of organic chemistry are great, and the differences between its processes or reactions as they are carried out in the organism and in the laboratory are many. The actions, catalytic and other, which go on in the living cell are of extraordinary complexity. But the contention that they are different in kind from what we term ordinary chemical operations, or that in the production of single asymmetric compounds there is actually to be witnessed, as Pasteur maintained, a prerogative of life, would seem to be no longer safely tenable. And furthermore, it behoves us to remember that, even though failure continued to attend all artificial attempts to originate the asymmetric or optically active compounds which organic nature produces in abundance, this would only prove that a certain physical force, or mode of physical action, is at work among living things though unknown elsewhere. It is a mode of action which we can easily imagine, though the actual mechanism we cannot set a-going when we please. And it follows that such a difference between living matter and dead would carry us but a little way, for it would still be confined strictly to the physical or mechanical plane. Our historic interest in the whole question is increased by the fact, or the great probability, that the tenacity with which Pasteur fought against the doctrine of spontaneous generation was not unconnected with his belief that chemical compounds of one-sided symmetry could not arise save under the influence of life. But the question whether spontaneous generation be a fact or not does not depend upon theoretical considerations. Our negative response is based, and is so far soundly based, on repeated failures to demonstrate its occurrence. Many a great law of physical science, not excepting gravitation itself, has no higher claim on our acceptance. Let us return then, after this digression, to the general subject of the forms assumed by certain chemical bodies when deposited or precipitated within the organism, and to the question of how far these forms may be artificially imitated or theoretically explained. Mr. George Rainey, of St. Bartholomew's Hospital, to whom we have already referred, and Professor P. Harding, of Utrecht, were the first to deal with this specific problem. Mr. Rainey published, between 1857 and 1861, a series of valuable and thoughtful papers to shew that shell and bone and certain other organic structures were formed by a process of molecular coalescence, demonstrable in certain artificially formed products. Professor Harding, after 30 years of experimental work, published in 1872 a paper, which has become classical, entitled Recherches de morphologie synthétique, sur la production artificielle de quelques formations calcaires organiques. His aim was to pave the way for a morphology synthétique, as Wöhler had laid the foundations of a chimie synthétique, by his classical discovery 40 years before. Rainey and Harding used similar methods, and these were such as many other workers have continued to employ, partly with the direct object of explaining the genesis of organic forms and partly as an integral part of what is now known as colloid chemistry. The whole gist of the method was to bring some soluble salt of lime, such as the chloride or nitrate, into solution within a colloid medium, such as gum, gelatin, or albumin, and then to precipitate it out in the form of some insoluble compound, such as the carbonate or oxalate. Harding found that, when he added a little sodium or potassium carbonate to a concentrated solution of calcium chloride in albumin, he got at first a gelatinous mass, or colloid precipitate, which slowly transformed by the Figure 195. Chalcospherites, or concretions, of calcium carbonate, deposited in white of egg. After Harding Figure 196. A single chalcosphorite, with central nucleus, and striated, iridescent border. After hardening. Appearance of tiny microscopic particles, at first motionless, but afterwards as they grew larger shewing the typical Brownian movement. So far, very much the same phenomena were witnessed whether the solution were albuminous or not, and similar appearances indeed had been witnessed and recorded by Gustave Rose, so far back as 1837. But in the later stages the presence of albuminoid matter made a great difference. Now, after a few days, the calcium carbonate was seen to be deposited in the form of large rounded concretions, with a more or less distinct central nucleus, and with a surrounding structure at once radiate and concentric. The presence of concentric zones or lamellae, alternately dark and clear, was especially characteristic. These round, chalcospherites shewed a tendency to aggregate together. Figure 197. Later stages in the same experiment. In layers, and then to assume polyhedral, or often regularly hexagonal, outlines. In this latter condition they closely resemble. Figure 198 and A, section of shell of Maya, B. Section of hinge tooth of dew. After Carpenter. The early stages of calcification in a molluscan, Fig, or still more in a crustacean shell. While in their isolated condition they very closely resemble the little calcareous bodies in the tissues of a trematode or a cestode worm, or in the esophageal glands of an earthworm. Figure 199. Large irregular calcareous concretions, or spicules, deposited in a piece of dead cartilage, in presence of calcium phosphate. After hardening. When the albumin was somewhat scanty, or when it was mixed with gelatin, and especially when a little phosphate of lime was added to the mixture, the spheroidal globules tended to become rough, by an outgrowth of spinous or digitiform projections. And in some cases, but not without the presence of the phosphate, the result was an irregularly shaped knobby spicule, precisely similar to those which are characteristic of the Alcyonaria. The rough spicules of the Alcyonaria are extraordinarily variable in shape and size, as, looking at them from the chemist's or the physicist's point of view, we should expect them to be. Partly upon the form of these spicules, and partly on the general form or mode of branching of the entire colony. Figure 200. Additional illustrations of Alcyonarian spicules. Eunicea. After Studer. Of polyps, a vast number of separate species have been based by systematic zoologists. But it is now admitted that even in specimens of a single species, from one and the same locality, the spicules may vary immensely in shape and size, and Professor Hickson declares, in a paper published while these sheets are passing through the press, that after many years of laborious work in striving to determine species of these animal colonies, he feels quite convinced that we have been engaged in a more or less fruitless task. The formation of a tooth has very lately been shown to be a phenomenon of the same order. That is to say, calcification in both dentine and enamel is in great part a physical phenomenon. The actual deposit in both tissues occurs in the form of chalcospherites, and the process in mammalian tissue is identical in every point with the same process occurring in lower organisms. The ossification of bone, we may be sure, is in the same sense and to the same extent a physical phenomenon. The typical structure of a chalcosphorite is no other than that of a pearl, nor does it differ essentially from that of the otolith of a mollusk or of a bony fish. The otoliths, by the way, of the elasmobranch fishes, like those of reptiles and birds, are not developed after this fashion, but are true crystals of calcspar. Throughout these phenomena, the effect of surface tension is manifest. It is by surface tension that ultramicroscopic particles are brought together in the first floccular precipitate or coagulum. Figure 201. A crust of close-packed calcareous concretions, precipitated at the surface of an albuminous solution. After hardening. Figure 202. Aggregated chalcospherites. After hardening. By the same agency, the coarser particles are in turn agglutinated into visible lumps, and the form of the chalcospherites, whether it be that of the solitary spheres or that assumed in various stages of aggregation, e.g. Fig. is likewise due to the same agency. From the point of view of colloid chemistry, the whole phenomenon is very important and significant. And not the least significant part is this tendency of the solidified deposits to assume the form of spherolites and other rounded contours. In the phraseology of that science, we are dealing with a two-phase system, which finally consists of solid particles in suspension in a liquid, the former being styled the disperse phase, the latter the dispersion medium. In accordance with a rule first recognized by Ostwald, when a substance begins to separate out from a solution, so making its appearance as a new phase, it always makes its appearance first as a liquid. Here is a case in point. The minute quantities of material, on their way from a state of solution to a state of suspension, pass through a liquid to a solid form. And their temporary sojourn in the former leaves its impress in the rounded contours which surface tension brought about while the little aggregate was still labile or fluid, while coincidently with this surface tension effect upon the surface, crystallization tended to take place throughout the little liquid mass, or in such portion of it as had not yet consolidated and crystallized. Figure 203. After Harding. Where we have simple aggregates of 2 or 3 chalcospherites, the resulting figure is precisely that of so many contiguous soap bubbles. In other cases, composite forms result which are not so easily explained, but which, if we could only account for them, would be of very great interest to the biologist. For instance, when smaller chalcospheres seem, as it were, to invade the substance of a larger one, we get curious conformations which in the closest possible way resemble the outlines of certain of the diatoms, Fig. Another very curious formation, which Harding calls a conostat, is of frequent occurrence, and in it we see at least a suggestion of analogy with the configuration which, in a protoplasmic structure, we have spoken of as a collar cell. The conostats, which are formed in the surface layer of the solution, consist of a portion of a spheroidal chalcosphorite, whose upper part is continued into a thin spheroidal collar, of somewhat larger radius than the solid sphere. But the precise manner in which the collar is formed, possibly around a bubble of gas, possibly about a vortex-like diffusion current, is not obvious. Among these various phenomena, the concentric striation observed in the chalcosphorite has acquired a special interest and importance. It is part of a phenomenon now widely known, and recognized as an important factor in colloid chemistry, under the name of Liesgang's rings. Figure 204. Conostats. After Harding. If we dissolve, for instance, a little bichromate of potash in gelatin, pour it on to a glass plate, and after it is set place upon it a drop of silver nitrate solution, there appears in the course of a few hours the phenomenon of Liesgang's rings. At first the silver forms a central patch of abundant reddish-brown chromate precipitate. But around this, as the silver nitrate diffuses slowly through the gelatin, the precipitate no longer comes down in a continuous, uniform layer, but forms a series of zones, beautifully regular, which alternate with clear interspaces of jelly, and which stand farther and farther apart, in logarithmic ratio, as they recede from the center. For a discussion of the raison d'être of this phenomenon, still somewhat problematic, the student must consult the textbooks of physical and colloid chemistry. But, speaking very generally, we may say the appearance of Liesgang's rings is but a particular and striking case of a more general phenomenon, namely the influence on crystallization of the presence of foreign bodies or impurities, represented in this case by the gel or colloid matrix. Faraday shewed long ago that to the presence of slight impurities might be ascribed the banded structure of ice, of banded quartz or agate, onyx, etc., and Quink and Tomlinson have added to our scanty knowledge of the same phenomenon. Figure 205. Liesgang's rings. After Leduc. Besides the tendency to rhythmic action, as manifested in Liesgang's rings, the association of colloid matter with a crystalloid in solution may lead to other well-marked effects. These, according to Professor J. H. Bowman, may be grouped somewhat as follows: 1. Total prevention of crystallization, 2. Suppression of certain of the lines of crystalline growth. 3. Extension of the crystal to abnormal proportions, with a tendency for it to become a compound crystal. 4. A curving or gyrating of the crystal or its parts. Figure 206. Relay crystals. Of common salt. After Bowman. For instance, it would seem that, if the supply of material to the growing crystal be not forthcoming in sufficient quantity, as may well happen in a colloid medium, for lack of convection currents, then growth will follow only the strongest lines of crystallizing force, and will be suppressed or partially suppressed along other axes. The crystal will have a tendency to become filiform, or fibrous, and the rhaphides of our plant cells are a case in point. Again, the long slender crystal so formed, pushing its way into new material, may initiate a new center of crystallization. We get the phenomenon known as a relay, along the Figure 207. Wheel-like crystals in a colloid. After Bowman. Principal lines of force, and sometimes along subordinate axes as well. This phenomenon is illustrated in the accompanying figure of crystallization in a colloid medium of common salt. And it may possibly be that we have here an explanation, or part of an explanation, of the compound siliceous spicules of the hexactinellid sponges. Lastly, when the crystallizing force is nearly equaled by the resistance of the viscous medium, the crystal takes the line of least resistance, with very various results. One of these results would seem to be a gyratory course, giving to the crystal a curious wheel-like shape, as in Fig. And other results are the feathery, fern-like or arborescent shapes so frequently seen in microscopic crystallization. To return to Liesegan's rings, the typical appearance of concentric rings upon a gelatinous plate may be modified in various experimental ways. For instance, our gelatinous medium may be placed in a capillary tube immersed in a solution of the precipitating salt. And in this case we shall obtain a vertical succession of bands or zones regularly interspaced, the result being very closely comparable to the banded pigmentation which we see in the hair of a rabbit or a rat. In the ordinary plate preparation, the free surface of the gelatin is under different conditions to the lower layers and especially to the lowest layer in contact with the glass. And therefore it often happens that we obtain a double series of rings, one deep and the other superficial, which by occasional blending or interlacing, may produce a netted pattern. In some cases, as when only the inner surface of our capillary tube is covered with a layer of gelatin, there is a tendency for the deposit to take place in a continuous spiral line, rather than in concentric and separate zones. By such means, according to Custer, various forms of annular, spiral and reticulated thickenings in the vascular tissue of plants may be closely imitated. And he and certain other writers have of late been inclined to carry the same chemico-physical phenomenon a very long way, in the explanation of various banded, striped and other rhythmically successional types of structure or pigmentation. For example, the striped pigmentation of the leaves in many plants, such as Eulalia japonica, the striped or clouded coloring of many feathers or of a cat's skin, the patterns of many fishes. Such for instance as the brightly colored tropical chaetodonts and the like, are all regarded by him as so many instances of diffusion figures, closely related to the typical Liesegang phenomenon. Gebhardt has made a particular study of the same subject in the case of insects. He declares, for instance, that the banded wings of Papilio podalirius are precisely imitated in Liesgang's experiments. That the finer markings on the wings of the goat moth, Cossus ligniperta, shew the double arrangement of larger and of smaller intermediate rhythms, likewise manifested in certain cases of the same kind. That the alternate banding of the antennae, for instance in Caesia speciformis, a pigmentation not concurrent with the segmented structure of the antenna, is explicable in the same way. And that the ocelli, for instance of the emperor moth, are typical illustrations of the common concentric type. Darwin's well-known disquisition on the ocellar pattern of the feathers of the Argus pheasant, as a result of sexual selection, will occur to the reader's mind, in striking contrast to this or to any other direct physical explanation. To turn from the distribution of pigment to more deeply seated structural characters, Leduc has shown how, for instance, the laminar structure of the cornea or the lens is again, apparently, a similar phenomenon. In the lens of the fish's eye, we have a very curious appearance, the consecutive lamellae being roughened or notched by close-set, interlocking sinuosities. And precisely the same appearance, save that it is not quite so regular, is presented in one of Custer's figures as the effect of precipitating a little sodium phosphate in a gelatinous medium. Biderman has studied, from the same point of view, the structure and development of the molluscan shell, the problem which Rainey had first attacked more than 50 years before. And Liesgang himself has applied his results to the formation of pearls, and to the development of bone. Among all the many cases where this phenomenon of Liesgang's comes to the naturalist's aid in explanation of rhythmic or zonary configurations in organic forms, it has a special interest where the presence of concentric zones or rings appears. At first sight, as a sure and certain sign of periodicity of growth, depending on the seasons, and capable therefore of serving as a mark and record of the creature's age. This is the case, for instance, with the scales, bones and otoliths of fishes, and a kindred phenomena in starch grains has given rise, in like manner, to the belief that they indicate a diurnal and nocturnal periodicity of activity and rest. Fig. 208. That this is actually the case in growing starch grains is generally believed, on the authority of Meyer. But while under certain circumstances a marked alternation of growing and resting periods may occur, and may leave its impress on the structure of the grain, there is now great reason to believe that, apart from such external influences, the internal phenomena of diffusion may, just as in the typical Liesgang experiment, produce the well-known concentric rings. The sphericrystals of inulin, in like manner, shew, like the calcospherites of Harding, Fig, a concentric structure which in all likelihood has had no causative impulse save from within. Figure 209. Otoliths of place, showing 4 zones or age rings. After Wallace. The striation, or concentric lamellation, of the scales and otoliths of fishes has been much employed of recent years as a trustworthy and unmistakable mark of the fish's age. There are difficulties in the way of accepting this hypothesis, not the least of which is the fact that the otolith zones, for instance, are extremely well marked even in the case of some fishes which spend their lives in deep water, where the temperature and other physical conditions shew little or no appreciable fluctuation with the seasons of the year. There are, on the other hand, phenomena which seem strongly confirmatory of the hypothesis, for instance the fact, if it be fully established, that in such a fish as the cod, zones of growth, identical in number, are found both on the scales and in the otoliths. The subject has become a much debated one, and this is not the place for its discussion. But it is at least obvious, with the Liesgang phenomenon in view, that we have no right to assume that an appearance of rhythm and periodicity in structure and growth is necessarily bound up with, and indubitably brought about by, a periodic recurrence of particular external conditions. But while in the Liesgang phenomenon we have rhythmic precipitation which depends only on forces intrinsic to the system, and is independent of any corresponding rhythmic changes in temperature or other external conditions, we have not far to seek for instances of chemico-physical phenomena where rhythmic alternations of appearance or structure are produced in close relation to periodic fluctuations of temperature. A well-known instance is that of the Stassfurt deposits, where the rock salt alternates regularly with thin layers of anhydrite, or, in another series of beds, with polyhalite, and where these zones are commonly regarded as marking years, and their alternate bands as having been formed in connection with the seasons. A discussion, however, of this remarkable and significant phenomenon, and of how the chemist explains it, by help of the phase rule, in connection with temperature conditions, would lead us far beyond our scope. We now see that the methods by which we attempt to study the chemical or chemico-physical phenomena which accompany the development of an inorganic concretion or spicule within the body of an organism soon introduce us to a multitude of kindred phenomena, of which our knowledge is still scanty, and which we must not attempt to discuss at greater length. As regards our main point, namely the formation of spicules and other elementary skeletal forms, we have seen that certain of them may be safely ascribed to simple precipitation or crystallization of inorganic materials, in ways more or less modified by the presence of albuminous or other colloid substances. The effect of these latter is found to be much greater in the case of some crystallizable bodies than in others. For instance, Harding, and Rainey also, found as a rule that calcium oxalate was much less affected by a colloid medium than was calcium carbonate. It shewed in their hands no tendency to form rounded concretions or calcospherites in presence of a colloid, but continued to crystallize, either normally, or with a tendency to form needles or rhaphides. It is doubtless for this reason that, as we have seen, crystals of calcium oxalate are so common in the tissues of plants, while those of other calcium salts are rare. But true calcospherites or spherocrystals of the oxalate are occasionally found, for instance in certain cacti, and Büchli has succeeded in making them artificially in Harding's usual way. That is to say by crystallization in a colloid medium. Their link on to these latter observations, and to the statement already quoted that calcareous deposits are associated with the dead products rather than with the living cells of the organism. Certain very interesting facts in regard to the solubility of salts in colloid media, which have been made known to us of late, and which go far to account for the presence, apart from the form, of calcareous precipitates within the organism. It has been shown, in the first place, that the presence of albumin has a notable effect on the solubility in a watery solution of calcium salts, increasing the solubility of the phosphate in a marked degree, and that of the carbonate in still greater proportion. But the sulfate is only very little more soluble in presence of albumin than in pure water, and the rarity of its occurrence within the organism is so far accounted for. On the other hand, the bodies derived from the breaking down of the albumins, their catabolic products, such as the peptones, etc., dissolve the calcium salts to a much less degree than albumin itself. And in the case of the phosphate, its solubility in them is scarcely greater than in water. The probability is, therefore, that the actual precipitation of the calcium salts is not due to the direct action of carbonic acid, etc. on a more soluble salt, as was at one time believed, but to catabolic changes in the proteids of the organism, which tend to throw down the salts already formed, which had remained hitherto in albuminous solution. The very slight solubility of calcium phosphate under such circumstances accounts for its predominance in, for instance, mammalian bone, and wherever, in short, the supply of this salt has been available to the organism. To sum up, we see that, whether from food or from seawater, calcium sulfate will tend to pass but little into solution in the albuminoid substances of the body. Calcium carbonate will enter more freely, but a considerable part of it will tend to remain in solution, while calcium phosphate will pass into solution in considerable amount, but will be almost wholly precipitated again, as the albumin becomes broken down in the normal process of metabolism. We have still to wait for a similar and equally illuminating study of the solution and precipitation of silica, in presence of organic colloids. From the comparatively small group of inorganic formations which, arising within living organisms, owe their forms solely to precipitation or to crystallization, that is to say to chemical or other molecular forces, we shall presently pass to that other and larger group which appear to be conformed in direct relation to the forms and the arrangement of the cells or other protoplasmic elements. The two principles of conformation are both illustrated in the spicular skeletons of the sponges. Figure 2.10. Close-packed calcospherites, or so-called spicules, of Astrosclera. After Lister. In a considerable number, but withal a minority of cases, the form of the sponge spicule may be deemed sufficiently explained on the lines of Harding's and Rainey's experiments. That is to say as the direct result of chemical or physical phenomena associated with the deposition of lime or of silica in presence of colloids. This is the case, for instance, with various small spicules of a globular or spheroidal form, formed of amorphous silica, concentrically striated within, and often developing irregular knobs or tiny tubercles over their surfaces. In the aberrant sponge Astrosclera, we have, to begin with, rounded, striated discs or globules, which in like manner are nothing more or less than the calcospherites of Harding's experiments. And as these grow they become closely aggregated together, Fig, and assume an angular, polyhedral form, once more in complete accordance with the results of experiment. Again, in many monaxenid sponges, we have irregularly shaped, or branched spicules, roughened or tuberculated by secondary superficial deposits, and reminding one of the spicules of some Alcyon area. These also must be looked upon as the simple result of chemical deposition, the form of the deposit being somewhat modified in conformity with the surrounding tissues. Just as in the simple experiment the form of the concretionary precipitate is affected by the heterogeneity, visible or invisible, of the matrix. Lastly, the simple needles of amorphous silica, which constitute one of the commonest types of spicule, call for little in the way of explanation. They are accretions or deposits about a linear axis, or fine thread of organic material, just as the ordinary rounded chalcosphorite is deposited about some minute point or center of crystallization. And as ordinary crystallization is often started by a particle of atmospheric dust. In some cases they also, like the others, are apt to be roughened by more irregular secondary deposits, which probably, as in Harding's experiments, appear in this irregular form when the supply of material has become relatively scanty. Our few foregoing examples, diverse as they are in look and kind and ranging from the spicules of astrosclera or alcyonium to the otoliths of a fish, seem all to have their free origin in some larger or smaller fluid-containing space or cavity of the body, pretty much as Harding's calcospheres made their appearance in the albuminous content of a dish. But we now come at last to a much larger class of spicular and skeletal structures, for whose regular and often complex forms some other explanation than the intrinsic forces of crystallization or molecular adhesion is manifestly necessary. As we enter on this subject, which is certainly no small or easy one, it may conduce to simplicity, and to brevity, if we try to make a rough classification, by way of forecast, of the chief conditions which we are likely to meet with. Just as we look upon animals as constituted, some of a vast number of cells, and others of a single cell or of a very few, and just as the shape of the former has no longer a visible relation to the individual shapes of its constituent cells, while in the latter it is cell form which dominates or is actually equivalent to the form of the organism, so shall we find it to be, with more or less exact analogy, in the case of the skeleton. For example, our own skeleton consists of bones, in the formation of each of which a vast number of minute-living cellular elements are necessarily concerned. But the form and even the arrangement of these bone-forming cells or corpuscles are monotonously simple, and we cannot find in these a physical explanation of the outward and visible configuration of the bone. It is as part of a far larger field of force, in which we must consider gravity, the action of various muscles, the compressions, tensions and bending moments due to variously distributed loads. The whole interaction of a very complex mechanical system, that we must explain, if we are to explain at all, the configuration of a bone. In contrast to these massive skeletons, or constituents of a skeleton, we have other skeletal elements whose whole magnitude, or whose magnitude in some dimension or another, is commensurate with the magnitude of a single living cell. Or, as comes to very much the same thing, is comparable to the range of action of the molecular forces. Such is the case with the ordinary spicules of a sponge, with the delicate skeleton of a radiolarian, or with the denser and robuster shells of the foraminifera. The effect of scale, then, of which we had so much to say in our introductory chapter on magnitude, is bound to be apparent in the study of skeletal fabrics, and to lead to essential differences between the big and the little, the massive and the minute, in regard to their controlling forces and their resultant forms. And if all this be so, and if the range of action of the molecular forces be in truth the important and fundamental thing, then we may somewhat extend our statement of the case, and include in it not only association with the living cellular elements of the body, but also association with any bubbles, drops, vacuoles, or vesicles which may be comprised within the bounds of the organism, and which are, as their names and characters connote, of the order of magnitude of which we are speaking. Proceeding a little farther in our classification, we may conceive each little skeletal element to be associated, in one case, with a single cell or vesicle, and in another with a cluster or system of consociated cells. In either case there are various possibilities. For instance, the calcified or other skeletal material may tend to overspread the entire outer surface of the cell or cluster of cells. and so tend accordingly to assume some configuration comparable to that of a fluid drop or of an aggregation of drops. This, in brief, is the gist and essence of our story of the foraminiferal shell. Another common, but very different condition will arise if, in the case of the cell aggregates, the skeletal material tends to accumulate in the interstices between the cells, in the partition walls which separate them. Or in the still more restricted distribution indicated by the lines of junction between these partition walls. Conditions such as these will go a very long way to help us in our understanding of many sponge spicules and of an immense variety of radiolarian skeletons. And lastly, for the present, there is a possible and very interesting case of a skeletal element associated with the surface of a cell, not so as to cover it like a shell, but only so as to pursue a course of its own within it, and subject to the restraints imposed by such confinement to a curved and limited surface. With this curious condition we shall deal immediately. This preliminary and much simplified classification of skeletal forms, as is evident enough, does not pretend to completeness. It leaves out of account some kinds of conformation and configuration with which we shall attempt to deal, and others which we must perforce omit. But nevertheless it may help to clear or to mark our way towards the subjects which this chapter has to consider, and the conditions by which they are at least partially defined. Among the several possible, or conceivable, types of microscopic skeletons let us choose, to begin with, the case of a spicule, more or less simply linear as far as its intrinsic powers of growth are concerned, but which owes its now somewhat complicated form to a restraint imposed by the individual cell to which it is confined, and within whose bounds it is generated. The conception of a spicule developed under such conditions we owe to a distinguished physicist, the late Professor G. F. Fitzgerald. Many years ago, Solas pointed out that if a spicule begin to grow in some particular way, presumably under the control or constraint imposed by the organism, it continues to grow by further chemical deposition in the same form or direction even after it has got beyond the boundaries of the organism or its cells. This phenomenon is what we see in, and this imperfect explanation goes so far to account for, the continued growth in straight lines of the long calcareous spines of Globigerina or Hastigerina, or the similarly radiating but siliceous spicules of many radiolaria. In physical language, if our crystalline structure has once begun to be laid down in a definite orientation, further additions tend to accrue in a like regular fashion and in an identical direction. And this corresponds to the phenomenon of so-called oriented adsorption, as described by Lehmann. In Globigerina or in Acanthocystis the long needles grow out freely into the surrounding medium, with nothing to impede their rectilinear growth and their approximately radiate distribution. But let us consider some simple cases to illustrate the forms which a spicule will tend to assume when, striving, as it were, to grow straight, it comes under the influence of some simple and constant restraint or compulsion. If we take any 2 points on some curved surface, such as that of a sphere or an ellipsoid, and imagine a string stretched between them, we obtain what is known in mathematics as a geodetic curve. It is the shortest line which can be traced between the 2 points, upon the surface itself. And the most familiar of all cases, from which the name is derived, is that curve upon the Earth's surface which the navigator learns to follow in the practice of great circle sailing. Where the surface is spherical, the geodetic is always literally a great circle, a circle, that is to say, whose center is the center of the sphere. If instead of a sphere we be dealing with an ellipsoid, the geodetic becomes a variable figure, according to the position of our 2 points. For obviously, if they lie in a line perpendicular to the long axis of the ellipsoid, the geodetic which connects them is a circle, also perpendicular to that axis. And if they lie in a line parallel to the axis, their geodetic is a portion of that ellipse about which the whole figure is a solid of revolution. But if our 2 points lie, relatively to one another, in any other direction, then their geodetic is part of a spiral curve in space, winding over the surface of the ellipsoid. To say, as we have done, that the geodetic is the shortest line between 2 points upon the surface, is as much as to say that it is a projection of some particular straight line upon the surface in question. And it follows that, if any linear body be confined to that surface, while retaining a tendency to grow by successive increments always, save only for its confinement to that surface, in a straight line. The resultant form which it will assume will be that of a geodetic. In mathematical language, it is a property of a geodetic that the plane of any two consecutive elements is a plane perpendicular to that in which the geodetic lies. Or, in simpler words, any two consecutive elements lie in a straight line in the plane of the surface, and only diverge from a straight line in space by the actual curvature of the surface to which they are restrained. Let us now imagine a spicule, whose natural tendency is to grow into a straight linear element, either by reason of its own molecular anisotropy, or because it is deposited about a thread-like axis. And let us suppose that it is confined either within a cell wall or in adhesion thereto. It at once follows that its line of growth will be simply a geodetic to the surface of the cell. And if the cell be an imperfect sphere, or a more or less regular ellipsoid, the spicule will tend to grow into one or other of three forms, either a plane curve of circular arc, or, more commonly, a plane curve which is a portion of an ellipse. Or, most commonly of all, a curve which is a portion of a spiral in space. In the latter case, the number of turns of the spiral will depend, not only on the length of the spicule, but on the relative dimensions of the ellipsoidal cell, as well as upon the angle by which the spicule is inclined to the ellipsoid axis. But a very common case will probably be that in which the spicule looks at first sight to be a plain C-shaped figure, but is discovered, on more careful inspection, to lie not in one plane but in a more complicated spiral twist. Figure 211. Sponge and holothurian spicules. This investigation includes a series of forms which are abundantly represented among actual sponge spicules, as illustrated in Figure 212. Figs, and 212. If the spicule be not restricted to linear growth, but have a tendency to expand, or to branch out from a main axis, we shall obtain a series of more complex figures, all related to the geodetic system of curves. A very simple case will arise where the spicule occupies, in the first instance, the axis of the containing cell, and then, on reaching its boundary, tends to branch or spread outwards. We shall now get various figures, in some of which the spicule will appear as an axis expanding into a disc or will at either end, and in other cases, the terminal disc. Figure 213. An amphidisc of hyalonema will be replaced, or represented, by a series of rays or spokes, with a reflex curvature, corresponding to the spherical or ellipsoid curvature of the surface of the cell. Such spicules as these are again exceedingly common among various sponges, Fig. Furthermore, if these mechanical methods of conformation, and others like to these, be the true cause of the shapes which the spicules assume, it is plain that the production of these spicular shapes is not a specific function of sponges or of any particular sponge, but that we should expect the same or very similar phenomena to occur in other organisms. Wherever the conditions of inorganic secretion within closed cells was very much the same. As a matter of fact, in the group of Holothuroidea, where the formation of intracellular spicules is a characteristic feature of the group, all the principal types of conformation which we have just described can be closely paralleled. Indeed, in many cases, the forms of the holothurian spicules are identical and indistinguishable from those of the sponges. But the holothurian spicules are composed of calcium carbonate, while those which we have just described in the case of sponges are usually, if not always, silicious. This being just another proof of the fact that in such cases the form of the spicule is not due to its chemical nature or molecular structure, but to the external forces to which, during its growth, the spicule is submitted. So much for that comparatively limited class of sponge spicules whose forms seem capable of explanation on the hypothesis that they are developed within, or under the restraint imposed by, the surface of a cell or vesicle. Such spicules are usually of small size, as well as of comparatively simple form, and they are greatly outstripped in number, in size, and in supposed importance as guides to zoological classification, by another class of spicules. This new class includes such as we have supposed to be capable of explanation on the assumption that they develop in association, of some sort or another, with the lines of junction of contiguous cells. They include the triradiate spicules of the calcareous sponges, the quadriradiate or tetractinellid spicules which occur in the same group, but more characteristically in certain siliceous sponges known as the tetractinellidae. And lastly perhaps, though these last are admittedly somewhat harder to understand, the six-rayed spicules of the hexactinellids. The spicules of the calcareous sponges are commonly triradiate, and the three radii are usually inclined to one another at equal, or nearly equal angles. In certain cases, two of the three rays are nearly in a straight line, and at right angles to the third. They are seldom in a plane, but are usually inclined to one another in a solid, trihedral angle, not easy of precise measurement under the microscope. The three rays are very often supplemented by a fourth, which is set tetrahedrally, making, that is to say, coequal angles with the other three. The calcareous spicule consists mainly of carbonate of lime, in the form of calcite, with, according to von Ebner, some admixture of soda and magnesia, of sulfates and of water. According to the same writer, but the fact, though it would seem easy to test, is still disputed, there is no organic matter in the spicule, either in the form of an axial filament or otherwise, and the appearance of stratification, often simulating the presence of an axial fiber, is due to mixed crystallization of the various constituents. The spicule is a true crystal, and therefore its existence and its form are primarily due to the molecular forces of crystallization. Moreover, it is a single crystal and not a group of crystals, as is at once seen by its behavior in polarized light. But its axes are not crystalline axes, and its form neither agrees with, nor in any way resembles, any one of the many polymorphic forms in which calcite is capable of crystallizing. It is as though it were carved out of a solid crystal. It is, in fact, a crystal under restraint, a crystal growing, as it were, in an artificial mold, and this mold is constituted by the surrounding cells, or structural vesicles of the sponge. We have already studied in an elementary way, but amply for our present purpose, the manner in which three or more cells, or bubbles, tend to meet together under the influence of surface tension. And also the outwardly similar phenomena which may be brought about by a uniform distribution of mechanical pressure. We have seen that when we confine ourselves to a plane assemblage of such bodies, we find them meeting one another in threes. That in a section or plane projection of such an assemblage we see the partition walls meeting one another at equal angles of 120 degree, that when the bodies are uniform in size, the partitions are straight lines, which combine to form regular hexagons. And that when the bodies are unequal in size, the partitions are curved, and combine to form other and less regular polygons. It is plain, accordingly, that in any flattened or stratified assemblage of such cells, a solidified skeletal deposit which originates or accumulates either between the cells or within the thickness of their mutual partitions, will tend to take the form of triradiate bodies, whose rays, in a typical case, will be set at equal angles of 120 degrees, Fig. F. And this latter condition of equality will be open to modification in various ways. It will be Figure 2.14. Spicules of Grantia and other calcareous sponges. After Haeckel. Modified by any inequality in the specific tensions of adjacent cells. As a special case, it will be apt to be greatly modified at the surface of the system, where a spicule happens to be formed in a plane perpendicular to the cell layer, so that one of its three rays lies between two adjacent cells and the other two are associated with the surface of contact between the cells and the surrounding medium. In such a case, as in the cases considered in connection with the forms of the cells themselves on P, we shall tend to obtain a spicule with two equal angles and one unequal, Fig. A, C. In the last case, the two outer, or superficial rays, will tend to be markedly curved. Again, the equiangular condition will be departed from, and more or less curvature will be imparted to the rays, wherever the cells of the system cease to be uniform in size, and when the hexagonal symmetry of the system is lost accordingly. Lastly, although we speak of the rays as meeting at certain definite angles, this statement applies to their axes, rather than to the rays themselves. For, if the triradiate spicule be developed in the interspace between three juxtaposed cells, it is obvious that its sides will tend to be concave, for the interspace between our three contiguous equal circles is an equilateral curvilinear triangle. And even if our spicule be deposited, not in the space between our three cells, but in the thickness of the intervening wall, then we may recollect, from p. that the several partitions never actually meet at sharp angles, but the angle of contact is always bridged over by a small accumulation of material, varying in amount according to its fluidity, whose boundary takes the form of a circular arc, and which constitutes the bourrelet of Plateau. In any sample of the triradiate spicules of Grantia, or in any series of careful drawings, such as those of Haeckel among others, we shall find that all these various configurations are precisely and completely illustrated. The tetrahedral, or rather tetractinellid, spicule needs no explanation in detail, Fig. D, E. For just as a triradiate spicule corresponds to the case of three cells in mutual contact, so does the four-rayed spicule to that of a solid aggregate of four cells, these latter tending to meet one another in a tetrahedral system. Shewing four edges, at each of which four surfaces meet, the edges being inclined to one another at equal angles of about 109 degrees. And even in the case of a single layer, or superficial layer, of cells, if the skeleton originate in connection with all the edges of mutual contact, we shall, in complete and typical cases, have a four-rayed spicule, of which one straight limb will correspond to the line of junction between the three cells, and the other three limbs, which will then be curved limbs, will correspond to the edges where two cells meet one another on the surface of the system. But if such a physical explanation of the forms of our spicules is to be accepted, we must seek at once for some physical agency by which we may explain the presence of the solid material just at the junctions or interfaces of the cells, and for the forces by which it is confined to, and molded to the form of, these intercellular or interfacial contacts. It is to Dreyer that we chiefly owe the physical or mechanical theory of spicular conformation which I have just described, a theory which ultimately rests on the form assumed, under surface tension, by an aggregation of cells or vesicles. But this fundamental point being granted, we have still several possible alternatives by which to explain the details of the phenomenon. Dreyer, if I understand him aright, was content to assume that the solid material, secreted or excreted by the organism, accumulated in the interstices between the cells, and was there subjected to mechanical pressure or constraint as the cells got more and more crowded together by their own growth and that of the system generally. As far as the general form of the spicules goes, such explanation is not inadequate, though under it we may have to renounce some of our assumptions as to what takes place at the outer surface of the system. But in all, or most, cases where, but a few years ago, the concepts of secretion or excretion seemed precise enough, we are nowadays inclined to turn to the phenomenon of adsorption as a further stage towards the elucidation of our facts. Here we have a case in point. In the tissues of our sponge, wherever two cells meet, there we have a definite surface of contact, and there accordingly we have a manifestation of surface energy. And the concentration of surface energy will tend to be a maximum at the lines or edges whereby the three, or four, such surfaces are conjoined. Of the microchemistry of the sponge cells our ignorance is great. But, without venturing on any hypothesis involving the chemical details of the process, we may safely assert that there is an inherent probability that certain substances will tend to be concentrated and ultimately deposited just in these lines of intercellular contact and conjunction. In other words, adsorptive concentration, under osmotic pressure, at and in the surface film which constitutes the mutual boundary between contiguous cells, emerges as an alternative, and, as it seems to me, a highly preferable alternative, to Dreyer's conception of an accumulation under mechanical pressure in the vacant spaces left between one cell and another. But a purely chemical, or purely molecular adsorption, is not the only form of the hypothesis on which we may rely. For from the purely physical point of view, angles and edges of contact between adjacent cells will be loci in the field of distribution of surface energy. And any material particles whatsoever will tend to undergo a diminution of freedom on entering one of those boundary regions. In a very simple case, let us imagine a couple of soap bubbles in contact with one another. Over the surface of each bubble there glide in every direction, as usual, a multitude of tiny bubbles and droplets. But as soon as these find their way into the groove or re-entrant angle between the two bubbles, their freedom of movement is so far restrained, and out of that groove they have little or no tendency to emerge. A cognate phenomenon is to be witnessed in microscopic sections of steel or other metals. Here, amid the crystalline structure of the metal, wherein cooling its imperfectly homogeneous material has developed a cellular structure, shewing, in section, hexagonal or polygonal contours, we can easily observe. As Professor Petty has shown me, that the little particles of graphite and other foreign bodies common in the matrix have tended to aggregate themselves in the walls and at the angles of the polygonal cells, this being a direct result of the diminished freedom which the particles undergo on entering one of these boundary regions. It is by a combination of these two principles, chemical adsorption on the one hand, and physical quasi-adsorption or concentration of grosser particles on the other, that I conceive the substance of the sponge spicule to be concentrated and aggregated at the cell boundaries. And the forms of the triradiate and tetractinellate spicules are in precise conformity with this hypothesis. A few general matters, and a few particular cases, remain to be considered. It matters little or not at all, for the phenomenon in question, what is the histological nature or grade of the vesicular structures on which it depends. In some cases, apart from sponges, they may be no more than the little alveoli of the intracellular protoplasmic network, and this would seem to be the case at least in one known case, that of the protozoan Entosolenia aspera, in which, within the vesicular protoplasm of the single cell, Mobius has described tiny spicules in the shape of little tetrahedra with concave sides. It is probably also the case in the small beginnings of the echinoderm spicules, which are likewise intracellular, and are of similar shape. In the case of our sponges we have many varying conditions, which we need not attempt to examine in detail. In some cases there is evidence for believing that the spicule is formed at the boundaries of true cells or histological units. But in the case of the larger triradiate or tetractinellate spicules of the sponge body, they far surpass in size the actual cells. We find them lying, regularly and symmetrically arranged, between the porcanals, or ciliated chambers, and it is in conformity with the shape and arrangement of these rounded or spheroidal structures that their shape is assumed. Again, it is not necessarily at variance with our hypothesis to find that, in the adult sponge, the larger spicules may greatly outgrow the bounds not only of actual cells but also of the ciliated chambers, and may even appear to project freely from the surface of the sponge. For we have already seen that the spicule is capable of growing, without marked change of form, by further deposition, or crystallization, of layer upon layer of calcareous molecules, even in an artificial solution. And we are entitled to believe that the same process may be carried on in the tissues of the sponge, without greatly altering the symmetry of the spicule. Long after it has established its characteristic form of a system of slender trihedral or tetrahedral rays. Neither is it of great importance to our hypothesis whether the rayed spicule necessarily arises as a single structure, or does so from separate minute centers of aggregation. Minchin has shown that, in some cases at least, the latter is the case. The spicule begins, he tells us, as three tiny rods, separate from one another, each developed in the interspace between two sister cells, which are themselves the results of the division of one of a little trio of cells. And the little rods meet and fuse together while still very minute, when the whole spicule is only about 1/200 of a millimeter long. At this stage, it is interesting to learn that the spicule is non-crystalline. But the new accretions of calcareous matter are soon deposited in crystalline form. This observation threw considerable difficulties in the way of former mechanical theories of the conformation of the spicule, and was quite at variance with Dreyer's theory, according to which the spicule was bound to begin from a central nucleus coinciding with the meeting place of the three contiguous cells, or rather the interspace between them. But the difficulty is removed when we import the concept of adsorption, for by this agency it is natural enough, or conceivable enough, that the process of deposition should go on at separate parts of a common system of surfaces. And if the cells tend to meet one another by their interfaces before these interfaces extend to the angles and so complete the polygonal cell, it is again conceivable and natural that the spicule should first arise in the form of separate and detached limbs or rays. Figure 2.15. Spicules of tetractinellid. Sponges, after solas. A.e. anatrienes, d.f. protrienes. Among the tetractinellid sponges, whose spicules are composed of amorphous silica or opal, all or most of the above-described main types of spicule occur, and, as the name of the group implies, the four-rayed tetrahedral spicules are especially represented. A somewhat frequent type of spicule is one in which one of the four rays is greatly developed, and the other three constitute small prongs diverging at equal angles from the main or axial ray. In all probability, as Dreyer suggests, we have here had to do with a group of four vesicles, of which three were large and co-equal, while a fourth and very much smaller one lay above and between the other three. In certain cases where we have likewise one large and three much smaller rays, the latter are recurved, as in Fig. This type, save for the constancy of the number of rays, and the limitation of the terminal ones to 3, and save also for the more important difference that they occur only at one and not at both ends of the long axis, is similar to the type of spicule illustrated in Fig. Which we have explained as being probably developed within an oval cell, by whose walls its branches have been conformed to geodetic curves. But it is much more probable that we have here to do with a spicule developed in the midst of a group of three co-equal and more or less elongated or cylindrical cells or vesicles, the long axial ray corresponding to their common line of contact, and the three short rays having each lain in the surface furrow between two out of the three adjacent cells. Figure 2.16. Various holothurian spicules. After Thiel. Just as in the case of the little curved or shaped spicules, formed apparently within the bounds of a single cell, so also in the case of the larger tetractinellid and analogous types do we find among the holothuroidea the same configurations reproduced as we have dealt with in the sponges. The holothurian spicules are a little less neatly formed, a little rougher, than the sponge spicules, and certain forms occur among the former group which do not present themselves among the latter. But for the most part a community of type is obvious and striking, Fig. A curious and, physically speaking, strictly analogous formation to the tetrahedral spicules of the sponges is found in the spores of a certain little group of parasitic protozoa, the actinomyxidea. These spores are formed from clusters of 6 cells, of which 3 come to constitute the capsule of the spore. And this capsule, always triradiate in its symmetry, is in some species drawn out into long rays, of which one constitutes a straight central axis, while the others, coming off from it at equal angles, are recurved in wide circular arcs. The account given of the development of this structure by its discoverers is somewhat obscure to me, but I think that, on physical grounds, there can be no doubt whatever that the quadriradiate capsule has been somehow modeled upon a group of 3 surrounding cells, its axis lying between the 3, and its 3 radial arcs occupying the furrows between adjacent pairs. Figure 2.17. Spicules of hexactinellid sponges. After F. E. Scholze. The typically 6-rayed siliceous spicules of the hexactinellid sponges, while they are perhaps the most regular and beautifully formed spicules to be found within the entire group, have been found very difficult to explain. And Dreyer has confessed his complete inability to account for their conformation. But, though it is doubtless only throwing the difficulty a little further back, we may so far account for them by considering that the cells or vesicles by which they are conformed are not arranged in what is known as closest packing, but in linear series. So that in their arrangement, and by their mutual compression, we tend to get a pattern, not of hexagons, but of squares, or, looking to the solid, not of dodecahedra but of cubes or parallelepipeda. This indeed appears to be the case, not with the individual cells, in the histological sense, but with the larger units or vesicles which make up the body of the hexactinellid. And this being so, the spicules formed between the linear, or cubical series of vesicles, will have the same tendency towards a hexactinellid shape, corresponding to the angles and adjacent edges of a system of cubes. As in our former case, they had to a triradiate or a tetractinellid form, when developed in connection with the angles and edges of a system of hexagons, or a system of dodecahedra. Histologically, the case is illustrated by a well-known phenomenon in embryology. In the segmenting ovum, there is a tendency for the cells to be budded off in linear series. And so they often remain, in rows side by side, at least for a considerable time and during the course of several consecutive cell divisions. Such an arrangement constitutes what the embryologists call the radial type of segmentation. But in what is described as the spiral type of segmentation, it is stated that, as soon as the first horizontal furrow has divided the cells into an upper and a lower layer, those of the upper layer are shifted in respect to the lower layer, by means of a rotation about the vertical axis. It is, of course, evident that the whole process is merely that which is familiar to physicists as close packing. It is a very simple case of what Lord Kelvin used to call a problem in tactics. It is a mere question of the rigidity of the system, of the freedom of movement on the part of its constituent cells, whether or at what stage this tendency to slip into the closest propinquity, or position of minimum potential, will be found to manifest itself. However the hexactinellid spicules be arranged, and this is not at all easy to determine, in relation to the tissues and chambers of the sponge, it is at least clear that, whether they be separate or be fused together, as often happens, in a composite skeleton, they effect a symmetrical partitioning of space according to the cubical system. In contrast to that closer packing which is represented and effected by the tetrahedral system. This question of the origin and causation of the forms of sponge spicules, with which we have now briefly dealt, is all the more important and all the more interesting because it has been discussed time and again, from points of view which are characteristic of very different schools of thought in biology. Haeckel found in the form of the sponge spicule a typical illustration of his theory of biocrystallization. He considered that these biocrystals represented something midway, middling, between an inorganic crystal and an organic secretion. That there was a compromise between the crystallizing efforts of the calcium carbonate and the formative activity of the fused cells of the syncytium. And that the semicrystalline secretions of calcium carbonate were utilized by natural selection as spicules for building up a skeleton, and afterwards, by the interaction of adaptation and heredity, became modified in form and differentiated in a vast variety of ways in the struggle for existence. What Haeckel precisely signified by these words is not clear to me. F.E. Schulze, perceiving that identical forms of spicule were developed whether the material were crystalline or non-crystalline, abandoned all theories based upon crystallization. He simply saw in the form and arrangement of the spicule something which was best fitted for its purpose, that is to say for the support and strengthening of the porous walls of the sponge, and found clear evidence of utility in the specific structure of these skeletal elements. Solas and Dreyer, as we have seen, introduced in various ways the conception of physical causation, as indeed Haeckel himself had done in regard to one particular, when he supposed the position of the spicules to be due to the constant passage of the water currents. Though even here, by the way, if I understand Haeckel aright, he was thinking not merely of a direct or immediate physical causation, but of one manifesting itself through the agency of natural selection. Solas laid stress upon the path of least resistance as determining the direction of growth, while Dreyer dealt in greater detail with the various tensions and pressures to which the growing spicule was exposed, amid the alveolar or vesicular structure which was represented alike by the chambers of the sponge, by the reticulum of constituent cells, or by the minute structure of the intracellular protoplasm. But neither of these writers, so far as I can discover, was inclined to doubt for a moment the received canon of biology, which sees in such structures as these the characteristics of true organic species, and the indications of an hereditary affinity by which blood relationship and the succession of evolutionary descent throughout geologic time can be ultimately deduced. Lastly, Minchin, in a well-known paper, took sides with Schulze, and gave reasons for dissenting from such mechanical theories as those of Sollas and of Dreyer. For example, after pointing out that all protoplasm contains a number of granules, or microsomes, contained in the alveolar framework and lodged at the nodes of the reticulum, he argued that these also ought to acquire a form such as the spicules possess, if it were the case that these latter owed their form to their very similar or identical position. If vesicular tension cannot in any other instance cause the granules at the nodes to assume a tetraxin form, why should it do so for the sclerites? In all probability the answer to this question is not far to seek. If the force which the mechanical hypothesis has in view were simply that of mechanical pressure, as between solid bodies, then indeed we should expect that any substances whatsoever, lying between the impinging spheres, would tend, unless they were infinitely hard, to assume the quadriradiate or tetraxin form. But this conclusion does not follow at all, in so far as it is to surface energy that we ascribe the phenomenon. Here the specific nature of the substances involved makes all the difference. We cannot argue from one substance to another. Adsorptive attraction shews its effect on one and not on another. And we have not the least reason to be surprised if we find that the little granules of protoplasmic material, which as they lie bathed in the more fluid protoplasm have, presumably, and as their shape indicates, a strong surface tension of their own, behave towards the adjacent vesicles in a very different fashion to the incipient aggregations of calcareous or siliceous matter in a colloid medium. The ontogeny of the spicules, says Professor Minchin, points clearly to their regular form being a phylogenetic adaptation, which has become fixed and handed on by heredity, appearing in the ontogeny as a prophetic adaptation. And again, the forms of the spicules are the result of adaptation to the requirements of the sponge as a whole, produced by the action of natural selection upon variation in every direction. It would scarcely be possible to illustrate more briefly and more cogently than by these few words, or the similar words of Haeckel quoted on p. The fundamental difference between the Darwinian conception of the causation and determination of form, and that which is characteristic of the physical sciences. If I have dealt comparatively briefly with the inorganic skeleton of sponges, in spite of the obvious importance of this part of our subject from the physical or mechanical point of view, it has been owing to several reasons. In the first place, though the general trend of the phenomena is clear, it must be at once admitted that many points are obscure, and could only be discussed at the cost of a long argument. In the second place, the physical theory is, as I have shown, in manifest conflict with the accounts given by various embryologists of the development of the spicules, and of the current biological theories which their descriptions embody. It is beyond our scope to deal with such descriptions in detail. Lastly, we find ourselves able to illustrate the same physical principles with greater clearness and greater certitude in another group of animals, namely the radiolaria. In our description of the skeletons occurring within this group we shall by no means abandon the preliminary classification of microscopic skeletons which we have laid down. But we shall have occasion to blend with it the consideration of certain other more or less correlated phenomena. The group of microscopic organisms known as the radiolaria is extraordinarily rich in diverse forms, or species. I do not know how many of such species have been described and defined by naturalists, but some 30 years ago the number was said to be over 4,000, arranged in more than 700 genera. Of late years there has been a tendency to reduce the number, it being found that some of the earlier species and even genera are but growth stages of one and the same form, sometimes mere fragments or fission products common to several species. Or sometimes forms so similar and so interconnected by intermediate forms that the naturalist denominates them not species, but varieties. It has to be admitted, in short, that the conception of species among the radiolaria has not hitherto been, and is not yet, on the same footing as that among most other groups of animals. But apart from the extraordinary multiplicity of forms among the radiolaria, there are certain other features in this multiplicity which arrest our attention. For instance, the distribution of species in space is curious and vague. Many species are found all over the world, or at least every here and there, with no evidence of specific limitations of geographical habitat, others occur in the neighborhood of the two poles. Some are confined to warm and others to cold currents of the ocean. In time also their distribution is not less vague, so much so that it has been asserted of them that, from the Cambrian age downwards, the families and even genera appear identical with those now living. Lastly, except perhaps in the case of a few large, colonial forms, we seldom if ever find, as is usual in most animals, a local predominance of one particular species. On the contrary, in a little pinch of deep-sea mud or of some fossil, radiolarian earth, we shall probably find scores, and it may be even hundreds, of different forms. Moreover, the radiolarian skeletons are of quite extraordinary delicacy and complexity, in spite of their minuteness and the comparative simplicity of the unicellular organisms within which they grow. And these complex conformations have a wonderful and unusual appearance of geometric regularity. All these general considerations seem such as to prepare us for the special need of some physical hypothesis of causation. The little skeletal fabrics remind us of such objects as snow crystals, themselves almost endless in their diversity, rather than of a collection of distinct animals, constructed in apparent accordance with functional needs, and distributed in accordance with their fitness for particular situations. Nevertheless, great efforts have been made of recent years to attach a biological meaning to these elaborate structures, and to justify the hope that in time the utilitarian character of the skeleton will be more completely recognized. In the majority of cases, the skeleton of the radiolaria is composed, like that of so many sponges, of silica. In one large family, the Acantheria, and perhaps in some others, it is composed, in great part at least, of a very unusual constituent, namely strontium sulfate. There is no fundamental or important morphological character in which the shells formed of these two constituents differ from one another. And in no case can the chemical properties of these inorganic materials be said to influence the form of the complex skeleton or shell, save only in this general way that, by their rigidity and toughness, they may give rise to a fabric far more delicate and slender than we find developed among calcareous organisms. A slight exception to this rule is found in the presence of true crystals, which occur within the central capsules of certain radiolaria, for instance the genus Caulosphera. Johannes Müller, whose knowledge and insight never fail to astonish us, remarked that these were identical in form with crystals of celestine, a sulfate of strontium and barium. And Büchle's discovery of sulfates of strontium and of barium in kindred forms render it all but certain that they are actually true crystals of celestine. In its typical form, the radiolarian body consists of a spherical mass of protoplasm, around which, and separated from it by some sort of porous capsule, lies a frothy mass, composed of protoplasm honeycombed into a multitude of alveoli or vacuoles, filled with a fluid which can scarcely differ much from seawater. According to their surface tension conditions, these vacuoles may appear more or less isolated and spherical, or joining together in a froth of polygonal cells. And in the latter, which is the commoner condition, the cells tend to be of equal size, and the resulting polygonal meshwork beautifully regular. In many cases, a large number of such simple individual organisms are associated together, forming a floating colony, and it is highly probable that many other forms, with whose scattered skeletons we are alone acquainted, had in life formed part likewise of a colonial organism. In contradistinction to the sponges, in which the skeleton always begins as a loose mass of isolated spicules, which only in a few exceptional cases, such as Euplectella and Faria, fuse into a continuous network. The characteristic feature of the radiolarians lies in the possession of a continuous skeleton, in the form of a netted mesh or perforated lacework, sometimes however replaced by and often associated with minute-independent spicules. Before we proceed to treat of the more complex skeletons, we may begin, then, by dealing with these comparatively simple cases where either the entire skeleton or a considerable part of it is represented, not by a continuous fabric, but by a quantity of loose, separate spicules, or aciculae, which seem, like the spicules of Alcyonium, to be developed as free and isolated formations or deposits, precipitated in the colloid matrix, with no relation of form to the cellular or vesicular boundaries. These simple acicular spicules occupy a definite position in the organism. Sometimes, as for instance among the freshwater Heliozoa, e.g. Raphidiophrys, they lie on the outer surface of the organism, and not infrequently, when the spicules are few in number, they tend to collect round the bases of the pseudopodia, or around the large radiating spicules, or axial rays. In the cases where these latter are present, when the spicules are thus localized around some prominent center, they tend to take up a position of symmetry in regard to it. Instead of forming a tangled or felted layer, they come to lie side by side, in a radiating cluster round the focus. In other cases, as for instance in the well-known radiolarian Olacantha scalamantha, the felted layer of aciculae lies at some depth below the surface, forming a sphere concentric with the entire spherical organism. In either case, whether the layer of spicules be deep or be superficial, it tends to mark a surface of discontinuity, a meeting place between two distinct layers of protoplasm or between the protoplasm and the water around. And it is obvious that, in either case, there are manifestations of surface energy at the boundary, which cause the spicules to be retained there, and to take up their position in its plane. The case is somewhat, though not directly, analogous to that of a cirrus cloud, which marks the place of a surface of discontinuity in a stratified atmosphere. Figure 218. We have, then, to inquire what are the conditions which shall, apart from gravity, confine an extraneous body to a surface film, and we may do this very simply, by considering the surface energy of the entire system. In Fig. We have two fluids in contact with one another, let us call them water and protoplasm, and a body, B, which may be immersed in either, or may be restricted to the boundary between. We have here three possible interfacial contacts, each with its own specific surface energy, per unit of surface area, namely, that between our particle and the water, let us call it alpha, that between the particle and the protoplasm, beta. And that between water and protoplasm, gamma. When the body lies in the boundary of the two fluids, let us say half in one and half in the other, the surface energies concerned are equivalent to S2, alpha plus S2, beta. But we must also remember that, by the presence of the particle, a small portion, equal to its sectional area S, of the original contact surface between water and protoplasm has been obliterated, and with it a proportionate quantity of energy, equivalent to S gamma, has been set free. When, on the other hand, the body lies entirely within one or other fluid, the surface energies of the system, so far as we are concerned, are equivalent to S alpha plus S gamma, or S beta plus S gamma, as the case may be. According as alpha be less or greater than beta, the particle will have a tendency to remain immersed in the water or in the protoplasm. But if S2, alpha plus beta, S gamma be less than either S alpha or S beta, then the condition of minimal potential will be found when the particle lies, as we have said, in the boundary zone, half in one fluid and half in the other. And, if we were to attempt a more general solution of the problem, we should evidently have to deal with possible conditions of equilibrium under which the necessary balance of energies would be attained by the particle rising or sinking in the boundary zone, so as to adjust the relative magnitudes of the surface areas concerned. It is obvious that this principle may, in certain cases, help us to explain the position even of a radial spicule, which is just a case where the surface of the solid spicule is distributed between the fluids with a minimal disturbance, or minimal replacement, of the original surface of contact between the one fluid and the other. In like manner we may provide for the case, a common and an important one, where the protoplasm creeps up the spicule, covering it with a delicate film. In Acanthocystis we have yet another special case, where the radial spicules plunge only a certain distance into the protoplasm of the cell, being arrested at a boundary surface between an inner and an outer layer of cytoplasm. Here we have only to assume that there is a tension at this surface, between the two layers of protoplasm, sufficient to balance the tensions which act directly on the spicule. In various acanthometridae, besides such typical characters as the radial symmetry, the concentric layers of protoplasm, and the capillary surfaces in which the outer, vacuolated protoplasm is festooned upon the projecting radii, we have another curious feature. On the surface of the protoplasm where it creeps up the sides of the long radial spicules, we find a number of elongated bodies, forming in each case one or several little groups, and lying neatly arranged in parallel bundles. A Russian naturalist, Skyuikov, whose views have been accepted in the textbooks, tells us that these are muscular structures, serving to raise or lower the conical masses of protoplasm about the radial spicules, which latter serve as so many tent poles, or masts, on which the protoplasmic membranes are hoisted up. And the little elongated bodies are dignified with various names, such as myonemes, or myofrisks, in allusion to their supposed muscular nature. This explanation is by no means convincing. To begin with, we have precisely similar festoons of protoplasm in a multitude of other cases where the myonemes are lacking, from their minute size, 0.06012 mm. And the amount of contraction they are said to be capable of, the myonemes can hardly be very efficient instruments of traction. And further, for them to act, as is alleged, for a specific purpose, namely the hydrostatic regulation of the organism giving it power to sink or to swim, would seem to imply a mechanism of action and of coordination which is difficult to conceive in these minute and simple organisms. The fact is, as it seems to me, that the whole method of explanation is unnecessary. Just as the supposed hauling up of the protoplasmic festoons is at once explained by capillary phenomena, so also, in all probability, is the position and arrangement of the little elongated bodies. Whatever the actual nature of these bodies may be, whether they are truly portions of differentiated protoplasm, or whether they are foreign bodies or spicular structures, as bodies occupying a similar position in other cases undoubtedly are, we can explain their situation on the surface of the protoplasm, and their arrangement around the radial spicules, all on the principles of surface tension. This last case is not of the simplest, and I do not forget that my explanation of it, which is wholly theoretical, implies a doubt of Skyuikov's statements, which are founded on direct personal observation. This I am none too willing to do. But whether it be justly done in this case or not, I hold that it is in principle justifiable to look with great suspicion upon a number of kindred statements where it is obvious that the observer has left out of account the purely physical aspect of the phenomenon, and all the opportunities of simple explanation which the consideration of that aspect might afford. Whether it be wholly applicable to this particular and complex case or no, our general theorem of the localization and arrestment of solid particles in a surface film is of very great biological importance. For on it depends the power displayed by many little naked protoplasmic organisms of covering themselves with an agglutinated shell. Sometimes, as in Deflugia, Asteroiza, Fig. And others, this covering consists of sand grains picked up from the surrounding medium, and sometimes, on the other hand, as in Quadrilla, it consists of solid particles which are said to arise, as inorganic deposits or concretions, within the protoplasm itself, and which find their way outwards to a position of equilibrium in the surface layer. And in both cases, the mutual capillary attractions between the particles, confined to the boundary layer but enjoying a certain measure of freedom therein, tends to the orderly arrangement of the particles one with another, and even to the appearance of a regular pattern as the result of this arrangement. Figure 219. Arenaceous foraminifera. Asteroiza lamicola and arenaria. From Brady's Challenger monograph. The picking up by the protoplasmic organism of a solid particle with which to build its house, for it is hard to avoid this customary use of anthropomorphic figures of speech, misleading though they be, is a physical phenomenon kindred to that by which an amoeba swallows a particle of food. This latter process has been reproduced or imitated in various pretty experimental ways. For instance, Rumbler has shown that if a thread of glass be covered with shellac and brought near a drop of chloroform suspended in water, the drop takes in the spicule, robs it of its shellac covering, and then passes it out again. It is all a question of relative surface energies, leading to different degrees of adhesion between the chloroform and the glass or its covering. Thus it is that the amoeba takes in the diatom, dissolves off its proteid covering, and casts out the shell. Furthermore, as the whole phenomenon depends on a distribution of surface energy, the amount of which is specific to certain particular substances in contact with one another, we have no difficulty in understanding the selective action, which is very often a conspicuous feature in the phenomenon. Just as some caddis worms make their houses of twigs, and others of shells and again others of stones, so some rhizopods construct their agglutinated test out of stray sponge spicules, or frustules of diatoms, or again of tiny mud particles or of larger grains of sand. In all these cases, we have apparently to deal with differences in specific surface energies, and also doubtless with differences in the total available amount of surface energy in relation to gravity or other extraneous forces. In my early student days, Wentworth Thompson used to tell us that certain deep-sea difflugias, after constructing a shell out of particles of the black volcanic sand common in parts of the North Atlantic, finished it off with a clean white collar of little grains of quartz. Even this phenomenon may be accounted for on surface tension principles, if we assume that the surface energy ratios have tended to change either with the growth of the protoplasm or by reason of external variation of temperature or the like. And we are by no means obliged to attribute the phenomenon to a manifestation of volition, or taste, or aesthetic skill, on the part of the microscopic organism. Nor, when certain radiolaria tend more than others to attract into their own substance diatoms and such like foreign bodies, is it scientifically correct to speak, as some textbooks do, of species in which diatom selection has become a regular habit. To do so is an exaggerated misuse of anthropomorphic phraseology. The formation of an agglutinated shell is thus seen to be a purely physical phenomenon, and indeed a special case of a more general physical phenomenon which has many other important consequences in biology. For the shell to assume the solid and permanent character which it acquires, for instance, in difflugia, we have only to make the additional assumption that some small quantities of a cementing substance are secreted by the animal, and that this substance flows or creeps by capillary attraction between all the interstices of the little quartz grains, and ends by binding them all firmly together. Rumbler has shown us how these agglutinated tests, of spicules or of sand grains, can be precisely imitated, and how they are formed with greater or less ease, and greater or less rapidity, according to the nature of the materials employed. That is to say, according to the specific surface tensions which are involved. For instance, if we mix up a little powdered glass with chloroform, and set a drop of the mixture in water, the glass particles gather neatly round the surface of the drop so quickly that the eye cannot follow the operation. If we perform the same experiment with oil and fine sand, dropped into 70% alcohol, a still more beautiful artificial rhizopod shell is formed, but it takes some 3 hours to do. It is curious that, just at the very time when Rumbler was thus demonstrating the purely physical nature of the difflugian shell, Verworn was studying the same and kindred organisms from the older standpoint of an incipient psychology. But, as Rumbler himself admits, Verworn was very careful not to overestimate the apparent signs of volition, or selective choice, in the little organism's use of the material of its dwelling. This long parenthesis has led us away, for the time being, from the subject of the radiolarian skeleton, and to that subject we must now return. Leaving aside, then, the loose and scattered spicules, which we have sufficiently discussed, the more perfect radiolarian skeletons consist of a continuous and regular structure. And the siliceous, or other inorganic, material of which this framework is composed tends to be deposited in one or other of two ways or in both combined, 1, in the form of long spicular axes, usually conjoined at, or emanating from, the center of the protoplasmic body, and forming a symmetric radial system. 2, in the form of a crust, developed in various ways, either on the outer surface of the organism or in relation to the various internal surfaces which separate its concentric layers or its component vesicles. Not unfrequently, this superficial skeleton comes to constitute a spherical shell, or a system of concentric or otherwise associated spheres. We have already learned that a great part of the body of the radiolarian, and especially that outer portion to which Haeckel has given the name of the colima, is built up of a great mass of vesicles, forming a sort of stiff. Figure 220. Reticulum plasmatique. After Carnot. Froth, an equivalent in the physical sense, though not necessarily in the biological sense, to cells, inasmuch as the little vesicles have their own well-defined boundaries, and their own surface phenomena. In short, all that we have said of cell surfaces, and cell conformations, in our discussion of cells and of tissues, will apply in like manner, and under appropriate conditions, to these. In certain cases, even in so common and simple a one as the vacuolated substance of an actinosphaerium, we may see a very close resemblance, or formal analogy, to an ordinary cellular or parenchymatous tissue. In the close-packed arrangement and consequent configuration of these vesicles, and even at times in a slight membranous hardening of their walls. Leidy has figured some curious little bodies, like small masses of consolidated froth, which seem to be nothing else than the dead and empty husks, or filmy skeletons, of actinosphaerium. And Carnoy has demonstrated in certain cell nuclei an all but precisely similar framework, of extreme delicacy and minuteness, as the result of partial solidification of interstitial matter in a close-packed system of alveoli, Fig. Let us now suppose that, in our radiolarian, the outer surface of the animal is covered by a layer of froth-like vesicles, uniform or nearly so in size. We know that their tensions will tend to conform them into a honeycomb, or regular meshwork of hexagons, and that the free end of each hexagonal prism will be a little spherical cap. Suppose now that it be at the outer surface of the protoplasm, that namely which is in contact with the surrounding sea water, that the siliceous particles have a tendency to be secreted or adsorbed. It will at once follow that they will show a tendency to aggregate in the grooves which separate the vesicles, and the result will be the development of a most delicate sphere composed of tiny rods arranged in a regular hexagonal network, e.g. Aulonia. Such a conformation is extremely common, and among its many variants may be found cases in which, e.g. actinoma, the vesicles have. Figure 221. Aulonia hexagona, HKL. Figure 222. Actinoma archidophorum. HKL. Been less regular in size, and some in which the hexagonal meshwork has been developed not only on one outer surface, but at successive surfaces, producing a system of concentric spheres. If the siliceous material be not limited to the linear junctions of the cells, but spread over a portion of the outer spherical surfaces or caps, then we shall have the condition represented in Fig. Ethmosphaera, where the shell appears perforated by circular instead of hexagonal apertures, and the circular pores are set on slight spheroidal eminences. And, interconnected with such types as this, we have others in which the accumulating pellicles of skeletal matter have extended from the edges into the substance of the boundary walls. Figure 223. Ethmosphaera conosophonia, HKL. Figure 224. Portions of shells of two species of Cenosphaera, upper figure, C. favosa, lower, C. Vesperia, HKL. And have so produced a system of films, normal to the surface of the sphere, constituting a very perfect honeycomb, as in Cenosphaera favosa and Vesperia. In one or two very simple forms, such as the freshwater Clathrylina, just such a spherical perforated shell is produced out of some organic, acanthon-like substance. And in some examples of Clathrylina the chitinous lattice-work of the shell is just as regular and delicate, with the meshes just as beautifully hexagonal, as in the siliceous shells of the oceanic radiolaria. This is only another proof, if proof be needed, that the peculiar conformation of these little skeletons is not due to the material of which they are composed, but to the molding of that material upon an underlying vesicular structure. Figure 225. Alastrum triceros, HKL. Let us next suppose that, upon some such latticework as has just been described, another and external layer of cells or vesicles is developed, and that instead of, or perhaps only in addition to, a second hexagonal latticework, which might develop concentrically to the first in the boundary furrows of this new layer of cells, the siliceous matter now tends to be deposited radially, or normally to the surface of the sphere. Just in the lines where the external layer of vesicles meet one another, 3 by 3. The result will be that, when the vesicles themselves are removed, a series of radiating spicules will be revealed, directed outwards from each of the angles of the original hexagon, as is seen in Fig. And it may further happen that these radiating skeletal rods are continued at their distal ends into divergent rays, forming a triple fork. And corresponding, after a fashion which we have already described as occurring in certain sponge spicules, to the three superficial furrows between the adjacent cells. This last is, as it were, an intermediate stage between the simple rods and the complete formation of another concentric sphere of latticed hexagons. Another possible case is when the large and uniform vesicles of the outer protoplasm are mixed with, or replaced by, much smaller vesicles, piled on one another in more or less concentric layers, in this case the radiating. Figure 226. Figure 227. A nacellarian. Skeleton, Callimetra carolodi, HKL. Rods will no longer be straight, but will be bent into a zigzag pattern, with angles in three vertical planes, corresponding to the successive contacts of the groups of cells around the axis, Fig. Among a certain group called the nacellaria, we find geometrical forms of peculiar simplicity and beauty, such for instance as that which I have represented in Fig. It is obvious at a glance that this is such a skeleton as may have been formed, I think we may go so far as to say must have been formed, at the interfaces of a little tetrahedral group of cells. The four equal cells of the tetrahedron being in this particular case supplemented by a little one in the center of the system. We see, precisely as in the internal boundary system of an artificial group of four soap bubbles, the plane surfaces of contact, 6 in number. The relation to one another of each triple set of interfacial planes, meeting one another at equal angles of 120 degree. And finally the relation of the four lines or edges of triple contact, which tend, but for the little central vesicle, to meet at coequal solid angles in the center of the system, all as we have described on p. In short, each triple-walled reentrant angle of the little shell has essentially the configuration, or a part thereof, of what we have called a Maraldi pyramid, in our account of the architecture of the honeycomb, on p. There are still 2 or 3 remarkable or peculiar features in this all but mathematically perfect shell, and they are in part easy and in part they seem more difficult of interpretation. We notice that the amount of solid matter deposited in the plane interfacial boundaries is greatly increased at the outer margin of each boundary wall, where it merges or coincides with the superficial furrow which separates the free spherical surfaces of the bubbles from one another. And we may sometimes find that, along these edges, the skeleton remains complete and strong, while it shows signs of imperfect development or of breaking away over great part of the rest of the interfacial surfaces. In this there is nothing anomalous, for we have already recognized that it is at the edges or margins of the interfacial partition walls that the manifestation of surface energy will tend to reach its maximum. And just as we have seen that, in certain of our multicellular, spherical radiolarians, it is at the superficial edges or borders of. Figure 228. An isolated portion of the skeleton of Dictyocha. The partitions, and here only, that skeletal formation occurs, giving rise to the netted shell with its hexagonal meshes of Fig. So also at times, in the case of such little aggregates of cells or vesicles as the four-celled system of Callimetra, it may happen that about the external boundary lines, and not in the interior boundary planes, the whole of the skeletal matter is aggregated. In Fig, we see a curious little skeletal structure or complex spicule, whose conformation is easily accounted for after this. Figure 229. Dictyocha stapedia, HKL. Fashion. Little spicules such as this form isolated portions of the skeleton in the genus Dictyocha, and occur scattered over the spherical surface of the organism, Fig. The more or less basket-shaped spicule has evidently been developed about a little cluster of 4 cells or vesicles, lying in or on the plane of the surface of the organism, and therefore arranged, not in the tetrahedral form of Callimetra, but in the manner in which 4 contiguous cells lying side by side normally set themselves, like the 4 cells of a segmenting egg, that is to say with an intervening, polar furrow, whose ends mark the meeting place, at equal angles of the cells in groups of 3. The little projecting spokes, or spikes, which are set normally to the main basketwork, seem to be incomplete portions of a larger basket. Or in other words, imperfectly formed elements corresponding to the interfacial contacts in the surrounding parts of the system. Similar but more complex formations, all explicable as basket-like frameworks developed around a cluster of cells, are known in great variety. In our Nacellarian itself, and in many other cases where the plane interfacial boundary walls are skeletonized, we see that the siliceous matter is not deposited in an even and continuous layer, like the waxen walls of a bee's cell, but constitutes a meshwork of fine curvilinear threads. And the curves seem to run, on the whole, isogonally, and to form three main series, one approximately parallel to, or concentric with, the outer or free edge of the partition, and the other two related severally to its two edges of attachment. Sometimes, as may also be seen in our figure, the system is still further complicated by a fourth series of linear elements, which tend to run radially from the center of the system to the free edge of each partition. As regards the former, their arrangement is such as would result if deposition or solidification had proceeded in waves, starting independently from each of the three boundaries of the little partition wall. And something of this kind is doubtless what has happened. We are reminded at once of the wave-like periodicity of the Liesegang phenomenon. But apart from this we might conceive of other explanations. For instance, the liquid film which originally constitutes the partition must easily be thrown into vibrations. And, like the dust upon a Chladni's plate, minute particles of matter in contact with the film would tend to take up their position in a symmetrical arrangement, in direct relation to the nodal points or lines of the vibrating surface. Some such explanation as this, to my thinking, must be invoked to account for the minute and varied and very beautiful patterns upon many diatoms. The resemblance of which patterns, in certain of their simpler cases, to the Chladni figures is sometimes striking and obvious. But the many special problems which the diatom skeleton suggests I have not attempted to consider. Figure 230. The last peculiarity of our Nacellarian lies in an apparent departure from what we should at first expect in the way of its external symmetry. Were the system actually composed of four spherical vesicles in mutual contact, the outer margin of each of the six interfacial planes would obviously be a circular arc. And accordingly, at each angle of the tetrahedron, we should expect to have a depressed, or reentrant angle, instead of a prominent cusp. This is all doubtless due to some simple balance of tensions, whose precise nature and distribution is meanwhile a matter of conjecture. But it seems as though an extremely simple explanation would go a long way, and possibly the whole way, to meet this particular case. In our ordinary plane diagram of three cells, or soap bubbles, in contact, we know, and we have just said, that the tensions of the three partitions draw inwards the outer walls of the system. Till at each point of triple contact, P, we tend to get a triradiate, equiangular junction. But if we introduce another bubble into the center of the system, Fig. Then, as Plateau shewed, the tensions of its walls and those of the three partitions by which it is now suspended, again balance one another, and the central bubble appears, in plane projection, as a curvilinear, equilateral triangle. We have only got to convert this plane diagram into that of a tetrahedral solid to obtain almost precisely the configuration which we are seeking to explain. Now we observe that, so far as our figure of collimatura informs us, this is just the shape of the little bubble which occupies the center of the tetrahedral system in that radiolarian skeleton. And I conceive, accordingly, that the entire organism was not limited to the four cells or vesicles, together with the little central fifth, which we have hitherto been imagining, but there must have been an outer tetrahedral system, enclosing the cells which fabricated the skeleton, just as these latter enclosed, and deformed, the little bubble in the center of all. We have only to suppose that this hypothetical tetrahedral series, forming the outer layer or surface of the whole system, was for some chemico-physical reason incapable of secreting at its interfacial contacts a skeletal fabric. In this hypothetical case, the edges of the skeletal system would be circular arcs, meeting one another at an angle of 120 degrees, or, in the solid pyramid, of 109 degrees, and this latter is very nearly the condition which our little skeleton actually displays. But we observe in Fig that, in the immediate neighborhood of the tetrahedral angle, the circular arcs are slightly drawn out into projecting cusps, cf. Fig. b. There is no shaped curvature of the tetrahedral edges as a whole, but a very slight one, a very slight change of curvature, close to the apex. This, I conceive, is nothing more than what, in a material system, we are bound to have, to represent a surface of continuity. It is a phenomenon precisely analogous to Plateau's bourrelet, which we have already seen to be a constant feature of all cellular systems. Rounding off the sharp angular contacts by which, in our more elementary treatment, we expect one film to make its junction with another. In the foregoing examples of radiolaria, the symmetry which the organism displays would seem to be identical with that symmetry of forces which is due to the assemblage of surface tensions in the whole system. This symmetry being displayed, in one class of cases, in a complex spherical mass of froth, and in another class in a simpler aggregate of a few, otherwise isolated, vesicles. But among the vast number of other known radiolaria, there are certain forms, especially among the Phaedaria and Acantheria, which display a still more remarkable symmetry, the origin of which is by no means clear. Though surface tension doubtless plays a part in its causation. These are cases in which, as in some of those already described, the skeleton consists, 1. Of radiating spicular rods, definite in number and position, and, 2. Of interconnecting rods or plates. Tangential to the more or less spherical body of the organism, whose form becomes, accordingly, that of a geometric, polyhedral solid. It may be that there is no mathematical difference, save one of degree, between such a hexagonal polyhedron as we have seen in Alacantha, and those which we are about to describe. But the greater regularity, the numerical symmetry, and the apparent simplicity of these latter, makes of them a class apart, and suggests problems which have not been solved nor even investigated. The matter is sufficiently illustrated by the accompanying figures, all drawn from Haeckel's monograph of the Challenger radiolaria. In one of these we see a regular octahedron, in another a regular, or pentagonal dodecahedron, in a third a regular icosahedron. In all cases the figure appears to be perfectly symmetrical, though neither the triangular facets of the octahedron and icosahedron, nor the pentagonal facets of the dodecahedron, are necessarily plane surfaces. In all of these cases, the radial spicules correspond to the solid angles of the figure, and they are, accordingly, 6 in number in the octahedron, 20 in the dodecahedron, and 12 in the icosahedron. If we add to these three figures the regular tetrahedron, which we have had frequent occasion to study, and the cube, which is represented, at least in outline, in the skeleton of the hexactinellid sponges, we have completed the series of the 5 regular polyhedra known to geometers, the Platonic bodies of the older mathematicians. It is Figure 231. Skeletons of various radiolarians, after Haeckel. 1. Cercoporus. Sexfurcus, 2. C. Octahedrus, 3. Cercogonia. Icosahedra, 4. Cercospithus novena, 5. Cercoregma. Dodecahedra. At first sight all the more remarkable that we should here meet with the whole 5 regular polyhedra, when we remember that, among the vast variety of crystalline forms known among minerals, the regular dodecahedron and icosahedron, simple as they are from the mathematical point of view, never occur. Not only do these latter never occur in crystallography, but, as is explained in textbooks of that science, it has been shown that they cannot occur, owing to the fact that their indices, or numbers expressing the relation of the faces to the 3 primary axes, involve an irrational quantity, whereas it is a fundamental law of crystallography, involved in the whole theory of space partitioning, that the indices of any and every face of a crystal are small whole numbers. At the same time, an imperfect pentagonal dodecahedron, whose pentagonal sides are non-equilateral, is common among crystals. If we may safely judge from Haeckel's figures, the pentagonal dodecahedron of the radiolarian is perfectly regular, and we must presume, accordingly, that it is not brought about by principles of space partitioning similar to those which manifest themselves in the phenomenon of crystallization. It will be observed that in all these radiolarian polyhedral shells, the surface of each external facet is formed of a minute hexagonal network, whose probable origin, in relation to a vesicular structure, is such as we have already discussed. In certain allied radiolaria, Fig, which, like the dodecahedral form figured in Fig. 5, have 20 radial spines, these latter are commonly described as being arranged in a certain very singular way. It is stated that their arrangement may be referred to a series of 5 parallel circles on the sphere, corresponding to the equator, C, the tropics, B, D, and the polar circles, A, E. And that beginning with 4 equidistant spines in the equator, we have alternating whorls of 4, radiating outwards from the sphere in each of the other parallel zones. This rule was laid down by the celebrated Johannes Müller, and has ever since been used and quoted as Müller's law. The chief point in this alleged arrangement, which strikes us at first sight as very curious, is that there is said to be no spine at either pole, and when we come to examine carefully the figure of the organism, we find that the received. Figure 232. Doritaspis sp. Diagrammatic. Description does not do justice to the facts. We see, in the first place, from such figures as Figs. 234, that here, unlike our former cases, the radial spines issue through the facets, and through all the facets, of the polyhedron, instead of through its solid angles. And accordingly, that our 20 spines correspond, not, as before, to a dodecahedron, but to some sort of an icosahedron. We see in the next place, that this icosahedron is composed of faces, or plates, of 2 different kinds, some hexagonal and some pentagonal. And when we look closer, we discover that the whole figure is that of a hexagonal prism, whose 12 solid angles are replaced by pentagonal facets. Both hexagons and pentagons appear to be perfectly equilateral, but if we try to construct a plain-sided polyhedron of this kind, we soon find that it is impossible. For into the angles between the 6 equatorial hexagons those of the 6 united pentagons will not fit. The figure however can be easily constructed if we replace the straight edges, or some of them, by curves, and the plane facets by corresponding, slightly curved, surfaces. The true symmetry of this figure, then, is hexagonal, with a polar axis, produced into 2 polar spicules, with 6 equatorial spicules, or rays. And with 2 sets of 6 spicular rays, interposed between the polar axis and the equatorial rays, and alternating in position with the latter. Müller's description was amended by Brandt, and what is now known as Brandt's law, viz. that the symmetry consists of 2 polar rays, and 3 whorls of 6 each. Coincides with the above description so far as the spicular axes go, save only that Brandt specifically states that the intermediate whorls stand equidistant between the equator and the poles, i.e., in latitude 45 degrees. While not far from the truth, this statement is not exact, for according to the geometry of the figure, the intermediate cycles obviously stand in a slightly higher latitude, but this latitude I have not attempted to determine. For the calculation seems to be a little troublesome owing to the curvature of the sides of the figure, and the inquiring mathematician will perform it more easily than I. Brandt, if I understand him rightly, did not propose his law as a substitute for Müller's law, but as a second law applicable to a few particular cases. I on the other hand can find no case to which Müller's law properly applies. If we construct such a polyhedron, and set it in the position of Fig. B, we shall easily see that it is capable of explanation, though improperly, in accordance with Müller's law. For the 4 equatorial rays of Müller, C, now correspond to the 2 polar and to 2 opposite equatorial facets of our polyhedron, the 4 polar rays of Müller, or E, correspond to 2 adjacent hexagons and 2 intermediate pentagons of the figure, and Müller's tropical rays, B or D, are those which emanate from the remaining 4 pentagonal facets. In each half of the figure. In some cases, such as Haeckel's Phatnaspis cristata, Fig, we have an ellipsoidal body, from which the spines emerge in the order described, but which is not obviously divided by facets. In Fig. I have indicated the facets corresponding to the rays, and dividing the surface in the usual symmetrical way. Figure 233. Phatnaspis cristata, HKL. Figure 234. The same, diagrammatic. Within any polyhedron we may always inscribe another polyhedron, whose corners correspond in number to the sides or facets of the original figure, or, in alternative cases, to a certain number of these sides. And a similar result is obtained by beveling off the corners of the original polyhedron. We may obtain a precisely similar symmetrical result if, in such a case as these radiolarians which we are describing, we imagine the radial spines to be interconnected by tangential rods, instead of by the complete facets which we have just been dealing with. In our complicated polyhedron with its 20 radial spines arranged in the manner described, there are various symmetrical ways in which we may imagine these interconnecting bars to be arranged. The most symmetrical of these is one in which the whole surface is divided into 18 rhomboidal areas, obtained by systematically connecting each group of 4 adjacent radii. This figure has 18 faces, f, 20 corners, c, and therefore 36 edges, e, in conformity with Euler's theorem, f plus c equals e plus 2. Figure 235. Fractaspis prototopus, HKL. Another symmetrical arrangement will divide the surface into 14 rhombs and 8 triangles. This latter arrangement is obtained by linking up the radial rods as follows: AAAA, ABA, ABP, BCDC, etc. Here we have again 20 corners, but we have 22 faces. The number of edges, or tangential spicular bars, will be found, therefore, by the above formula, to be 40. In Haeckel's figure of Fractaspis prototopus we have a spicular skeleton which appears to be constructed precisely upon this plan, and to be derivable from the faceted polyhedron precisely after this manner. In all these latter cases it is the arrangement of the axial rods, or in other words the polar symmetry, of the entire organism, which lies at the root of the matter, and which, if only we could account for it, would make it comparatively easy to explain the superficial configuration. But there are no obvious mechanical forces by which we can so explain this peculiar polarity. This at least is evident, that it arises in the central mass of protoplasm, which is the essential living portion of the organism as distinguished from that frothy peripheral mass whose structure has helped us to explain so many phenomena of the superficial or external skeleton. To say that the arrangement depends upon a specific polarization of the cell is merely to refer the problem to other terms, and to set it aside for future solution. But it is possible that we may learn something about the lines in which to seek for such a solution by considering the case of Liemann's fluid crystals, and the light which they throw upon the phenomena of molecular aggregation. The phenomenon of fluid crystallization is found in a number of chemical bodies. It is exhibited at a specific temperature for each substance. And it would seem to be limited to bodies in which there is a more or less elongated, or chain-like, arrangement of the atoms in the molecule. Such bodies, at the appropriate temperature, tend to aggregate themselves into masses, which are sometimes spherical drops or globules, the so-called spherulites, and sometimes have the definite form of needle-like or prismatic crystals. In either case they remain liquid, and are also doubly refractive, polarizing light in brilliant colors. Together with them are formed ordinary solid crystals, also with characteristic polarization, and into such solid crystals all the fluid material ultimately turns. It is evident that in these liquid crystals, though the molecules are freely mobile, just as are those of water, they are yet subject to, or endowed with, directive force, a force which confers upon them a definite configuration or polarity. The Gestaltungskraft of Liemmann. Such an hypothesis as this had been gradually extruded from the theories of mathematical crystallography. And it had come to be believed that the symmetrical conformation of a homogeneous crystalline structure was sufficiently explained by the mere mechanical fitting together of appropriate structural units along the easiest and simplest lines of close packing, just as a pile of oranges becomes definite, both in outward form and inward structural arrangement, without the play of any specific directive force. But while our conceptions of the tactical arrangement of crystalline molecules remain the same as before, and our hypotheses of modes of packing, or of space lattices, remain as useful as ever for the definition and explanation of the molecular arrangements, An entirely new theoretical conception is introduced when we find such space lattices maintained in what has hitherto been considered the molecular freedom of a liquid field. And we are constrained, accordingly, to postulate a specific molecular force, or Gestaltungskraft, not unlike Kepler's facultas for matrix, to account for the phenomenon. Now just as some sort of specific Gestaltungskraft had been of old the deus ex machina accounting for all crystalline phenomena, narratocious geometriae, etiam ea exercita, as Kepler said, and as such an hypothesis, after being dethroned and repudiated, has now fought its way back and has made good its right to be heard, so it may be also in biology. We begin by an easy and general assumption of specific properties, by which each organism assumes its own specific form. We learn later, as it is the purpose of this book to shew, that throughout the whole range of organic morphology there are innumerable phenomena of form which are not peculiar to living things, but which are more or less simple manifestations of ordinary physical law. But every now and then we come to certain deep-seated signs of protoplasmic symmetry or polarization, which seem to lie beyond the reach of the ordinary physical forces. It by no means follows that the forces in question are not essentially physical forces, more obscure and less familiar to us than the rest. And this would seem to be the crucial lesson for us to draw from Liemann's surprising and most beautiful discovery. For Liemmann seems actually to have demonstrated, in non-living, chemical bodies, the existence of just such a determinant, just such a Gestaltungskraft, as would be of infinite help to us if we might postulate it for the explanation, for instance, of our Radiolarian's axial symmetry. But further than this we cannot go, for such analogy as we seem to see in the Liemmann phenomenon soon evades us, and refuses to be pressed home. Not only is it the case, as we have already seen, that certain of the geometric forms assumed by the symmetrical Radiolarian shells are just such as the space lattice theory would seem to be inapplicable to. But it is in other ways obvious that symmetry of crystallization, whether liquid or solid, has no close parallel, but only a series of analogies, in the protoplasmic symmetry of the living cell. Chapter 10, a parenthetic note on geodetics. We have made use in the last chapter of the mathematical principle of geodetics, or geodesics, in order to explain the conformation of a certain class of sponge spicules. But the principle is of much wider application in morphology, and would seem to deserve attention which it has not yet received. Figure 236. Annular and spiral thickenings in the walls of plant cells. Defining, meanwhile, our geodetic line, as we have already done, as the shortest distance between 2 points on the surface of a solid of revolution, we find that the geodetics of the cylinder give us one of the simplest of cases. Here it is plain that the geodetics are of 3 kinds: 1, a series of annuli around the cylinder, that is to say, a system of circles, in planes parallel to one another and at right angles to the axis of the cylinder, Fig. A. 2, a series of straight lines parallel to the axis, and 3, a series of spiral curves winding round the wall of the cylinder, B, C. These 3 systems are all of frequent occurrence, and are all illustrated in the local thickenings of the wall of the cylindrical cells or vessels of plants. The spiral, or rather helicoid, geodetic is particularly common in cylindrical structures, and is beautifully shown for instance in the spiral coil which stiffens the tracheal tubes of an insect, or the so-called tracheids of a woody stem. A similar phenomenon is often witnessed in the splitting of a glass tube. If a crack appear in a thin tube, such as a test tube, it has a tendency to be prolonged in its own direction. And the more perfectly homogeneous and isotropic be the glass, the more evenly will the split tend to follow the straight course in which it began. As a result, the crack in our test tube is often seen to continue till the tube is split into a continuous spiral ribbon. In a right cone, the spiral geodetic falls into closer and closer coils as the diameter of the cone narrows. And a very beautiful geodetic of this kind is exemplified in the sutural line of a spiral shell, such as turritella, or in the striations which run parallel with the spiral suture. Similarly, in an ellipsoidal surface, we have a spiral geodetic, whose coils get closer together as we approach the ends of the long axis of the ellipse. In the splitting of the integument of an equisetum spore, by which are formed the spiral elaters of the spore, we have a case of this kind, though the spiral is not sufficiently prolonged to shew all its features in detail. We have seen in these various cases, that our original definition of a geodetic requires to be modified. For it is only subject to conditions that it is the shortest distance between 2 points on the surface of the solid, and one of the commonest of these restricting conditions is that our geodetic may be constrained to go twice, or many times, round the surface on its way. In short, we must redefine our geodetic as a curve drawn upon a surface, such that, if we take any 2 adjacent points on the curve gives the shortest distance between them. Again, in the geodetic systems which we meet with in morphology, it sometimes happens that we have 2 opposite systems of geodetic spirals separate and distinct from one another, as in Fig. C. And it is also common to find the 2 systems interfering with one another, and forming a crisscross, or reticulated arrangement. This is a very common source of reticulated patterns. Among the ciliated infusoria, we have in the spiral lines along which their cilia are arranged a great variety of beautiful geodetic curves. Though it is probable enough that in some complicated cases these are not simple geodetics, but projections of curves other than a straight line upon the surface of the solid. Lastly, a very instructive case is furnished by the arrangement of the muscular fibers on the surface of a hollow organ, such as the heart or the stomach. Here we may consider the phenomenon from the point of view of mechanical efficiency, as well as from that of purely descriptive or objective anatomy. In fact, we have an a priori right to expect that the muscular fibers covering such hollow or tubular organs will coincide with geodetic lines, in the sense in which we are now using the term. For if we imagine a contractile fiber, or elastic band, to be fixed by its 2 ends upon a curved surface, it is obvious that its first effort of contraction will tend to expend itself in accommodating the band to the form of the surface, in stretching it tight, or in other words in causing it to assume a direction which is the shortest possible line upon the surface between the 2 extremes, and it is only then that further contraction will have the effect of constricting the tube and so exercising pressure on its contents. Thus the muscular fibers, as they wind over the curved surface of an organ, arrange themselves automatically in geodesic curves, in precisely the same manner as we also automatically construct complex systems of geodesics whenever we wind a ball of wool or a spindle of tow, or when the skillful surgeon bandages a limb. In these latter cases we see the production of those figures of 8, to which, in the case for instance of the heart muscles, Pettigrew and other anatomists have ascribed peculiar importance. In the case of both heart and stomach we must look upon these organs as developed from a simple cylindrical tube, after the fashion of the glassblower, as is further discussed on p. of this book, the modification of the simple cylinder consisting of various degrees of dilatation and of twisting. In the primitive undistorted cylinder, as in an artery or in the intestine, the muscular fibers run in geodetic lines, which as a rule are not spiral, but are merely either annular or longitudinal. These are the ordinary, circular and longitudinal coats, which form the normal musculature of all tubular organs, or of the body wall of a cylindrical worm. If we consider each muscular fiber as an elastic strand, embedded in the elastic membrane which constitutes the wall of the organ, it is evident that, whatever be the distortion suffered by the entire organ, the individual fiber will follow the same course, which will still, in a sense, be a geodetic. But if the distortion be considerable, as for instance if the tube become bent upon itself, or if at some point its walls bulge outwards in a diverticulum or pouch, it is obvious that the old system of geodetics will only mark the shortest distance between 2 points more or less approximate to one another, and that new systems of geodetics will tend to appear, peculiar to the new surface, and linking up points more remote from one another. This is evidently the case in the human stomach. We still have the systems, or their unobliterated remains, of circular and longitudinal muscles. But we also see 2 new systems of fibers, both obviously geodetic, or rather, when we look more closely, both parts of one and the same geodetic system, in the form of annuli encircling the pouch or diverticulum at the cardiac end of the stomach. and of oblique fibers taking a spiral course from the neighborhood of the esophagus over the sides of the organ. In the heart we have a similar, but more complicated phenomenon. Its musculature consists, in great part, of the original simple system of circular and longitudinal muscles which enveloped the original arterial tubes, which tubes, after a process of local thickening, expansion, and especially twisting, came together to constitute the composite, or double, mammalian heart. And these systems of muscular fibers, geodetic to begin with, remain geodetic, in the sense in which we are using the word, after all the twisting to which the primitive cylindrical tube or tubes have been subjected. That is to say, these fibers still run their shortest possible course, from start to finish, over the complicated curved surface of the organ. And it is only because they do so that their contraction, or longitudinal shortening, is able to produce its direct effect, as Borelli well understood, in the contraction or systole of the heart. As a parenthetic corollary to the case of the spiral pattern upon the wall of a cylindrical cell, we may consider for a moment the spiral line which many small organisms tend to follow in their path of locomotion. The helicoid spiral, traced around the wall of our cylinder, may be explained as a composition of two velocities, one a uniform velocity in the direction of the axis of the cylinder, the other a uniform velocity in a circle perpendicular to the axis. In a somewhat analogous fashion, the smaller ciliated organisms, such as the ciliate and flagellate infusoria, the rotifers, the swarm spores of various protists, and so forth, have a tendency to combine a direct with a revolving path in their ordinary locomotion. The means of locomotion which they possess in their cilia are at best somewhat primitive and inefficient, they have no apparent means of steering, or modifying their direction. And, if their course tended to swerve ever so little to one side, the result would be to bring them round and round again in an approximately circular path, such as a man astray on the prairie is said to follow, with little or no progress in a definite longitudinal direction. But as a matter of fact, either through the direct action of their cilia or by reason of a more or less unsymmetrical form of the body, all these creatures tend more or less to rotate about their long axis while they swim. And this axial rotation, just as in the case of a rifle bullet, causes their natural swerve, which is always in the same direction as regards their own bodies, to be in a continually changing direction as regards space, in short, to make a spiral course around, and more or less approximate to, a straight axial line. Chapter 11 The Logarithmic Spiral. The very numerous examples of spiral conformation which we meet with in our studies of organic form are peculiarly adapted to mathematical methods of investigation. But ere we begin to study them, we must take care to define our terms, and we had better also attempt some rough preliminary classification of the objects with which we shall have to deal. In general terms, a spiral curve is a line which, starting from a point of origin, continually diminishes in curvature as it recedes from that point, or, in other words, whose radius of curvature continually increases. This definition is wide enough to include a number of different curves, but on the other hand it excludes at least one which in popular speech we are apt to confuse with a true spiral. This latter curve is the simple screw, or cylindrical helix, which curve, as is very evident, neither starts from a definite origin, nor varies in its curvature as it proceeds. The spiral thickening of a woody plant cell, the spiral thread within an insect's tracheal tube, or the spiral twist and twine of a climbing stem are not, mathematically speaking, spirals at all, but screws or helices. They belong to a distinct, though by no means very remote, family of curves. Some of these helical forms we have just now treated of, briefly and parenthetically, under the subject of geodetics. Of true organic spirals we have no lack. We think at once of the beautiful spiral curves of the horns of ruminants, and of the still more varied, if not more beautiful, spirals of molluscan shells. Closely related spirals may be traced in the arrangement of the florets in the sunflower. A true spiral, though not, by the way, so easy of investigation, is presented to us by the outline of a cordate leaf. And yet again, we can recognize typical though transitory spirals in the coil of an elephant's trunk, in the circling spires of a snake, in the coils of a cuttlefish's arm, or of a monkey's or a chameleon's tail. Figure 237. The shell of Nautilus. Pompilius, from a radiograph, to shew the logarithmic spiral of the shell, together with the arrangement of the internal septa. From Messrs. Green and Gardiner, in Proc. Malacol. SOC 2. 1897. Among such forms as these, and the many others which we might easily add to them, it is obvious that we have to do with things which, though mathematically similar, are biologically speaking fundamentally different. And not only are they biologically remote, but they are also physically different, in regard to the nature of the forces to which they are severally due. For in the first place, the spiral coil of the elephant's trunk or of the chameleon's tail is, as we have said, but a transitory configuration, and is plainly the result of certain muscular forces acting upon a structure of a definite, and normally an essentially different, form. It is rather a position, or an attitude, than a form, in the sense in which we have been using this latter term, and, unlike most of the forms which we have been studying, it has little or no direct relation to the phenomenon of growth. Figure 238. A foraminiferal shell, Globigerina. Again, there is a manifest and not unimportant difference between such a spiral conformation as is built up by the separate and successive florets in the sunflower, and that which, in the snail or nautilus shell, is apparently a single and indivisible unit. And a similar, if not identical difference is apparent between the nautilus shell and the minute shells of the foraminifera, which so closely simulate it. Inasmuch as the spiral shells of these latter are essentially composite structures, combined out of successive and separate chambers, while the molluscan shell, though it may, as in Nautilus, become secondarily subdivided, has grown as one continuous tube. It follows from all this that there cannot possibly be a physical or dynamical, though there may well be a mathematical law of growth, which is common to, and which defines, the spiral form in the Nautilus, in the Globigerina, in the ram's horn, and in the disc of the sunflower. Of the spiral forms which we have now mentioned, every one, with the single exception of the outline of the cordate leaf, is an example of the remarkable curve known as the logarithmic spiral. But before we enter upon the mathematics of the logarithmic spiral, let us carefully observe that the whole of the organic forms in which it is clearly and permanently exhibited, however different they may be from one another in outward appearance, in nature and in origin, nevertheless all belong, in a certain sense, to one particular class of conformations. In the great majority of cases, when we consider an organism in part or whole, when we look, for instance, at our own hand or foot, or contemplate an insect or a worm, we have no reason, or very little, to consider one part of the existing structure as older than another. Through and through, the newer particles have been merged and commingled, by intussusception, among the old. The whole outline, such as it is due to forces which for the most part are still at work to shape it, and which in shaping it have shaped it as a whole. But the horn, or the snail shell, is curiously different. For in each of these, the presently existing structure is, so to speak, partly old and partly new, it has been conformed by successive and continuous increments. And each successive stage of growth, starting from the origin, remains as an integral and unchanging portion of the still growing structure, and so continues to represent what at some earlier epoch constituted for the time being the structure in its entirety. In a slightly different, but closely cognate way, the same is true of the spirally arranged florets of the sunflower. For here again we are regarding serially arranged portions of a composite structure, which portions, similar to one another in form, differ in age, and they differ also in magnitude in a strict ratio according to their age. Somehow or other, in the logarithmic spiral the time element always enters in, and to this important fact, full of curious biological as well as mathematical significance, we shall afterwards return. It is, as we have so often seen, an essential part of our whole problem, to try to understand what distribution of forces is capable of producing this or that organic form, to give, in short, a dynamical expression to our descriptive morphology. Now the general distribution of forces which lead to the formation of a spiral, whether logarithmic or other, is very easily understood, and need not carry us beyond the use of very elementary mathematics. Figure 239. If we imagine growth to act in a perpendicular direction, as for example the upward force of growth in a growing stem, OA, then, in the absence of other forces, elongation will as a matter of course proceed in an unchanging direction. That is to say, the stem will grow straight upwards. Suppose now that there be some constant external force, such as the wind, impinging on the growing stem, and suppose, for simplicity's sake, that this external force be in a constant direction, AB, perpendicular to the intrinsic force of growth. The direction of actual growth will be in the line of the resultant of the two forces, and, since the external force is, by hypothesis, constant in direction, while the internal force tends always to act in the line of actual growth, it is obvious that our growing organism will tend to be bent into a curve, to which, for the time being, the actual force of growth will be acting at a tangent. So long as the two forces continue to act, the curve will approach, but will never attain, the direction of AB, perpendicular to the original direction OA. If the external force be constant in amount, the curve will approximate to the form of a hyperbola, and, at any rate, it is obvious that it will never tend to assume a spiral form. In like manner, if we consider a horizontal beam, fixed at one end, the imposition of a weight at the other will bend the beam into a curve, which, as the beam elongates or the weight increases, will bring the weighted end nearer and nearer to the vertical. But such a force, constant in direction, will obviously never curve the beam into a spiral, a fact so patent and obvious that it would be superfluous to state it. Were it not that some naturalists have been in the habit of invoking gravity as the force to which may be attributed the spiral flexure of the shell. But if, on the other hand, the deflecting force be inherent in the growing body, or so connected with it in a system that its direction, instead of being constant, as in the former case, changes with the direction of growth, and is perpendicular, or inclined at some constant angle, to this changing direction of the growing force, then it is plain that there is no such limit to the deflection from the normal. But the growing curve will tend to wind round and round its point of origin. In the typical case of the snail shell, such an intrinsic force is manifestly present in the action of the columellar muscle. Many other simple illustrations can be given of a spiral course being impressed upon what is primarily rectilinear motion, by any steady deflecting force which the moving body carries, so to speak, along with it, and which continually gives a lopsided tendency to its forward movement. For instance, we have been told that a man or a horse, traveling over a great prairie, is very apt to find himself, after a long day's journey, back again near to his starting point. Here some small and imperceptible bias, such as might for instance be caused by one leg being in a minute degree longer or stronger than the other, has steadily deflected the forward movement to one side, and has gradually brought the traveler back, perhaps in a circle to the very point from which he set out, or else by a spiral curve, somewhere within reach and recognition of it. We come to a similar result when we consider, for instance, a cylindrical body in which forces of growth are at work tending to its elongation, but these forces are unsymmetrically distributed. Let the tendency to elongation along AB be of a magnitude proportional to BB, and that along CD be of a magnitude proportional to DD. And in each element parallel to AB and CD, let a parallel force of growth, proportionately intermediate in magnitude, be at work, and let EFF be the middle line. Then at any cross-section BFD, if we deduct the mean force FF, we have a certain positive force at B, equal to BB, and an equal and opposite force at D, equal to DD. But AB and CD are not separate. Figure 240. Structures, but are connected together either by a solid core, or by the walls of a tubular shell, and the forces which tend to separate B and D are opposed, accordingly, by a tension in BD. It follows therefore, that there will be a resultant force BG, acting in a direction intermediate between BB and BD, and also a resultant, DH, acting at D in an opposite direction. And accordingly, after a small increment of growth, the growing end of the cylinder will come to lie, not in the direction BD, but in the direction GH. The problem is therefore analogous to that of a beam to which we apply a bending moment. And it is plain that the unequal force of growth is equivalent to a couple, which will impart to our structure a curved form. For, if we regard the part ABDC as practically rigid, and the part BBDD as pliable, this couple will tend to turn strips such as BD about an axis perpendicular to the plane of the diagram, and passing through an intermediate point F. It is plain, also, since all the forces under consideration are intrinsic to the system, that this tendency will be continuous, and that as growth proceeds the curving body will assume either a circular or a spiral form. But the tension which we have here assumed to exist in the direction BD will obviously disappear if we suppose a sufficiently rapid rate of growth in that direction. For if we may regard the mouth of our tubular shell as perfectly extensible in its own plane, so that it exerts no traction whatsoever on the sides, then it will be drawn out into more and more elongated ellipses, forming the more and more oblique orifices of a straight tube. In other words, in such a structure as we have presupposed, the existence or Figure 241. Maintenance of a constant ratio between the rates of extension or growth in the vertical and transverse directions will lead, in general, to the development of a logarithmic spiral. The magnitude of that ratio will determine the character, that is to say, the constant angle, of the spiral, and the spiral so produced will include, as special or limiting cases, the circle and the straight line. We may dispense with the hypothesis of bending moments, if we simply presuppose that the increments of growth take place at a constant angle to the growing surface, as AB, but more rapidly at A, which we shall call the outer edge, than at B. And that this difference of velocity maintains a constant ratio. Let us also assume that the whole structure is rigid, the new accretions solidifying as soon as they are laid on. For example, let Fig. represent in section the early growth of a nautilus shell, and let the part ARB represent the earliest stage of all, which in nautilus is nearly semicircular. We have to find a law governing the growth of the shell, such that each edge shall develop into an equiangular spiral. And this law, accordingly, must be the same for each edge, namely that at each instant the direction of growth makes a constant angle with a line drawn from a fixed point, called the pole of the spiral, to the point at which growth is taking place. This growth, we now find, may be considered as effected by the continuous addition of similar quadrilaterals. Thus, in Fig. AEDB is a quadrilateral with AEDB parallel, and with the angle EAB of a certain definite. Figure 242. Magnitude, equals gamma. Let AB and ED meet, when produced, in C, and call the angle ACE, or XI, equals beta, make the angle YCZ equals angle XI, equals beta, draw EG, so that the angle YEG equals gamma, meeting CZ in G, and draw DF parallel to EG. It is then easy to show that AEDB and EGFD are similar quadrilaterals. And, when we consider the quadrilateral AEDB as having infinitesimal sides, AE and BD, the angle gamma tends to alpha, the constant angle of an equiangular spiral which passes through the points AEG. And of a similar spiral which passes through the points BDF. And the point C is the pole of both of these spirals. In a particular limiting case, when our quadrilaterals are all equal as well as similar, which will be the case when the angle gamma, or the angles EAC, etc., is a right angle, the spiral curve will be a circular arc, C being the center of the circle. Another, and a very simple illustration may be drawn from the cymose inflorescences of the botanists, though the actual mode of development of some of these structures is open to dispute. And their nomenclature is involved in extraordinary historical confusion. Figure 243. A helicoid, B, a scorpioid. Cyme. In Fig. B, which represents the Cicinus of Schimper, or cyme unipair scorpioid of Bravais, as seen in the borage, we begin with a primary shoot from which is given off, at a certain definite angle, a secondary shoot, and from that in turn, on the same side and at the same angle, another shoot, and so on. The deflection, or curvature, is continuous and progressive, for it is caused by no external force but only by causes intrinsic in the system. And the whole system is symmetrical, the angles at which the successive shoots are given off being all equal, and the lengths of the shoots diminishing in constant ratio. The result is that the successive shoots, or successive increments of growth, are tangents to a curve, and this curve is a true logarithmic spiral. But while, in this simple case, the successive shoots are depicted as lying in a plane, it may also happen that, in addition to their successive angular divergence from one another within that plane, they also tend to diverge by successive equal angles from that plane of reference. And by this means, there will be superposed upon the logarithmic spiral a helicoid twist or screw. And, in the particular case where this latter angle of divergence is just equal to 180 degrees, or 2 right angles, the successive shoots will once more come to lie in a plane, but they will appear to come off from one another on alternate sides. As in Fig. A, this is the Schraubel or Bostrix of Schimper, the sine unipair helicoid of Bravais. The logarithmic spiral is still latent in it, as in the other, but is concealed from view by the deformation resulting from the helicoid. The confusion of nomenclature would seem to have arisen from the fact that many botanists did not recognize, as the brothers Bravais did, the mathematical significance of the latter case, but were led, by the snail-like spiral of the Scorpioid cyme, to transfer the name helicoid to it. In the study of such curves as these, then, we speak of the point of origin as the pole, O. A straight line having its extremity in the pole and revolving about it, is called the radius vector. And a point, P, which is conceived as traveling along the radius vector under definite conditions of velocity, will then describe our spiral curve. Of several mathematical curves whose form and development may be so conceived, the two most important, and the only two with which we need deal, are those which are known as, 1, the equable spiral, or spiral of Archimedes, and 2, the logarithmic, or equiangular spiral. Figure 244. The former may be illustrated by the spiral coil in which a sailor coils a rope upon the deck. As the rope is of uniform thickness, so in the whole spiral coil is each whirl of the same breadth as that which precedes and as that which follows it. Using its ancient definition, we may define it by saying, that, if a straight line revolve uniformly about its extremity, a point which likewise travels uniformly along it will describe the equable spiral. Or, putting the same thing into our more modern words, if, while the radius vector revolve uniformly about the pole, a point, P, travel with uniform velocity along it, the curve described will be that called the equable spiral, or spiral of Archimedes. It is plain that the spiral of Archimedes may be compared to a cylinder coiled up. And it is plain also that a radius, r equals OP, made up of the successive and equal whirls, will increase in arithmetical progression, and will equal a certain constant quantity, A, multiplied by the whole number of whirls. Or, more strictly speaking, multiplied by the whole angle, theta, through which it has revolved, so that r equals A theta. But, in contrast to this, in the logarithmic spiral of the nautilus or the snail shell, the whirls gradually increase in breadth, and do so in a steady and unchanging ratio. Our definition is as follows: if, instead of traveling with a uniform velocity, our point move along the radius vector with a velocity increasing as its distance from the pole, then the path described is called a logarithmic spiral. Each whirl which the radius vector intersects will be broader than its predecessor in a definite ratio. The radius vector will increase in length in geometrical progression, as it sweeps through successive equal angles. And the equation to the spiral will be r equals a theta. As the spiral of Archimedes, in our example of the coiled rope, might be looked upon as a coiled cylinder, so may the logarithmic spiral, in the case of the shell, be pictured as a cone coiled upon itself. Now it is obvious that if the whirls increase very slowly indeed, the logarithmic spiral will come to look like a spiral of Archimedes, with which however it never becomes identical. For it is incorrect to say, as is sometimes done, that the Archimedean spiral is a limiting case of the logarithmic spiral. The nummulite is a case in point. Here we have a large number of whirls, very narrow, very close together, and apparently of equal breadth, which give rise to an appearance similar to that of our coiled rope. And, in a case of this kind, we might actually find that the whirls were of equal breadth, being produced, as is apparently the case in the nummulite, not by any very slow and gradual growth in thickness of a continuous tube, but by a succession of similar cells or chambers laid on, round and round, determined as to their size by constant surface tension conditions and therefore of unvarying dimensions. But even in this case we should have no Archimedean spiral, but only a logarithmic spiral in which the constant angle approximated to 90 degrees. For, in the logarithmic spiral, when alpha tends to 90 degrees, the expression r equals a theta cot alpha tends to r equals a, 1 plus theta cot alpha, while the equation to the Archimedean spiral is r equals b theta. The nummulite must always have a central core, or initial cell, around which the coil is not only wrapped, but out of which it springs, and this initial chamber corresponds to r in the expression r equals a plus a theta cot alpha. The outer whorls resemble those of an Archimedean spiral, because of the other term a theta cot alpha in the same expression. It follows from this that in all such cases the whorls must be of excessively small breadth. There are many other specific properties of the logarithmic spiral, so interrelated to one another that we may choose pretty well any one of them as the basis of our definition, and deduce the others from it either by analytical methods or by the methods of elementary geometry. For instance, the equation r equals a theta may be written in the form log r equals theta log a, or theta equals log r log a, or, since a is a constant, theta equals k log r. Which is as much as to say that the vector angles about the pole are proportional to the logarithms of the successive radii, from which circumstance the name of the logarithmic spiral is derived. Figure 245. Let us next regard our logarithmic spiral from the dynamical point of view, as when we consider the forces concerned in the growth of a material, concrete spiral. In a growing structure, let the forces of growth exerted at any point P be a force F acting along the line joining P to a pole O and a force T acting in a direction perpendicular to OP. And let the magnitude of these forces be in the same constant ratio at all points. It follows that the resultant of the forces F and T, as PQ, makes a constant angle with the radius vector. But the constancy of the angle between tangent and radius vector at any point is a fundamental property of the logarithmic spiral, and may be shown to follow from our definition of the curve. It gives to the curve its alternative name of equiangular spiral. Hence in a structure growing under the above conditions the form of the boundary will be a logarithmic spiral. Figure 246. In such a spiral, radial growth and growth in the direction of the curve bear a constant ratio to one another. For, if we consider a consecutive radius vector, OP, whose increment as compared with OP is dr, while ds is the small arc pp, then dr ds equals cos alpha equals constant. In the concrete case of the shell, the distribution of forces will be, originally, a little more complicated than this, though by resolving the forces in question, the system may be reduced to this simple form. And furthermore, the actual distribution of forces will not always be identical. For example, there is a distinct difference between the cases, as in the snail, where a columellar muscle exerts a definite traction in the direction of the pole, and those, such as Nautilus, where there is no columellar muscle, and where some other force must be discovered, or postulated, to account for the flexure. In the most frequent case, we have, as in Fig. 3 forces to deal with, acting at a point, P, L, acting. Figure 247. In the direction of the tangent to the curve, and representing the force of longitudinal growth. T, perpendicular to L, and representing the organism's tendency to grow in breadth, and P, the traction exercised, in the direction of the pole, by the columellar muscle. Let us resolve L and T into components along P, namely A, B, and perpendicular to P, namely A, B. We have now only two forces to consider, viz. PAB, and AB. And these two latter we can again resolve, if we please, so as to deal only with forces in the direction of P and T. Now, the ratio of these forces remaining constant, the locus of the point P is an equiangular spiral. Furthermore, we see how any slight change in any one of the forces P, T, L will tend to modify the angle alpha, and produce a slight departure from the absolute regularity of the logarithmic spiral. Such slight departures from the absolute simplicity and uniformity of the theoretic law we shall not be surprised to find, more or less frequently, in nature, in the complex system of forces presented by the living organism. In the growth of a shell, we can conceive no simpler law than this, namely, that it shall widen and lengthen in the same unvarying proportions, and this simplest of laws is that which nature tends to follow. The shell, like the creature within it, grows in size but does not change its shape. And the existence of this constant relativity of growth, or constant similarity of form, is of the essence, and may be made the basis of a definition, of the logarithmic spiral. Such a definition, though not commonly used by mathematicians, has been occasionally employed, and it is one from which the other properties of the curve can be deduced with great ease and simplicity. In mathematical language it would run as follows: any plane curve proceeding from a fixed point, which is called the pole, and such that the arc intercepted between this point and any other whatsoever on the curve is always similar to itself, is called an equiangular, or logarithmic, spiral. In this definition, we have what is probably the most fundamental and intrinsic property of the curve. Namely the property of continual similarity, and this is indeed the very property by reason of which it is peculiarly associated with organic growth in such structures as the horn or the shell, or the scorpioid sign which is described on p. For it is peculiarly characteristic of the spiral of a shell, for instance, that, under all normal circumstances, it does not alter its shape as it grows. Each increment is geometrically similar to its predecessor, and the whole, at any epoch, is similar to what constituted the whole at another and an earlier epoch. We feel no surprise when the animal which secretes the shell, or any other animal whatsoever, grows by such symmetrical expansion as to preserve its form unchanged. Though even there, as we have already seen, the unchanging form denotes a nice balance between the rates of growth in various directions, which is but seldom accurately maintained for long. But the shell retains its unchanging form in spite of its asymmetrical growth. It grows at one end only, and so does the horn. And this remarkable property of increasing by terminal growth, but nevertheless retaining unchanged the form of the entire figure, is characteristic of the logarithmic spiral, and of no other mathematical curve. Figure 248. We may at once illustrate this curious phenomenon by drawing the outline of a little nautilus shell within a big one. We know, or we may see at once, that they are of precisely the same shape. So that, if we look at the little shell through a magnifying glass, it becomes identical with the big one. But we know, on the other hand, that the little nautilus shell grows into the big one, not by uniform growth or magnification in all directions, as is, though only approximately, the case when the boy grows into the man, but by growing at one end only. Though of all curves, this property of continued similarity is found only in the logarithmic spiral, there are very many rectilinear figures in which it may be observed. For instance, as we may easily see, it holds good of any right cone. For evidently, in Fig. The little inner cone, represented in its triangular section, may become identical with the larger one either by magnification all round, as in A, or simply by an increment at one end, as in B. Indeed, in the case of the cone, we have yet a third possibility, for the same result is attained when it increases all round, save only at the base, that is to say when the triangular section increases on two of its sides, as in C. All this is closely associated with the fact, which we have already noted, that the nautilus shell is but a cone rolled up. In other words, the cone is but a particular variety, or limiting case, of the spiral shell. This property, which we so easily recognize in the cone, would seem to have engaged the particular attention of the most ancient mathematicians even from the days of Pythagoras, and so, with little doubt, from the more ancient days of that Egyptian school whence he derived the foundations of his learning. And its bearing on our biological problem of the shell, though apparently indirect, is yet so close that it deserves our further consideration. Figure 249. Figure 250. If, as in Fig, we add to two sides of a square a symmetrical L-shaped portion, similar in shape to what we call a carpenter's square, the resulting figure is still a square, and the portion which we have added is called, by Aristotle, Phys. 3, 4, a gnomon. Euclid extends the term to include the case of any parallelogram, whether rectangular or not, Fig. And Hero of Alexandria specifically defines a gnomon, as indeed Aristotle implicitly defines it, as any figure which, being added to any figure whatsoever, leaves the resultant figure similar to the original. Included in this important definition is the case of numbers, considered geometrically, that is to say, the epsilon delta eta tau iota kappa omicron rho iota theta mu omicron, which can be translated into form, by means of rows of dots or other signs, cf. Arist. Metaph. 1092b12, or in the pattern of a tiled floor, all according to the mystical way of Pythagoras, and the secret magic of numbers. Thus for example, the odd numbers are mnemonic numbers, because 0 plus 1 equals 1 2, 1 2 plus 3 equals 2 2, 2 2 plus 5 equals 3 2, 3 2 plus 7 equals 4 2 etc. Which relation we may illustrate graphically sigma chi eta mu alpha tau omicron gamma rho alpha phi epsilon nu by the successive numbers of dots which keep the annexed figure a perfect square, as follows. There are other mnemonic figures more curious still. For instance, if we make a rectangle, Fig, such that the two sides, Figure 251, Figure 252, are in the ratio of 1, 2, it is obvious that, on doubling it, we obtain a precisely similar figure, for 1, 2, 2, 2. And each half of the figure, accordingly, is now a gnomon to the other. Another elegant example is when we start with a rectangle, A, whose sides are in the proportion of 1, 1/2, 5, 1, or, approximately, 1, 0, 6, 18. The gnomon to this figure is a square, B, erected on its longer side, and so on successively, Fig. Figure 253. Figure 254. In any triangle, as Aristotle tells us, one part is always a gnomon to the other part. For instance, in the triangle ABC, Fig, let us draw CD, so as to make the angle BCD equal to the angle A. Then the part BCD is a triangle similar to the whole triangle ABC, and ADC is a gnomon to BCD. A very elegant case is when the original triangle ABC is an isosceles triangle having one angle of 36 degrees, and the other two angles, therefore, each equal to 72 degrees, Fig. Then, by bisecting one of the angles of the base, we subdivide the large isosceles triangle into two isosceles triangles, of which one is similar to the whole figure and the other is its gnomon. There is good reason to believe that this triangle was especially studied by the Pythagoreans. For it lies at the root of many interesting geometrical constructions, such as the regular pentagon, and the mystical pentalpha, and a whole range of other curious figures beloved of the ancient mathematicians. Figure 255. If we take any one of these figures, for instance the isosceles triangle which we have just described, and add to it, or subtract from it, in succession a series of gnomons, so converting it into larger and larger, or smaller and smaller, triangles all similar to the first, we find that the apices, or other corresponding points, of all these triangles have their locus upon a logarithmic spiral, a result which follows directly from that alternative definition of the logarithmic spiral which I have quoted from Wentworth, p. Again, we may build up a series of right-angled triangles, each of which is a gnomon to the preceding figure, and here again, a logarithmic spiral is the locus of corresponding points in these successive triangles. And lastly, whensoever we fill up space with Figure 256. Logarithmic spiral derived from corresponding points in a system of squares. A collection of either equal or similar figures, similarly situated, as in Figs. 257, there we can always discover a series of inscribed or escribed logarithmic spirals. Once more, then, we may modify our definition, and say that, any plane curve proceeding from a fixed point, or pole, and such that the vectorial area of any sector is always a gnomon to the whole preceding figure, is called an equiangular or logarithmic spiral. And we may now introduce this new concept and nomenclature into our description of the nautilus shell and other related organic forms, by saying that, 1. If a growing Figure 257. The same in a system of hexagons. Structure be built up of successive parts, similar and similarly situated, we can always trace through corresponding points a series of logarithmic spirals, figs. 259, etc. 2. It is characteristic of the growth of the horn, of the shell, and of all other organic forms in which a logarithmic spiral can be recognized, that each successive increment of growth is a gnomon to the entire pre-existing structure. And conversely, 3. It follows obviously, that in the logarithmic spiral outline of the shell or of the horn we can always inscribe an endless variety of other mnemonic figures, having no necessary relation, save as a mathematical accident, to the nature or mode of development of the actual structure. Figure 258. A shell of Haliotis, with 2 of the many lines of growth, or generating curves, marked out in black, the areas bounded by these lines of growth being in all cases gnomons to the pre-existing shell. Figure 259. A spiral foraminifer pulvinulina, to show how each successive chamber continues the symmetry of, or constitutes a gnomon to the rest of the structure. Of these 3 propositions, the second is of very great use and advantage for our easy understanding and simple description of the molluscan shell, and of a great variety of other structures whose mode of growth is analogous, and whose mathematical properties are therefore identical. We see at once that the successive chambers of a spiral nautilus, fig, or of a straight orthoceras, fig, each whorl or part of a whorl of a periwinkle or other gastropod, fig, each new increment of the operculum of a gastropod, fig. Each additional increment of Figure 260. Another spiral foraminifer. Crystalleria. An elephant's tusk, or each new chamber of a spiral foraminifer, figs. And 260, has its leading characteristic at once described and its form so far explained by the simple statement that it constitutes a gnomon to the whole previously existing structure. And herein lies the explanation of that time element, in the development of organic spirals of which we have spoken already, in a preliminary and empirical way. For it follows as a simple corollary to this theorem of gnomons that we must not expect to find the logarithmic spiral manifested in a structure whose parts are simultaneously produced, as for instance in the margin of a leaf, or among the many curves that make the contour of a fish. But we must rather look for it wherever the organism retains for us, and still presents to us at a single view, the successive phases of preceding growth, the successive magnitudes attained, the successive outlines occupied. As the organism or a part thereof pursued the even tenor of its growth, year by year and day by day. And it easily follows from this, that it is in the hard parts of organisms, and not the soft, fleshy, actively growing parts, that this spiral is commonly and characteristically found. Not in the fresh mobile tissues whose form is constrained merely by the active forces of the moment, but in things like shell and tusk, and horn and claw, where the object is visibly composed of parts successively, and permanently, laid down. In the main, the logarithmic spiral is characteristic, not of the living tissues, but of the dead. And for the same reason, it will always or nearly always be accompanied, and adorned, by a pattern formed of lines of growth, the lasting record of earlier and successive stages of form and magnitude. It is evident that the spiral curve of the shell is, in a sense, a vector diagram of its own growth. For it shews at each instant of time, the direction, radial and tangential, of growth, and the unchanging ratio of velocities in these directions. Regarding the actual velocity of growth in the shell, we know very little, or practically nothing, by way of experimental measurement. But if we make a certain simple assumption, then we may go a good deal further in our description of the logarithmic spiral as it appears in this concrete case. Let us make the assumption that similar increments are added to the shell in equal times, that is to say, that the amount of growth in unit time is measured by the area subtended by equal angles. Thus, in the outer whirl of a spiral shell a definite area marked out by ridges, tubercles, etc. has very different linear dimensions to the corresponding areas of the inner whirl, but the symmetry of the figure implies that it subtends an equal angle with these. And it is reasonable to suppose that the successive regions, marked out in this way by successive natural boundaries or patterns, are produced in equal intervals of time. If this be so, the radii measured from the pole to the boundary of the shell will in each case be proportional to the velocity of growth at this point upon the circumference, and at the time when it corresponded with the outer lip, or region of active growth. And while the direction of the radius vector corresponds with the direction of growth in thickness of the animal, so does the tangent to the curve correspond with the direction, for the time being, of the animal's growth in length. The successive radii are a measure of the acceleration of growth, and the spiral curve of the shell itself is no other than the hodograph of the growth of the contained organism. So far as we have now gone, we have studied the elementary properties of the logarithmic spiral, including its fundamental property of continued similarity. And we have accordingly learned that the shell or the horn tends necessarily to assume the form of this mathematical figure, because in these structures growth proceeds by successive increments, which are always similar in form, similarly situated, and of constant relative magnitude one to another. Our chief objects in inquiring further into the mathematical properties of the logarithmic spiral will be, 1. To find means of confirming and verifying the fact that the shell, or other organic curve, is actually a logarithmic spiral. 2. To learn how, by the properties of the curve, we may further extend our knowledge or simplify our descriptions of the shell. And, 3. To understand the factors by which the characteristic form of any particular logarithmic spiral is determined. And so to comprehend the nature of the specific or generic characters by which one spiral shell is found to differ from another. Of the elementary properties of the logarithmic spiral, so far as we have now enumerated them, the following are those which we may most easily investigate in the concrete case. Such as we have to do within the molluscan shell: 1. That the polar radii of points whose vectorial angles are in arithmetical progression, are themselves in geometrical progression. And 2. That the tangent at any point of a logarithmic spiral makes a constant angle, called the angle of the spiral, with the polar radius vector. Figure 261. The former of these two propositions may be written in what is, perhaps, a simpler form, as follows: radii which form equal angles about the pole of the logarithmic spiral, are themselves continued proportionals. That is to say, in Fig. when the angle ROQ is equal to the angle QOP, then or OQ, OQ, OP. A particular case of this proposition is when the equal angles are each angles of 360 degrees, that is to say when in each case the radius vector makes a complete revolution, and when, therefore P, Q and R all lie upon the same radius. It was by observing, with the help of very careful measurement, this continued proportionality, that Moseley was enabled to verify his first assumption, based on the general appearance of the shell. That the shell of Nautilus was actually a logarithmic spiral, and this demonstration he was immediately afterwards in a position to generalize by extending it to all the spiral ammonitoid and gastropod mollusca. For, taking a median transverse section of a Nautilus pompilius, and carefully measuring the successive breadths of the whorls, from the dark line which marks what was originally the outer surface, before it was covered up by fresh deposits on the part of the growing and advancing shell, Moseley found that the distance of any two of its whorls measured upon a radius vector is 1/3 that of the two next whorls measured upon the same radius vector. Thus, in Fig, AB is 1/3 of BC, D of EF, GH of high, and KL of LM. The curve is therefore a logarithmic spiral. The numerical ratio in the case of the Nautilus happens to be one of unusual simplicity. Let us take, with Moseley, a somewhat more complicated example. From the apex of a large specimen of Turboduplicatus a line was drawn across its whorls, and their widths were measured upon it in succession, beginning with the last but one. The measurements were, as before, made with a fine pair of compasses and a diagonal scale. The sight was assisted by a magnifying glass. In a parallel column to the following measurements are the terms of a geometric progression, whose first term is the width of the widest whorl measured, and whose common ratio is 1/1804. Figure 262. Widths of successive whorls measured in inches and parts of an inch. Terms of a geometrical progression, whose first term is the width of the widest whorl, and whose common ratio is 1/1804. 131. 131. 112. 1/1098. 94. 94018. 80. 79651. 67. 67476. 57. 57164. 48. 48427. 41. 41026. The close coincidence between the observed and the calculated figures is very remarkable, and is amply sufficient to justify the conclusion that we are here dealing with a true logarithmic spiral. Nevertheless, in order to verify his conclusion still further, and to get partially rid of the inaccuracies due to successive small measurements, Moseley proceeded to investigate the same shell, measuring not single whorls, but groups of whorls, taken several at a time, making use of the following property of a geometrical progression, that, if represent the ratio of the sum of every even number, m, of its terms to the sum of half that number of terms, then the common ratio, r, of the series is represented by the formula r equals 1 to m. Accordingly, Moseley made the following measurements, beginning from the second and third whorls respectively. Width of ratio 6 whorls, 3 whorls, 537, 203, 2645, 455, 172, 2645, 4 whorls, 2 whorls, ratio 415, 174, 2385, 352, 147, 2394. By the ratios of the two first measurements, the formula gives r equals 1/645, 13 equals 1/1804. By the mean of the ratios deduced from the second two measurements, it gives r equals 1/389, 12 equals 1/1806. It is scarcely possible to imagine a more accurate verification than is deduced from these larger measurements, and we may with safety annex to the species Turboduplicatus the characteristic number 118. By similar and equally concordant observations, Moseley found for Turbophasianus the characteristic ratio, 1/75, and for Buccinum subulatum that of 1/13. From the table referring to Turboduplicatus, on page, it is perhaps worthwhile to illustrate the logarithmic statement of the same facts, that is to say, the elementary corollary to the fact that the successive radii are in geometric progression, that their logarithms differ from one another by a constant amount. Turboduplicatus. Relative widths of successive whorls. Logarithms of successive whorls. Difference of successive logarithms. 2-11727, 2-04922, 06805, 1-97313, 07609, 1-90309, 07004, 1-82607. 07702 175587 07020 168124 07463 116128 06846 Mean Difference 07207 and 07207 is the logarithm of 1/1805. Figure 263. Operculum of turbo. The logarithmic spiral is not only very beautifully manifested in the molluscan shell, but also, in certain cases, in the little lid or operculum by which the entrance to the tubular shell is closed after the animal has withdrawn itself within. In the spiral shell of turbo, for instance, the operculum is a thick calcareous structure, with a beautifully curved outline, which grows by successive increments applied to one portion of its edge, and shews, accordingly, a spiral line of growth upon its surface. The successive increments leave their traces on the surface of the operculum, Fig. 1, which traces have the form of curved lines in turbo, and of straight lines in, e.g., Nerida, Fig. 2. That is to say, apart from the side constituting the outer edge of the operculum, which side is always and of necessity curved, the successive increments constitute curvilinear triangles in the one case, and rectilinear triangles in the other. The sides of these triangles are tangents to the spiral line of the operculum, and may be supposed to generate it by their consecutive intersections. Figure 264. Opercula of 1. Turbo. 2. Nerita. After Moseley. In a number of such opercula, Moseley measured the breadths of the successive whorls along a radius vector, just in the same way as he did with the entire shell in the foregoing cases, and here is one example of his results. Operculum of turbo SP, breadth, in inches, of successive whorls, measured from the pole. Distance. Ratio. Distance. Ratio. Distance. Ratio. Distance. Ratio. 24. 16. 2. 18. 228. 231. 230. 230. 55. 37. 6. 42. 232. 230. 230. 224. 128. 85. 138. 94. The ratio is approximately constant, and this spiral also is. Therefore, a logarithmic spiral. But here comes in a very beautiful illustration of that property of the logarithmic spiral which causes its whole shape to remain unchanged, in spite of its apparently unsymmetrical, or unilateral, mode of growth. For the mouth of the tubular shell, into which the operculum has to fit, is growing or widening on all sides, while the operculum is increasing, not by additions made at the same time all round its margin, but by additions made only on one side of it at each successive stage. One edge of the operculum thus remains unaltered as it is advanced into each new position, and as it is placed in a newly formed section of the tube, similar to but greater than the last. Nevertheless, the two opposed structures, the chamber and its plug, at all times fit one another to perfection. The mechanical problem, by no means an easy one, is thus solved: how to shape a tube of a variable section, so that a piston driven along it shall, by one side of its margin, coincide continually with its surface as it advances. Provided only that the piston be made at the same time continually to revolve in its own plane. As Moseley puts it, that the same edge which fitted a portion of the first less section should be capable of adjustment, so as to fit a portion of the next similar but greater section. Supposes a geometrical provision in the curved form of the chamber of great apparent complication and difficulty. But God hath bestowed upon this humble architect the practical skill of a learned geometrician, and he makes this provision with admirable precision in that curvature of the logarithmic spiral which he gives to the section of the shell. This curvature obtaining, he has only to turn his operculum slightly round in its own plane as he advances it into each newly formed portion of his chamber, to adapt one margin of it to a new and larger surface and a different curvature, leaving the space to be filled up by increasing the operculum wholly on the other margin. But in many, and indeed more numerous gastropod mollusca, the operculum does not grow in this remarkable spiral fashion, but by the apparently much simpler process of accretion by concentric rings. This suggests to us another mathematical feature of the logarithmic spiral. We have already seen that the logarithmic spiral has a number of limiting cases, apparently very diverse from one another. Thus the right cone is a logarithmic spiral in which the revolution of the radius vector is infinitely slow, and, in the same sense, the straight line itself is a limiting case of the logarithmic spiral. The spiral of Archimedes, though not a limiting case of the logarithmic spiral, closely resembles one in which the angle of the spiral is very near to 90 degrees, and the spiral is coiled around a central core. But if the angle of the spiral were actually 90 degrees, the radius vector would describe a circle, identical with the core of which we have just spoken. And accordingly it may be said that the circle is, in this sense, a true limiting case of the logarithmic spiral. In this sense, then, the circular concentric operculum, for instance of Turritella or Littorina, does not represent a breach of continuity, but a limiting case of the spiral operculum of Turbo. The successive gnomons are now not lateral or terminal additions, but complete concentric rings. Viewed in regard to its own fundamental properties and to those of its limiting cases, the logarithmic spiral is the simplest of all known curves. And the rigid uniformity of the simple laws, or forces, by which it is developed sufficiently account for its frequent manifestation in the structures built up by the slow and steady growth of organisms. In order to translate into precise terms the whole form and growth of a spiral shell, we should have to employ a mathematical notation, considerably more complicated than any that I have attempted to make use of in this book. But, in the most elementary language, we may now at least attempt to describe the general method, and some of the variations, of the mathematical development of the shell. Let us imagine a closed curve in space, whether circular or elliptical or of some other and more complex specific form, not necessarily in a plane, such a curve as we see before us when we consider the mouth, or terminal orifice, of our tubular shell. And let us imagine some one characteristic point within this closed curve, such as its center of gravity. Then, starting from a fixed origin, let this center of gravity describe an equiangular spiral in space, about a fixed axis, namely the axis of the shell, while at the same time the generating curve grows, with each angular increment of rotation, in such a way as to preserve the symmetry of the entire figure, with or without a simultaneous movement of translation along the axis. Figure 265. Melo Ethiopicus, L. It is plain that the entire resulting shell may now be looked upon in either of two ways. It is, on the one hand, an ensemble of similar closed curves spirally arranged in space, gradually increasing in dimensions, in proportion to the increase of their vectorial angle from the pole. In other words, we can imagine our shell cut up into a system of rings, following one another in continuous spiral succession from that terminal and largest one, which constitutes the lip of the orifice of the shell. Or, on the other hand, we may figure to ourselves the whole shell as made up of an ensemble of spiral lines in space, each spiral having been traced out by the gradual growth and revolution of a radius vector from the pole to a given point of the generating curve. Both systems of lines, the generating spirals, as these latter may be called, and the closed generating curves corresponding to successive margins or lips of the shell, may be easily traced in a great variety of cases. Thus, for example, in Dolium, Ebernia, and a host of others, the generating spirals are beautifully marked out. Figure 266. 1. Harpa, 2. Dolium. The ridges on the shell correspond in 1. to generating curves, in 2. to generating spirals. By ridges, tubercles or bands of color. In Trophon, Scalaria, and, among countless others, in the ammonites, it is the successive generating curves which more conspicuously leave their impress on the shell. And in not a few cases, as in Harpa, Dolium perdix, etc., both alike are conspicuous, ridges and color bands intersecting one another in a beautiful isogonal system. In the complete mathematical formula, such as I have not ventured to set forth, for any given turbinate shell, we should have, accordingly, to include factors for at least the following elements: 1. For the specific form of the section of the tube, which we have called the generating curve. 2. For the specific rate of growth of this generating curve. 3. For its specific rate of angular rotation about the pole, perpendicular to the axis. 4. In turbinate, as opposed to nautiloid, shells, for its rate of shear, or screw translation parallel to the axis. There are also other factors of which we should have to take account, and which would help to make our whole expression a very complicated one. We should find, for instance, 5, that in very many cases our generating curve was not a plane curve, but a sinuous curve in 3 dimensions. And we should also have to take account, 6, of the inclination of the plane of this generating curve to the axis, a factor which will have a very important influence on the form and appearance of the shell. For instance, in Haliotis it is obvious that the generating curve lies in a plane very oblique to the axis of the shell. Lastly, we at once perceive that the ratios which happen to exist between these various factors, the ratio for instance between the growth factor and the rate of angular revolution, will give us endless possibilities of permutation of form. For instance, 7, with a given velocity of vectorial rotation, a certain rate of growth in the generating curve will give us a spiral shell of which each successive whirl will just touch its predecessor and no more. With a slower growth factor, the whirls will stand asunder, as in a ram's horn. With a quicker growth factor, each whirl will cut or intersect its predecessor, as in an ammonite or the majority of gastropods, and so on, cf. In like manner, 8, the ratio between the growth factor and the rate of screw translation parallel to the axis will determine the apical angle of the resulting conical structure, will give us the difference, for example, between the sharp pointed cone of Turritella, the less acute one of Fusus or Buccinum, and the obtuse one of Harpa or Dolium. In short, it is obvious that all the differences of form which we observe between one shell and another are referable to matters of degree, depending, one and all, upon the relative magnitudes of the various factors in the complex equation to the curve. The paper in which, nearly 80 years ago, Canon Moseley thus gave a simple mathematical expression to the spiral forms of univalve shells, is one of the classics of natural history. But other students before him had come very near to recognizing this mathematical simplicity of form and structure. About the year 1818, Reinecke had suggested that the relative breadths of the adjacent whorls in an ammonite formed a constant and diagnostic character, and Leopold von Buch accepted and developed the idea. But long before, Swammerdam, with a deeper insight, had grasped the root of the whole matter, for, taking a few diverse examples, such as helix and spirula, he shewed that they and all other spiral shells whatsoever were referable to one common type, namely to that of a simple tube, variously curved according to definite mathematical laws. That all manner of ornamentation, in the way of spines, tuberosities, color bands and so forth, might be superposed upon them, but the type was one throughout, and specific differences were of a geometrical kind. Omnis animque inter eas animadvertitur differentia ex sola nascitur diversitate gyrationem, cabus si in super externa quidem adjunguntur ornamenta panarum, sinuum, and fractuum, planetarum, eminentiarum, profunditatum, extensionum, impressionum, circumvolutionum, colorumque. Tunc de inceps facile est, quorum cum cochlearum figuras geometricas, curvasque, obliquos ac rectos angulos, ad unicam omnes speciem redigere, ad oblongum videlicet tubulum, cavario modo curvatus, crispatus. Extrorsum et introrsum flexus, ita concrevit. Figure 267. D'Orbigny S. Helicometer. For some years after the appearance of Moseley's paper, a number of writers followed in his footsteps, and attempted, in various ways, to put his conclusions to practical use. For instance, D'Orbigny devised a very simple protractor, which he called a helicometer, and which is represented in Fig. By means of this little instrument, the apical angle of the turbinate shell was immediately read off, and could then be used as a specific and diagnostic character. By keeping one limb of the protractor parallel to the side of the cone while the other was brought into line with the suture between two adjacent whorls, another specific angle, the sutural angle, could in like manner be recorded. And, by the linear scale upon the instrument, the relative breadths of the consecutive whorls, and that of the terminal chamber to the rest of the shell, might also, though somewhat roughly, be determined. For instance, in Terebra dimidiata, the apical angle was found to be 13 degrees, the sutural angle 109 degrees, and so forth. It was at once obvious that, in such a shell as is represented in Fig. The entire outline of the shell, always excepting that of the immediate neighborhood of the mouth, could be restored from a broken fragment. For if we draw our tangents to the cone, it follows from the symmetry of the figure that we can continue the projection of the sutural line, and so mark off the successive whorls, by simply drawing a series of consecutive parallels. And by then filling into the quadrilaterals so marked off a series of curves similar to one another, and to the whorls which are still intact in the broken shell. But the use of the helicometer soon shewed that it was by no means universally the case that one and the same right cone was tangent to all the turbinate whorls. In other words, there was not always one specific apical angle which held good for the entire system. In the great majority of cases, it is true, the same tangent touches all the whorls, and is a straight line. But in others, as in the large Cerithium nodosum, such a line is slightly convex to the axis of the shell, and in the short spire of Dolium, for instance, the convexity is marked, and the apex of the spire is a distinct cusp. On the other hand, in Pupa and Clausilia, the common tangent is concave to the axis of the shell. So also is it, as we shall presently see, among the ammonites, where there are some species in which the ratio of whorl to whorl remains, to all appearance, perfectly constant, others in which it gradually, though only slightly increases. And others again in which it slightly and gradually falls away. It is obvious that, among the manifold possibilities of growth, such conditions as these are very easily conceivable. It is much more remarkable that, among these shells, the relative velocities of growth in various dimensions should be as constant as it is, than that there should be an occasional departure from perfect regularity. In such cases as these latter, the logarithmic law of growth is only approximately true. The shell is no longer to be represented as a right cone which has been rolled up, but as a cone which had grown trumpet-shaped, or conversely whose mouth had narrowed in, and which in section is a curvilinear instead of a rectilinear triangle. But all that has happened is that a new factor, usually of small or all but imperceptible magnitude, has been introduced into the case. So that the ratio, log r equals theta log alpha, is no longer constant, but varies slightly, and in accordance with some simple law. Some writers, such as Naumann and Grabow, maintain that the molluscan spiral was no true logarithmic spiral, but differed from it specifically, and they gave to it the name of conchospiral. They pointed out that the logarithmic spiral originates in a mathematical point, while the molluscan shell starts with a little embryonic shell, or central chamber, the protoconch of the conchologists, around which the spiral is subsequently wrapped. It is plain that this undoubted and obvious fact need not affect the logarithmic law of the shell as a whole. We have only to add a small constant to our equation, which becomes r equals m plus a theta. There would seem, by the way, to be considerable confusion in the books with regard to the so-called protoconch. In many cases it is a definite structure, of simple form, representing the more or less globular embryonic shell before it began to elongate into its conical or spiral form. But in many cases what is described as the protoconch is merely an empty space in the middle of. Figure 268. The spiral coil, resulting from the fact that the actual spiral shell has a definite magnitude to begin with, and that we cannot follow it down to its vanishing point in infinity. For instance, in the accompanying figure, the large space A is styled the protoconch, but it is the little bulbous or hemispherical chamber within it, at the end of the spire, which is the real beginning of the tubular shell. The form and magnitude of the space A are determined by the angle of retardation, or ratio of rate of growth between the inner and outer curves of the spiral shell. They are independent of the shape and size of the embryo, and depend only, as we shall see better presently, on the direction and relative rate of growth of the double contour of the shell. Figure 269. Now that we have dealt, in a very general way, with some of the more obvious properties of the logarithmic spiral, let us consider certain of them a little more particularly. Keeping in view as our chief object the investigation, on elementary lines, of the possible manner and range of variation of the molluscan shell. There is yet another equation to the logarithmic spiral, very commonly employed, and without the help of which we shall find that we cannot get far. It is as follows. R equals epsilon theta cot alpha. This follows directly from the fact that the angle alpha, the angle between the radius vector and the tangent to the curve, is constant. For, then, tan alpha equals tan phi. Equals are d theta dr. Therefore, drr equals d theta cot alpha. And, integrating, log r equals theta cot alpha, or r equals epsilon theta cot alpha. As we have seen throughout our preliminary discussion, the two most important constants, or chief, specific characters, as the naturalist would say, in any given logarithmic spiral, are, 1, the magnitude of the angle of the spiral, or, constant angle, alpha, and, 2, the rate of increase of the radius vector for any given angle of revolution, theta. Of this latter, the simplest case is when theta equals 2 pi, or 360 degree, that is to say when we compare the breadths, along the same radius vector, of two successive whorls. As our two magnitudes, that of the constant angle, and that of the ratio of the radii or breadths of whorl, are related to one another, we may determine either of them by actual measurement and proceed to calculate the other. In any complete spiral, such as that of Nautilus, it is, as we have seen, easy to measure any two radii, r, or the breadths in a radial direction of any two whorls, w. We have then merely to apply the formula Rn plus 1 Rn equals E theta cot alpha, or Wn plus 1 Wn equals E theta cot alpha, which we may simply write R equals E theta cot alpha, etc. Since our first radius or whorl is regarded, for the purpose of comparison, as being equal to unity. Thus, in the diagram, OCOE, or EFBD, or DCEF, being in each case radii, or diameters, at right angles to one another, are all equal to E, pi 2, cot alpha. While in like manner, EO of, EGFH, or GOHO, all equal E pi cot alpha. And BCBA, or COOB equals E 2 pi cot alpha. Figure 270. As soon, then, as we have prepared tables for these values, the determination of the constant angle alpha in a particular shell becomes a very simple matter. A complete table would be cumbrous, and it will be sufficient to deal with the simple case of the ratio between the breadths of adjacent, or immediately succeeding, whorls. Here we have R equals E 2 pi cot alpha, or log R equals log E times 2 pi times cot alpha. From which we obtain the following figures. Ratio of breadth of each whorl to the next preceding. R1. Constant angle alpha 1 89 degrees 8 1 25 87 58 1 5 86 18 2 0 83 42 2 5 81 42 3 0 85 3 5 78 43 4 0 77 34 4 5 76 32 5 0 75 38 10 0 69 53 20 0 64 31 50 0 58 5 100 0. 5346. 1. 0000. 4217. 10,000. 3419. 100,000. 2837. 1 million. 2428. 10 million. 2118. 100 million. 1850. 1 billion. 1652. We learn several interesting things from this short table. We see, in the first place, that where each whirl is about 3 times the breadth of its neighbor and predecessor, as is the case in Nautilus. Figure 271. The constant angle is in the neighborhood of 80 degrees. And hence also that, in all the ordinary ammonitoid shells, and in all the typically spiral shells of the gastropods, the constant angle is also a large one, being very seldom less than 80 degrees, and usually between 80 degrees and 85 degrees. In the next place, we see that with smaller angles the apparent form of the spiral is greatly altered, and the very fact of its being a spiral soon ceases to be apparent. Figs. 272. Suppose one whirl to be an inch in breadth, then, if the angle of the spiral were 80 degrees, the next whirl would, as we have just seen, be about 3 inches broad. If it were 70 degrees, the next whirl would be nearly 10 inches, and if it were 60 degrees, the next whirl would be nearly 4 feet broad. If the angle were 28 degrees, the next whirl would be 1.5 miles in breadth. And if it were 17 degrees, the next would be some 15,000 miles broad. Figure 272. In other words, the spiral shells of gentle curvature, or of small constant angle, such as Dentalium or Nodoceria, are true logarithmic spirals, just as are those of Nautilus or Rhotalia, from which they differ only in degree. In the magnitude of an angular constant. But this diminished magnitude of the angle causes the spiral to dilate with such immense rapidity that, so to speak, it never comes round, and so, in such a shell as Dentalium, we never see but a small portion of the initial whirl. Figure 273. We might perhaps be inclined to suppose that, in such a shell as Dentalium, the lack of a visible spiral convolution was only due to our seeing but a small portion of the curve, at a distance from the pole, and when, therefore, its curvature had already greatly diminished. That is to say, we might suppose that, however small the angle A, and however rapidly the whirls accordingly increased, there would nevertheless be a manifest spiral convolution in the immediate neighborhood of the pole, as the starting point of the curve. But it may be shown that this is not so. For, taking the formula R equals A epsilon theta cot alpha, this, for any given spiral, is equivalent to A epsilon k theta. Therefore, log Ra equals k theta, or 1k equals theta log Ra. Then, if theta increase by 2 pi, while R increases to R1, 1k equals theta plus 2 pi log R1a, which leads, by subtraction, to 1k log R1r equals 2 pi. Now, as alpha tends to 0, k, i.e. cot alpha, tends to, and therefore, as k, log, R1r, and also R1r. Therefore if one whirl exists, the radius vector of the other is infinite. In other words, there is nowhere, even in the near neighborhood of the pole, a complete revolution of the spire. Our spiral shells of small constant angle, such as Dentalium, may accordingly be considered to represent sufficiently well the true commencement of their respective spirals. Let us return to the problem of how to ascertain, by direct measurement, the spiral angle of any particular shell. The method already employed is only applicable to complete spirals, that is to say to those in which the angle of the spiral is large, and furthermore it is inapplicable to portions, or broken fragments, of a shell. In the case of the broken fragment, it is plain that the determination of the angle is not merely of theoretic interest. but may be of great practical use to the conchologist as being the one and only way by which he may restore the outline of the missing portions. We have a considerable choice of methods, which have been summarized by, and are partly due to, a very careful student of the cephalopoda, the late Reverend J. F. Blake. Figure 274. 1. The following method is useful and easy when we have a portion of a single whorl, such as to shew both its inner and its outer edge. A broken whorl of an ammonite, a curved shell such as dentalium, or a horn of similar form to the latter, will fall under this head. We have merely to draw a tangent, GEH, to the outer whorl at any point E. Then draw to the inner whorl a tangent parallel to GEH, touching the curve in some point F. The straight line joining the points of contact, EF, must evidently pass through the pole, and, accordingly, the angle GEF is the angle required. In shells which bear longitudinal striae or other ornaments, any pair of these will suffice for our purpose, instead of the actual boundaries of the whorl. But it is obvious that this method will be apt to fail us when the angle alpha is very small. And when, consequently, the points E and F are very remote. Figure 275. An ammonite, 2. Shoe corrugated surface pattern. Figure 276. 2. In shells, or horns, shoeing rings, or other transverse ornamentation, we may take it that these ornaments are set at a constant angle to the spire, and therefore to the radii. The angle, theta, between two of them, as AC, BD, is therefore equal to the angle theta between the polar radii from A and B, or from C and D, and therefore BDAC equals E theta cot alpha, which gives us the angle alpha in terms of known quantities. 3. If only the outer edge be available, we have the ordinary geometrical problem, given an arc of an equiangular spiral, to find its pole and spiral angle. The methods we may employ depend, 1. On determining directly the position of the pole, and, 2. On determining the radius of curvature. Figure 277. The first method is theoretically simple, but difficult in practice. For it requires great accuracy in determining the points. Let AD, DB, be two tangents drawn to the curve. Then a circle drawn through the points ABD will pass through the pole O, since the angles OAD, OBE, the supplement of OBD, are equal. The point O may be determined by the intersection of two such circles, and the angle DBO is then the angle, alpha, required. Or we may determine, graphically, at 2 points, the radii of curvature, ρ1 ρ2. Then, if S be the length of the arc between them, which may be determined with fair accuracy by rolling the margin of the shell along a ruler. Cot alpha equals, ρ1 ρ2, S. The following method, given by Blake, will save actual determination of the radii of curvature. Measure along a tangent to the curve, the distance, AC, at which a certain small offset, CD, is made by the curve. And from another point B, measure the distance at which the curve makes an equal offset. Then, calling the offset mu, the arc AB, S. And AC, B, respectively x1, x2, we have ρ1 equals, x12 plus mu2, 2 mu, approximately. And cot alpha equals, x22 x12, 2 microseconds. Of all these methods by which the mathematical constants, or specific characters, of a given spiral shell may be determined, the only one of which much use has been made is that which Moseley first employed, namely, the simple method of determining the relative breadths of the whorl at distances separated by some convenient vectorial angle, such as 90 degrees, 180 degrees, or 360 degrees. Very elaborate measurements of a number of ammonites have been made by Naumann, by Sandberger, and by Grabau, among which we may choose a couple of cases for consideration. In the following table I have taken a portion of Grabau's determinations of the breadth of the whorls in ammonites, arc estis. Ammonites interslabiatus. Breadth of whorls, 180 degrees. Apart, mm. Ratio of breadth of Successive whorls. 360 degrees apart. The angle, alpha. As calculated. 0, 30. 0, 30. 1, 333. 87 degrees 23. 0, 40. 1, 500. 86, 19. 0, 45. 1, 500. 86, 19. 0, 60. 1, 444. 86, 39. 0, 65. 1, 417. 86, 49. 0, 85. 1, 692. 85, 13. 1, 10. 1, 588. 85, 47. 1, 35. 1, 545. 86, 2. 1, 70. 1, 630. 85, 33. 2, 20. 1, 441. 86, 40. 2, 45. 1, 432. 86, 43. 3, 15. 1, 735. 85, 0. 4, 25. 1, 683. 85, 16. 5, 30. 1, 482. 86, 25. 6, 30. 1, 5, 19. 86, 12. 8, 0, 5. 1, 6, 35. 85, 32. 10, 30. 1, 4, 16. 86, 50. 11, 40. 1, 2, 52. 87, 57. 12, 90. Mean. 86 degrees 15. Interdisciplinary. These measurements Grabow gives for every 45 degrees of arc, but I have only set forth 1/4 of these measurements, that is to say, the breadths of successive whorls measured along one diameter on both sides of the pole. The ratio between alternate measurements is therefore the same ratio as Moseley adopted, namely the ratio of breadth between contiguous whorls along a radius vector. I have then added to these observed values the corresponding calculated values of the angle alpha, as obtained from our usual formula. There is considerable irregularity in the ratios derived from these measurements, but it will be seen that this irregularity only implies a variation of the angle of the spiral between about 85 degrees and 87 degrees. And the values fluctuate pretty regularly about the mean, which is 86 degrees 15. Considering the difficulty of measuring the whorls, especially towards the center, and in particular the difficulty of determining with precise accuracy the position of the pole, it is clear that in such a case as this we are scarcely justified in asserting that the law of the logarithmic spiral is departed from. In some cases, however, it is undoubtedly departed from. Here for instance is another table from Grabow, showing the corresponding ratios in an ammonite of the group of Arcestis tornatus. In this case we see a distinct tendency of the ratios to ammonites tornatus. Breadth of whorls, 180 degrees. Apart, mm. Ratio of breadth of successive whorls. 360 degrees apart. The spiral angle, alpha, as calculated. 0, 25. 0, 30. 1, 400. 86 degrees 56. 0, 35. 1, 667. 85, 21. 0, 50. 2, 0, 0, 0. 83, 42. 0, 70. 2, 0, 0, 0. 83, 42. 1, 0, 0. 2, 0, 0, 0. 83, 42. 1, 40. 2, 100. 83, 16. 2, 10. 2, 179. 82, 56. 3, 0, 5. 2, 238. 8242. 470. 2, 492. 8144. 760. 2, 574. 8127. 1210. 2, 546. 8133. 1935. Mean. 83 degrees 22. Increase as we pass from the center of the coil outwards. And consequently for the values of the angle alpha to diminish. The case is precisely comparable to that of a cone with slightly curving sides, in which, that is to say, there is a slight acceleration of growth in a transverse as compared with the longitudinal direction. In a tubular spiral, whether plane or helicoid, the consecutive whorls may either be 1. Isolated and remote from one another, or 2. They may precisely meet, so that the outer border of one and the inner border of the next just coincide. Or 3. They may overlap, the vector plane of each outer whorl cutting that of its immediate predecessor or predecessors. Looking, as we have done, upon the spiral shell as being essentially a cone rolled up, it is plain that, for a given spiral angle, intersection or non-intersection of the successive whorls will depend upon the apical angle of the original cone. For the wider the cone, the more rapidly will its inner border tend to encroach on the outer border of the preceding whorl. But it is also plain that the greater be the apical angle of the cone, and the broader, consequently, the cone itself be, the greater difference will there be between the total lengths of its inner and outer border. Under given conditions of flexure. And, since the inner and outer borders are describing precisely the same spiral about the pole, it is plain that we may consider the inner border as being retarded in growth as compared with the outer. And as being always identical with a smaller and earlier part of the latter. If lambda be the ratio of growth between the outer and the inner curve, then, the outer curve being represented by r equals ae theta cot alpha. The equation to the inner one will be r equals a lambda e theta cot alpha, or r equals ae theta beta cot alpha. And beta may then be called the angle of retardation, to which the inner curve is subject by virtue of its slower rate of growth. Dispensing with mathematical formulae, the several conditions may be illustrated as follows. Figure 278. In the diagrams, Fig. O P1 P2 P3, etc. represents a radius, on which P1, P2, P3, are the points attained by the outer border of the tubular shell after as many entire consecutive revolutions. And P1, P2, P3, are the points similarly intersected by the inner border. OP being always equals lambda, which is the ratio of growth, or cutting down factor. Then, obviously, when OP1 is less than OP2 the whorls will be separated by an interspace, A. 2. When OP1 equals OP2 they will be in contact, B, and 3. When OP1 is greater than OP2 there will a greater or less extent of overlapping, that is to say of concealment of the surfaces of the earlier by the later whorls, C. And as a further case, 4, it is plain that if lambda be very large, that is to say if OP1 be greater, not only than OP2 but also than OP3, OP4, etc. we shall have complete, or all but complete concealment by the last formed whorl, of the whole of its predecessors. This latter condition is completely attained in Nautilus Pompilius, and approached, though not quite attained, in N. umbilicatus. And the difference between these two forms, or species, is constituted accordingly by a difference in the value of lambda. 5. There is also a final case, not easily distinguishable externally from 4, where P lies on the opposite side of the radius vector to P, and is therefore imaginary. This final condition is exhibited in Argonauta. The limiting values of lambda are easily ascertained. Figure 279. In Fig, we have portions of two successive whorls, whose corresponding points on the same radius vector, as r and r, are, therefore, at a distance apart corresponding to 2 pi. Let r and r refer to the inner, and r, are to the outer sides of the two whorls. Then, if we consider R equals AE theta cot alpha, it follows that R equals AE theta plus 2 pi cot alpha, R equals lambda AE theta cot alpha equals AE theta beta cot alpha, and R equals lambda AE theta plus 2 pi cot alpha equals AE theta plus 2 pi beta cot alpha. Now in the three cases, A, B, C, represented in Fig, it is plain that are, respectively. That is to say, lambda AE theta plus 2 pi cot alpha, AE theta cot alpha, and lambda E 2 pi cot alpha. 1. The case in which lambda E 2 pi cot alpha equals 1, or log lambda equals 2 pi cot alpha log epsilon, is the case represented in Fig. B, that is to say, the particular case, for each value of alpha, where the consecutive whorls just touch, without interspace or overlap. For such cases, then, we may tabulate the values of lambda, as follows. Constant angle. Alpha of spiral. Ratio, lambda, of rate. Of growth of inner border. Of tube. As compared with that of the outer border. 89 degrees. 896. 88. 803. 87. 720. 86. 645. 85. 577. 80. 330. 75. 234. 70. 1016. 65. 0534. We see, accordingly, that in plane spirals whose constant angle lies, say, between 65 degrees and 70 degrees. We can only obtain contact between consecutive whorls if the rate of growth of the inner border of the tube be a small fraction, a tenth or a 20th, of that of the outer border. In spirals whose constant angle is 80 degrees, contact is attained when the respective rates of growth are, approximately, as 3 to 1. While in spirals of constant angle from about 85 degrees to 89 degrees, contact is attained when the rates of growth are in the ratio of from about 3:5 to 9:10. Figure 280. If on the other hand we have, for any given value of alpha, a value of lambda greater or less than the value given in the above table, then we have, respectively, the conditions of separation or of overlap which are exemplified in Fig. A and C. And, just as we have constructed this table of values of lambda for the particular case of simple contact between the whorls, so we could construct similar tables for various degrees of separation, or degrees of overlap. For instance, a case which admits of simple solution is that in which the interspace between the whorls is everywhere a mean proportional between the breadths of the whorls themselves, Fig. In this case, let us call OA equals R, OC equals R1 and OB equals R. We then have R1 equals OA equals AE theta cot alpha. R2 equals OC equals AE theta plus 2 pi cot alpha. R1 R2 equals AE2 theta plus pi cot alpha equals R2, and R2 equals 1 lambda 2 epsilon 2 theta cot alpha. Whence, equating 1 lambda equals E pi cot alpha. The corresponding values of lambda are as follows. Constant angle, alpha. Ratio, lambda, of rates. Of growth of outer and inner border. Such as to produce a spiral with interspaces between the whorls. The breadth of which interspaces is a mean proportional between the breadths of the whorls themselves. 90 degrees. 100, imaginary. 89. 95. 88, 89, 87, 85, 86, 81, 85, 76, 80, 57, 75, 43, 70, 32, 65, 23, 60, 18, 55, 13, 50, 090, 45, 063, 40, 042, 35, 026, 30, 016. As regards the angle of retardation, beta, in the formula R equals lambda e theta cot alpha, or R equals e theta beta cot alpha, and in the case R equals e 2 pi beta cot alpha, or log lambda equals 2 pi beta cot alpha, it is evident that when beta equals 2 pi, that will mean that lambda equals 1. In other words, the outer and inner borders of the tube are identical, and the tube is constituted by one continuous line. When lambda is a very small fraction, that is to say when the rates of growth of the two borders of the tube are very diverse, then beta will tend towards infinity, tend that is to say towards a condition in which the inner border of the tube never grows at all. This condition is not infrequently approached in nature. The nearly parallel-sided cone of dentalium, or the widely separated whorls of lithoites, are evidently cases where lambda nearly approaches unity in the one case, and is still large in the other, beta being correspondingly small. While we can easily find cases where beta is very large and lambda is a small fraction, for instance in Haliotis or in Graphia. For the purposes of the morphologist, then, the main result of this last general investigation is to shew that all the various types of open and closed spirals, all the various degrees of separation or overlap of the successive whorls, are simply the outward expression of a varying ratio in the rate of growth of the outer as compared with the inner border of the tubular shell. The foregoing problem of contact, or intersection, of the successive whorls, is a very simple one in the case of the discoid shell but a more complex one in the turbinate. For in the discoid shell contact will evidently take place when the retardation of the inner as compared with the outer whorl is just 360 degrees, and the shape of the whorls need not be considered. As the angle of retardation diminishes from 360 degrees, the whorls will stand further and further apart in an open coil. As it increases beyond 360 degrees, they will more and more overlap. And when the angle of retardation is infinite, that is to say when the true inner edge of the whorl does not grow at all, then the shell is said to be completely involute. Of this latter condition we have a striking example in Argonauta, and one a little more obscure in Nautilus pompilius. In the turbinate shell, the problem of contact is twofold. For we have to deal with the possibilities of contact on the same side of the axis, which is what we have dealt with in the discoid, and also with the new possibility of contact or intersection on the opposite side. It is this latter case which will determine the presence or absence of an umbilicus, and whether, if present, it will be an open conical space or a twisted cone. It is further obvious that, in the case of the turbinate, the question of contact or no contact will depend on the shape of the generating curve. And if we take the simple case where this generating curve may be considered as an ellipse, then contact will be found to depend on the angle which the major axis of this ellipse makes with the axis of the shell. The question becomes a complicated one, and the student will find it treated in Blake's paper already referred to. When one whorl overlaps another, so that the generating curve cuts its predecessor, at a distance of 2 pi, on the same radius vector, the locus of intersection will follow a spiral line upon the shell, which is called the suture by conchologists. It is evidently one of that ensemble of spiral lines in space of which, as we have seen, the whole shell may be conceived to be constituted, and we might call it a contact spiral, or spiral of intersection. In discoid shells, such as an ammonite or a planorbis, or in Nautilus umbilicatus, there are obviously two such contact spirals, one on each side of the shell, that is to say one on each side of a plane perpendicular to the axis. In turbinate shells such a condition is also possible, but is somewhat rare. We have it for instance, in Solarium perspectivum, where the one contact spiral is visible on the exterior of the cone, and the other lies internally, winding round the open cone of the umbilicus. But this second contact spiral is usually imaginary, or concealed within the whorls of the turbinate shell. Again, in Haliotis, one of the contact spirals is non-existent, because of the extreme obliquity of the plane of the generating curve. In Scalaria preciosa and in Spirula there is no contact spiral, because the growth of the generating curve has been too slow, in comparison with the vector rotation of its plane. In Argonauta and in Cyprea, there is no contact spiral, because the growth of the generating curve has been too quick. Nor, of course, is there any contact spiral in Patella or in Dentalium, because the angle alpha is too small ever to give us a complete revolution of the spire. The various forms of straight or spiral shells among the cephalopods, which we have seen to be capable of complete definition by the help of elementary mathematics, have received a very complicated descriptive nomenclature from the paleontologists. For instance, the straight cones are spoken of as orthoceracones or bactridocones, the loosely coiled forms as gyroseracones or mimoseracones, the more closely coiled shells, in which one whorl overlaps the other, as nautilocones or ammoniticones. And so forth. In such a succession of forms the biologist sees undoubted and unquestioned evidence of ancestral descent. For instance, we read in Zittle's Paleontology, the bactridicone obviously represents the primitive or primary radical of the ammonoidea, and the mimoseracone the next or secondary radical of this order. While precisely the opposite conclusion was drawn by Owen, who supposed that the straight-chambered shells of such fossil cephalopods as Orthoceras had been produced by the gradual unwinding of a coiled nautiloid shell. To such phylogenetic hypotheses the mathematical or dynamical study of the forms of shells lends no valid support. If we have two shells in which the constant angle of the spire be respectively 80 degrees and 60 degrees, that fact in itself does not at all justify an assertion that the one is more primitive, more ancient, or more ancestral than the other. Nor, if we find a third in which the angle happens to be 70 degrees, does that fact entitle us to say that this shell is intermediate between the other two, in time, or in blood relationship, or in any other sense whatsoever save only the strictly formal and mathematical one. For it is evident that, though these particular arithmetical constants manifest themselves in visible and recognizable differences of form, yet they are not necessarily more deep-seated or significant than are those which manifest themselves only in difference of magnitude. And the student of phylogeny scarcely ventures to draw conclusions as to the relative antiquity of two allied organisms on the ground that one happens to be bigger or less, or longer or shorter, than the other. At the same time, while it is obviously unsafe to rest conclusions upon such features as these, unless they be strongly supported and corroborated in other ways, for the simple reason that there is unlimited room for coincidence, or separate and independent attainment of this or that magnitude or numerical ratio, yet on the other hand it is certain that, in particular cases, the evolution of a race has actually involved gradual increase or decrease in some one or more numerical factors, magnitude itself included, that is to say increase or decrease in some one or more of the actual and relative velocities of growth. When we do meet with a clear and unmistakable series of such progressive magnitudes or ratios manifesting themselves in a progressive series of allied forms, then we have the phenomenon of orthogenesis. For orthogenesis is simply that phenomenon of continuous lines or series of form, and also of functional or physiological capacity, which was the foundation of the theory of evolution, alike to Lamarck and to Darwin and Wallace, and which we see to exist whatever be our ideas of the origin of species, or of the nature and origin of functional adaptations. And to my mind, the mathematical, as distinguished from the purely physical, study of morphology bids fair to help us to recognize this phenomenon of orthogenesis in many cases where it is not at once patent to the eye. And also, on the other hand, to warn us, in many other cases, that even strong and apparently complex resemblances in form may be capable of arising independently, and may sometimes signify no more than the equally accidental numerical coincidences which are manifested in identity of length or weight, or any other simple magnitudes. I have already referred to the fact that, while in general a very great and remarkable regularity of form is characteristic of the molluscan shell, that complete regularity is apt to be departed from. We have clear cases of such a departure in pupa, clausilia, and various bulimi, where the enveloping cone of the spire is not a right cone but a cone whose sides are curved. It is plain that this condition may arise in two ways, either by a gradual change in the ratio of growth of the whorls, that is to say in the logarithmic spiral itself, or by a change in the velocity of translation along the axis. That is to say in the helicoid which, in all turbinate shells, is superposed upon the spiral. Very careful measurements will be necessary to determine to which of these factors, or in what proportions to each, the phenomenon is due. But in many amonitoidea where the helicoid factor does not enter into the case, we have a clear illustration of gradual and marked changes in the spiral angle itself. That is to say of the ratio of growth corresponding to increase of vectorial angle. We have seen from some of Naumann's and Grabau's measurements that such a tendency to vary, such an acceleration or retardation, may be detected even in ammonites which present nothing abnormal to the eye. But let us suppose that the spiral angle increases somewhat rapidly, we shall then get a spiral with gradually narrowing whorls, and this condition is characteristic. Figure 281. An ammonitoid shell. Macroscophites, to shew change of curvature. Of echotrosts, a subgenus of ammonites. If on the other hand, the angle alpha gradually diminishes, and even falls away to zero, we shall have the spiral curve opening out, as it does in scaphites, ancyloceras and litchuites. Until the spiral coil is replaced by a spiral curve so gentle as to seem all but straight. Lastly, there are a few cases, such as Bellerophon expansus and some goniotites, where the outer spiral does not perceptibly change, but the whorls become more embracing, or the whole shell more involute. Here it is the angle of retardation, the ratio of growth between the outer and inner parts of the whorl, which undergoes a gradual change. In order to understand the relation of a close-coiled shell to one of its straighter congeners, to compare, for example, an ammonite with an orthoceras, it is necessary to estimate the length of the right cone which has, so to speak, been coiled up into the spiral shell. Our problem then is, to find the length of a plane logarithmic spiral, in terms of the radius and the constant angle alpha. In the annex diagram, if OP be a radius vector, OQ a line of reference perpendicular to OP, and PQ a tangent to the curve, PQ, or SEC alpha, is equal in length to the spiral arc OP. And this is practically obvious, for PPPR equals DSDR equals SEC alpha, and therefore SEC alpha equals SR, or the ratio of arc to radius vector. Figure 282. Accordingly, the ratio of L, the total length, to R, the radius vector up to which the total length is to be measured, is expressed by a simple table of secants. As follows. Alpha. LR. 5 degrees. 1004. 10. 1015. 20. 1064. 30. 1165. 40. 1305. 50. 156. 60. 20. 70. 29. 75. 39. 80. 58. 85. 11.5. 86. 14.3. 87. 19.1. 88. 28.7. 89. 57.3. 89 degrees 10. 68.8. 20. 85.9. 30. 114.6. 40. 171-9. 50. 343-8. 55. 687-5. 59. 3437-7. 90. Infinite. Putting the same table inversely, so as to shew the total length in whole numbers, in terms of the radius. We have as follows. Total length. In terms of the radius. Constant angle. 2. 60 degrees. 3. 70-31. 4. 75-32. 5. 78-28. 10. 84-16. 20. 87-8. 30. 88-6. 40. 88-34. 50. 88-51. 100. 89-26. 1000. 89-56-36. 10. 000. 89-59-30. Accordingly, we see that, 1. When the constant angle of the spiral is small, the spiral itself is scarcely distinguishable from a straight line, and its length is but very little greater than that of its own radius vector. This remains pretty much the case for a considerable increase of angle, say from 0 degrees to 20 degrees or more. 2. For a very considerably greater increase of the constant angle, say to 50 degrees or more, the shell would only have the appearance of a gentle curve. 3. The characteristic close coils of the nautilus or ammonite would be typically represented only when the constant angle lies within a few degrees on either side of about 80 degrees. The coiled-up spiral of a nautilus, with a constant angle of about 80 degrees, is about 6 times the length of its radius vector, or rather more than 3 times its own diameter. While that of an ammonite, with a constant angle of, say, from 85 degrees to 88 degrees, is from about 6 to 15 times as long as its own diameter. And, 4, as we approach an angle of 90 degrees, at which point the spiral vanishes in a circle, the length of the coil increases with enormous rapidity. Our spiral would soon assume the appearance of the close coils of a nummulite, and the successive increments of breadth in the successive whorls would become inappreciable to the eye. The logarithmic spiral of high constant angle would, as we have already seen, tend to become indistinguishable, without the most careful measurement, from an Archimedean spiral. And it is obvious, moreover, that our ordinary methods of determining the constant angle of the spiral would not in these cases be accurate enough to enable us to measure the length of the coil. We should have to devise a new method, based on the measurement of radii or diameters over a large number of whorls. The geometrical form of the shell involves many other beautiful properties, of great interest to the mathematician, but which it is not possible to reduce to such simple expressions as we have been content to use. For instance, we may obtain an equation which shall express completely the surface of any shell, in terms of polar or of rectangular coordinates, as has been done by Moseley and by Blake, or in Hamiltonian vector notation. It is likewise possible, though of little interest to the naturalist, to determine the area of a conchoidal surface, or the volume of a conchoidal solid, and to find the center of gravity of either surface or solid. And Blake has further shown, with considerable elaboration, how we may deal with the symmetrical distortion, due to pressure, which fossil shells are often found to have undergone. And how we may reconstitute by calculation their original undistorted form, a problem which, were the available methods only a little easier, would be very helpful to the paleontologist. For, as Blake himself has shown, it is easy to mistake a symmetrically distorted specimen of, for instance, an ammonite, for a new and distinct species of the same genus. But it is evident that to deal fully with the mathematical problems contained in, or suggested by, the spiral shell, would require a whole treatise, rather than a single chapter of this elementary book. Let us then, leaving mathematics aside, attempt to summarize, and perhaps to extend, what has been said about the general possibilities of form in this class of organisms. The univalve shell, a summary. The surface of any shell, whether discoid or turbinate, may be imagined to be generated by the revolution about a fixed axis of a closed curve, which, remaining always geometrically similar to itself, increases continually its dimensions, and since the rate of growth of the generating curve and its velocity of rotation follow the same law, the curve traced in space by corresponding points in the generating curve is, in all cases, a logarithmic spiral. In discoid shells, the generating figure revolves in a plane perpendicular to the axis, as in Nautilus, the Argonaut and the Ammonite. In turbinate shells, it slides continually along the axis of revolution, and the curve in space generated by any given point partakes, therefore, of the character of a helix, as well as of a logarithmic spiral. It may be strictly entitled a helicospiral. Such turbinate or helicospiral shells include the snail, the periwinkle, and all the common typical gastropods. The generating figure, as represented by the mouth of the shell, is sometimes a plane curve, of simple form. In other and more numerous cases, it becomes more complicated in form and its boundaries do not lie in one plane, but in such cases as these we. Figure 283. Section of a spiral, or turbinate, univalve, Triton corrugatus, lamb, from Woodward. May replace it by its trace, on a plane at some definite angle to the direction of growth, for instance by its form as it appears in a section through the axis of the helicoid shell. The generating curve is of very various shapes. It is circular in scalaria or cyclostoma, and in spirula, it may be considered as a segment of a circle in Natica or in Planorbis. It is approximately triangular in Conus, and rhomboidal in Solarium or Potamides. It is very commonly more or less elliptical, the long axis of the ellipse being parallel to the axis of the shell in Oliva and Cyprea, all but perpendicular to it in many trochee, and oblique to it in many well-marked cases, such as Stomatella, Lamellaria, Sigaritas haliatoides, Fig, and Haliotis. In Nautilus pompilius it is approximately a semi-ellipse, and in N. umbilicatus rather more than a semi-ellipse, the long axis lying in both cases perpendicular to the axis of the shell. Its form is seldom open to easy mathematical expression, save when it is an actual circle or ellipse. But an exception to this rule may be found in certain ammonites, forming the group Chordati, where, as Blake points out, the curve is very nearly represented by a cardioid, whose equation is r equals a, 1 plus cos theta. The generating curve may grow slowly or quickly, its growth factor is very slow in Dentalium or Turritella, very rapid in Nerita, or Pileopsis, or Haliotis or the limpet. It may contain the axis in its plane, as in Nautilus. It may be parallel to the axis, as in the majority of gastropods, or it may be inclined to the axis, as it is in a very marked degree in Haliotis. In fact, in Haliotis the generating curve is so oblique to the axis of the shell that the latter appears to grow by additions to one margin only, cf. Fig, as in the case of the opercula of Turbo and Nerita referred to on p. And this is what Moseley supposed it to do. Figure 284. A. Lamellaria. Perspicua, b. Sigaritas haliatoides. After Woodward. The general appearance of the entire shell is determined, apart from the form of its generating curve, by the magnitude of three angles. And these in turn are determined, as has been sufficiently explained, by the ratios of certain velocities of growth. These angles are, 1, the constant angle of the logarithmic spiral, alpha. 2, in turbinate shells, the enveloping angle of the cone, or, taking half that angle, the angle, theta, which a tangent to the whorls makes with the axis of the shell. And, 3, an angle called the angle of retardation, beta, which expresses the retardation in growth of the inner as compared with the outer part of each whorl, and therefore measures the extent to which one whorl overlaps, or the extent to which it is separated from another. The spiral angle, alpha, is very small in a limpet, where it is usually taken as equals 0 degree, but it is evidently of a significant amount, though obscured by the shortness of the tubular shell. In Dentalium it is still small, but sufficient to give the appearance of a regular curve. It amounts here probably to about 30 degrees to 40 degrees. In Haliotis it is from about 70 degrees to 75 degrees, in Nautilus about 80 degrees. And it lies between 80 degrees and 85 degrees, or even more, in the majority of gastropods. The case of Fissurella is curious. Here we have, apparently, a conical shell with no trace of spiral curvature, or, in other words, with a spiral angle which approximates to 0 degree. But in the minute embryonic shell, as in that of the limpet, a spiral convolution is distinctly to be seen. It would seem, then, that what we have to do with here is an unusually large growth factor in the generating curve, which causes the shell to dilate into a cone of very wide angle, the apical portion of which has become lost or absorbed, and the remaining part of which is too short to show clearly its intrinsic curvature. In the closely allied emarginula, there is likewise a well-marked spiral in the embryo, which however is still manifested in the curvature of the adult, nearly conical, shell. In both cases we have to do with a very wide-angled cone, and with a high retardation factor for its inner, or posterior, border. The series is continued, from the apparently simple cone to the complete spiral, through such forms as calyptria. The angle alpha, as we have seen, is not always, nor rigorously, a constant angle. In some ammonites it may increase with age, the whorls becoming closer and closer. In others it may decrease rapidly, and even fall to 0, the coiled shell then straightening out, as in litchuites and similar forms. It diminishes somewhat, also, in many orthocerata, which are slightly curved in youth, but straight in age. It tends to increase notably in some common land shells, the pupae and bulimi, and it decreases in succinia. Directly related to the angle alpha is the ratio which subsists between the breadths of successive whorls. The following table gives a few illustrations of this ratio in particular cases, in addition to those which we have already studied. Ratio of breadth of consecutive whorls. Pointed turbinates. Obtuse turbinates and discoids. Telescopium fuscum. 1:14. Conus virgo. 1:25. Acus subulatus. 1:16. Conus literatus. 1:40. Turritella terebellata. 1:18. Conus becellina. 1:43. Turritella imbricata. 1:20. Helix nemiralis. 1:50. Cerithium paluster. 1:22. Solarium perspectivum. 1:50. Turritella duplicata. 1:23. Solarium trochleaire. 1:62. Melanopsis terebralis. 1:23. Solarium magnificum. 1:75. Cerithium nodulosum. 1:24. Natica aperta. 2:00. Turritella carinata. 1:25. Euomphalus pentangulatus. 2:00. Acus crenulatus. 1:25. Planorbis corneas. 2:00. Terebra maculata, Fig. 1:25. Solaropsis peliserpentis. 2:00. Cerithium lignitarum. 1:26. Dolium zonatum. 2:10. Acus dimidiatus. 1:28. Natica glossina. 3:00. Cerithium sulcatum. 1:32. Nautilus pompilius. 3:00. Fusus longissimus. 1:34. Haliotis excavatus. 4:20. Pleurotomeria conoidea. 1:34. Haliotis parvus. 6:00. Truchus niloticus, Fig. 1:41. Delphinula atrata. 6:00. Mitra episcopalis. 1:43. Haliotis rugoso placata. 9:30. Fusus antiquus. 150. Haliotis viridis. 1000. Scalaria preciosa. 156. Fusus coloceus. 171. Phasianella bouloides. 180. Helicostilla. Polychroa. 200. Those marked from Naumann. The rest from McAllister. In the case of turbinate shells, we require to take into account the angle theta, in order to determine the spiral angle alpha from the ratio of the breadths of consecutive whorls, for the short table given on p. Is only applicable to discoid shells, in which the angle theta is an angle of 90 degrees. Our formula, as mentioned on p, now becomes r equals epsilon 2 pi sin theta cot alpha. For this formula I have worked out the following table. Table showing values of the spiral angle alpha, corresponding to certain ratios of breadth of successive whorls of the shell, for various values of the apical semi-angle. Theta. Ratio. R1. Theta equals 5 degrees. 10 degrees. 15 degrees. 20 degrees. 30 degrees. 40 degrees. 50 degrees. 60 degrees. 70 degrees. 80 degrees. 90 degrees. 1. 80 degrees 8. 85 degrees 0. 86 degrees 44. 87 degrees 28. 88 degrees 16. 88 degrees 39. 88 degrees 52. 89 degrees 0. 89 degrees 4. 89 degrees 7. 89 degrees 8. 125. 67 51. 78 27. 82 11. 84 5. 85 56. 86 50. 87 21. 87 39. 87 50. 87 56. 87 58. 15. 53 30. 69 37. 76 0. 79 21. 82 39. 84 16. 85 13. 85 44. 86 4. 86 15. 86 18. 20. 38 20. 57 35. 66 55. 73 11. 77 34. 80 16. 81 52. 82 45. 83 18. 83 37. 83 42. 2 5. 30 53. 50 0. 60 35. 67 0. 73 45. 77 13. 79 19. 80 26. 81 11. 81 35. 81 42. 3 0. 26 32. 44 50. 56 0. 63 0. 70 45. 74 45. 77 17. 78 35. 79 28. 79 56. 85. 3 5. 23 37. 41 5. 52 25. 59 50. 68 15. 72 45. 75 35. 77 2. 78 1. 78 33. 78 43. 40. 21 35. 38 10. 49 35. 5715. 6610. 713. 749. 7542. 7647. 7722. 7734. 45. 20. 360. 4715. 555. 6425. 6935. 7254. 7433. 7543. 7620. 7635. 50. 1845. 3410. 4520. 5315. 6255. 6815. 7148. 7331. 7445. 7525. 7538. 10. 1325. 2520. 3515. 435. 5345. 6020. 6457. 674. 6842. 6935. 6953. 20. 1025. 20. 2830. 3545. 4625. 5325. 5852. 6110. 636. 6410. 6431. 50. 80. 1535. 2235. 2850. 3845. 4555. 521. 5418. 5628. 5742. 586. 100. 650. 1320. 1930. 255. 3420. 4115. 4735. 4945. 523. 5320. 5346. From this table, by interpolation, we may easily fill in the approximate values of alpha, as soon as we have determined the apical angle theta and measured the ratio r. As follows. R. Theta. Alpha. Turritella sp. 1, 12. 7 degrees. 81 degrees. Cerithium nodulosum. 1, 24. 15. 82. Conus Virgo. 1, 25. 70. 88. Mitra episcopalis. 1, 43. 16. 78. Scalaria preciosa. 1, 56. 26. 81. Phasianella bouloides. 1, 80. 26. 80. Solarium perspectivum. 1, 50. 53. 85. Natica aperta. 2, 00. 70. 83. Planorbis corneus. 2, 00. 90. 84. Euomphalus pentangulatus. 2, 00. 90. 84. We see from this that shells so different in appearance as Cerithium, Solarium, Natica and Planorbis differ very little indeed in the magnitude of the spiral angle alpha, that is to say in the relative velocities of radial and tangential growth. It is upon the angle theta. Figure 285. Terebra maculata, L. That the difference in their form mainly depends, that is to say the amount of longitudinal shearing, or displacement parallel to the axis of the shell. The enveloping angle, or rather semi-angle, theta, of the cone may be taken as 90 degrees in the discoid shells, such as Nautilus and Planorbis. It is still a large angle, of 70 degrees or 75 degrees, in Conus or in Simba, somewhat less in Cassis, Harpa, Dolium or Natica. It is about 50 degrees to 55 degrees in the various species of Solarium, about 35 degrees in the typical trochee, such as T. niloticus or T. ziziphonus, and about 25 degrees or 26 degrees in Scalaria preciosa and Phasianella bouloides. It becomes a very acute angle, of 15 degrees, 10 degrees, or even less, in Ultima, Turritella or Cerithium. The costly Conus gloriameris, one of the great treasures of the conchologist, differs from its congeners in no important particular save in the somewhat produced spire, that is to say in the comparatively low value of the angle theta. A variation with advancing age of theta is common, but, as Blake points out, it is often not to be distinguished or disentangled from an alteration of alpha. Whether alone, or combined with a change in alpha, we find it in all those many gastropods whose whorls cannot all be touched by the same enveloping cone, and whose spire is accordingly described as concave or convex. The former condition, as we have it in Cerithium, and in the cusp-like spire of Cassis. Figure 286. Trachus niloticus. L. Dolium and some cones, is much the commoner of the two. And such tendency to decrease may lead to theta becoming a negative angle. In which case we have a depressed spire, as in the Cyprii. When we find a reversed shell, a whelk or a snail for instance whose spire winds to the left instead of to the right, we may describe it mathematically by the simple statement that the angle theta has changed sign. In the genus Ampullaria, or apple snails, inhabiting tropical or subtropical rivers, we have a remarkable condition. For in certain species the spiral turns to the right, in others to the left, and in others again we have a flattened, discoid shell. And furthermore we have numerous intermediate stages, on either side, shewing right and left-handed spirals of varying degrees of acuteness. In this case, the angle theta may be said to vary, within the limits of a genus, from somewhere about 35 degrees to somewhere about 125 degrees. The angle of retardation, beta, is very small in Dentalium and Patella, it is very large in Haliotis. It becomes infinite in Argonauta and in Cypria. Connected with the angle of retardation are the various possibilities of contact or separation, in various degrees, between adjacent whorls in the discoid, and between both adjacent and opposite whorls in the turbinate shell. But with these phenomena we have already dealt sufficiently. Of bivalve shells. Hitherto we have dealt only with univalve shells, and it is in these that all the mathematical problems connected with the spiral, or helicospiral, are best illustrated. But the case of the bivalve shell, of lamellibranchs or of brachiopods, presents no essential difference, save only that we have here to do with two conjugate spirals, whose two axes have a definite relation to one another. And some freedom of rotatory movement relatively to one another. The generating curve is particularly well seen in the bivalve, where it simply constitutes what we call the outline of the shell. It is for the most part a plane curve, but not always. For there are forms, such as Hippopus, Tridacna and many cockles, or Rhynchonella and Spirophora among the brachiopods, in which the edges of the two valves interlock, and others, such as Pholos, Maya, etc., where in part they fail to meet. In such cases as these the generating curves are conjugate, having a similar relation, but of opposite sign, to a median plane of reference. A great variety of form is exhibited by these generating curves among the bivalves. In a good many cases the curve is approximately circular, as in Anomia, Cyclas, Artemis, Isocardia, it is nearly semicircular in Argiope. It is approximately elliptical in Ortiz and in Anodon, it may be called semi-elliptical in Spirophore. It is a nearly rectilinear triangle in Lithocardium, and a curvilinear triangle in Mactra. Many apparently diverse but more or less related forms may be shown to be deformations of a common type, by a simple application of the mathematical theory of transformations, which we shall have to study in a later chapter. In such a series as is furnished, for instance, by Gervillia, Perna, Avicula, Modiala, Mytilus, etc., simple shear accounts for most, if not all, of the apparent differences. Upon the surface of the bivalve shell we usually see with great clearness the lines of growth, which represent the successive margins of the shell, or in other words the successive positions assumed during growth by the growing generating curve. And we have a good illustration, accordingly, of how it is characteristic of the generating curve that it should constantly increase, while never altering its geometric similarity. Underlying these lines of growth, which are so characteristic of a molluscan shell, and of not a few other organic formations, there is, then, a law of growth which we may attempt to inquire into and which may be illustrated in various ways. The simplest cases are those in which we can study the lines of growth on a more or less flattened shell, such as the one valve of an oyster, a pecten or a telina, or some such bivalve mollusk. Here around an origin, the so-called umbo of the shell, we have a series of curves, sometimes nearly circular, sometimes elliptical, and often asymmetrical. And such curves are obviously not concentric, though we are often apt to call them so, but are always coaxial. This manner of arrangement may be illustrated by various analogies. We might for instance compare it to a series of waves, radiating outwards from a point, through a medium which offered a resistance increasing, with the angle of divergence, according to some simple law. We may find another, and perhaps a simpler illustration as follows. Figure 287. In a very simple and beautiful theorem, Galileo shewed that, if we imagine a number of inclined planes, or gutters, sloping downwards, in a vertical plane, at various angles from a common starting point, and if we imagine a number of balls rolling each down its own gutter under the influence of gravity, and without hindrance from friction, then, at any given instant, the locus of all these moving bodies is a circle passing through the point of origin. For the acceleration along any one of the sloping paths, for instance AB, Fig, is such that AB equals 1/2 g cos theta t2 equals 1/2 g ABAC t2. Therefore, t2 equals 2g AC. That is to say, all the balls reach the circumference of the circle at the same moment as the ball which drops vertically from A to C. Where, then, as often happens, the generating curve of the shell is approximately a circle passing through the point of origin, we may consider the acceleration of growth along various radiants to be governed by a simple mathematical law, closely akin to that simple law of acceleration which governs the movements of a falling body. And, mutatis mutandis, a similar definite law underlies the cases where the generating curve is continually elliptical, or where it assumes some more complex, but still regular and constant form. It is easy to extend the proposition to the particular case where the lines of growth may be considered elliptical. In such a case we have x2a2 plus y2b2 equals 1, where a and b are the major and minor axes of the ellipse. Or, changing the origin to the vertex of the figure, x2a2 2xa plus y2b2 equals 0, giving xa 2a2 plus y2b2 equals 1. Then, transferring to polar coordinates, where our cosine theta equals x, our sine theta equals y, we have our cosine 2 theta, a 2 cosine theta, a plus, our sine theta, b2, equals 0. Which is equivalent to r equals 2a b2 cosine theta, b2 cosine 2 theta plus a 2 sine 2 theta. Or, eliminating the sine function, r equals 2a b2 cos theta, b2 a 2, cos 2 theta plus a 2. Obviously, in the case when a equals b, this gives us the circular system which we have already considered. For other values, or ratios, of a and b, and for all values of theta, we can easily construct a table, of which the following is a sample. Chords of an ellipse, whose major and minor axes, A, B, are in certain given ratios. Theta AB equals 1 3, 1 2, 2 3, 1 1, 3 2, 2 1, 3 1, 0 degrees, 1 0, 1 0, 1 0, 1 0, 1 0, 1 0, 1 0, 1 0 1, 1 0 1, 1 0 0 2, 985, 948, 902, 793, 105, 103, 1005, 940, 820, 695, 485, 115, 1065, 1005, 866, 666, 495, 289, 121, 111, 995, 766, 505, 342, 178, 134, 145, 952, 643, 372, 232, 113, 150, 142, 857, 500, 258, 152, 071, 159, 1015, 670, 342, 163, 092, 042, 1235, 635, 375, 174, 078, 045, 020, 0 0, 0 0, 0 0, 0 0, 0 0, 0 0, 0 0. Fig. 288. The coaxial ellipses which we then draw, from the values given in the table, are such as are shown in Fig, for the ratio AB equals 3 1, and in Fig, for the ratio AB equals 1 2. These are fair approximations to the actual outlines, and to the actual arrangement of the lines of growth, in such forms as Solicurtus or Coltellus, and in Tellina or Cimobia. It is not difficult to introduce a constant into our equation to meet the case of a shell which is somewhat unsymmetrical on either side of the median axis. It is a somewhat more troublesome matter, however, to bring these configurations into relation with a law of growth, as was so easily done in the case of the circular figure, in other words. To formulate a law of acceleration according to which points starting from the origin O, and moving along radial lines, would all lie, at any future epoch, on an ellipse passing through O. And this calculation we need not enter into. Figure 289. All that we are immediately concerned with is the simple fact that where a velocity, such as our rate of growth, varies with its direction, varies that is to say as a function of the angular divergence from a certain axis, then, in a certain simple case, we get lines of growth laid down as a system of coaxial circles, and, when the function is a more complex one, as a system of ellipses or of other more complicated coaxial figures. Which figures may or may not be symmetrical on either side of the axis. Among our bivalve mollusca we shall find the lines of growth to be approximately circular in, for instance, Anomia, in Lima, e.g. L. Subauriculata, we have a system of nearly symmetrical ellipses with the vertical axis about twice the transverse. In Solon pellucidus, we have again a system of lines of growth which are not far from being symmetrical ellipses, in which however the transverse is between 3 and 4 times as great as the vertical axis. In the great majority of cases, we have a similar phenomenon with the further complication of slight, but occasionally very considerable, lateral asymmetry. In certain little crustacea, of the genus Asteria, the carapace takes the form of a bivalve shell, closely simulating that of a lamellibranchiate mollusk, and bearing lines of growth in all respects analogous to or even identical with those of the latter. The explanation is very curious and interesting. In ordinary crustacea the carapace, like the rest of the chitinized and calcified integument, is shed off in successive molts, and is restored again as a whole. But in Asteria, and one or two other small crustacea, the molt is incomplete, the old carapace is retained, and the new, growing up underneath it, adheres to it like a lining, and projects beyond its edge, so that in course of time the margins of successive old carapaces appear as lines of growth upon the surface of the shell. In this mode of formation, then, but not in the usual one, we obtain a structure which is partly old and partly new, and whose successive increments are all similarly situated, and enlarged in a continued progression. We have, in short, all the conditions appropriate and necessary for the development of a logarithmic spiral. And this logarithmic spiral, though it is one of small angle, gives its own character to the structure, and causes the little carapace to partake of the characteristic conformation of the molluscan shell. The essential simplicity, as well as the great regularity of the curves of growth, which result in the familiar configurations of our bivalve shells, sufficiently explain, in a general way, the ease with which they may be imitated. As for instance in the so-called artificial shells, which Kappers has produced from the conchoidal form and lamination of lumps of melted and quickly cooled paraffin. In the above account of the mathematical form of the bivalve shell, we have supposed, for simplicity's sake, that the pole or origin of the system is at a point where all the successive curves touch one another. But such an arrangement is neither theoretically probable, nor is it actually the case, for it would mean that in a certain direction growth fell, not merely to a minimum, but to zero. As a matter of fact, the center of the system, the umbo of the conchologists, lies not at the edge of the system, but very near to it. In other words, there is a certain amount of growth all round. But to take account of this condition would involve more troublesome mathematics, and it is obvious that the foregoing illustrations are a sufficiently near approximation to the actual case. Among the bivalves the spiral angle, alpha, is very small in the flattened shells, such as orthis, lingula, or anomia. It is larger, as a rule, in the lamellibranchs than in the brachiopods, but in the latter it is of considerable magnitude among the pentameri. Among the lamellibranchs it is largest in such forms as Isocardia and Diceras, and in the very curious genus Caprinella. In all of these last-named genera its magnitude leads to the production of a spiral shell of several whorls, precisely as in the univalves. The angle is usually equal, but of opposite sign, in the two valves of the lamellibranch, and usually of opposite sign but unequal in the two valves of the brachiopod. It is very unequal in many Ostriidae, and especially in such forms as Graphia, or in Caprinella, which is a kind of exaggerated Graphia. Occasionally it is of the same sign in both valves, that is to say, both valves curve the same way, as we see sometimes in anomia, and much better in Productus or Strophomina. Figure 290. Caprinella adversa. After Woodward. Figure 291. Section of Productus. Strophomina, sp. from Woods. Owing to the large growth factor of the generating curve, and the comparatively small angle of the spiral, the whole shell seldom assumes a spiral form so conspicuous as to manifest in a typical way the helical twist or shear which is so conspicuous in the majority of univalves. Or to let us measure or estimate the magnitude of the apical angle, theta, of the enveloping cone. This however we can do in forms like Isocardia and Diceras, while in Caprinella we see that the whorls lie in a plane perpendicular to the axis, forming a discoidal spire. As in the latter shell, so also universally among the brachiopods, there is no lateral asymmetry in the plane of the generating curve such as to lead to the development of a helix. But in the majority of the lamellibranchiata it is obvious, from the obliquity of the lines of growth, that the angle theta is significant in amount. The so-called spiral arms of Spirifer and many other brachiopods are not difficult to explain. They begin as a single structure, in the form. Figure 292. Skeletal loop of Terebratula. From Woods. Of a loop of shelly substance, attached to the dorsal valve of the shell, in the neighborhood of the hinge. This loop has a curvature of its own, similar to but not necessarily identical with that of the valve to which it is attached. And this curvature will tend to be developed, by continuous and symmetrical growth, into a fully formed logarithmic spiral, so far as it is permitted to do so under the constraint of the shell in which it is contained. In various terebratulae we see the spiral growth of the loop, more or less flattened and distorted by the restraining pressure of the ventral valve. In a number of cases the loop remains small, but gives off two nearly parallel branches or offshoots, which continue to grow. And these, starting with just such a slight curvature as the loop itself possessed, grow on and on till they may form close-wound spirals. Always provided that the spiral angle of the curve is such that the resulting spire can be freely contained within the cavity of the shell. Owing to the bilateral symmetry of the whole system, the case will be rare, and unlikely to occur, in which each separate arm will coil strictly in a plane, so as to constitute a discoid spiral. For the original direction of each of the two branches, parallel to the valve, or nearly so, and outwards from the middle line, will tend to constitute a curve of double curvature, and so, on further growth, to develop into a helicoid. This is what actually occurs, in the great majority of cases. But the curvature may be such that the helicoid grows outwards from the middle line, or inwards towards the middle line, a very slight difference in the initial curvature being sufficient to direct the spire the one way or the other. The middle course of an undeviating discoid spire will be rare, from the usual lack of any obvious controlling force to prevent its deviation. The cases in which the helicoid spires point towards, or point away from, the middle line are ascribed, in zoological classification, to particular families of brachiopods, the former condition defining. Figure 293. Spiral arms of Spirifer. From Woods. Figure 294. Inwardly directed spiral arms of Atripa. Or helping to define, the Atripody and the latter the Spiriferidae and Aetheridae. It is obvious that the incipient curvature of the arms, and consequently the form and direction of the spirals, will be influenced by the surrounding pressures, and these in turn by the general shape of the shell. We shall expect, accordingly, to find the long outwardly directed spirals associated with shells which are transversely elongated, as Spirifer is, while the more rounded Atripas will tend to the opposite condition. In a few cases, as in Certina or Reticularia, where the shell is comparatively narrow but long, and where the uncoiled basal support of the arms is long also, the spiral coils into which the latter grow are turned backwards, in the direction where there is room for them. And in the few cases where the shell is very considerably flattened, the spirals, if they find room to grow at all, will be constrained to do so in a discoid or nearly discoid fashion. And this is actually the case in such flattened forms as Conincina or Thesidium. The shells of pteropods. While mathematically speaking we are entitled to look upon the bivalve shell of the lamellibranch as consisting of two distinct elements, each comparable to the entire shell of the univalve, we have no biological grounds for such a statement. For the shell arises from a single embryonic origin, and afterwards becomes split into portions which constitute the two separate valves. We can perhaps throw some indirect light upon this phenomenon, and upon several other phenomena connected with shell growth, by a consideration of the simple conical or tubular shells of the pteropods. The shells of the latter are in few cases suitable for simple mathematical investigation, but nevertheless they are of very considerable interest in connection with our general problem. Figure 295. Pteropod shells. 1. Cuviarina columella. 2. Cleodora Chirurgiae. 3. C. Pygmea. After. Boas. The morphology of the pteropods is by no means well understood, and in speaking of them I will assume that there are still grounds for believing, in spite of Boas and Pelsinier's arguments, that they are directly related to, or may at least be directly compared with, the cephalopoda. The simplest shells among the pteropods have the form of a tube, more or less cylindrical, Coviarina, more often conical, Cresius, Clio, and this tubular shell, as we have already had occasion to remark, on p. frequently tends, when it is very small and delicate, to assume the character of an unduloid. In such a case it is more than likely that the tiny shell, or that portion of it which constitutes the unduloid, has not grown by successive increments or rings of growth, but has developed as a whole. A thickened rib is often, perhaps generally, present on the dorsal side of the little conical shell. In a few cases, Limacina, Paraclus, the tube becomes spirally coiled, in a normal logarithmic spiral or helicospiral. Figure 296. Diagrammatic transverse sections. Or outlines of the mouth, in certain pteropod shells. A. B. Cleodora australis, C. C. pyramidalis, D. C. Balantium, E. C. cuspidata. After Boas. Figure 297. Shells of thecosome pteropods. After Boas. 1. Cleodora cuspidata, 2. Hyalea. Trispinosa, 3. H. globulosa, 4. H. uncinata, 5. H. inflexa. In certain cases, e.g. Cleodora, Hyalea, the tube or cone is curiously modified. In the first place, its cross-section, originally circular or nearly so, becomes flattened or compressed dorsoventrally, and the angle, or rather edge, where dorsal and ventral walls meet, becomes more and more drawn out into a ridge or keel. Along the free margin, both of the dorsal and the ventral portion of the shell, growth proceeds with a regularly varying velocity, so that these margins, or lips, of the shell become regularly curved or markedly sinuous. At the same time, growth in a transverse direction proceeds with an acceleration which manifests itself in a curvature of the sides, replacing the straight borders of the original cone. In other words, the cross-section of the cone, or what we have been calling the generating curve, increases its dimensions more rapidly than its distance from the pole. Figure 298. Cleodora cuspidata. In the above figures, for instance in that of Cleodora cuspidata, the markings of the shell which represent the successive edges of the lip at former stages of growth furnish us at once with a graph of the varying velocities of growth as measured, radially, from the apex. We can reveal more clearly the nature of these variations in the following way, which is simply tantamount to converting our radial into rectangular coordinates. Neglecting curvature, if any, of the sides and treating the shell, for simplicity's sake, as a right cone, we lay off equal angles from the apex O, along the radii OA, OB, etc. If we then plot, as vertical equidistant ordinates, the magnitudes OA, OB, OY, and again onto OA, we obtain a diagram such as the following, Fig. By help of which we not only see more clearly the way in which the growth rate varies from point to point, but we also recognize much better than before, the similar nature of the law which governs this variation in the different species. Fig. 299, curves obtained by transforming radial ordinates, as in Fig. into vertical equidistant ordinates. 1. Hyalea trispinosa, 2. Cleodora cuspidata. Furthermore, the young shell having become differentiated into a dorsal and a ventral part, marked off from one another by a lateral edge or keel, and the inequality of growth being such as to cause each portion. Figure 300. Development of the shell of Hyalea, Cavalinia, Tridentata, Forskull, the earlier stages being the pluripus longifilis of Troschel. After Tesch. To increase most rapidly in the median line, it follows that the entire shell will appear to have been split into a dorsal and a ventral plate, both connected with, and projecting from, what remains of the original undivided cone. Putting the same thing in other words, we may say that the generating figure, which lay at first in a plane perpendicular to the axis of the cone, has now, by unequal growth, been sharply bent or folded, so as to lie approximately in two planes, parallel to the anterior and posterior faces of the cone. We have only to imagine the apical connecting portion to be further reduced, and finally to disappear or rupture, and we should have a bivalve shell developed out of the original simple cone. In its outer and growing portion, the shell of our pteropod now consists of two parts which, though still connected together at the apex, may be treated as growing practically independently. The shell is no longer a simple tube, or simple cone, in which regular inequalities of growth will lead to the development of a spiral. And this for the simple reason that we have now two opposite maxima of growth, instead of a maximum on the one side and a minimum on the other side of our tubular shell. As a matter of fact, the dorsal and the ventral plate tend to curve in opposite directions, towards the middle line, the dorsal curving ventrally and the ventral curving towards the dorsal side. In the case of the lamellibranch or the brachiopod, it is quite possible for both valves to grow into more or less pronounced spirals, for the simple reason that they are hinged upon one another. And each growing edge, instead of being brought to a standstill by the growth of its opposite neighbor, is free to move out of the way, by the rotation about the hinge of the plane in which it lies. But where, as in the pteropod, there is no such hinge, the dorsal and ventral halves of the shell, or dorsal and ventral valves, if we may call them so, if they curve towards one another, as they do in a cockle, would soon interfere with one another's progress, and the development of a pair of conjugate spirals would become impossible. Nevertheless, there is obviously, in both dorsal and ventral valve, a tendency to the development of a spiral curve, that of the ventral valve being more marked than that of the larger and overlapping dorsal one. Exactly as in the two unequal valves of Pterobrachula. In many cases, e.g. Cleodora cuspidata, the dorsal valve or plate, strengthened and stiffened by its midrib, is nearly straight, while the curvature of the other is well displayed. But the case will be materially altered and simplified if growth be arrested or retarded in either half of the shell. Suppose for instance that the dorsal valve grew so slowly that after a while, in comparison with the other, we might speak of it as being absent altogether, or suppose that it merely became so reduced in relative size as to form no impediment to the continued growth of the ventral one. The latter would continue to grow in the direction of its natural curvature, and would end by forming a complete and coiled logarithmic spiral. It would be precisely analogous to the spiral shell of Nautilus, and, in regard to its Figure 301. Pteropod shells, from the side. 1. Cleodora cuspidata, 2. Hyalea longirostrus, 3. H. trispinosa. After boas. Ventral position, concave towards the dorsal side, it would even deserve to be called directly homologous with it. Suppose, on the other hand, that the ventral valve were to be greatly reduced, and even to disappear, the dorsal valve would then pursue its unopposed growth. And, were it to be markedly curved, it would come to form a logarithmic spiral, concave towards the ventral side, as is the case in the shell of Spirula. Were the dorsal valve to be destitute of any marked curvature, or in other words, to have but a low spiral angle, it would form a simple plate, as in the shells of Sepia or Loligo. Indeed, in the shells of these latter, and especially in that of Sepia, we seem to recognize a manifest resemblance to the dorsal plate of the pteropod shell, as we have it, e.g., in Cleodora or Hyalea. The little rostrum of Sepia is but the apex of the primitive cone, and the rounded anterior extremity has grown according to a law precisely such as that which has produced the curved margin of the dorsal valve in the pteropod. The ventral portion of the original cone is nearly, but not wholly, wanting. It is represented by the so-called posterior wall of the siphuncular space. In many decapod cuttlefishes also, e.g. totorodes, ilex, etc. We still see at the posterior end of the pen, a vestige of the primitive cone, whose dorsal margin only has continued to grow, and the same phenomenon, on an exaggerated scale, is represented in the belemnites. It is not at all impossible that we may explain on the same lines the development of the curious operculum of the ammonites. This consists of a single horny plate, anaptychus, or of a thicker, more calcified plate divided into two symmetrical halves, aptychi, often found inside the terminal chamber of the ammonite, and occasionally to be seen lying in situ as an operculum which partially closes the mouth of the shell. This structure is known to exist even in connection with the early embryonic shell. In form the anaptychus, or the pair of conjoined aptychi, shew an upper and a lower border, the latter strongly convex, the former sometimes slightly concave, sometimes slightly convex, and usually shewing a median projection or slightly developed rostrum. From this rostral border the curves of growth start, and course round parallel to, finally constituting, the convex border. It is this convex border which fits into the free margin of the mouth of the ammonite's shell, while the other is applied to and overlaps the preceding whorl of the spire. Now this relationship is precisely what we should expect, were we to imagine as our starting point a shell similar to that of Hyalea, in which however the dorsal part of the split cone had become separate from the ventral half, had remained flat, and had grown comparatively slowly, while at the same time it kept slipping forward over the growing and coiling spire into which the ventral half of the original shell develops. In short, I think there is reason to believe, or at least to suspect, that we have in the shell and aptychus of the ammonites, two portions of a once united structure, of which other cephalopods retain not both parts but only one or other, one as the ventrally situated shell of Nautilus, the other as the dorsally placed shell for example of Sepia or of Spirula. In the case of the bivalve shells of the lamellibranchs or of the brachiopods, we have to deal with a phenomenon precisely analogous to the split and flattened cone of our pteropods. Save only that the primitive cone has been split into two portions, not incompletely as in the pteropod, Hyalea, but completely, so as to form two separate valves. Though somewhat greater freedom is given to growth now that the two valves are separate and hinged, yet still the two valves oppose and hamper one another, so that in the longitudinal direction each is capable of only a moderate curvature. This curvature, as we have seen, is recognizable as a logarithmic spiral, but only now and then does the growth of the spiral continue so far as to develop successive coils, as it does in a few symmetrical forms such as Isocardia Cor. And as it does still more conspicuously in a few others, such as Graphia and Caprinella, where one of the two valves is stunted, and the growth of the other is, relatively speaking, unopposed. Of septa. Before we leave the subject of the molluscan shell, we have still another problem to deal with, in regard to the form and arrangement of the septa which divide up the tubular shell into chambers, in the nautilus, the ammonite and their allies, fig. etc. The existence of septa in a nautiloid shell may probably be accounted for as follows. We have seen that it is a property of a cone that, while growing by increments at one end only, it conserves its original shape, therefore the animal within, which, though growing by a different law, also conserves its shape, will continue to fill the shell if it actually fills it to begin with, as does a snail or other gastropod. But suppose that our mollusk fills a part only of a conical shell, as it does in the case of Nautilus. Then, unless it alter its shape, it must move upward as it grows in the growing cone, until it come to occupy a space similar in form to that which it occupied before, just, indeed, as a little ball drops far down into the cone. But a big one must stay farther up. Then, when the animal after a period of growth has moved farther up in the shell, the mantle surface continues its normal secretory activity, and that portion which had been in contact with the former septum secretes a septum anew. In short, at any given epoch, the creature is not secreting a tube and a septum by separate operations, but is secreting a shelly case about its rounded body, of which case one part appears to us as the continuation of the tube, and the other part, merging with it by indistinguishable boundaries, appears to us as the septum. The various forms assumed by the septa in spiral shells present us with a number of problems of great beauty, simple in their essence, but whose full investigation would soon lead us into mathematics of a very high order. We do not know in great detail how these septa are laid down, but the essential facts are clear. The septum begins as a very thin cuticular membrane, composed apparently of a substance called conchiolin, which is secreted by the skin, or mantle surface, of the animal. And upon this membrane nacreous matter is gradually laid down on the mantle side, that is to say between the animal's body and the cuticular membrane which has been thrown off from it. So that the membrane remains as a thin pellicle over the hinder surface of the septum, and so that, to begin with, the membranous septum is molded on the flexible and elastic surface of the animal, within which the fluids of the body must exercise a uniform, or nearly uniform pressure. Let us think, then, of the septa as they would appear in their uncalcified condition, formed of, or at least superposed upon, an elastic membrane. They must then follow the general law, applicable to all elastic membranes under uniform pressure, that the tension varies inversely as the radius of curvature, and we come back once more to our old equation of Laplace, that P equals T, 1r plus 1r. Figure 302. Moreover, since the cavity below the septum is practically closed, and is filled either with air or with water, P will be constant over the whole area of the septum. And further, we must assume, at least to begin with, that the membrane constituting the incipient septum is homogeneous or isotropic. Let us take first the case of a straight cone, of circular section, more or less like an orthoceras. And let us suppose that the septum is attached to the shell in a plane perpendicular to its axis. The septum itself must then obviously be spherical. Moreover, the extent of the spherical surface is constant, and easily determined. For obviously, in Fig. the angle LCL equals the supplement of the angle, LOL, of the cone, that is to say, the circle of contact subtends an angle at the center of the spherical surface, which is constant, and which is equal to pi 2 theta. The case is not excluded where, owing to an asymmetry of tensions, the septum meets the side walls of the cone at other than a right angle. Figure 303. As in Fig. And here, while the septa still remain portions of spheres, the geometrical construction for the position of their centers is equally easy. If, on the other hand, the attachment of the septum to the inner walls of the cone be in a plane oblique to the axis, then it is evident that the outline of the septum will be an ellipse, and its surface an ellipsoid. If the attachment of the septum be not in one plane, but form a sinuous line of contact with the cone, then the septum will be a saddle-shaped surface, of great complexity and beauty. In all cases, provided only that the membrane be isotropic, the form assumed will be precisely that of a soap bubble under similar conditions of attachment, that is to say, it will be, with the usual limitations or conditions, a surface of minimal area. If our cone be no longer straight, but curved, then the septa will be symmetrically deformed in consequence. A beautiful and interesting case is afforded us by Nautilus itself. Here the outline of the septum, referred to a plane, is approximately bounded by two elliptic curves, similar and similarly situated, whose areas are to one another in a definite ratio. Namely as A1A2 equals R1R1, R2R2 equals epsilon 4 pi cot alpha. And a similar ratio exists in ammonites and all other close-whorled spirals, in which however we cannot always make the simple assumption of elliptical form. In a median section of Nautilus, we see each septum forming a tangent to the inner and to the outer wall, just as it did in a section of the straight orthoceras. But the curvatures in the neighborhood of these 2 points of contact are not identical, for they now vary inversely as the radii, drawn from the pole of the spiral shell. The contour of the septum in this median plane is a spiral curve identical with the original logarithmic spiral. Of this it is the invert, and the fact that the original curve and its invert are both identical is one of the most beautiful properties of the logarithmic spiral. But while the outline of the septum in median section is simple and easy to determine, the curved surface of the septum in its entirety is a very complicated matter, even in Nautilus, which is one of the simplest of actual cases. For, in the first place, since the form of the septum, as seen in median section, is that of a logarithmic spiral, and as therefore its curvature is constantly altering, it follows that, in successive transverse sections, the curvature is also constantly altering. But in the case of Nautilus, there are other aspects of the phenomenon, which we can illustrate, but only in part, in the following simple manner. Let us imagine. Figure 304. Section of Nautilus, shoeing. The contour of the septa in the median plane, the septa. Being, in this plane, logarithmic spirals, of which the shell spiral is the evolute. A pack of cards, in which we have cut out of each card a similar concave arc of a logarithmic spiral, such as we actually see in the median section of the septum of a nautilus. Then, while we hold the cards together, foursquare, in the ordinary position of the pack, we have a simple, ruled surface, which in any longitudinal section has the form of a logarithmic spiral but in any transverse section is a straight horizontal line. If we shear or slide the cards upon one another, thrusting the middle cards of the pack forward in advance of the others, till the one end of the pack is a convex, and the other a concave, ellipse, the cut edges which combine to represent our septum will now form a curved surface. Fig. 305, cast of the interior of Nautilus, to shew the contours of the septa at their junction with the shell wall. Of much greater complexity. And this is part, but not by any means all, of the deformation produced as a direct consequence of the form in Nautilus of the section of the tube within which the septum has to lie. And the complex curvature of the surface will be manifested in a sinuous outline of the edge, or line of attachment of the septum to the tube, and will vary according to the configuration of the latter. In the case of Nautilus, it is easy to shew empirically, though not perhaps easy to demonstrate mathematically, that the sinuous or saddle-shaped form of the suture, or line of attachment of the septum to the tube, is such as can be precisely accounted for in this manner. It is also easy to see that, when the section of the tube, or generating curve, is more complicated in form, when it is flattened, grooved, or otherwise ornamented, the curvature of the septum and the outline of its sutural attachment will become very complicated indeed. But it will be comparatively simple in the case of the first few sutures of the young shell, laid down before any overlapping of whorls has taken place, and this comparative simplicity of the first formed sutures is a marked feature among ammonites. We have other sources of complication, besides those which are at once introduced by the sectional form of the tube. For instance, the siphuncle, or little inner tube which perforates the septa, exercises a certain amount of tension, sometimes evidently considerable, upon the latter. So that we can no longer consider each septum as an isotropic surface, under uniform pressure. And there may be other structural modifications, or inequalities, in that portion of the animal's body with which the septum is in contact, and by which it is conformed. It is hardly likely, for all these reasons, that we shall ever attain to a full and particular explanation of the septal surfaces and their sutural outlines throughout the whole range of cephalopod shells. But in general terms, the problem is probably not beyond the reach of mathematical analysis. The problem might be approached experimentally, after the manner of Plateau's experiments, by bending a wire into the complicated form of the suture line, and studying the form of the liquid film which constitutes the corresponding surface minime areae. Figure 306. Ammonites, Sunninea. Sauerby. From Zittel, after Steinmann and Doderlein. In certain ammonites the septal outline is further complicated in another way. Superposed upon the usual sinuous outline, with its lobes, and saddles, we have here a minutely ramified, or arborescent outline. Figure 307. Suture line of a Triassic ammonite. Pinacoceras. From Zittel, after Hauer. In which all the branches terminate in wavy, more or less circular arcs, looking just like the landscape marble, from the Bristol Reedick. We have no difficulty in recognizing in this a surface tension phenomenon. The figures are precisely such as we can imitate, for instance, by pouring a few drops of milk upon a greasy plate, or of oil upon an alkaline solution. We have very far from exhausted, we have perhaps little more than begun, the study of the logarithmic spiral and the associated curves which find exemplification in the multitudinous diversities of molluscan shells. But, with a closing word or two, we must now bring this chapter to an end. In the spiral shell we have a problem, or a phenomenon, of growth, immensely simplified by the fact that each successive increment is irrevocably fixed in regard to magnitude and position, instead of remaining in a state of flux and sharing in the further changes which the organism undergoes. In such a structure, then, we have certain primary phenomena of growth manifested in their original simplicity, undisturbed by secondary and conflicting phenomena. What actually grows is merely the lip of an orifice, where there is produced a ring of solid material, whose form we have treated of under the name of the generating curve, and this generating curve grows in magnitude without alteration of its form. Besides its increase in areal magnitude, the growing curve has certain strictly limited degrees of freedom, which define its motions in space, that is to say, it has a vector motion at right angles to the axis of the shell. And it has a sliding motion along that axis. And, though we may know nothing whatsoever about the actual velocities of any of these motions, we do know that they are so correlated together that their relative velocities remain constant. And accordingly the form and symmetry of the whole system remain in general unchanged. But there is a vast range of possibilities in regard to every one of these factors. The generating curve may be of various forms, and even when of simple form, such as an ellipse, its axes may be set at various angles to the system. The plane also in which it lies may vary, almost indefinitely, in its angle relatively to that of any plane of reference in the system. And in the several velocities of growth, of rotation and of translation, and therefore in the ratios between all these, we have again a vast range of possibilities. We have then a certain definite type, or group of forms, mathematically isomorphous, but presenting infinite diversities of outward appearance, which diversities, as Swammerdam said, ex sola nascuntur diversitate gyrationum. And which accordingly are seen to have their origin in differences of rate, or of magnitude, and so to be, essentially, neither more nor less than differences of degree. In nature, we find these forms presenting themselves with but little relation to the character of the creature by which they are produced. Spiral forms of certain particular kinds are common to gastropods and to cephalopods, and to diverse families of each. While outside the class of mollusks altogether, among the foraminifera and among the worms, as in Spirorbes, Spirographus, and in the dentalium-like shell of Ditropa, we again meet with similar and corresponding forms. Again, we find the same forms, or forms which, save for external ornament, are mathematically identical, repeating themselves in all periods of the world's geological history. And, irrespective of climate or local conditions, we see them mixed up, one with another, in the depths and on the shores of every sea. It is hard indeed, to my mind, to see where natural selection necessarily enters in, or to admit that it has had any share whatsoever in the production of these varied conformations. Unless indeed we use the term natural selection in a sense so wide as to deprive it of any purely biological significance. And so recognize as a sort of natural selection whatsoever nexus of causes suffices to differentiate between the likely and the unlikely, the scarce and the frequent, the easy and the hard, and leads accordingly, under the peculiar conditions, limitations and restraints which we call ordinary circumstances, one type of crystal, one form of cloud, one chemical compound, to be of frequent occurrence and another to be rare. Chapter 12 The Spiral Shells of the Foraminifera. We have already dealt in a few simple cases with the shells of the foraminifera. And we have seen that wherever the shell is but a single unit or single chamber, its form may be explained in general by the laws of surface tension, the assumption being that the little mass of protoplasm which makes the simple shell behaves as a fluid drop, the form of which is perpetuated when the protoplasm acquires its solid covering. Thus the spherical orbulini and the flask-shaped lagini represent drops in equilibrium, under various conditions of freedom or constraint. While the irregular, amoeboid body of Astrorhiza is a manifestation not of equilibrium, but of a varying and fluctuating distribution of surface energy. When the foraminiferal shell becomes multilocular, the same general principles continue to hold. The growing protoplasm increases drop by drop, and each successive drop has its particular phenomena of surface energy, manifested at its fluid surface, and tending to confer upon it a certain place in the system and a certain shape of its own. It is characteristic and even diagnostic of this particular group of protozoa, 1. That development proceeds by a well-marked alternation of rest and of activity during which the protoplasm increases, and of rest during which the shell is formed. 2. That the shell is formed at the outer surface of the protoplasmic organism, and tends to constitute a continuous or all but continuous covering. And it follows, 3. From these two factors taken together that each successive increment is added on outside of and distinct from its predecessors, that the successive parts or chambers of the shell are of different and successive ages. That one part of the shell is always relatively new, and the rest old in various grades of seniority. The forms which we set together in the sister group of radiolaria are very differently characterized. Here the cells or vesicles of which each little composite organism is made up are but little separated, and in no way walled off, from one another. The hard skeletal matter tends to be deposited in the form of isolated spicules or of little connected rods or plates, at the angles, the edges, or the interfaces of the vesicles. The cells or vesicles form a coordinated and contemporaneous rather than a successive series. In a word, the whole quasi-fluid protoplasmic body may be likened to a little mass of froth or foam, that is to say, to an aggregation of simultaneously formed drops or bubbles, whose physical properties and geometrical relations are very different from those of a system of drops or bubbles which are formed one after another, each solidifying before the next is formed. Figure 308. Hastagerina sp. Tissue the mouth. With the actual origin or mode of development of the foraminiferal shell we are now but little concerned. The main factor is the adsorption, and subsequent precipitation at the surface of the organism, of calcium carbonate, the shell so formed being interrupted by pores or by some larger interspace or mouth, fig. Which interruptions we may doubtless interpret as being due to unequal distributions of surface energy. In many cases the fluid protoplasm picks up sand grains and other foreign particles, after a fashion which we have already described, p. And it cements these together with more or less of calcareous material. The calcareous shell is a crystalline structure. And the microcrystals of calcium carbonate are so set that their little prisms radiate outwards in each chamber through the thickness of the wall, which symmetry is subject to corresponding modification when the spherical chambers are more or less symmetrically deformed. In various ways the rounded, drop-like shells of the foraminifera, both simple and compound, have been artificially imitated. Thus, if small globules of mercury be immersed in water in which a little chromic acid is allowed to dissolve, as the little beads of quicksilver become slowly covered with a crystalline coat of mercuric chromate they assume various forms reminiscent of the monothalamic foraminifera. The mercuric chromate has a higher atomic volume than the mercury which it replaces, and therefore the fluid contents of the drop are under pressure, which increases with the thickness of the pellicle. Hence at some weak spot in the latter the contents will presently burst forth, so forming a mouth to the little shell. Sometimes a long thread is formed, just as in Rhabdamina linearis. And sometimes unduloid swellings make their appearance on such a thread, just as in R. discreta. And again, by appropriate modifications of the experimental conditions, it is possible, as Rumbler has shown, to build up a chambered shell. In a few forms, such as Globigerina and its close allies, the shell is beset during life with excessively long and delicate calcareous spines or needles. It is only in oceanic forms that these are present, because only when poised in water can such delicate structures endure. In dead shells, such as we are much more familiar with, every trace of them is broken and rubbed away. The growth of these long needles is explained, as we have already briefly mentioned, on p. by the phenomenon which Lehmann calls oriented adsorption, the tendency for a crystalline structure to grow by accretion, not necessarily in the outward form of a crystal, but continuing in any direction or orientation which has once been impressed upon it. In this case the spicular growth is simply in direct continuation of the radial symmetry of the microcrystalline elements of the shell wall. Over the surface of the shell the radiating spicules tend to occur in a hexagonal pattern, symmetrically grouped around the pores which perforate the shell. Rumbler has suggested that this arrangement is due to diffusion currents, forming little eddies about the base of the pseudopodia issuing from the pores, the idea being borrowed from Barnard. To whom is due the discovery of this type or order of vortices? In one of Barnard's experiments, a thin layer of paraffin is strewn with particles of graphite, then warmed to melting, whereupon each little solid granule becomes the center of a vortex. By the interaction of these vortices the particles tend to be repelled to equal distances from one another, and in the end they are found to be arranged in a hexagonal pattern. The analogy is plain between this experiment and those diffusion experiments by which Leduc produces his beautiful hexagonal systems of artificial cells, with which we have dealt in a previous chapter, p. But let us come back to the shell itself, and consider particularly its spiral form. That the shell in the foraminifera should tend towards a spiral form need not surprise us. For we have learned that one of the fundamental conditions of the production of a concrete spiral is just precisely what we have here, namely the gradual development of a structure by means of successive increments superadded to its exterior, which then form part, successively, of a permanent and rigid structure. This condition is obviously forthcoming in the foraminiferal, but not at all in the radiolarian, shell. Our second fundamental condition of the production of a logarithmic spiral is that each successive increment shall be so posited and so conformed that its addition to the system leaves the form of the whole system unchanged. We have now to inquire into this latter condition, and to determine whether the successive increments, or successive chambers, of the foraminiferal shell actually constitute gnomons to the entire structure. It is obvious enough that the spiral shells of the foraminifera closely resemble true logarithmic spirals. Indeed, so precisely do the minute shells of many foraminifera repeat or simulate the spiral shells of Nautilus and its allies that to the naturalists of the early 19th century they were known as the cephalopods microscopiques. Until Dujardin eschewed that their little bodies comprised no complex anatomy of organs, but consisted merely of that slime-like organic matter which he taught us to call sarcode, and which we learned afterwards from Schwann to speak of as protoplasm. Figure 309. Nummulina antiquae, R, and V. After V. von Mahler. One striking difference, however, is apparent between the shell of Nautilus and the little nautiloid or rhodoline shells of the foraminifera, namely that the septa in these latter, and in all other chambered foraminifera, are convex outwards, Fig. Whereas they are concave outwards in Nautilus, Fig. And in the rest of the chambered molluscan shells. The reason is perfectly simple. In both cases the curvature of the septum was determined before it became rigid, and at a time when it had the properties either of a fluid film or an elastic membrane. In both cases the actual curvature is determined by the tensions of the membrane and the pressures to which it was exposed. Now it is obvious that the extrinsic pressure which the tension of the membrane has to withstand is on opposite sides in the two cases. In Nautilus, the pressure to be resisted is that produced by the growing body of the animal, lying to the outer side of the septum, in the outer, wider portion of the tubular shell. In the foraminifera the septum at the time of its formation was no septum at all, it was but a portion of the convex surface of a drop, that portion namely which afterwards became overlapped and enclosed by the succeeding drop. And the curvature of the septum is concave towards the pressure to be resisted, which latter is inside the septum, being simply the hydrostatic pressure of the fluid contents of the drop. The one septum is, speaking generally, the reverse of the other, the organism, so to speak, is outside the one and inside the other. And in both cases alike, the septum tends to assume the form of a surface of minimal area, as permitted, or as defined, by all the circumstances of the case. The logarithmic spiral is easily recognizable in typical cases, and especially where the spire makes more than one visible revolution about the pole, by its fundamental property of continued similarity, that is to say, by reason of the fact that the big many-chambered shell is of just the same shape as the smaller and younger shell, which phenomenon is apparent and even obvious in the nautiloid foraminifera. As in Nautilus itself, but nevertheless the nature of the curve must be verified by careful measurement, just as Moseley determined or verified it in his original study of Nautilus, cf. p. This has accordingly been done, by various writers, and in the first instance by Valerian von Mahler. In an elaborate study of Phyllotaxis, a Paleozoic genus whose little shells have built up vast tracts of Carboniferous limestone over great part of European Russia. In this genus a growing surface of protoplasm may be conceived as wrapping round and round a small initial chamber, in such a way as to produce a fusiform or ellipsoidal shell, a transverse section of which reveals the close-wound spiral coil. The following are examples of measurements of the successive whorls in a couple of species of this genus. F. cylindrica, Fischer. F. Bacchi, V. Mahler. Breadth, in millimeters. Whorl. Observed. Calculated. Observed. Calculated. I. 132. 079. 2. 195. 198. 120. 119. 3. 300. 297. 180. 179. 4. 449. 445. 264. 267. V. 396. 401. In both cases the successive whorls are very nearly in the ratio of 1:5. And on this ratio the calculated values are based. Here is another of von Mahler's series of measurements of F. cylindrica, the measurements being those of opposite whorls, that is to say of whorls 180 degrees apart. Breadth in mm. 096. 117. 144. 176. 216. 264. 323. 395. Log. Of mm. 982. 068. 158. 246. 334. 422. 509. 597. Difference of logs. 086. 090. 088. 088. 088. 087. 088. The mean logarithmic difference is here 088 equals log 1, 225. Or the mean difference of alternate logs, corresponding to a vector angle of 2 pi, i.e. to consecutive measurements along the same radius, is 176, equals log 1/5, the same value as before. And this ratio of 1/5 between the breadths of successive whorls corresponds, as we see by our table on p, to a constant angle of about 86 degrees, or just such a spiral as we commonly meet with in the ammonites, cfp. Figure 310. A. Cornuspora foliacea, Phil, B. Operculina complanata, Deffr. In Phyllotaxis, and in some few other foraminifera, cf. Fig. A. The spire seems to wind evenly on, with little or no external sign of the successive periods of growth, or successive chambers of the shell. The septa which mark off the chambers, and correspond to retardations or cessations in the periodicity of growth, are still to be found in sections of the shell of Phyllotaxis, but they are somewhat irregular and comparatively inconspicuous. The measurements we have just spoken of are taken without reference to the segments or chambers, but only with reference to the whorls, or in other words with direct reference to the vectorial angle. The linear dimensions of successive chambers have been measured in a number of cases. Van Itterson has done so in various milliolinity, with such results as the following. Triloculina rotunda, Diorb. No. Of chamber. 2. 4. 6. 8. 10. Breadth of chamber in 45. 84. 142. 246. Breadth of chamber in, calculated. 45. 79. 140. 243. Here the mean ratio of breadth of consecutive chambers may be taken as 1:323, that is to say, the eighth root of 319/34. And the calculated values, as given above, are based on this determination. Again, Rumbler has measured the linear dimensions of a number of rhodoline forms, for instance Pulvinulina monardi, Fig. In which common species he finds the mean linear ratio of consecutive chambers to be about 1:187. In both cases, and especially in the latter, the ratio is not strictly constant from chamber to chamber, but is subject to a small secondary fluctuation. Figure 311. 1, 2, Miliolina pulchella. Deorb, 3 to 5, M. lineana, Deorb. After Brady. When the linear dimensions of successive chambers are in continued proportion, then, in order that the whole shell may constitute a logarithmic spiral, it is necessary that the several chambers should subtend equal angles of revolution at the pole. In the case of the Miliolida this is obviously the case, Fig. For in this family the chambers lie in 2 rows, biloculina, or 3 rows, triloculina, or in some other small number of series, so that the angles subtended by them are large, simple fractions of the circular arc, such as 180 degrees or 120 degrees. In many of the nautiloid forms, such as cyclamina, Fig, the angles. Figure 312. Cyclamina cancellata. Brady. Subtended, though of less magnitude, are still remarkably constant, as we may see by Fig. Where the angle subtended by each chamber is made equal to 20 degrees, and this diagrammatic figure is not perceptibly different from the other. In some cases the subtended angle is less constant. And in these it would be necessary to equate the several linear dimensions with the corresponding vector angles, according to our equation R equals E theta cot alpha. It is probable that, by so taking account of variations of theta, such variations of R as, according to Rumbler's measurements, Pulvinulina and other genera appear to shew, would be found to diminish or even to disappear. Figure 313. Cyclamina. SP. Diagrammatic. The law of increase by which each chamber bears a constant ratio of magnitude to the next may be looked upon as a simple consequence of the structural uniformity or homogeneity of the organism. We have merely to suppose, as this uniformity would naturally lead us to do, that the rate of increase is at each instant proportional to the whole existing mass. For if V0, V1 etc. be the volumes of the successive chambers, let V1 bear a constant proportion to V0, so that V1 equals Q V0. And let V2 bear the same proportion to the whole pre-existing volume, then V2 equals Q V0 plus V1 equals Q V0 plus Q V0 equals Q V0, 1 plus Q. And V2 V1 equals 1 plus Q. This ratio of 1 plus Q, is easily shown to be the constant ratio running through the whole series, from chamber to chamber. And if this ratio of volumes be constant, so also are the ratios of corresponding surfaces, and of corresponding linear dimensions, provided always that the successive increments, or successive chambers, are similar in form. We have still to discuss the similarity of form and the symmetry of position which characterized the successive chambers, and which, together with the law of continued proportionality of size, are the distinctive characters and the indispensable conditions of a series of gnomons. Figure 314. Orbulina. Universa, Deorb. The minute size of the foraminiferal shell or at least of each successive increment thereof, taken in connection with the fluid or semi-fluid nature of the protoplasmic substance, is enough to suggest that the molecular forces, and especially the force of surface tension, must exercise a controlling influence over the form of the whole structure. And this suggestion, or belief, is already implied in our statement that each successive increment of growing protoplasm constitutes a separate drop. These drops, partially concealed by their successors, but still shewing in part their rounded outlines, are easily recognizable in the various foraminiferal shells which are illustrated in this chapter. The accompanying figure represents, to begin with, the spherical shell characteristic of the common, floating, oceanic Orbulina. In the specimen illustrated, a second chamber, superadded to the first, has arisen as a drop of protoplasm which exuded through the pores of the first chamber, accumulated on its surface, and spread over the latter till it came to rest in a position of equilibrium. We may take it that this position of equilibrium is determined, at least in the first instance, by the law of the constant angle, which holds, or tends to hold. In all cases where the free surface of a given liquid is in contact with a given solid, in presence of another liquid or a gas, the corresponding equations are precisely the same as those which we have used in discussing the form of a drop, on p. Though some slight modification must be made in our definitions, inasmuch as the consideration of surface tension is no longer appropriate at the solid surfaces, and the concept of surface energy must take its place. Be that as it may, it is enough for us to observe that, in such a case as ours, when a given fluid, namely protoplasm, is in surface contact with a solid, viz. a calcareous shell, in presence of another fluid, seawater, then the angle of contact, or angle by which the common surface, or interface, of the two liquids abuts against the solid wall, tends to be constant, and that being so, the drop will have a certain definite form, depending, inter alia, on the form of the surface with which it is in contact. After a period of rest, during which the surface of our second drop becomes rigid by calcification, a new period of growth will recur and a new drop of protoplasm be accumulated. Circumstances remaining the same, this new drop will meet the solid surface of the shell at the same angle as did the former one. And, the other forces at work on the system remaining the same, the form of the whole drop, or chamber, will be the same as before. According to Rumbler, this law of the constant angle is the fundamental principle in the mechanical conformation of the foraminiferal shell, and provides for the symmetry of form as well as of position in each succeeding drop of protoplasm, which form and position, once acquired, become rigid and fixed with the onset of calcification. But Rumbler's explanation brings with it its own difficulties. It is by no means easy of verification, for on the very complicated curved surfaces of the shell it seems to me extraordinarily difficult to measure, or even to recognize, the actual angle of contact, of which angle of contact, by the way, but little is known, save only in the particular case where one of the three bodies is air, as when a surface of water is exposed to air and in contact with glass. It is easy moreover to see that in many of our foraminifera the angle of contact, though it may be constant in homologous positions from chamber to chamber, is by no means constant at all points along the boundary of each chamber. In Crystalleria, for instance, Fig, it would seem to be, and Rumbler. Figure 315. Crystalleria. Reniformis, D'Orb. Asserts that it actually is, about 90 degrees on the outer side and only about 50 degrees on the inner side of each septal partition. In Pulvinulina, Fig, according to Rumbler, the angles adjacent to the mouth are of 90 degrees, and the opposite angles are of 60 degrees, in each chamber. For these and other similar discrepancies Rumbler would account by simply invoking the heterogeneity of the protoplasmic drop, that is to say, by assuming that the protoplasm has a different composition and different properties, including a very different distribution of surface energy, at points near to and remote from the mouth of the shell. Whether the differences in angle of contact be as great as Rumbler takes them to be, whether marked heterogeneities of the protoplasm occur, and whether these be enough to account for the differences of angle, I cannot tell. But it seems to me that we had better rest content with a general statement, and that Rumbler has taken too precise and narrow a view. In the molecular growth of a crystal, although we must of necessity assume that each molecule settles down in a position of minimum potential energy, we find it very hard indeed to explain precisely, even in simple cases and after all the labors of modern crystallographers, why this or that position is actually a place of minimum potential. In the case of our little foraminifer, just as in the case of the crystal, let us then be content to assert that each drop or bead of protoplasm takes up a position of minimum potential energy, in relation to all the circumstances of the case. And let us not attempt, in the present state of our knowledge, to define the position of minimum potential by reference to angle of contact or any other particular condition of equilibrium. In most cases the whole exposed surface, on some portion of which the drop must come to rest, is an extremely complicated one, and the forces involved constitute a system which, in its entirety, is more complicated still. But from the symmetry of the case and the continuity of the whole phenomenon, we are entitled to believe that the conditions are just the same, or very nearly the same, time after time. From one chamber to another, as the one chamber is conformed so will the next tend to be, and as the one is situated relatively to the system so will its successor tend to be situated in turn. The physical law of minimum potential, including also the law of minimal area, is all that we need in order to explain, in general terms, the continued similarity of one chamber to another. And the physiological law of growth, by which a continued proportionality of size tends to run through the series of successive chambers, impresses upon this series of similar increments the form of a logarithmic spiral. In each particular case the nature of the logarithmic spiral, as defined by its constant angle, will be chiefly determined by the rate of growth, that is to say by the particular ratio in which each new chamber exceeds its predecessor in magnitude. But shells having the same constant angle, alpha, may still differ from one another in many ways, in the general form and relative position of the chambers, in their extent of overlap, and hence in the actual contour and appearance of the shell. And these variations must correspond to particular distributions of energy within the system, which is governed as a whole by the law of minimum potential. Our problem, then, becomes reduced to that of investigating the possible configurations which may be derived from the successive symmetrical apposition of similar bodies whose magnitudes are in continued proportion. And it is obvious, mathematically speaking, that the various possible arrangements all come under the head of the logarithmic spiral, together with the limiting cases which it includes. Since the difference between one such form and another depends upon the numerical value of certain coefficients of magnitude, it is plain that any one must tend to pass into any other by small and continuous gradations. In other words, that a classification of these forms must, like any classification whatsoever of logarithmic spirals or of any other mathematical curves, be theoretic or artificial. But we may easily make such an artificial classification, and shall probably find it to agree, more or less, with the usual methods of classification recognized by biological students of the foraminifera. Firstly, we have the typically spiral shells, which occur in great variety, and which, for our present purpose, we need hardly describe further. We may merely notice how in certain cases, for instance Globigerina, the individual chambers are little removed from spheres, in other words, the area of contact between the adjacent chambers is small. In such forms as Cyclamina and Pulvinulina, on the other hand, each chamber is greatly overlapped by its successor, and the spherical form of each is lost in a marked asymmetry. Furthermore, in Globigerina and some others we have a tendency to the development of a helicoid spiral in space, as in so many of our univalve molluscan shells. The mathematical problem of how a shell should grow, under the assumptions which we have made, would probably find its most general statement in such a case as that of Globigerina, where the whole organism lives and grows freely poised in a medium whose density is little different from its own. The majority of spiral forms, on the other hand, are plane or discoid spirals, and we may take it that in these cases some force has exercised a controlling influence, so as to keep all the chambers in a plane. This is especially the case in forms like Rotalia or Discorbina, Fig, where the organism lives attached to a rock or a frond of seaweed. For here, just as in the case of the coiled tubes which little worms such as Serpula and Spirorbes make, under similar conditions, the spiral disc is itself asymmetrical, its whorls being markedly flattened on their attached surfaces. Figure 316. Discorbina. Bertheloti, Diorb. We may also conceive, among other conditions, the very curious case in which the protoplasm may entirely overspread the surface of the shell without reaching a position of equilibrium. In which case a new shell will be formed enclosing the old one, whether the old one be in the form of a single, solitary chamber, or have already attained to the form of a chambered or spiral shell. This is precisely what often happens in the case of Orbulina, when within the spherical shell we find a small, but perfectly formed, spiral, Globigerina. The various Miliolidi, Fig. only differ from the typical spiral, or rhodoline forms, in the large angles subtended by each chamber, and the consequent abruptness of their inclination to each other. In these cases the outward appearance of a spiral tends to be lost. And it behoves us to recollect, all the more, that our spiral curve is not necessarily identical with the outline of the shell, but is always a line drawn through corresponding points in the successive chambers of the latter. Figure 317. A. Tertularia tracheus, Diorb. B. T. Concava, Carrer. We reach a limiting case of the logarithmic spiral when the chambers are arranged in a straight line. And the eye will tend to associate with this limiting case the much more numerous forms in which the spiral angle is small, and the shell only exhibits a gentle curve with no succession of enveloping whorls. This constitutes the notarian type, Fig. P, and here again, we must postulate some force which has tended to keep the chambers in a rectilinear series, such for instance as gravity, acting on a system of hanging drops. In Textularia and its allies, Fig, we have a precise parallel to the helicoid cyme of the botanists, CFP, that is to say we have a screw translation, perpendicular to the plane of the underlying logarithmic spiral. In other words, in tracing a genetic spiral through the whole succession of chambers, we do so by a continuous vector rotation, through successive angles of 180 degrees, or 120 degrees in some cases. While the pole moves along an axis perpendicular to the original plane of the spiral. Another type is furnished by the cyclic shells of the Orbitalidae, where small and numerous chambers tend to be added on round and round the system, so building up a circular flattened disk. This again we perceive to be, mathematically, a limiting case of the logarithmic spiral, where the spiral has become a circle and the constant angle is now an angle of 90 degrees. Lastly, there are a certain number of foraminifera in which, without more ado, we may simply say that the arrangement of the chambers is irregular, neither the law of constant ratio of magnitude or that of constant form being obeyed. The chambers are heaped pell-mell upon one another, and such forms are known to naturalists as the acervularity. While in these last we have an extreme lack of regularity, we must not exaggerate the regularity or constancy which the more ordinary forms display. We may think it hard to believe that the simple causes, or simple laws, which we have described should operate, and operate again and again, in millions of individuals to produce the same delicate and complex conformations. But we are taking a good deal for granted if we assert that they do so, and in particular we are assuming, with very little proof, the constancy of species, in this group of animals. Just as Verworn has shown that the typical amoeba Proteus, when a trace of alkali is added to the water in which it lives, tends, by alteration of surface tensions, to protrude the more delicate pseudopodia characteristic of A. radiosa, and again when the water is rendered a little more alkaline, to turn apparently into the so-called A. limax, so it is evident that a very slight modification in the surface energies concerned, might tend to turn one so-called species into another among the foraminifera. To what extent this process actually occurs, we do not know. But that this, or something of the kind, does actually occur we can scarcely doubt. For example, in the genus Peneroplus, the first portion of the shell consists of a series of chambers arranged in a spiral or nautiloid series. But as age advances the spiral is apt to be modified in various ways. Sometimes the successive chambers grow rapidly broader, the whole shell becoming fan-shaped. Sometimes the chambers become narrower, till they no longer enfold the earlier chambers but only come in contact each with its immediate predecessor, the result being that the shell straightens out. And, taking into account the earlier spiral portion, may be described as crozier-shaped. Between these extremes of shape, and in regard to other variations of thickness or thinness, roughness or smoothness, and so on, there are innumerable gradations passing one into another and intermixed without regard to geographical distribution. Wherever peneroplides abound this wide variation exists. And nothing can be more easy than to pick out a number of striking specimens and give to each a distinctive name, but in no other way can they be divided into species. Some writers have wondered at the peculiar variability of this particular shell. But for all we know of the life history of the foraminifera, it may well be that a great number of the other forms which we distinguish as separate species and even genera are no more than temporary manifestations of the same variability. Conclusion. If we can comprehend and interpret on some such lines as these the form and mode of growth of the foraminiferal shell, we may also begin to understand two striking features of the group, namely, on the one hand the large number of diverse types or families which exist and the large number of species and varieties within each. And on the other the persistence of forms which in many cases seem to have undergone little change or none at all from the Cretaceous or even from earlier periods to the present day. In few other groups, perhaps only among the Radiolaria, do we seem to possess so nearly complete a picture of all possible transitions between form and form, and of the whole branching system of the evolutionary tree, as though little or nothing of it had ever perished, and the whole web of life, past and present, were as complete as ever. It leads one to imagine that these shells have grown according to laws so simple, so much in harmony with their material, with their environment, and with all the forces internal and external to which they are exposed, that none is better than another and none fitter or less fit to survive. It invites one also to contemplate the possibility of the lines of possible variation being here so narrow and determinate that identical forms may have come independently into being again and again, while we can trace in the most complete and beautiful manner the passage of one form into another among these little shells, and ascribe them all at last, if we please, to a series which starts with the simple sphere of Orbulina or with the amoeboid body of Asterrhiza. The question stares us in the face whether this be an evolution which we have any right to correlate with historic time. The mathematician can trace one conic section into another, and evolve, for example, through innumerable graded ellipses, the circle from the straight line, which tracing of continuous steps is a true evolution, though time has no part therein. It was after this fashion that Hegel, and for that matter Aristotle himself, was an evolutionist, to whom evolution was a mental concept, involving order and continuity in thought, but not an actual sequence of events in time. Such a conception of evolution is not easy for the modern biologist to grasp, and harder still to appreciate. And so it is that even those who, like Dreyer and like Rumbler, study the foraminiferal shell as a physical system, who recognize that its whole plan and mode of growth is closely akin to the phenomena exhibited by fluid drops under particular conditions, and who explain the conformation of the shell by help of the same physical principles and mathematical laws, yet all the while abate no jot or tittle of the ordinary postulates of modern biology, nor doubt the validity and universal applicability of the concepts of Darwinian evolution. For these writers the biogenetisches Grundgesetz remains impregnable. The foraminifera remain for them a great family tree, whose actual pedigree is traceable to the remotest ages, in which historical evolution has coincided with progressive change, and in which structural fitness for a particular function, or functions, has exercised its selective action and ensured the survival of the fittest. By successive stages of historic evolution we are supposed to pass from the irregular Asterrhiza to a rhabdamina with its more concentrated disc, to the forms of the same genus which consist of but a single tube with central chamber. To those where this chamber is more and more distinctly segmented, so to the typical many-chambered Nodocerii, and from these, by another definite advance and later evolution to the spiral Trochamini. After this fashion, throughout the whole varied series of the foraminifera, Dreyer and Rumbler, following Neumayer, recognize so many successions of related forms, one passing into another, and standing towards it in a definite relationship of ancestry or descent. Each evolution of form, from simpler to more complex, is deemed to have been attended by an advantage to the organism, an enhancement of its chances of survival or perpetuation. Hence the historically older forms are, on the whole, structurally the simpler, or conversely the simpler forms, such as the simple sphere, were the first to come into being in primeval seas. And finally, the gradual development and increasing complication of the individual within its own lifetime is held to be at least a partial recapitulation of the unknown history of its race and dynasty. We encounter many difficulties when we try to extend such concepts as these to the foraminifera. We are led for instance to assert, as Rumbler does, that the increasing complexity of the shell, and of the manner in which one chamber is fitted on another, makes for advantage. And the particular advantage on which Rumbler rests his argument is strength. Increase of strength, die Festigkeitssteigerung, is according to him the guiding principle in foraminiferal evolution, and marks the historic stages of their development in geologic time. But in days gone by I used to see the beach of a little Connemara bay bestrewn with millions upon millions of foraminiferal shells, simple Lagini, less simple Nodocerii, more complex Rotalii, all drifted by wave and gentle current from their sea cradle to their sandy grave, all lying bleached and dead, one more delicate than another, but all, or vast multitudes of them, perfect and unbroken. And so I am not inclined to believe that niceties of form affect the case very much, nor in general that foraminiferal life involves a struggle for existence wherein breakage is a constant danger to be averted, and increased strength and advantage to be ensured. In the course of the same argument Rumbler remarks that foraminifera are absent from the coarse sands and gravels, as Williamson indeed had observed many years ago, so averting, or at least escaping, the dangers of concussion. But this is after all a very simple matter of mechanical analysis. The coarseness or fineness of the sediment on the sea bottom is a measure of the current. Where the current is strong the larger stones are washed clean, where there is perfect stillness the finest mud settles down. And the light, fragile shells of the foraminifera find their appropriate place, like every other graded sediment, in this spontaneous order of lixiviation. The theorem of organic evolution is one thing. The problem of deciphering the lines of evolution, the order of phylogeny, the degrees of relationship and consanguinity, is quite another. Among the higher organisms we arrive at conclusions regarding these things by weighing much circumstantial evidence, by dealing with the resultant of many variations, and by considering the probability or improbability of many coincidences of cause and effect. But even then our conclusions are at best uncertain, our judgments are continually open to revision and subject to appeal, and all the proof and confirmation we can ever have is that which comes from the direct, but fragmentary evidence of paleontology. But in so far as forms can be shown to depend on the play of physical forces, and the variations of form to be directly due to simple quantitative variations in these, just so far are we thrown back on our guard before the biological conception of consanguinity, and compelled to revise the vague canons which connect classification with phylogeny. The physicist explains in terms of the properties of matter, and classifies according to a mathematical analysis, all the drops and forms of drops and associations of drops, all the kinds of froth and foam, which he may discover among inanimate things. And his task ends there. But when such forms, such conformations and configurations, occur among living things, then at once the biologist introduces his concepts of heredity, of historical evolution, of succession in time, of recapitulation of remote ancestry in individual growth, of common origin, unless contradicted by direct evidence, of similar forms remotely separated by geographic space or geologic time, of fitness for a function, of adaptation to an environment, of higher and lower, of better and worse. This is the fundamental difference between the explanations of the physicist and those of the biologist. In the order of physical and mathematical complexity there is no question of the sequence of historic time. The forces that bring about the sphere, the cylinder or the ellipsoid are the same yesterday and tomorrow. A snow crystal is the same today as when the first snows fell. The physical forces which mold the forms of Orbulina, of Astrorhiza, of Lagina or of Nodoceria today were still the same, and for aught we have reason to believe the physical conditions under which they worked were not appreciably different in that yesterday which we call the Cretaceous epoch. Or, for aught we know, throughout all that duration of time which is marked, but not measured, by the geological record. In a word, the minuteness of our organism brings its conformation as a whole within the range of the molecular forces. The laws of its growth and form appear to lie on simple lines. What Bergson calls the ideal kinship is plain and certain, but the material affiliation is problematic and obscure. And, in the end and upshot, it seems to me by no means certain that the biologist's usual mode of reasoning is appropriate to the case, or that the concept of continuous historical evolution must necessarily, or may safely and legitimately, be employed. Chapter 13 The Shapes of Horns, and of Teeth or Tusks, with a note on torsion. We have had so much to say on the subject of shell spirals that we must deal briefly with the analogous problems which are presented by the horns of sheep, goats, antelopes and other horned quadrupeds. And all the more, because these horn spirals are on the whole less symmetrical, less easy of measurement than those of the shell, and in other ways also are less easy of investigation. Let us dispense altogether in this case with mathematics, and be content with a very simple account of the configuration of a horn. There are three types of horn which deserve separate consideration. Firstly, the horn of the rhinoceros. Secondly, the horns of the sheep, the goat, the ox or the antelope, that is to say, of the so-called hollow-horned ruminants, and thirdly, the solid bony horns, or antlers, which are characteristic of the deer. The horn of the rhinoceros presents no difficulty. It is physiologically equivalent to a mass of consolidated hairs, and, like ordinary hair, it consists of non-living or formed material, continually added to by the living tissues at its base. In section, that is to say in the form of its generating curve, the horn is approximately elliptical, with the long axis fore and aft, or, in some species, nearly circular. Its longitudinal growth proceeds with a maximum velocity anteriorly, and a minimum posteriorly, and the ratio of these velocities being constant, the horn curves into the form of a logarithmic spiral in the manner that we have already studied. The spiral is of small angle, but in the longer horn species, such as the great white rhinoceros, Ceratorinus, the spiral form is distinctly to be recognized. As the horn occupies a median position on the head, a position, that is to say, of symmetry in respect to the field of force on either side, there is no tendency towards a lateral twist. And the horn accordingly develops as a plain logarithmic spiral. When two horns coexist, the hinder one is much the smaller of the two, which is as much as to say that the force, or rate, of growth diminishes as we pass backwards, just as it does within the limits of the single horn. And accordingly, while both horns have essentially the same shape, the spiral curvature is less manifest in the second one, simply by reason of its comparative shortness. The paired horns of the ordinary hollow-horned ruminants, such as the sheep or the goat, grow under conditions which are in some respects similar, but which differ in other and important respects from the conditions under which the horn grows in the rhinoceros. As regards its structure, the entire horn now consists of a bony core with a covering of skin. The inner, or dermal, layer of the latter is richly supplied with nutrient blood vessels, while the outer layer, or epidermis, develops the fibrous or chitinous material, chemically and morphologically akin to a mass of cemented or consolidated hairs, which constitutes the sheath of the horn. A zone of active growth at the base of the horn keeps adding to this sheath, ring by ring, and the specific form of this annular zone is, accordingly, that of the generating curve of the horn. Each horn no longer lies, as it does in the rhinoceros, in the plane of symmetry of the animal of which it forms a part. And the limited field of force concerned in the genesis and growth of the horn is bound, accordingly, to be more or less laterally asymmetrical. But the two horns are in symmetry one with another. They form conjugate spirals, one being the mirror image of the other. Just as in the hairy coat of the animal each hair, on either side of the median, parting, tends to have a certain definite direction of its own axis, inclined away from the median axial plane of the whole system. So is it both with the bony core of the horn and with the consolidated mass of hairs or hair-like substance which constitutes its sheath. The primary axis of the horn is more or less inclined to, and may even be nearly perpendicular to, the axial plane of the animal. The growth of the horny sheath is not continuous, but more or less definitely periodic. Sometimes, as in the sheep, this periodicity is particularly well marked, and causes the horny sheath to be composed of a series of all but separate rings, which are supposed to be formed year by year, and so to record the age of the animal. Just as we sought for the true generating curve in the orifice, or lip, of the molluscan shell, so we might be apt to assume that in the spiral horn the generating curve corresponded to the lip or margin of one of the horny rings or annuli. This annular margin, or boundary of the ring, is usually a sinuous curve, not lying in a plane, but such as would form the boundary of an anticlastic surface of great complexity, to the meaning and origin of which phenomenon we shall return presently. But, as we have already seen in the case of the molluscan shell, the complexities of the lip itself, or of the corresponding lines of growth upon the shell, need not concern us in our study of the development of the spiral, inasmuch as we may substitute for these actual boundary lines, their trace, or projection on a plane perpendicular to the axis, in other words the simple outline of a transverse section of the whorl. In the horn, this transverse section is often circular or nearly so, as in the oxen and many antelopes. It now and then becomes of somewhat complicated polygonal outline, as in a highland ram. But in many antelopes, and in most of the sheep, the outline is that of an isosceles, or sometimes nearly equilateral triangle, a form which is typically displayed, for instance, in ovis ammon. The horn in this latter case is a trihedral prism, whose three faces are, 1, an upper, or frontal face, in continuation of the plane of the frontal bone, 2, an outer, or orbital, starting from the upper margin of the orbit, and, 3, an inner, or nuchal, abutting on the parietal bone. Along these three faces, and their corresponding angles or edges, we can trace in the fibrous substance of the horn a series of homologous spirals, such as we have called in a preceding chapter the ensemble of generating spirals, which constitute the surface. In some few cases, of which the male musk ox is one of the most notable, the horn is not developed in a continuous spiral curve. It changes its shape as growth proceeds. And this, as we have seen, is enough to show that it does not constitute a logarithmic spiral. The reason is that the bony exostoses, or horn cores, about which the horny sheath is shaped and molded, neither grow continuously nor even remain of constant size after attaining their full growth. But as the horns grow heavy the bony core is bent downwards by their weight, and so guides. Figure 3:18. Diagram of ram's horns. After Sir Vincent Brooke, from PZS, A, frontal, B, orbital, C, nuchal surface. The growth of the horn in a new direction. Moreover, as age advances, the horn core is further weakened and to a great extent absorbed, and the horny sheath or horn proper, deprived of its support, continues to grow, but in a flattened curve very different from its original spiral. The chamois is a somewhat analogous case. Here the terminal, or oldest, part of the horn is curved. It tends to assume a spiral form, though from its comparative shortness it seems merely to be bent into a hook. But later on, the bony core within, as it grows and strengthens, stiffens the horn, and guides it into a straighter course or form. The same phenomenon of change of curvature, manifesting itself at the time when, or the place where, the horn is freed from the support of the internal core, is seen in a good many other antelopes, such as the hartebeest, and in many buffaloes. And the cases where it is most manifest appear to be those where the bony core is relatively short, or relatively weak. Figure 3:19. Head of Arabian wild goat, Capra sinaitica. After Sclater, from PZS. But in the great majority of horns, we have no difficulty in recognizing a continuous logarithmic spiral, nor in referring it, as before, to an unequal rate of growth, parallel to the axis, on two opposite sides of the horn. The inequality maintaining a constant ratio as long as growth proceeds. In certain antelopes, such as the gemsbok, the spiral angle is very small, or in other words the horn is very nearly straight. In other species of the same genus Oryx, such as the Bisa antelope and the Leucoryx, a gentle curve, not unlike though generally less than that of a dentalium shell, is evident. And the spiral angle, according to the few measurements I have made, is found to measure from about 20 degrees to nearly 40 degrees. In some of the large wild goats, such as the Sind wild goat, we have a beautiful logarithmic spiral, with a constant angle of rather less than 70 degrees. And we may easily arrange a series of forms, such for example as the Siberian ibex, the mouflon, ovis ammon, etc. And ending with the longhorned highland ram, in which, as we pass from one to another, we recognize precisely homologous spirals, with an increasing angular constant, the spiral angle being, for instance, about 75 degrees or rather less in ovis ammon. And in the highland ram a very little more. We have already seen that in the neighborhood of 70 degrees or 80 degrees a small change of angle makes a marked difference in the appearance of the spire. And we know also that the actual length of the horn makes a very striking difference, for the spiral becomes especially conspicuous to the eye when a horn or shell is long enough to shew several whorls. Or at least a considerable part of one entire whorl. Even in the simplest cases, such as the wild goats, the spiral is never, strictly speaking, a plane or discoid spiral, but in greater or less degree there is always superposed upon the plane logarithmic spiral a helical spiral in space. Sometimes the latter is scarcely apparent, for the helical curvature is comparatively small, and the horn, though long, as in the said wild goats, is not nearly long enough to shew a complete convolution, at other times, as in the ram. And still better in many antelopes, such as the kudu, the helicoid or corkscrew curve of the horn is its most characteristic feature. Accordingly we may study, as in the molluscan shell, the helicoid component of the spire, in other words the variation in what we have called, on p. the angle theta. This factor it is which, more than the constant angle of the logarithmic spiral, imparts a characteristic appearance to the various species of sheep, for instance to the various closely allied species of Asiatic wild sheep, or argali. In all of these the constant angle of the logarithmic spiral is very much the same, but the shearing component differs greatly. And thus the long drawn-out horns of ovis poly, 4 feet or more from tip to tip, differ conspicuously from those of ovis ammon or O. Hodgsoni, in which a very similar logarithmic spiral is wound, as it were, round a much blunter cone. The ram's horn then, like the snail's shell, is a curve of double curvature, in which one component has imposed upon the structure a plane logarithmic spiral, and the other has produced a continuous displacement, or shear, proportionate in magnitude to, and perpendicular or otherwise inclined in direction to, the axis of the former spiral curvature. The result is precisely analogous to that which we have studied in the snail and other spiral univalves. But while the form, and therefore the resultant forces, are similar, the original distribution of force is not the same, for we have not here, as we had in the snail shell, a columellar muscle to introduce the component acting in the direction of the axis. We have, it is true, the central bony core, which in part performs an analogous function, but the main phenomenon here is apparently a complex distribution of rates of growth, perpendicular to the plane of the generating curve. Let us continue to dispense with mathematics, for the mathematical treatment of a curve of double curvature is never very simple, and let us deal with the matter by experiment. We have seen that the generating curve, or transverse section, of a typical ram's horn is triangular in form. Measuring, along the curve of the horn, the length of the 3 edges of the trihedral structure in a specimen of ovis ammon, and calling them respectively the outer, inner, and hinder edges, from their position at the base of the horn. Relatively to the skull, I find the outer edge to measure 80 centimeters. The inner 74 centimeters, and the posterior 45 centimeters, let us say that, roughly, they are in the ratio of 9, 8, 5. Then, if we make a number of little cardboard triangles, equip each with 3 little legs, I make them of cork, whose relative lengths are as 9, 8, 5, and pile them up and stick them all together. We straightway build up a curve of double curvature precisely analogous to the ram's horn, except only that, in this first approximation, we have not allowed for the gradual increment, or decrement, of the triangular surfaces, that is to say, for the tapering of the horn due to the growth in its own plane of the generating curve. In this case then, and in most other trihedral or 3-sided horns, one of the 3 components, or 3 unequal velocities of growth, is of relatively small magnitude, but the other two are nearly equal one to the other. It would involve but little change for these latter to become precisely equal, and again but little to turn the balance of inequality the other way. But the immediate consequence of this altered ratio of growth would be that the horn would appear to wind the other way, as it does in the antelopes, and also in certain goats, e.g. the marker, Capra falconeri. For these two opposite directions of twist Dr. Wary has introduced a convenient nomenclature. When the horn winds so that we follow it from base to apex in the direction of the hands of a watch, it is customary to call it a left-handed spiral. Such a spiral we have in the horn on the left-hand side of a ram's head. Accordingly, Dr. Wary calls the condition homonymous, where, as in the sheep, a right-handed spiral is on the right side of the head, and a left-handed spiral on the left side. While he calls the opposite condition heteronymous, as we have it in the antelopes, where the right-handed twist is on the left side of the head, and the left-handed twist on the right-hand side. Among the goats, we may have either condition. Thus the domestic and most of the wild goats agree with the sheep, but in the marker the twisted horns are heteronymous, as in the antelopes. The difference, as we have seen, is easily explained. And, very much as in the case of our opposite spirals in the apple snail, referred to on p, it has no very deep importance. Summarized then, in a very few words, the argument by which we account for the spiral conformation of the horn is as follows. The horn elongates by dint of continual growth within a narrow zone, or annulus, at its base. If the rate of growth be identical on all sides of this zone, the horn will grow straight. If it be greater on one side than on the other, the horn will become curved, and it probably will be greater on one side than on the other. Because each single horn occupies an unsymmetrical field with reference to the plane of symmetry of the animal. If the maximal and minimal velocities of growth be precisely at opposite sides of the zone of growth, the resultant spiral will be a plane spiral. But if they be not precisely or diametrically opposite, then the spiral will be a spiral in space, with a winding or helical component. And it is by no means likely that the maximum and minimum will occur at precisely opposite ends of a diameter, for no such plane of symmetry is manifested in the field of force to which the growing annulus corresponds or appertains. Now we must carefully remember that the rates of growth of which we are here speaking are the net rates of longitudinal increment. In which increment the activity of the living cells in the zone of growth at the base of the horn is only one, though it is the fundamental factor. In other words, if the horny sheath were continually being added to with equal rapidity all round its zone of active growth, but at the same time had its elongation more retarded on one side than the other, prior to its complete solidification, by varying degrees of adhesion or membranous attachment to the bone core within, then the net result would be a spiral curve precisely such as would have arisen from initial inequalities in the rate of growth itself. It seems highly probable that this is a very important factor, and sometimes even the chief factor in the case. The same phenomenon of attachment to the bony core, and the consequent friction or retardation with which the sheath slides over its surface, will lead to various subsidiary phenomena, among others to the presence of transverse folds or corrugations upon the horn, and to their unequal distribution upon its several faces or edges. And while it is perfectly true that nearly all the characters of the horn can be accounted for by unequal velocities of longitudinal growth upon its different sides, it is also plain that the actual field of force is a very complicated one indeed. For example, we can easily see that, at least in the great majority of cases, the direction of growth of the horny fibers of the sheath is by no means parallel to the axis of the core within. Accordingly these fibers will tend to wind in a system of helicoid curves around the core. And not only this helicoid twist but any other tendency to spiral curvature on the part of the sheath will tend to be opposed or modified by the resistance of the core within. But on the other hand living bone is a very plastic structure, and yields easily though slowly to any forces tending to its deformation. And so, to a considerable extent, the bony core itself will tend to be modeled by the curvature which the growing sheath assumes, and the final result will be determined by an equilibrium between these two systems of forces. While it is not very safe, perhaps, to lay down any general rule as to what horns are more, and what are less spirally curved, I think it may be said that, on the whole, the thicker the horn, the greater is its spiral curvature. It is the slender horns, of such forms as the bisa antelope, which are gently curved, and it is the robust horns of goats or of sheep in which the curvature is more pronounced. Other things being the same, this is what we should expect to find. For it is where the transverse section of the horn is large that we may expect to find the more marked differences in the intensity of the field of force, whether of active growth or of retardation, on opposite sides or in different sectors thereof. Figure 320. Head of Ovis Ammon, Shoeing Street. Venance curves. But there is yet another and a very remarkable phenomenon which we may discern in the growth of a horn, when it takes the form of a curve of double curvature, namely, an effect of torsional strain. And this it is which gives rise to the sinuous lines of growth, or sinuous boundaries of the separate horny rings, of which we have already spoken. It is not at first sight obvious that a mechanical strain of torsion is necessarily involved in the growth of the horn. In our experimental illustration, p. we built up a twisted coil of separate elements, and no torsional strain attended the development of the system. So would it be if the horny sheath grew by successive annular increments, free save for their relation to one another, and having no attachment to the solid core within. But as a matter of fact there is such an attachment, by subcutaneous connective tissue, to the bony core. And accordingly a torsional strain will be set up in the growing horny sheath, again provided that the forces of growth therein be directed more or less obliquely to the axis of the core. For a couple is thus introduced, giving rise to a strain which the sheath would not experience were it free, so to speak, to slip along, impelled only by the pressure of its own growth from below. And furthermore, the successive small increments of the growing horn, that is to say, of the horny sheath, are not instantaneously converted from living to solid and rigid substance. But there is an intermediate stage, probably long continued, during which the new-formed horny substance in the neighborhood of the zone of active growth is still plastic and capable of deformation. Now we know, from the celebrated experiments of St. Venant, that in the torsion of an elastic body, other than a cylinder of circular section, a very remarkable state of strain is introduced. If the body be thus cylindrical, whether solid or hollow, then a twist leaves each circular section unchanged, in dimensions and in figure. But in all other cases, such as an elliptic rod or a prism of any particular sectional form, forces are introduced which act parallel to the axis of the structure, and which warp each section into a complex anticlastic surface. Thus in the case of a triangular and equilateral prism, such as is shown in section in Fig. If the part of the rod represented in the section be twisted by a force acting in the direction of the arrow, then the originally plane section will be warped as indicated in the diagram, where the full contour lines represent elevation above. And the dotted lines represent depression below, the original level. On the external surface of the prism, then, contour lines which were originally parallel and horizontal, will be found warped into sinuous curves, such that, on each of the three faces, the curve will be convex upwards on one half, and concave upwards on the other half of the face. The ram's horn, and still better that of Ovis Ammon, is comparable to such a prism, save that in section it is not quite equilateral, and that its three faces are not plane. The warping is therefore not precisely identical on the three faces of the horn, but, in the general distribution of the curves, it is in complete accordance with theory. Similar anticlastic curves are well seen in many antelopes. But they are conspicuous by their absence in the cylindrical horns of oxen. The better to illustrate this phenomenon, the nature of which is indeed obvious enough from a superficial examination of the horn, I made a plaster cast of one of the horny rings in a horn of Ovis Ammon, so as to get an accurate pattern of its sinuous edge, and then, filling the mold up with wet clay, I modeled an anticlastic surface, such as to correspond as nearly as possible with the sinuous outline. Finally, after making a plaster cast of this sectional surface, I drew its contour lines, as shown in Fig, with the help of a simple form of spherometer. It will be seen that in great part this diagram is precisely. Figure 321. Figure 322. Similar to St. Venant's diagram of the cross-section of a twisted triangular prism, and this is especially the case in the neighborhood of the sharp angle of our prismatic section. That in parts the diagram is somewhat asymmetrical is not to be wondered at, and, apart from inaccuracies due to the somewhat rough means by which it was made, this asymmetry can be sufficiently accounted for by anisotropy of the material. By inequalities in thickness of different parts of the horny sheath, and especially, I think, by unequal distributions of rigidity due to the presence of the smaller corrugations of the horn. It is apparently on account of these minor corrugations that, in such horns as the Highland rams, where they are strongly marked, the main St. Venant effect is not nearly so well shown as in the smoother horns such as those of O. Ammon and its immediate congeners. A further note upon torsion. The phenomenon of torsion, to which we have been thus introduced, opens up many wide questions in connection with form. Some of the associated phenomena are admirably illustrated in the case of climbing plants, but we can only deal with these still more briefly and parenthetically. The subject of climbing plants has been elaborately dealt with not only in Darwin's books, but also by a very large number of earlier and later writers. In twining plants, which constitute the greater number of climbers, the essential phenomenon is a tendency of the growing shoot to revolve about a vertical axis, a tendency long ago discussed and investigated by such writers as Palm, H. Vaughan Moll and Dutrochet. This tendency to revolution, circumvolution, as Darwin calls it, revolving nutation, as Sachs puts it, is very closely comparable to the process by which an antelope's horn, such as the kudu's, grows into its spiral or rather helicoid form. And it is simply due, in like manner, to inequalities in the rate of growth on different sides of the growing stem. There is only this difference between the two cases, that in the antelope's horn the zone of active growth is confined to the base of the horn, while in the climbing stem the same phenomenon is at work throughout the whole length of the growing structure. This growth is in the main due to turgescence, that is to the extension, or elongation, of ready-formed cells through the imbibition of water. It is a phenomenon due to osmotic pressure. The particular stimuli to which these movements, that is to say, these inequalities of growth, have been ascribed, such as contact, phygmotaxis, exposure to light, heliotropism, and so forth, need not be discussed here. A simple stem growing upright in the dark, or in uniformly diffused light, would be in a position of equilibrium to a field of force radially symmetrical about its vertical axis. But this complete radial symmetry will not often occur. And the radial anomalies may be such as arise intrinsically from structural peculiarities in the stem itself, or externally to it by reason of unequal illumination or through various other localized forces. The essential fact, so far as we are concerned, is that in twining plants we have a very marked tendency to inequalities in longitudinal growth on different aspects of the stem, a tendency which is but an exaggerated manifestation of one which is more or less present, under certain conditions, in all plants whatsoever. Just as in the case of the ruminant's horns, so we find here, that this inequality may be, so to speak, positive or negative, the maximum lying to the one side or the other of the twining stem. And so it comes to pass that some climbers twine to the one side and some to the other, the hop and the honeysuckle following the sun, and the field convolvulus twining in the reverse direction. There are also some, like the woody nightshade, Solanum dulcamera, which twine indifferently either way. Together with this circumnudatory movement, there is very generally to be seen an actual torsion of the twining stem, a twist, that is to say, about its own axis. And Moll made the curious observation, confirmed by Darwin, that when a stem twines around a smooth cylindrical stick the torsion does not take place, save only in that degree which follows as a mechanical necessity from the spiral winding, but that stems which had climbed around a rough stick were all more or less, and generally much, twisted. Here Darwin did not refrain from introducing that teleological argument which pervades his whole train of reasoning. The stem, he says, probably gains rigidity by being twisted, on the same principle that a much twisted rope is stiffer than a slackly twisted one, and is thus indirectly benefited so as to be able to pass over inequalities in its spiral ascent, and to carry its own weight when allowed to revolve freely. The mechanical explanation would appear to be very simple, and such as to render the teleological hypothesis unnecessary. In the case of the roughened support, there is a temporary adhesion or clinging between it and the growing stem which twines around it. And a system of forces is thus set up, producing a couple, just as it was in the case of the ram's or antelope's horn through direct adhesion of the bony core to the surrounding sheath. The twist is the direct result of this couple, and it disappears when the support is so smooth that no such force comes to be exerted. Another important class of climbers includes the so-called leaf climbers. In these, some portion of the leaf, generally the petiole, sometimes, as in the fumitory, the elongated midrib, curls round a support, and a phenomenon of like nature occurs in many, though not all, of the so-called tendril bearers. Except that a different part of the plant, leaf or tendril instead of stem, is concerned in the twining process, the phenomenon here is strictly analogous to our former case. But in the resulting helix there is, as a rule, this obvious difference, that, while the twining stem, for instance of the hop, makes a slow revolution about its support, the typical leaf climber makes a close, firm coil. The axis of the latter is nearly perpendicular and parallel to the axis of its support, while in the twining stem the angle between the two axes is comparatively small. Mathematically speaking, the difference merely amounts to this, that the component in the direction of the vertical axis is large in the one case, and the corresponding component is small, if not absent, in the other. In other words, we have in the climbing stem a considerable vertical component, due to its own tendency to grow in height, while this longitudinal or vertical extension of the whole system is not apparent, or little apparent, in the other cases. But from the fact that the twining stem tends to run obliquely to its support, and the coiling petiole of the leaf climber tends to run transversely to the axis of its support, there immediately follows this marked difference. That the phenomenon of torsion, so manifest in the former case, will be absent in the latter. There is one other phenomenon which meets us in the twining and twisted stem, and which is doubtless illustrated also, though not so well, in the antelope's horn. It is a phenomenon which forms the subject of a second chapter of St. Venant's researches on the effects of torsional strain in elastic bodies. We have already seen how one effect of torsion, in for instance a prism, is to produce strains parallel to the axis, elevating parts and depressing other parts of each transverse section. But in addition to this, the same torsion has the effect of materially altering the form of the section itself, as we may easily see by twisting a square or oblong piece of india rubber. If we start with a cylinder, such as a round piece of catapult india rubber, and twist it on its own long axis, we have already seen that it suffers no other distortion. It still remains a cylinder, that is to say, it is still in section everywhere circular. But if it be of any other shape than cylindrical, the case is quite different, for now the sectional shape tends to alter under the strain of torsion. Thus, if our rod be elliptical in section to begin with, it will, under torsion, become a more elongated ellipse. If it be square, its angles will become more prominent, and its sides will curve inwards, till at length the square assumes the appearance of a four-pointed star, with rounded angles. Furthermore, looking at the results of this process of modification, we find experimentally that the resultant figures are more easily twisted, less resistant to torsion, than were those from which we evolved them. And this is a very curious physical or mathematical fact. So a cylinder, which is especially resistant to torsion, is very easily bent or flexed. While projecting ribs or angles, such as an engineer makes in a bar or pillar of iron for the purpose of greatly increasing its strength in the way of resistance to bending, actually make it much weaker than before, for the same amount of metal per unit length, in the way of resistance to torsion. In the hop itself, and in a very considerable number of other twining and twisting stems, the ribbed or channeled form of the stem is a conspicuous feature. We may safely take it, 1, that such stems are especially susceptible of torsion. And 2, that the effect of torsion will be to intensify any such peculiarities of sectional outline which they may possess, though not to initiate them in an originally cylindrical structure. In the leaf climbers the case does not present itself, for there, as we have seen, torsion itself is not, or is very slightly, manifested. There are very distinct traces of the phenomenon in the horns of certain antelopes, but the reason why it is not a more conspicuous feature of the antelope's horn or of the ram's is apparently a very simple one, namely, that the presence of the bony core within tends to check that deformation which is perpendicular, while it permits that which is parallel, to the axis of the horn. Of deer's antlers. But let us return to our subject of the shapes of horns, and consider briefly our last class of these structures, namely the bony antlers of the various species of elk and deer. The problems which these present to us are very different from those which we have had to do with in the antelope or the sheep. With regard to its structure, it is plain that the bony antler corresponds, upon the whole, to the bony core of the antelope's horn. While in place of the hard horny sheath of the latter, we have the soft, velvet, which every season covers the new growing antler, and protects the large nutrient blood vessels by help of which the antler grows. The main difference lies in the fact that, in the one case, the bony core, imprisoned within its sheath, is rendered incapable of branching and incapable also of lateral expansion, and the whole horn is only permitted to grow in length. While retaining a sectional contour that is identical with, or but little altered from, that which it possesses at its growing base, but in the antler, on the other hand, no such restraint is imposed, and the living growing fabric of bone may expand into a broad flattened plate over which the blood vessels run. In the immediate neighborhood of the main blood vessels growth will be most active. In the interspaces between, it may wholly fail, with the result that we may have great notches cut out of the flattened plate, or may at length find it reduced to the form of a simple branching structure. The main point, as it seems to me, is that the horn is essentially an axial rod, while the antler is. Figure 323. Antlers of Swedish elk. After Lundberg, from PZS. Essentially an outspread surface. In other words, I believe that the whole configuration of an antler is more easily understood by conceiving it as a plate or a surface, more and more notched and scalloped till but a slender skeleton may remain, than to look upon it the other way. Namely as an axial stem, or beam, giving off branches, or tines, the interspaces between which latter may sometimes be filled up to form a continuous plate. In a sense it matters very little whether we regard the broad plate-like antlers of the elk or the slender branching antlers of the stag as the more primitive type, for we are not concerned here with the question of hypothetical phylogeny. And even from the mathematical point of view it makes little or no difference whether we describe the plate as constituted by the interconnection of the branches, or the branches derived by a. Figure 324. Head and antlers of a stag. Service de Vasily. After Lydecker, from PZS. Process of notching or incision from the plate. The important point for us is to recognize that, save for occasional slight irregularities, the branching system in the one conforms essentially to the curved plate or surface which we see plainly in the other. In short, the arrangement of the branches is more or less comparable to that of the veins in a leaf, or to that of the blood vessels as they course over the curved surface of an organ. It is a process of ramification, not, like that of a tree, in various planes, but strictly limited to a single surface. And just as the veins within a leaf are not necessarily confined, as they happen to be in most ordinary leaves, to a plane surface, but, as in the petal of a tulip or the capsule of a poppy, may have to run their course within a curved surface. So does the analogy of the leaf lead us directly to the mode of branching which is characteristic of the antler. The surface to which the branches of the antler tend to be confined is a more or less spheroidal, or occasionally an ellipsoidal one. And furthermore, when we inspect any well-developed pair of antlers, such as those of a red deer, a somber or a wapiti, we have no difficulty in seeing that the two antlers make up between them a single surface, and constitute a symmetrical figure. Each half being the mirror image of the other. To put the case in another way, a pair of antlers, apart from occasional slight irregularities, tends to constitute a figure such that we could conceive an elastic sheet stretched over or round the entire system, so as to form one continuous and even surface. And not only would the surface curvature be on the whole smooth and even, but the boundary of the surface would also tend to be an even curve, that is to say the tips of all the tines would approximately have their locus in a continuous curve. It follows from this that if we want to make a simple model of a set of antlers, we shall be very greatly helped by taking some appropriate spheroidal surface as our groundwork or scaffolding. The best form of surface is a matter for trial and investigation in each particular case, but even in a sphere, by selecting appropriate areas thereof, we can obtain sufficient varieties of surface to meet all ordinary cases. With merely a bit of sculptor's clay or plasticine, we should be put hard to it to model the horns of a wapiti or a reindeer, but if we start with an orange, or a round Florence flask, and lay our little tapered rolls of plasticine upon it, in simple natural curves, it is surprising to see how quickly and successfully we can imitate one type of antler after another. In doing so, we shall be struck by the fact that our model may vary in its mode of branching within very considerable limits, and yet look perfectly natural. For the same wide range of variation is characteristic of the natural antlers themselves. As Sir V. Brooke says, op. cit. page 892, no two antlers are ever exactly alike. And the variation to which the antlers are subject is so great that in the absence of a large series they would be held to be indicative of several distinct species. But all these many variations lie within a limited range, for they are all subject to our general rule that the entire structure is essentially confined to a single curved surface. It is plain that in the curvatures both of the beam and of its tines, in the angles by which these latter meet the beam, and in the contours of the entire system, there are involved many elegant mathematical problems with which we cannot at present attempt to deal. Nor must we attempt meanwhile to inquire into the physical meaning or origin of these phenomena, for as yet the clue seems to be lacking and we should only heap one hypothesis upon another. That there is a complete contrast of mathematical properties between the horn and the antler is the main lesson with which, in the meantime, we must rest content. Of teeth, and of beak and claw. In a fashion similar to that manifested in the shell or the horn, we find the logarithmic spiral to be implicit in a great many other organic structures where the phenomena of growth proceed in a similar way, that is to say, where about an axis there is some asymmetry leading to unequal rates of longitudinal growth, and where the structure is of such a kind that each new increment is added on as a permanent and unchanging part of the entire conformation. Nail and claw, beak and tooth, all come under this category. The logarithmic spiral always tends to manifest itself in such structures as these, though it usually only attracts our attention in elongated structures, where, that is to say, the radius vector has described a considerable angle. When the canary bird's claws grow long from lack of use, or when the incisor tooth of a rabbit or a rat grows long by reason of an injury to the opponent tooth against which it was wont to bite, we know that the tooth or claw tends to grow into a spiral curve, and we speak of it as a malformation. But there has been no fundamental change of form, save only an abnormal increase in length. The elongated tooth or claw has the selfsame curvature that it had when it was short, but the spiral curvature becomes more and more manifest the longer it grows. A curious analogous case is that of the New Zealand huia bird, in which the beak of the female is described as being comparatively short and straight, while that of the male is long and curved. It is easy to see that there is a slight curvature also in the beak of the female, and that the beak of the male shows nothing but the same curve produced. In the case of the more curved beaks, such as those of an eagle or a parrot, we may, if we please, determine the constant angle of the logarithmic spiral, just as we have done in the case of the nautilus shell. And here again, as the bird grows older or the beak longer, the spiral nature of the curve becomes more and more apparent, as in the hooked beak of an old eagle, or as in the great beak of some large parrot such as a hyacinthine macaw. Let us glance at one or two instances to illustrate the spiral curvature of teeth. A dentist knows that every tooth has a curvature of its own, and that in pulling the tooth he must follow the direction of the curve. But in an ordinary tooth this curvature is scarcely visible, and is least so when the diameter of the tooth is large compared with its length. In the simply formed, more or less conical teeth, such as are those of the dolphin, and in the more or less similarly shaped canines and incisors of mammals in general, the curvature of the tooth is particularly well seen. We see it in the little teeth of a hedgehog, and in the canines of a dog or a cat it is very obvious indeed. When the great canine of the carnivore becomes still further enlarged or elongated, as in Machaerodus, it grows into the strongly curved saber tooth of that great extinct tiger. In rodents it is the incisors which undergo a great elongation. Their rate of growth differs, though but slightly, on the two sides, anterior and posterior, of the axis, and by summation of these slight differences in the rapid growth of the tooth an unmistakable logarithmic spiral is gradually built up. We see it admirably in the beaver, or in the great ground rat, Geomys. The elephant is a similar case, save that the tooth, or tusk, remains, owing to comparative lack of wear, in a more perfect condition. In the rodent, save only in those abnormal cases mentioned on the last page, the anterior, first formed, part of the tooth wears away as fast as it is added to from behind. And in the grown animal, all those portions of the tooth near to the pole of the logarithmic spiral have long disappeared. In the elephant, on the other hand, we see, practically speaking, the whole unworn tooth, from point to root. And its actual tip nearly coincides with the pole of the spiral. If we assume, as with no great inaccuracy we may do, that the tip actually coincides with the pole, then we may very easily construct the continuous spiral of which the existing tusk constitutes a part. And by so doing, we see the short, gently curved tusk of our ordinary elephant growing gradually into the spiral tusk of the mammoth. No doubt, just as in the case of our molluscan shells, we have a tendency to variation, both individual and specific, in the constant angle of the spiral. Some elephants, and some species of elephant, undoubtedly have a higher spiral angle than others. But in most cases, the angle would seem to be such that a spiral configuration would become very manifest indeed if only the tusk pursued its steady growth, unchanged otherwise in form, till it attained the dimensions which we meet with in the mammoth. In a species such as Mastodon angustidens, or M. arvanensis, the specific angle is low and the tusk comparatively straight. But the American mastodons and the existing species of elephant have tusks which do not differ appreciably, except in size, from the great spiral tusks of the mammoth. Though from their comparative shortness the spiral is little developed and only appears to the eye as a gentle curve. Wherever the tooth is very long indeed, as in the mammoth or the beaver, the effect of some slight and all but inevitable lateral asymmetry in the rate of growth begins to shew itself, in other words. The spiral is seen to lie not absolutely in a plane, but to be a curve of double curvature, like a twisted horn. We see this condition very well in the huge canine tusks of the Babirusa. It is a conspicuous feature in the mammoth, and it is more or less perceptible in any large tusk of the ordinary elephants. The form of a molar tooth, which is essentially a branching or budding system, and in which such longitudinal growth as gives rise to a spiral curve is but little manifest, constitutes an entirely different problem with which I shall not at present attempt to deal. Chapter 14 on Leaf Arrangement, or Phyllotaxis. The beautiful configurations produced by the orderly arrangement of leaves or florets on a stem have long been an object of admiration and curiosity. Leonardo da Vinci would seem, as Sir Theodore Cook tells us, to have been the first to record his thoughts upon this subject. But the old Greek and Egyptian geometers are not likely to have left unstudied or unobserved the spiral traces of the leaves upon a palm stem, or the spiral curves of the petals of a lotus or the florets in a sunflower. The spiral leaf order has been regarded by many learned botanists as involving a fundamental law of growth, of the deepest and most far-reaching importance. While others, such as Sachs, have looked upon the whole doctrine of phyllotaxis as a sort of geometrical or arithmetical playing with ideas, and the spiral theory as a mode of view gratuitously introduced into the plant. Sachs even goes so far as to declare this doctrine, in direct opposition to scientific investigation, and based upon the idealistic direction of the nature philosophy, the mystical biology of Oken and his school. The essential facts of the case are not difficult to understand, but the theories built upon them are so varied, so conflicting, and sometimes so obscure, that we must not attempt to submit them to detailed analysis and criticism. There are two chief ways by which we may approach the question, according to whether we regard, as the more fundamental and typical, one or other of the two chief modes in which the phenomenon presents itself. That is to say, we may hold that the phenomenon is displayed in its essential simplicity by the corkscrew spirals, or helices, which mark the position of the leaves upon a cylindrical stem or on an elongated fir cone. Or, on the other hand, we may be more attracted by, and regard as of greater importance, the logarithmic spirals which we trace in the curving rows of florets in the discoidal inflorescence of a sunflower. Whether one way or the other be the better, or even whether one be not positively correct and the other radically wrong, has been vehemently debated. In my judgment they are, both mathematically and biologically, to be regarded as inseparable and correlative phenomena. The helical arrangement, as in the fir cone, was carefully studied in the middle of the 18th century by the celebrated Bonnet, with the help of Calandrini, the mathematician. Memoirs published about 1835, by Schimper and Braun, greatly amplified Bonnet's investigations, and introduced a nomenclature which still holds its own in botanical textbooks. Naumann and the brothers Bravais are among those who continued the investigation in the years immediately following, and Hofmeister, in 1868, gave an admirable account and summary of the work of these and many other writers. Starting from some given level and proceeding upwards, let us mark the position of some one leaf, A, upon a cylindrical stem. Another, and a younger leaf, B, will be found standing at a certain distance around the stem, and a certain distance along the stem, from the first. The former distance may be expressed as a fractional divergence, such as 2/5 of the circumference of the stem, as the botanists describe it. Or by an angle of azimuth, such as phi equals 144 degrees, as the mathematician would be more likely to state it. The position of B relatively to A must be determined, not only by this angle phi, in the horizontal plane, but also by an angle, theta, in the vertical plane. For the height of B above the level of A, in comparison with the diameter of the cylinder, will obviously make a great difference in the appearance of the whole system. In short, the position of each leaf must be expressed by F, phi sin theta. But this matter botanical students have not concerned themselves with. In other words, their studies have been limited, or mainly limited, to the relation of the leaves to one another in azimuth. Whatever relation we have found between A and B, let precisely the same relation subsist between B and C, and so on. Let the growth of the system, that is to say, be continuous and uniform. It is then evident that we have the elementary conditions for the development of a simple cylindrical helix, and this primary helix or genetic spiral we can now trace, winding round and round the stem, through A, B, C, etc. But if we can trace such a helix through A, B, C, it follows from the symmetry of the system, that we have only to join A to some other leaf to trace another spiral helix, such, for instance, as A, C, E, etc. Parallel to which will run another and similar one, namely in this case B, D, F, etc. And these spirals will run in the opposite direction to the spiral ABC. In short, the existence of one helical arrangement of points implies and involves the existence of another and then another helical pattern, just as, in the pattern of a wallpaper, our eye travels from one linear series to another. A modification of the helical system will be introduced when, instead of the leaves appearing, or standing, in singular succession, we get two or more appearing simultaneously upon the same level. If there be two such, then we shall have two generating spirals precisely equivalent to one another, and we may call them A, B, C, etc., and A, B, C, and so on. These are the cases which we call whorled leaves, or in the simplest case, where the whorl consists of two opposite leaves only, we call them decussate. Among the phenomena of PHYLLOTAXIS, 2 points in particular have been found difficult of explanation, and have aroused discussion. These are, 1, the presence of the logarithmic spirals such as we have already spoken of in the sunflower. And 2, the fact that, as regards the number of the helical or spiral rows, certain numerical coincidences are apt to recur again and again, to the exclusion of others, and so to become characteristic features of the phenomenon. The first of these appears to me to present no difficulty. It is a mere matter of strictly mathematical deformation. The stem which we have begun to speak of as a cylinder is not strictly so, inasmuch as it tapers off towards its summit. The curve which winds evenly around this stem is, accordingly, not a true helix. For that term is confined to the curve which winds evenly around the cylinder. It is a curve in space which, like the spiral curve we have studied in our turbinate shells, partakes of the characters of a helix and of a logarithmic spiral. And which is in fact a logarithmic spiral with its pole drawn out of its original plane by a force acting in the direction of the axis. If we imagine a tapering cylinder, or cone, projected, by vertical projection, on a plane, it becomes a circular disk. And the helix described about the cone necessarily becomes in the disk a logarithmic spiral described about a focus which corresponds to the apex of our cone. In like manner we may project an identical spiral in space upon such surfaces as, for instance, a portion of a sphere or of an ellipsoid. And in all these cases we preserve the spiral configuration, which is the more clearly brought into view the more we reduce the vertical component by which it was accompanied. The converse is, of course, equally true, and equally obvious. Namely that any logarithmic spiral traced upon a circular disk or spheroidal surface will be transformed into a corresponding spiral helix when the plane or spheroidal disk is extended into an elongated cone approximating to a cylinder. This mathematical conception is translated, in botany, into actual fact. The fir cone may be looked upon as a cylindrical axis contracted at both ends, until it becomes approximately an ellipsoidal solid of revolution, generated about the long axis of the ellipse. And the semi-ellipsoidal capitulum of the teasel, the more or less hemispherical one of the thistle, and the flattened but still convex one of the sunflower, are all beautiful and successive deformations of what is typically a long, conical, and all but cylindrical stem. On the other hand, every stem as it grows out into its long cylindrical shape is but a deformation of the little spheroidal or ellipsoidal surface, or cone, which was its forerunner in the bud. This identity of the helical spirals around the stem with spirals projected on a plane was clearly recognized by Hofmeister, who was accustomed to represent his diagrams of leaf arrangement either in one way or the other, though not in a strictly geometrical projection. According to Mr. H. Church, who has dealt very carefully and elaborately with the whole question of phyllotaxis. The logarithmic spirals such as we see in the disk of the sunflower have a far greater importance and a far deeper meaning than this brief treatment of mine would accord to them, and Sir Theodore Cook, in his book on the curves of life, has adopted and has helped to expound and popularize Mr. Church's investigations. Mr. Church, regarding the problem as one of uniform growth, easily arrives at the conclusion that, if this growth can be conceived as taking place symmetrically about a central point or pole, the uniform growth would then manifest itself in logarithmic spirals, including of course the limiting cases of the circle and straight line. With this statement I have little fault to find, it is in essence identical with much that I have said in a previous chapter. But other statements of Mr. Church's, and many theories woven about them by Sir T. Cook and himself, I am less able to follow. Mr. Church tells us that the essential phenomenon in the sunflower disk is a series of orthogonally intersecting logarithmic spirals. Unless I wholly misapprehend Mr. Church's meaning, I should say that this is very far from essential. The spirals intersect isogonally, but orthogonal intersection would be only one particular case, and in all probability a very infrequent one, in the intersection of logarithmic spirals developed about a common pole. Again on the analogy of the hydrodynamic lines of force in certain vortex movements, and of similar lines of force in certain magnetic phenomena. Mr. Church proceeds to argue that the energies of life follow lines comparable to those of electric energy, and that the logarithmic spirals of the sunflower are, so to speak, lines of equipotential. And Sir T. Cook remarks that this theory, if correct, would be fundamental for all forms of growth, though it would be more easily observed in plant construction than in animals. The parallel I am not able to follow. Mr. Church sees in phyllotaxis an organic mystery, a something for which we are unable to suggest any precise cause, a phenomenon which is to be referred, somehow, to waves of growth emanating from a center. but on the other hand not to be explained by the division of an apical cell, or any other histological factor. As Sir T. Cook puts it, at the growing point of a plant where the new members are being formed, there is simply nothing to see. But it is impossible to deal satisfactorily, in brief space, either with Mr. Church's theories, or my own objections to them. Let it suffice to say that I, for my part, see no subtle mystery in the matter, other than what lies in the steady production of similar growing parts, similarly situated, at similar successive intervals of time. If such be the case, then we are bound to have in consequence a series of symmetrical patterns, whose nature will depend upon the form of the entire surface. If the surface be that of a cylinder, we shall have a system, or systems, of spiral helices; if it be a plane, with an infinitely distant focus, such as we obtain by unwrapping our cylindrical surface, we shall have straight lines. If it be a plane containing the focus within itself, or if it be any other symmetrical surface containing the focus, then we shall have a system of logarithmic spirals. The appearance of these spirals is sometimes spoken of as a subjective phenomenon, but the description is inaccurate. It is a purely mathematical phenomenon, an inseparable secondary result of other arrangements which we, for the time being, regard as primary. When the bricklayer builds a factory chimney, he lays his bricks in a certain steady, orderly way, with no thought of the spiral patterns to which this orderly sequence inevitably leads, and which spiral patterns are by no means subjective. The designer of a wallpaper not only has no intention of producing a pattern of crisscross lines, but on the contrary he does his best to avoid them. Nevertheless, so long as his design is a symmetrical one, the crisscross intersections inevitably come. Let us, however, leave this discussion, and return to the facts of the case. Our second question, which relates to the numerical coincidences so familiar to all students of phyllotaxis, is not to be set and answered in a word. Let us, for simplicity's sake, avoid consideration of simultaneous or whorled leaf origins, and consider only the more frequent cases where a single genetic spiral can be traced throughout the entire system. It is seldom that this primary, genetic spiral catches the eye, for the leaves which immediately succeed one another in this genetic order are usually far apart on the circumference of the stem. And it is only in close-packed arrangements that the eye readily apprehends the continuous series. Accordingly, in such a case as a fir cone, for instance, it is certain of the secondary spirals or parastiches which catch the eye. And among fir cones, we can easily count these, and we find them to be on the whole very constant in number, according to the species. Thus in many cones, such as those of the Norway spruce, we can trace 5 rows of scales winding steeply up the cone in one direction, and 3 rows winding less steeply the other way. In certain other species, such as the common larch, the normal number is 8 rows in the one direction and 5 in the other, while in the American larch we have again 3 in the one direction and 5 in the other. It not seldom happens that 2 arrangements grade into one another on different parts of one and the same cone. Among other cases in which such spiral series are readily visible we have, for instance, the crowded leaves of the stonecrops and mesembryanthemums, and, as we have said, the crowded florets of the composites. Among these we may find plenty of examples in which the numbers of the serial rows are similar to those of the fir cones. But in some cases, as in the daisy and others of the smaller composites, we shall be able to trace 13 rows in one direction and 21 in the other, or perhaps 21 and 34. While in a great big sunflower we may find, in one and the same species, 34 and 55, 55 and 89, or even as many as 89 and 144. On the other hand, in an ordinary pentamerous flower, such as a ranunculus, we may be able to trace, in the arrangement of its sepals, petals and stamens, shorter spiral series, 3 in one direction and 2 in the other. It will be at once observed that these arrangements manifest themselves in connection with very different things, in the orderly interspacing of single leaves and of entire florets, and among all kinds of leaf-like structures, foliage leaves, bracts, cone scales, and the various parts or members of the flower. Again we must be careful to note that, while the above numerical characters are by much the most common, so much so as to be deemed normal, many other combinations are known to occur. The arrangement, as we have seen, is apt to vary when the entire structure varies greatly in size, as in the disk of the sunflower. It is also subject to less regular variation within one and the same species, as can always be discovered when we examine a sufficiently large sample of fir cones. For instance, out of 505 cones of the Norway spruce, Beale found 92%. In which the spirals were in 5 and 8 rows, in 6% the rows were 4 and 7, and in 4% they were 4 and 6. In each case they were nearly equally divided as regards direction. For instance, of the 467 cones shewing the 5-8 arrangement, the 5 series ran in right-handed spirals in 224 cases, and in left-handed spirals in 243. Omitting the abnormal cases, such as we have seen to occur in a small percentage of our cones of the spruce, the arrangements which we have just mentioned may be set forth as follows. The fractional number used being simply an abbreviated symbol for the number of associated helices or parastiches which we can count running in the opposite directions 2 3, 3 5, 5 8, 8 13, 13 21, 21 34, 34 55, 55 89. 89 144. Now these numbers form a very interesting series, which happens to have a number of curious mathematical properties. We see, for instance, that the denominator of each fraction is the numerator of the next. And further, that each successive numerator, or denominator, is the sum of the preceding two. Our immediate problem, then, is to determine, if possible, how these numerical coincidences come about. And why these particular numbers should be so commonly met with as to be considered normal and characteristic features of the general phenomenon of phyllotaxis. The following account is based on a short paper by Professor P. G. Tate. Figure 325. Of the two following diagrams, Fig. Represents the general case, and Fig. A particular one, for the sake of possibly greater simplicity. Both diagrams represent a portion of a branch, or fir cone, regarded as cylindrical, and unwrapped to form a plane surface. A, at the two ends of the baseline, represent the same initial leaf or scale. O is a leaf which can be reached from A by M steps in a right-hand spiral, developed into the straight line AO, and by N steps from A in a left-handed spiral AO. Now it is obvious in our fir cone, that we can include all the scales upon the cone by taking so many spirals in the one direction, and again include them all by so many in the other. Accordingly, in our diagrammatic construction, the spirals AO and AO must, and always can, be so taken that M spirals parallel to AO, and N spirals parallel to AO, shall separately include all the leaves upon the stem or cone. If M and N have a common factor, L, it can easily be shown that the arrangement is composite, and that there are L fundamental, or genetic spirals, and L leaves, including A, which are situated exactly on the line AA. That is to say, we have here a whorled arrangement, which we have agreed to leave unconsidered in favor of the simpler case. We restrict ourselves, accordingly, to the cases where there is but one genetic spiral, and when therefore M and N are prime to one another. Our fundamental, or genetic, spiral, as we have seen, is that which passes from A, or A, to the leaf which is situated nearest to the baseline AA. The fundamental spiral will thus be right-handed, A, P, etc. If P, which is nearer to A than to A, be this leaf, left-handed if it be P. That is to say, we make it a convention that we shall always, for our fundamental spiral, run round the system, from one leaf to the next, by the shortest way. Now it is obvious, from the symmetry of the figure, as further shown in Fig, that, besides the spirals running along AO and AO, we have a series running from the steps on AO to the steps on AO. In other words, we can find a leaf, S, upon AO, which, like the leaf O, is reached directly by a spiral series from A and from A, such that as includes N steps, and AS, being part of the old spiral line AO, now includes MN. Figure 326. Steps. And, since M and N are prime to one another, for otherwise the system would have been a composite or whirled one. It is evident that we can continue this process of convergence until we come down to a one-one arrangement. That is to say, to a leaf which is reached by a single step, in opposite directions from A and from A, which leaf is therefore the first leaf, next to A, of the fundamental or generating spiral. If our original lines along AO and AO contain, for instance, 13 and 8 steps respectively, i.e. m equals 13, n equals 8, then our next series, observable in the same cone, will be 8 and 13 8, or 5, the next 5 and 8 5, or 3, the next 3 2. And the next 2, 1, leading to the ultimate condition of 1 1. These are the very series which we have found to be common, or normal. And so far as our investigation has yet gone, it has proved to us that, if one of these exists, it entails, ipso facto, the presence of the rest. In following down our series, according to the above construction, we have seen that at every step we have changed direction, the longer and the shorter sides of our triangle changing places every time. Let us stop for a moment, when we come to the 1, 2 series, or at of Fig. It is obvious that there is nothing to prevent us making a new 1, 3 series if we please, by continuing the generating spiral through 3 leaves, and connecting the leaf so reached directly with our initial 1. But in the case represented in Fig, it is obvious that these 2 series, A, 1, 2, 3, etc., and A, 3, 6, etc., will be running in the same direction, i.e. they will both be right-handed, or both left-handed spirals. The simple meaning of this is that the third leaf of the generating spiral was distant from our initial leaf by more than the circumference of the cylindrical stem. In other words, that there were more than 2, but less than 3 leaves in a single turn of the fundamental spiral. Less than 2 there can obviously never be. When there are exactly 2, we have the simplest of all possible arrangements, namely that in which the leaves are placed alternately on opposite sides of the stem. When there are more than 2, but less than 3, we have the elementary condition for the production of the series which we have been considering, namely 1, 2, 2, 3, 3, 5, etc. To put the latter part of this argument in more precise language, let us say that, if, in our descending series, we come to steps 1 and t, where t is determined by the condition that 1 and t plus 1 would give spirals both right-handed, or both left-handed, it follows that there are less than t plus 1 leaves in a single turn of the fundamental spiral. And, determined in this manner, it is found in the great majority of cases, in fir cones and a host of other examples of PHYLLOTAXIS, that t equals 2. In other words, in the great majority of cases, we have what corresponds to an arrangement next in order of simplicity to the simplest case of all, next, that is to say, to the arrangement which consists of opposite and alternate leaves. These simple considerations, as Tate says, explain completely the so-called mysterious appearance of terms of the recurring series 1, 2, 3, 5, 8, 13, etc. The other natural series, usually but misleadingly represented by convergence to an infinitely extended continuous fraction, are easily explained, as above, by taking t equals 3, 4, 5, etc., etc. Many examples of these latter series have been given by Dickson and other writers. We have now learned, among other elementary facts, that wherever any one system of helical spirals is present, certain others invariably and of necessity accompany it, and are definitely related to it. In any diagram, such as Fig, in which we represent our leaf arrangement by means of uniform and regularly interspaced dots, we can draw one series of spirals after another, and one as easily as another. But in our fir cone, for instance, one particular series, or rather 2 conjugate series, are always conspicuous, while the others are sought and found with comparative difficulty. The phenomenon is illustrated by Fig. D. The ground plan of all these diagrams is identically the same. The generating spiral in each case represents a divergence of 3/8, or 135 degrees of azimuth, and the points succeed one another at the same successional distances parallel to the axis. The rectangular outlines, which correspond to the exposed surface of the leaves or cone scales, are of equal area, and of equal number. Nevertheless, the appearances presented by these diagrams are very different. For in one the eye catches a 5-8 arrangement, in another a 3-5, and so on, down to an arrangement of 1-1. The mathematical side of this very curious phenomenon I have not attempted to investigate. But it is quite obvious that, in a system within which various spirals are implicitly contained, the conspicuousness of one set or another does not depend upon angular divergence. It depends on the Figure 327. Relative proportions in length and breadth of the leaves themselves, or, more strictly speaking, on the ratio of the diagonals of the rhomboidal figure by which each leaf area is circumscribed. When, as in the fir cone, the scales by mutual compression conform to these rhomboidal outlines, their inclined edges at once guide the eye in the direction of some one particular spiral. And we shall not fail to notice that in such cases the usual result is to give us arrangements corresponding to the middle diagrams in Fig. Which are the configurations in which the quadrilateral outlines approach most nearly to a rectangular form, and give us accordingly the least possible ratio, under the given conditions, of sectional boundary wall to surface area. The manner in which one system of spirals may be caused to slide, so to speak, into another, has been ingeniously demonstrated by Schwendener on a mechanical model, consisting essentially of a framework which can be opened or closed to correspond with one after another of the above series of diagrams. The determination of the precise angle of divergence of two consecutive leaves of the generating spiral does not enter into the above general investigation, though Tate gives, in the same paper, a method by which it may be easily determined. And the very fact that it does not so enter shews it to be essentially unimportant. The determination of so-called orthostiches, or precisely vertical successions of leaves, is also unimportant. We have no means, other than observation, of determining that one leaf is vertically above another, and spiral series such as we have been dealing with will appear, whether such orthostiches exist, whether they be near or remote, or whether the angle of divergence be such that no precise vertical superposition ever occurs. And lastly, the fact that the successional numbers, expressed as fractions, 1 2, 2 3, 3 5, represent a convergent series, whose final term is equal to 0, 6 1 8 0 3. The sectio aurea or golden mean of unity is seen to be a mathematical coincidence, devoid of biological significance. It is but a particular case of Lagrange's theorem that the roots of every numerical equation of the second degree can be expressed by a periodic continued fraction. The same number has a multitude of curious arithmetical properties. It is the final term of all similar series to that with which we have been dealing, such for instance as 1 3, 3 4, 4 7, etc., or 1 4, 4 5, 5 9, etc. It is a number beloved of the circle squarer, and of all those who seek to find, and then to penetrate, the secrets of the Great Pyramid. It is deep set in Pythagorean as well as in Euclidean geometry. It enters, as the chord of an angle of 36 degrees, into the thrice isosceles triangle of which we have spoken on P. It is a number which becomes, by the addition of unity, its own reciprocal, its properties never end. To Kepler, as Neighbor tells us, it was a symbol of creation, or generation. Its recent application to biology and art criticism by Sir Theodore Cook and others is not new. Neighbor's book, already quoted, is full of it. Ziesing, in 1854, found in it the key to all morphology, and the same writer, later on, declared it to dominate both architecture and music. But indeed, to use Sir Thomas Browne's words, though it was of another number that he spoke, to enlarge this contemplation into all the mysteries and secrets accommodable unto this number, or inexcusable Pythagorism. If this number has any serious claim at all to enter into the biological question of PHYLLOTAXIS, this must depend on the fact, first emphasized by Chauncey Wright, that if the successive leaves of the fundamental spiral be placed at the particular azimuth which divides the circle in this sectio aurea, then no two leaves will ever be superposed. And thus we are said to have the most thorough and rapid distribution of the leaves round the stem, each new or higher leaf falling over the angular space between the two older ones which are nearest in direction. so as to divide it in the same ratio, k, in which the first two or any two successive ones divide the circumference. Now 5/8 and all successive fractions differ inappreciably from k. To this view there are many simple objections. In the first place, even 5/8, or 6/25, is but a moderately close approximation to the golden mean. In the second place, the arrangements by which a better approximation is got, such as 8/13, 13/21, and the very close approximations such as 34/55, 55/89, 89/144, etc., are comparatively rare, while the much less close approximations of 3/5 or 2/3, or even 1/2, are extremely common. Again, the general type of argument such as that which asserts that the plant is aiming at something which we may call an ideal angle, is one that cannot commend itself to a plain student of physical science, nor is the hypothesis rendered more acceptably when Sir T. Cook qualifies it by telling us that all that a plant can do is to vary, to make blind shots at constructions, or to mutate, as it is now termed. And the most suitable of these constructions will in the long run be isolated by the action of natural selection. Finally, and this is the most concrete objection of all, the supposed isolation of the leaves, or their most complete distribution to the action of the surrounding atmosphere, is manifestly very little affected by any conditions which are confined to the angle of azimuth. If we could imagine a case in which all the leaves of the stem, or all the scales of a fir cone, were crushed down to one and the same level, into a simple ring or whirl of leaves, then indeed they would have their most equable distribution under the condition of the ideal angle, that is to say of the golden mean. But if it be, so to speak, nature's object to set them further apart than they actually are, to give them freer exposure to the air than they actually have, then it is surely manifest that the simple way to do so is to elongate the axis, and to set the leaves further apart, lengthways on the stem. This has at once a far more potent effect than any nice manipulation of the angle of divergence. For it is obvious that in f, phi sin theta, we have a greater range of variation by altering theta than by altering phi. We come then, without more ado, to the conclusion that the Fibonacci series, and its supposed usefulness, and the hypothesis of its introduction into plant structure through natural selection, are all matters which deserve no place in the plain study of botanical phenomena. As Sachs shrewdly recognized years ago, all such speculations as these hark back to a school of mystical idealism. Chapter 15 on the shapes of eggs, and of certain other hollow structures.